In the history of physics, few discoveries have had as profound an impact as Isaac Newton's formulation of the laws of motion and the law of universal gravitation. These groundbreaking insights not only revolutionized our understanding of the physical world, but also laid the foundation for classical mechanics, a framework that would dominate science for over 300 years. Newton's ideas continue to be fundamental to our understanding of everything, from the movement of planets to the launch of rockets. The story of Newton's discoveries is often told with the iconic image of him sitting under an apple tree, watching an apple fall to the ground. While the tale may have been simplified over time, it encapsulates the essence of Newton's curiosity. Born in 1642, Isaac Newton was a mathematician, astronomer, and physicist who sought to answer the most fundamental questions about how objects moved and interacted in the universe. At the time, no one had a clear understanding of the forces that governed the motion of objects, either on Earth or in the heavens. As the story goes, one day, Newton observed an apple fall straight to the ground, which led him to ponder why the apple fell downwards rather than sideways or in some other direction. This seemingly simple observation sparked a chain of thoughts that would lead to one of the most important breakthroughs in the history of science. Newton realized that the force that caused the apple to fall to the ground must also be the same force that governed the motion of the moon in its orbit around the Earth. This insight would form the basis for his theory of gravity. Before Newton, philosophers and scientists had proposed various theories about motion, but they lacked a unified mathematical explanation. Newton's laws of motion, introduced in his seminal work Philosophiae Naturalis Principia Mathematica in 1687, created a comprehensive framework that described how objects move and interact under the influence of forces. These laws still serve as the foundation for much of classical mechanics. Newton's first law states that an object at rest will remain at rest, and an object in motion will continue moving with the same speed and in the same direction unless acted upon by an unbalanced force. This principle of inertia was a revolutionary idea, as it challenged the previous Aristotelian notion that objects in motion naturally come to rest unless continuously pushed. Newton's insight revealed that objects would keep moving indefinitely in a straight line unless something, such as friction or gravity, stopped them. Imagine you're sliding a hockey puck on ice. In a frictionless environment, the puck would continue sliding forever in a straight line unless you hit it with a stick or some other object intervenes. Newton's second law describes how the velocity of an object changes when it is acted upon by a force. It states that the force exerted on an object is equal to its mass times its acceleration. This equation gives a quantitative relationship between force, mass, and acceleration, providing the foundation for how we understand how forces influence motion. If you try to push a shopping cart and a car with the same amount of force, the cart will accelerate much faster because it has much less mass. Newton's second law explains why this happens. Newton's third law asserts that for every action, there is an equal and opposite reaction. This law applies to all interactions between objects, whether they're in contact with each other or acting at a distance. When you push on a wall, the wall pushes back with an equal and opposite force. You might not move the wall, but the force is still there, and it's pushing back with the same strength. These three laws formed the backbone of Newtonian physics, providing a way to predict how objects would move and interact under various conditions. Whether it was the motion of a car or the trajectory of a planet, Newton's laws allowed for precise calculations of forces and movements. While Newton's laws of motion provided a framework for understanding the motion of objects, it was his discovery of gravity that truly changed our view of the universe. Newton proposed that every object in the universe exerts an attractive force on every other object. This force, called gravity, decreases with the square of the distance between two objects. What made Newton's law so revolutionary was that it applied not just to objects on Earth, but to all objects in the universe, including planets, moons, and stars. Newton had bridged the gap between terrestrial mechanics and celestial mechanics. He showed that the same force that causes an apple to fall to the ground also governs the orbits of planets and the motions of moons. This was a bold and far-reaching insight that unified the heavens and the earth under one universal principle. Newton's laws transformed the way we understood the universe. His work provided precise explanations for the orbits of planets, the behavior of projectiles, the motions of tides, and much more. It laid the foundation for later discoveries in physics, from the work of Albert Einstein on relativity to the discovery of quantum mechanics. Newton's laws also had practical implications. For example, understanding motion and gravity enabled the development of technologies like space travel and satellite communications. When humans first set foot on the moon in 1969, it was Newton's laws that made that possible. Modern rockets and spacecraft are designed based on these very principles. Despite the overwhelming success of Newton's laws, they weren't the final word in our understanding of the universe. In the 20th century, Albert Einstein's theory of relativity provided a more comprehensive explanation of gravity, particularly in extreme conditions such as near black holes or at speeds approaching the speed of light. However, Even in the face of these advancements, Newton's laws remain remarkably accurate in many practical situations and continue to be essential in fields like engineering and everyday physics. Isaac Newton's laws of motion and his law of universal gravitation represent one of the greatest intellectual achievements in the history of science. Through his brilliant synthesis of earlier knowledge and original insights, Newton not only explained the workings of the natural world, but also provided a framework that continues to shape our understanding of physics today. From the fall of an apple to the motion of planets, Newton's laws have helped us unlock the mysteries of the universe, and they remain a cornerstone of science, guiding everything from engineering to space exploration. Discovery of thermodynamics and the laws of heat. In the 17th and 18th centuries, as machines began transforming the world, scientists started noticing something fascinating about heat, work, and energy. The Industrial Revolution brought engines that needed fuel and created power, driving ships and factories. Yet, despite all their practical skills in building these machines, engineers and scientists couldn't fully explain why some engines worked better than others. This sparked a revolution in understanding how heat behaves, known as thermodynamics. The story begins in the early 19th century with a French engineer named Sadi Carnot, often regarded as the father of thermodynamics. Carnot wanted to improve steam engines, which were the beating heart of the Industrial Revolution. To him, heat was a mysterious fluid that flowed between objects, carrying energy along with it. In 1824, he wrote a small book where he introduced the concept of the ideal engine cycle, now known as the Carnot cycle. Although Carnot didn't have the complete modern understanding of heat and energy, his work laid the groundwork by posing essential questions. Why can't an engine be 100% efficient? Where does the lost energy go? Carnot's insights inspired others to dig deeper. Soon, scientists like Rudolf Clausius, William Thomson, and James Joule expanded upon his ideas, leading to the formulation of the fundamental laws of thermodynamics. They realized that energy, in all its forms, follows strict rules that govern everything from boiling water to burning stars. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed. This idea, called the conservation of energy, was solidified by James Joule in the 1840s. Joule conducted a simple but brilliant experiment. He attached weights to a paddle wheel submerged in water. As the weights fell, they turned the paddle, stirring the water and causing its temperature to rise. Joule measured the temperature change and concluded that the mechanical energy from the falling weights was transforming into thermal energy in the water. This law marked a huge leap in scientific thought. It meant that energy is like currency. It can be spent, saved, and exchanged, but it never disappears. Whether it's chemical energy and fuel, thermal energy as heat, or kinetic energy as motion, all forms of energy are convertible but conserved. Rudolf Clausius took thermodynamics to the next level with the second law, which states that in any energy transfer or transformation, entropy, or disorder, will always increase in an isolated system. Clausius's work in the 1850s formalized this idea, showing that while energy is conserved, it tends to spread out, moving from concentrated to dispersed states. To make sense of this, imagine an ice cube melting in a warm room. The heat from the air flows into the ice, melting it into water. The second law explains that heat will naturally flow from a warmer area, the room, to a cooler one, the ice, and never in reverse. The disorder increases as the energy spreads out and the ice melts, representing a higher entropy state. This law tells us why time appears to move in one direction, why your coffee cools down, and why a broken egg doesn't put itself back together. Entropy gives us the arrow of time. In the late 19th century, as scientists probed even deeper, they discovered the third law of thermodynamics. This law, proposed by Walter Nernst, states that as the temperature of a system approaches absolute zero Kelvin, or minus 273.15 degrees Celsius, its entropy approaches a minimum value. At absolute zero, a system would be in a state of perfect order, with no random motion among its particles. While absolute zero is theoretically achievable, in practice, it's impossible to reach. The closer you get, the harder it becomes to remove the remaining energy. This law helped physicists understand the behavior of materials at extremely low temperatures and opened doors for research into superconductors and quantum states of matter. Interestingly, the zeroth law of thermodynamics was formalized last, even though it's foundational. It states that if two systems are each in thermal equilibrium with a third system, they are in thermal equilibrium with each other. This law allows us to define temperature as a measurable, transitive property, making thermometers meaningful tools. Without it, comparing temperatures would be inconsistent and unreliable. These laws aren't just scientific curiosities. They're the backbone of how we understand and harness energy. They explain why engines need fuel and why refrigerators keep food cool. They shape everything from chemical reactions to the life cycles of stars. Without thermodynamics, the engines powering cars, the turbines generating electricity, and even our body's metabolic processes would be incomprehensible. Thermodynamics also gives us a glimpse into the fate of the universe itself. According to the second law, the universe is constantly increasing in entropy. This points toward a future heat death, a state where all energy is evenly distributed. and no work can be done. Stars will burn out, and matter will be scattered thinly across space, leaving a cold, dark cosmos. From its roots in the study of engines to its role in defining our universe's ultimate fate, thermodynamics is a profound framework. It teaches us that while energy remains constant, it naturally spreads out, creating complexity, fueling life, and driving the evolution of the cosmos. Discovery of electromagnetism. The story of electromagnetism begins in the early 19th century with a simple yet groundbreaking observation. Electricity and magnetism are not separate forces, but deeply interconnected aspects of the same fundamental phenomenon. This idea, which seems straightforward today, was revolutionary for scientists in the early 1800s, and its discovery changed the way we understand forces in the natural world. In 1820, a Danish physicist named Hans Christian Ørsted was teaching a class on electricity when he noticed something unusual. When he brought a compass near a current-carrying wire, the needle moved. This was strange, as compass needles are generally influenced only by magnetic fields. Ørsted's simple experiment revealed something profound. An electric current can create a magnetic field. With this, the field of electromagnetism was born. Before this, electricity and magnetism were seen as completely separate phenomena. Electricity was the flow of charge, seen in batteries and lightning, while magnetism was associated with materials like lodestone and observed mainly in natural magnets. Ørsted's discovery hinted that the two were connected, a spark that led scientists around the world to dig deeper. Michael Faraday, an English scientist, was one of those who pursued Ørsted's discovery. Faraday was fascinated by the interplay between electricity and magnetism, and his experiments took Ørsted's initial finding much further. In 1831, Faraday made a landmark discovery. Moving a magnet near a coil of wire could induce an electric current in the wire. This phenomenon is known as electromagnetic induction. To understand Faraday's work, imagine moving a bar magnet quickly in and out of a loop of wire. As you move the magnet, it disturbs the space around it, creating a changing magnetic field, which in turn creates an electric current in the wire. This was the basis for electromagnetic induction, and would become the foundation for all electric generators and transformers. Faraday's insight was transformative. If moving a magnet could produce electricity, it meant that electrical energy could be generated, transmitted, and manipulated in ways previously unimagined. Faraday's work laid the groundwork for the development of electric power, a technological leap that powers cities, homes, and industries to this day. While Faraday made these key discoveries, he didn't fully develop a unified theory of electromagnetism. That achievement would come with James Clerk Maxwell, a Scottish physicist whose work in the mid-19th century brought all these ideas together into a single, elegant framework. In the 1860s, Maxwell synthesized the discoveries of Ørsted, Faraday, and others into a set of 4 mathematical equations, now known as Maxwell's equations. These equations describe how electric and magnetic fields interact and propagate through space. They reveal that changing electric fields can create magnetic fields and vice versa, forming a self-sustaining wave. This is the essence of electromagnetic waves. Maxwell's equations showed that light itself is an electromagnetic wave. This meant that visible light, radio waves, X-rays, and all other forms of electromagnetic radiation were part of the same spectrum. This insight was groundbreaking. It united optics, the study of light, with electricity and magnetism, bridging disciplines and creating a single coherent framework for understanding the electromagnetic spectrum. The practical implications of electromagnetism are nearly endless. Faraday's discovery of electromagnetic induction led directly to the creation of generators and transformers. By moving a coil of wire in a magnetic field, generators can convert mechanical energy into electrical energy. This principle is the backbone of modern power generation, from coal-fired power plants to wind turbines and hydroelectric dams. Electromagnetism also forms the basis for electric motors, which operate by converting electrical energy back into mechanical energy. Motors use the interaction between current and magnetic fields to create rotation, powering everything from household appliances to industrial machinery. The development of telecommunications was also made possible by understanding electromagnetic waves. In the late 19th century, Heinrich Hertz demonstrated the existence of radio waves, confirming Maxwell's theories. Soon after, inventors like Guglielmo Marconi found ways to harness these waves to send signals wirelessly, leading to the invention of radio. Radio waves, microwaves, and eventually fiber optics would reshape communication, making it possible to send information across vast distances instantaneously. Electromagnetism isn't just useful for human technology. It's a fundamental force that shapes the natural world. From the Earth's magnetic field, which protects us from solar radiation, to the chemical bonds holding atoms together, electromagnetism plays a key role in the structure and behavior of matter. Consider, for example, how electrons orbit the nucleus of an atom. This arrangement is governed by the electromagnetic attraction between negatively charged electrons and positively charged protons. In this way, electromagnetism binds atoms together to form molecules, and ultimately the matter we see around us. Without electromagnetism, there would be no structure in the universe as we know it. The auroras, or northern and southern lights, are a stunning example of electromagnetic phenomena. When charged particles from the sun collide with Earth's magnetic field, they spiral around the magnetic lines and collide with molecules in the atmosphere, creating vibrant displays of green, blue, and red light. These phenomena remind us of the invisible, yet powerful forces at play in our universe. Electromagnetism is not just a branch of physics. It is one of the pillars of modern science and technology. From its discovery in a classroom experiment to its role in powering the modern world, electromagnetism has reshaped human civilization. Its principles underlie everything from the light in our homes to the intricate workings of electronic devices and even our understanding of the cosmos. Today, we continue to build upon the legacy of Ørsted, Faraday, and Maxwell. Advances in quantum electrodynamics, QED, a theory that combines quantum mechanics and electromagnetism, have led to deeper insights into particle interactions. As we continue to explore the mysteries of electromagnetism, it's clear that this force, fundamental to our universe, will continue to drive scientific and technological innovation for generations to come. Rutherford's gold foil experiment. In the early 20th century, physicists were striving to understand the structure of the atom, a question that had puzzled scientists for centuries. The prevailing model was known as the plum pudding model, proposed by J.J. Thomson after his discovery of the electron in 1897. According to this model, the atom was thought to be a sphere of positive charge with negatively charged electrons embedded within it, like raisins in a pudding. However, this model would soon be challenged by an experiment that became one of the most pivotal in modern physics, Ernest Rutherford's gold foil experiment. The early 1900s was an era of exploration in atomic theory. Scientists knew atoms contained both positive and negative charges, but they didn't know exactly how these were arranged. Thomson's plum pudding model, though widely accepted, lacked solid experimental backing and left many questions unanswered. Was positive charge evenly spread across the atom? How were electrons arranged? And what kept atoms stable? In 1909, Ernest Rutherford, a physicist from New Zealand working at the University of Manchester, set out to investigate these mysteries. Rutherford was a student of atomic structure, deeply curious about the forces within an atom. He and his students, Hans Geiger and Ernest Marsden, designed a simple but ingenious experiment that would change atomic theory forever. The experiment Rutherford, Geiger, and Marsden devised involved firing a beam of positively charged particles, alpha particles, at an extremely thin sheet of gold foil. Alpha particles, which consist of 2 protons and 2 neutrons, are positively charged and relatively heavy compared to electrons. They were chosen for their high energy and the fact that they could penetrate thin materials, allowing them to pass through the foil with minimal interaction, at least according to the predictions of the plum pudding model. If Thomson's model were correct, the alpha particles should pass almost straight through the foil, perhaps being slightly deflected by the pudding of positive charge in the atom. After all, in Thomson's view, the positive charge was weakly distributed throughout the atom, offering little resistance to the alpha particles. To detect the path of these particles, Rutherford's team used a screen coated with a zinc sulfide layer, which would flash when struck by an alpha particle. By observing the pattern of flashes on this screen, they could determine the paths of the alpha particles as they passed through or bounced off the gold foil. The results were both astonishing and puzzling. Most of the alpha particles did indeed pass through the foil with minimal deflection, just as the plum pudding model would predict. However, a small number of particles were deflected at large angles, some even rebounding almost straight back toward the source. This unexpected observation left Rutherford astonished. In his own words, he later remarked that it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The plum pudding model could not explain such large deflections. There had to be something much more concentrated within the atom that was strong enough to repel the alpha particles. Rutherford concluded that the atom's positive charge was not spread out evenly, as Thomson had suggested. Instead, it was concentrated in a very small, dense center, which he called the nucleus. The nucleus, Rutherford realized, contained nearly all the mass of the atom and carried a positive charge strong enough to repel the alpha particles that came close to it. The rest of the atom, Rutherford inferred, was mostly empty space, with electrons orbiting around this central nucleus. This was a radical shift from the idea of a pudding filled with positive charge to a structured model in which electrons moved around a dense core. This nuclear model of the atom not only explained the deflection patterns observed in the experiment, but also laid the groundwork for the planetary model of the atom, where electrons orbit a central nucleus in a manner similar to planets orbiting the sun. Rutherford's model transformed our understanding of atomic structure. His discovery of the nucleus paved the way for future developments in atomic theory, including Niels Bohr's model of the atom, which introduced quantized electron orbits and further explained atomic stability. Rutherford's work was also foundational for the field of nuclear physics. In 1917, he became the first to successfully split the atom, identifying the proton as a fundamental particle within the nucleus. Beyond atomic theory, Rutherford's findings reshaped our understanding of matter itself. The idea that atoms are mostly empty space was startling. It revealed that the solidity we perceive in matter is largely an illusion. a result of electromagnetic forces, and not a packed mass of particles. This concept would later inform quantum mechanics, as scientists sought to understand the forces that govern subatomic particles. In retrospect, Rutherford's experiment was elegantly simple, yet it yielded insights that were anything but. By challenging the prevailing assumptions of his time, Rutherford uncovered one of the fundamental structures of the natural world. His discovery of the nucleus and the new atomic model didn't just update the scientific picture of the atom, it revolutionized physics, influencing everything from chemistry to quantum mechanics. The gold foil experiment is often celebrated not just for its groundbreaking findings, but also for its exemplary scientific approach. It showed how a well-designed experiment could dismantle established ideas and lead to a paradigm shift. Rutherford, with his open-minded interpretation and willingness to question accepted theories, set a high standard for scientific inquiry. In the end, Rutherford's work exemplifies the spirit of discovery, an experiment that seemed straightforward at the outset but yielded answers to some of the deepest questions about the structure of matter. His insights continue to shape our understanding of the atomic world and underscore the power of curiosity-driven science. Discovery of the electron. In the late 19th century, scientists were closing in on one of the most important discoveries in the history of physics, the electron. Before its discovery, the structure of the atom was a mystery. Many believed it was indivisible, the smallest building block of matter. This belief stemmed from ancient Greek philosophers, particularly Democritus, who had coined the term atom from the Greek word atomos, meaning uncuttable or indivisible. However, as experimental techniques advanced, scientists began finding clues that hinted at the atom's complexity, and the story of the electron's discovery would become a pivotal moment in unraveling that complexity. The journey to the electron's discovery begins with experiments on cathode rays. In the mid-1800s, scientists were fascinated by a strange phenomenon that occurred in vacuum tubes. When a high voltage was applied across two electrodes in a partially evacuated glass tube, a mysterious glow would appear inside. These glowing rays, known as cathode rays, seemed to flow from the negative electrode, or cathode, toward the positive electrode, or anode. Yet, the nature of these rays puzzled scientists. Were they particles, or were they waves of some kind? A series of experiments conducted throughout the late 19th century revealed that these rays could be deflected by magnetic and electric fields, which hinted at a particle-like nature. However, the scientific community remained divided, with some believing that cathode rays were a new type of wave, similar to light, and others arguing they were composed of particles. It was J.J. Thomson, an English physicist, who would solve this mystery. In 1897, Joseph John Thomson set up a series of experiments at the Cavendish Laboratory in Cambridge to analyze cathode rays more precisely. Thomson was determined to find out if cathode rays were indeed particles, and if so, what kind of properties they had. Using a specialized cathode ray tube that allowed him to apply both an electric and a magnetic field to the rays, Thomson was able to measure how the rays were deflected in each field. This setup was crucial. By adjusting the strength of the electric and magnetic fields until the deflection of the cathode rays canceled out, Thomson could calculate the ratio of the particle's charge to its mass, known as the charge-to-mass ratio, EEM. His measurements revealed that these particles were roughly 1,800 times lighter than a hydrogen atom, the lightest atom known. This was astounding. No one had ever imagined that there could be particles so much smaller than atoms. From his experiments, Thomson concluded that cathode rays were composed of particles that were far smaller than any atom, and carried a negative electric charge. This discovery was revolutionary because it contradicted the idea that atoms were indivisible. Thomson had not only demonstrated that atoms could indeed be split into smaller parts, but he had also discovered the very first subatomic particle, which he named the electron. To help explain his findings, Thomson proposed a new model of the atom. Since he had observed negatively charged electrons, he reasoned that atoms must also contain positive charge to balance out the negative charge of the electrons. This led to the creation of the plum pudding model, in which an atom was envisioned as a pudding of positive charge, with negatively charged electrons embedded within it like plums in a dessert. Although the model was ultimately replaced by later discoveries, it represented a major step forward in understanding atomic structure. The discovery of the electron had immediate and profound implications. By proving that atoms contained even smaller particles, Thomson had opened the door to an entirely new realm of science, subatomic physics. The existence of electrons challenged scientists to rethink the nature of matter itself and raised new questions. If atoms contained electrons, where was the positive charge located? How were electrons arranged within atoms, and what held these particles together? Thomson's work also inspired a new generation of scientists. The quest to understand atomic structure became a central focus in physics, leading to groundbreaking work by Ernest Rutherford, who later identified the atomic nucleus, and Niels Bohr, who proposed a model of the atom that incorporated quantum mechanics. Moreover, the discovery of the electron had immediate applications. Electronics, as a field, owes its origins to Thomson's discovery, as understanding the behavior of electrons laid the groundwork for the development of transistors, semiconductors, and computing today. Nearly every piece of technology, from smartphones to medical imaging devices, relies on principles first glimpsed through the study of the electron. Reflecting on the discovery of the electron, it's remarkable how much impact a single breakthrough can have on science and society. Thomson's meticulous experiments showed how careful observation and a willingness to challenge accepted ideas could redefine our understanding of the universe. The electron's discovery marked the beginning of quantum theory and modern atomic physics, setting science on a course that would lead to some of the most profound advancements of the 20th and 21st centuries. In many ways, Thomson's work epitomizes the spirit of scientific discovery. He took what appeared to be a simple phenomenon, a glowing ray in a glass tube, and pursued it relentlessly, even when it defied the understanding of the time. Today, every time we flip a light switch, send an email, or use a computer, we are indirectly benefiting from Thomson's dedication to unraveling the mysteries of the electron. And so, with his discovery, J.J. Thomson didn't just identify a new particle. He forever changed the way we understand the fabric of matter and paved the way for the atomic age, theory of relativity. The story of the theory of relativity begins at the dawn of the 20th century, a time when science was beginning to challenge the very foundations of classical physics. For centuries, Isaac Newton's laws had dominated our understanding of motion, gravity, and the cosmos. But as scientists peered deeper into the workings of the universe, they discovered strange and perplexing phenomena that Newton's framework couldn't fully explain. The man who would rewrite the laws of space and time and change the course of science forever was Albert Einstein. Before Einstein, the scientific world had a well-accepted view of space and time, thanks to the works of Newton. His laws seemed to govern everything from the fall of an apple to the motion of planets. Space was considered to be a static, unchanging stage, and time was thought to flow at a constant rate everywhere. But something began to unravel this neat picture in the late 1800s and early 1900s, the behavior of light. In 1865, James Clerk Maxwell, a Scottish physicist, had formulated the equations that describe electromagnetic waves, including light. According to Maxwell, light was a form of energy that traveled in waves. More importantly, these waves were self-sustaining electric and magnetic fields created and propagated each other, traveling through space at a constant speed of about 299,792 kilometers per second, the speed of light, symbolized as c. This idea that light had a fixed speed regardless of the observer's motion was deeply puzzling. The Michelson-Morley experiment in 1887, which tried to measure the speed of light in relation to a supposed medium called the ether, a hypothetical substance thought to carry light waves, had failed to detect any difference. It seemed that no matter how fast the Earth was moving through space, the speed of light remained constant. This observation shook the foundation of classical physics. Enter Albert Einstein. Born in 1879, Einstein was an unconventional thinker who saw the world of physics not just through equations, but through thought experiments. He was inspired by the strange behavior of light and the mysteries of the ether. Instead of accepting the idea of ether or sticking with Newtonian physics, Einstein had a radical idea. What if space and time themselves were not fixed and absolute? What if they were dynamic, malleable, and could stretch or shrink, depending on the conditions of the universe? This was the birth of special relativity. In 1905, at the age of 26, Einstein published a paper titled On the Electrodynamics of Moving Bodies, in which he proposed his theory of special relativity. He suggested two simple but profound ideas that would change everything. 1. The laws of physics are the same for all observers, no matter how fast they are moving. Whether you are standing still, walking, or riding a train, the physical laws, like the rules governing light and motion, don't change. 2. The speed of light is constant for all observers, no matter how fast they are moving relative to the light source. This was a stunning idea. The concept that the speed of light is the same for everyone, regardless of their motion or the motion of the light source, shattered the old understanding of space and time. Under Newtonian physics, we would expect that if you were moving toward a light source, you'd measure the speed of light as faster than someone who was moving away from the source. But Einstein's theory said that light speed didn't change. It was the same for everyone, no matter how they moved. The consequences: time and space are not what they seem. Einstein's breakthrough in special relativity also introduced an entirely new way of thinking about space and time. If time and space were fixed, they were easily understood and predictable. But in Einstein's world, space and time were interconnected. They were not absolute, unchanging entities. They were fluid. The concept of space-time was born, and ideas that fused the three dimensions of space, length, width, and height, with the dimension of time into a four-dimensional continuum. This realization had far-reaching consequences. One of the most famous results of special relativity is time dilation, the idea that time moves slower for objects that are moving near the speed of light. Imagine you were on a spaceship traveling at 99% the speed of light. If you traveled for what seemed like 1 year to you on the ship, you would return to Earth to find that many years had passed on Earth. The faster you move, the more your time slows down compared to someone who is standing still. Another remarkable result was length contraction. As objects move faster and approach the speed of light, their length in the direction of motion seems to shrink. An astronaut traveling near the speed of light might look at a stick of normal length and find that it appears to shrink when viewed from the perspective of someone on Earth. The grand leap, general relativity, and gravity. Einstein didn't stop with special relativity. In 1915, he introduced general relativity, a broader theory that included gravity, something special relativity didn't address. Before Einstein, gravity was understood as a force, as described by Newton's law of gravitation. But Einstein showed that gravity wasn't just a force. It was a result of the warping of space-time by mass. Imagine space-time as a stretched-out rubber sheet. If you place a heavy ball in the center, it causes the sheet to sag around the ball. This is how massive objects like stars or planets warp space-time. Smaller objects like planets or satellites move along these curves, which we experience as the force of gravity. For the first time, gravity was understood not as an invisible force acting at a distance, but as a bending of the very fabric of the universe itself. The legacy of relativity. Einstein's theory of relativity had profound implications for both physics and our view of the universe. It was confirmed through experiments like the bending of light around the sun during a solar eclipse, which was observed by Arthur Eddington in 1919. The results matched Einstein's predictions exactly. Today, relativity forms the cornerstone of modern physics. GPS satellites, for example, must account for time dilation effects, predicted by Einstein's theory to provide accurate positioning data. Without relativity, the world of modern technology, and even our understanding of the universe, would be unrecognizable. The theory of relativity didn't just revolutionize physics. It changed the way we think about time, space, and reality itself. It showed us that the universe is far more complex and stranger than we ever imagined, forever altering our perspective of the world around us. The photoelectric effect. The photoelectric effect is one of the cornerstones of quantum physics, and it marks a pivotal moment in the journey toward understanding the strange and counterintuitive world of subatomic particles. In the early 20th century, physicists were already puzzled by some phenomena that didn't quite fit into the classical framework of physics. Among these anomalies was the way light interacted with metals to release electrons, a phenomenon that seemed to challenge everything physicists thought they knew about light. Enter Albert Einstein, whose work on the photoelectric effect would not only solve this mystery, but also lay the foundation for the quantum revolution. To understand the significance of the photoelectric effect, we first need to understand what was going on in the world of physics at the time. In the 19th century, light was traditionally thought of as a wave. This wave theory of light was beautifully explained by James Clerk Maxwell, whose equation showed that light was an electromagnetic wave traveling through space as oscillating electric and magnetic fields. This wave theory worked perfectly to explain many phenomena, from the bending of light around objects to the colors seen in a rainbow. But something curious began to happen when light interacted with metal surfaces. Scientists had observed that when light of a certain frequency was shone onto a metal surface, electrons were emitted from the metal. This was called the photoelectric effect. In theory, according to classical physics, this should have been a simple process. The wave-like nature of light suggested that if the light's intensity, brightness, was increased, the energy of the waves should also increase. Therefore, it was expected that brighter light would knock electrons out of a metal surface more effectively, regardless of the frequency of the light. However, experiments showed a surprising result. The energy of the emitted electrons did not depend on the brightness of the light. Instead, the light had to have a certain minimum frequency called the threshold frequency before any electrons were ejected. Once the frequency was above this threshold, the energy of the emitted electrons increased with the light's intensity, but only if the frequency was high enough. This was a major puzzle. If light were indeed just a wave, as classical physics suggested, the results didn't make sense. Why was the frequency, not the intensity, so crucial for the emission of electrons? This is where Albert Einstein entered the picture. In 1905, in a paper that would forever change the course of physics, Einstein proposed a radically new idea. Light could also behave as if it were made of particles. These particles, which he called quanta, later known as photons, carried energy that was proportional to the frequency of the light. Einstein argued that when light hits a metal surface, it is the individual photons, not the overall wave of light, that transfer their energy to the electrons. If a photon has enough energy, that is, if its frequency is above the threshold, it can knock an electron loose from the metal surface. If the photon's energy is less than the threshold, it will not have enough power to eject an electron, no matter how bright the light is. In classical wave theory, the intensity of light is linked to the amplitude of the wave. The greater the intensity, the more energy the wave carries, and thus more electrons should be ejected, regardless of the light's frequency. But Einstein's explanation turned this view upside down. With his particle theory of light, it wasn't the intensity that mattered, but the frequency. A bright light of low frequency still wouldn't have enough energy per photon to release an electron, no matter how many photons it had. Only high-frequency light, like ultraviolet light, contained photons with enough energy to knock electrons loose. This was a key insight that would eventually lead to the development of quantum mechanics, a field of physics that governs the behavior of particles at the smallest scales. Einstein's work showed that energy, light, and matter were not as separate as they once seemed. Instead, light could behave both as a wave and a particle, depending on the situation, a principle known as wave-particle duality. Einstein's explanation of the photoelectric effect was groundbreaking, but it wasn't immediately accepted by all scientists. The notion that light could act as both a wave and a particle was difficult for many to grasp, as it contradicted centuries of established thinking. However, the experimental evidence was undeniable. Einstein's work on the photoelectric effect was confirmed by numerous experiments, and in 1921 he was awarded the Nobel Prize in Physics for his contributions to our understanding of light. This discovery had far-reaching consequences. It not only helped to establish the theory of quantum mechanics, but also provided a clear demonstration of the quantization of energy, the idea that energy comes in discrete packets rather than being continuous. This idea would later extend to the behavior of atoms, electrons, and other subatomic particles. Furthermore, the photoelectric effect provided practical applications in technology. The phenomenon is the basis for devices such as solar cells, which convert sunlight into electricity, photodetectors, and light sensors, all of which rely on the interaction of light and matter in ways that Einstein helped explain. The photoelectric effect wasn't just an isolated phenomenon. It was a key piece of the puzzle that allowed scientists to understand the nature of light, energy, and matter at the deepest level. Einstein's work on the photoelectric effect remains one of the most important contributions to modern physics, showing us that light has a dual nature and laying the foundation for the quantum world that would be developed in the decades following his discoveries. In a sense, the photoelectric effect is a window into the quantum world where the rules are very different from our everyday experience. It's a world where particles can act like waves, energy comes in discrete packets, and time and space themselves become malleable. And it all started with a simple yet profound question about the nature of light and how it interacts with matter, questions that continue to shape the way we explore and understand the universe today. Quantum mechanics. In the early 20th century, physicists found themselves on the brink of an extraordinary breakthrough. Classical physics, with its elegant laws governing motion, gravity, and electricity, had done a remarkable job of explaining the world around us. Yet, as scientists peered deeper into the realm of the very small, the behavior of matter began to defy these well-established laws. The minute particles that made up atoms and molecules didn't behave like anything we had observed before. Atoms didn't follow the predictable paths classical physics suggested. Instead, these particles seemed to exist in a strange, fluctuating world governed by rules that were far from intuitive. This strange new world would come to be called quantum mechanics. The seeds of quantum mechanics were first sown in the late 19th century, with the study of blackbody radiation. Scientists were trying to understand how objects like metal rods emitted radiation when heated. Classical physics suggested that objects at high temperatures should emit an endless amount of energy in a rainbow of wavelengths. Yet experiments showed that only certain wavelengths were emitted, and the amount of energy emitted at each wavelength was sharply limited. This was known as the ultraviolet catastrophe, a paradox that classical physics couldn't explain. The breakthrough came in 1900 when Max Planck, a German physicist, proposed a radical idea. Planck suggested that energy wasn't emitted in a continuous stream, but rather in discrete packets, or quanta. This was the first crack in the armor of classical physics. Planck's idea introduced the concept of quantization, the idea that energy, at the smallest scale, exists in discrete quantities. Though Planck's work solved the blackbody radiation problem, it was seen as a mathematical trick to avoid the paradox, rather than a fundamental shift in understanding. Just 5 years later, in 1905, Albert Einstein took Planck's idea a step further. Einstein, in his study of the photoelectric effect, proposed that light, which had been treated as a wave, also had a particle-like nature. He suggested that light was composed of discrete packets of energy, which he called photons. When light struck a material, the photons would transfer their energy to electrons, knocking them free from the material's surface, much like how balls of energy might knock particles loose from a surface. Einstein's work showed that light behaved both like a wave and a particle, depending on the situation. This became the wave-particle duality. His explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921 and laid the groundwork for the quantum revolution. Light wasn't just a wave, and it wasn't just a particle. It was something in between, depending on how we observed it. But it wasn't just light that needed a new explanation. By the 1920s, physicists were finding that atoms themselves weren't behaving according to classical physics. The idea of atoms as tiny billiard balls following well-defined orbits around the nucleus was being shattered. Niels Bohr, in 1913, proposed a new model of the atom based on quantized energy levels. In Bohr's model, electrons orbit the nucleus at certain discrete distances and could only gain or lose energy by jumping between these orbits. This idea was revolutionary. It explained why atoms emitted light only at specific wavelengths, and it introduced the idea that matter, too, might exhibit quantum properties. But the most famous contributions to the development of quantum mechanics came in the mid-1920s, when several physicists, including Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, contributed to the formal development of quantum theory. In 1925, Heisenberg developed matrix mechanics, a mathematical framework that described the behavior of particles in terms of observable quantities like position and momentum. His work was groundbreaking, but it didn't provide a clear picture of what was happening at the quantum level. Just a year later, Schrödinger developed his famous wave equation, which treated particles as waves rather than solid objects. The equation was a significant advance. It allowed physicists to predict where a particle might be though it only gave probabilities, not certainties. The key insight of quantum mechanics was that particles, like electrons, didn't have definite positions or speeds until they were measured. Before being observed, particles existed in a superposition of all possible states, as waves of probability. When a measurement was made, the wave of possibilities collapsed, and the particle was found at a specific position. This fundamental uncertainty was formalized by Heisenberg's uncertainty principle, which stated that we cannot know both the position and momentum of a particle with absolute certainty at the same time. What quantum mechanics revealed was a world utterly unlike anything we could observe with our senses. At the quantum level, particles could exist in multiple states at once, superposition, be instantly connected across vast distances, entanglement, and move in ways that seemed to defy classical logic. But perhaps most surprisingly, these strange behaviors were not the result of flawed experiments or theoretical mistakes. Rather, they were the very nature of reality itself, shaped by the probabilistic laws of quantum mechanics. The key to understanding this new reality lies in the idea that at very small scales, the rules we take for granted in the macroscopic world, like certainty, continuity, and determinism, don't apply. Instead, probability and uncertainty take center stage. The behavior of particles can only be predicted in terms of the likelihood of finding them in particular states, not with certainty. In fact, many of the principles that define the quantum world, like the wave-particle duality, superposition, and entanglement, are so strange that they challenge our basic understanding of reality. Quantum mechanics opened up a new way of thinking about the universe and led to the development of countless modern technologies, including transistors, lasers, and even the computer you are using right now. But it also raised deeper philosophical questions. If particles exist in superpositions, how can they choose which state to be in when measured? If particles are entangled, does that imply some form of communication faster than the speed of light? These mysteries continue to shape the study of quantum mechanics today. But one thing is certain: quantum mechanics has completely reshaped our understanding of the universe at its most fundamental level. It's not just a set of mathematical formulas. It's a radically new way of understanding the nature of reality itself. In conclusion, quantum mechanics is one of the most successful theories in all of science. It has been tested and confirmed in countless experiments, and its implications continue to drive advancements in technology and our understanding of the universe. While the quantum world may seem strange and unfathomable, it is, at its heart, a world governed by fundamental principles that describe everything from the smallest particles to the entire cosmos. It is, in essence, the rulebook for the universe at its most microscopic level. The uncertainty principle. Imagine you're at a concert trying to capture a perfect moment on your camera. You aim the lens and focus carefully on the stage, trying to capture a musician in action. As you get the perfect shot, something unexpected happens. The musician starts to move just as you click the shutter. The moment is blurry, and the motion isn't clear in the photograph. Now, imagine the opposite. If you had zoomed out to capture the full stage and froze the shot, the musician might be perfectly still, but the moment's detail is lost. The more you focus on one detail, position or movement, the more you lose track of the other. In a sense, this experience is not unlike a fundamental property of the quantum world, a concept known as Heisenberg's uncertainty principle. Just as in photography, where the clarity of one aspect comes at the cost of another, quantum particles, like electrons, cannot have both their position and momentum precisely measured at the same time, no matter how advanced our tools get. This principle, discovered by Werner Heisenberg in 1927, challenges our intuitive understanding of measurement and observation at the microscopic scale. To understand the development of this principle, let's step back to the 1920s. By this time, quantum mechanics was rapidly developing. Scientists like Niels Bohr, Erwin Schrödinger, and Werner Heisenberg had laid out the early foundations of quantum theory. In this new framework, particles like electrons were no longer seen as simple solid objects, but as quantum waves, existing in a probability cloud of different possible locations and energies. These particles could behave like both particles and waves, depending on the situation. A bizarre realization that shook the very foundation of classical physics. Heisenberg's contribution came when he was grappling with the complexities of quantum behavior. He was searching for a way to reconcile the behavior of particles and waves in a consistent way. At the time, Heisenberg had been studying the interactions between light and electrons, especially when light interacted with the electrons in an atom. The more precisely you tried to measure the position of an electron, the more uncertain its momentum, how fast it was moving and in which direction, became, and vice versa. This observation led Heisenberg to propose that there was a fundamental limit to how precisely certain pairs of physical properties could be measured at the same time. The uncertainty principle was born out of this realization. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Heisenberg's insight into this idea was not just philosophical, it had a mathematical foundation. This equation describes the precise relationship between the uncertainty in the position of a particle and the uncertainty in its momentum. The more precisely you measure one, the greater the uncertainty in the other. At first glance, this might seem like an experimental flaw, a limitation of our tools, but Heisenberg's point was much deeper. It was not a problem of measurement, but a fundamental aspect of nature itself. In the quantum world, uncertainty wasn't just a limitation of technology, it was built into the fabric of reality. A quantum challenge to determinism. Before Heisenberg's discovery, classical physics was grounded in the idea of determinism. Determinism states that if we know the position and velocity of a particle at one moment in time, we can predict where it will be in the future. It was a comforting, predictable worldview where everything from the motion of planets to the flight of a baseball could be understood through precise measurements and formulas. However, in the quantum world, Heisenberg's principle shattered this deterministic view. The behavior of quantum particles could no longer be described with the same certainty. The notion that we could know both the exact position and momentum of a particle at the same time was simply false. Instead, we had to embrace a new philosophy. Quantum mechanics was inherently probabilistic. Rather than precise trajectories, quantum particles exist in a cloud of probabilities, only becoming defined when we measure them. This uncertainty wasn't just due to our lack of knowledge. It was an inherent property of the quantum world. The philosophical implications. The uncertainty principle raised profound questions not only about physics, but also about the nature of reality itself. Could there ever be a point where we could know everything about a system, its position, velocity, energy, and more? The answer, according to Heisenberg, was a resounding no. This led to a shift in how physicists and philosophers viewed the act of measurement. In classical physics, measurement was seen as passive. We simply observe the system without affecting it. But in the quantum world, the very act of measurement influences the system. The particle's wave-like nature collapses into a specific position or momentum only once we measure it, and in doing so, we lose all other potentialities. This led to the Copenhagen interpretation of quantum mechanics, championed by Niels Bohr and Werner Heisenberg. According to this view, reality at the quantum level is not fixed until it is observed. Until we measure it, a particle exists in a superposition of all possible states. Once we observe it, it chooses a specific state. But the uncertainty principle ensures that this choice comes with a trade-off between position and momentum, everyday life, and the uncertainty principle. While the uncertainty principle might seem like an abstract concept far removed from daily life, it has practical implications in our modern world. The principle is behind the phenomenon of quantum tunneling, where particles pass through barriers that they classically shouldn't be able to. This principle is the reason why some technologies, like semiconductors and MRI scanners, work. The behavior of electrons in semiconductors is governed by the uncertainty principle, which allows modern electronics to function. Though the uncertainty principle challenges our classical intuitions about the universe, it has been validated countless times through experiments. It is a cornerstone of quantum mechanics and has had profound effects on technology, philosophy, and even our understanding of the universe. By showing us that there is a limit to our knowledge of the quantum world, Heisenberg revealed a deeper truth. Uncertainty is not just an inconvenience, but a fundamental feature of reality. Conclusion: the uncertainty principle doesn't just shape how we look at particles and waves, but it fundamentally changes our understanding of knowledge itself. It suggests that there are limits to what we can know about the universe. As technology advances and quantum mechanics continues to evolve, these principles will remain at the heart of our quest to understand the very nature of reality. Through uncertainty, we learn that there is beauty in the mystery, and sometimes the greatest discoveries come from embracing what we cannot fully know. Quantum entanglement. Imagine two friends separated by thousands of miles, yet when one of them laughs or cries, the other instantly knows. This seemingly magical link, one that defies distance and logic, resembles a concept in quantum physics known as quantum entanglement, discovered in the early 20th century. Entanglement has been famously described by Albert Einstein as spooky action at a distance. Despite sounding mystical, quantum entanglement is one of the most verified and compelling phenomena in quantum mechanics, a phenomenon that challenges our very understanding of space, time, and reality. The roots of quantum entanglement date back to the early 20th century, during the infancy of quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment, now famously known as the EPR paradox. Einstein-Podolsky-Rosen paradox. At the time, Einstein was skeptical of quantum mechanics. He couldn't reconcile the inherent randomness and uncertainty of quantum theory with his belief in a predictable, orderly universe. Einstein and his colleagues suggested that if quantum mechanics were correct, it implied the existence of strange, non-local connections between particles. In other words, two particles could be linked in such a way that the state of one particle would instantaneously influence the state of another, no matter how far apart they were. They believed this spooky action at a distance hinted at a flaw in quantum mechanics. For them, this paradox was a way of highlighting the theory's incompleteness, suggesting there must be hidden variables that explained the behavior in a more classical, predictable way. Then, in the 1960s, John Bell, an Irish physicist, took Einstein's challenge seriously. Bell devised a mathematical framework called Bell's theorem, which allowed scientists to test the validity of quantum mechanics versus Einstein's hidden variable theory. His theorem showed that if quantum mechanics was correct, there would be measurable differences in the statistical correlations between entangled particles compared to any classical theory. In the following decades, several experiments tested Bell's theorem, most famously those led by physicist Alain Aspect in the 1980s. Each experiment confirmed that quantum mechanics held true. Entangled particles did indeed behave as if they were instantaneously connected, regardless of the distance between them. These results defied any classical explanation and solidified entanglement as a fundamental aspect of quantum mechanics. Quantum entanglement is a unique relationship between two or more particles in which the particles become linked, such that the state of one particle directly influences the state of the other, no matter the distance between them. If one particle's properties are measured, the properties of its entangled partner are determined immediately, even if it's all on the other side of the universe. To understand this more intuitively, let's imagine flipping two coins that are somehow quantum entangled. Normally, if we flip two coins, we'd expect independent results. One coin might land heads while the other might land tails. However, with entangled coins, every time you flip one coin and observe its outcome, the other coin instantly shows the opposite result, as if they communicate with each other instantaneously. No matter where these coins are located, whether in your hand or across the galaxy, the link between them holds. In quantum terms, this means if two particles, such as electrons or photons, are entangled, they share a quantum state. The state of one particle is mirrored in the other. For example, if two photons are entangled, and you measure one photon to have a certain polarization, say vertical, the other photon's polarization will instantaneously align in a complementary way, regardless of the physical distance separating them. Entanglement defies classical logic because, according to the theory of relativity, information or influence shouldn't be able to travel faster than the speed of light. In entanglement, however, the changes appear to be instantaneous. This phenomenon seems to suggest that space, in some way, is an illusion, or at the very least, doesn't function as we intuitively understand it. The spooky connection between entangled particles suggests that, at a fundamental level, everything might be interconnected in ways that transcend traditional notions of locality. Although entanglement is strange and counterintuitive, it's far from being just a theoretical curiosity. Quantum entanglement has real-world applications, especially in the burgeoning field of quantum computing. Unlike classical bits that are either a 0 or a 1, quantum bits, or qubits, can exist in a state of 0, 1, or both simultaneously, thanks to a principle called superposition. Entanglement allows qubits to interact in complex ways, enabling quantum computers to perform calculations exponentially faster than traditional computers for certain tasks. Another exciting application is quantum cryptography, where entanglement can be used to create secure communication channels. With entangled particles, any eavesdropper attempting to intercept the particles would disturb the entanglement, revealing their presence immediately. This could pave the way for unbreakable encryption methods that provide unparalleled levels of security in communication. Entanglement also plays a role in emerging research on quantum teleportation. While it doesn't involve physically transporting objects as in science fiction, quantum teleportation allows the instantaneous transfer of quantum information from one location to another using entanglement. This has significant implications for data transfer and secure communication across vast distances. Quantum entanglement challenges our fundamental understanding of reality, sparking debate and philosophical discussions. The phenomenon raises questions about the nature of space and time, the limits of human knowledge, and the interconnectedness of the universe. Some physicists and philosophers speculate that entanglement could hint at a deeper, underlying reality, a type of hidden layer beneath the observable universe where everything is interconnected. The nature of this connection is still a mystery. Is there a hidden mechanism that links entangled particles, or is space itself, as we understand it, not as fundamental as it seems? Quantum entanglement encourages us to explore these ideas and consider possibilities that defy our current understanding of the universe. Quantum entanglement represents one of the most profound insights into the quantum world. Through the efforts of Einstein, Podolsky, Rosenbell, and countless experimental physicists, we've learned that the quantum world operates by rules that challenge classical physics and our very perception of reality. Entanglement suggests a universe more interconnected than we can imagine, a world where particles separated by immense distances still speak to one another instantaneously. It's a phenomenon that opens up questions about the fundamental structure of the universe, hinting at hidden layers and relationships that transcend our current understanding. In studying entanglement, we are reminded that reality is not as straightforward as it appears, and that, at its deepest level, the universe holds mysteries waiting to be unveiled. The Big Bang Theory. Imagine rewinding the history of the universe like a film, watching galaxies drift backward, stars collapse, and cosmic clouds of dust and gas condense into tight knots. This backward journey reveals a universe that once occupied an unimaginably small, dense, and hot point. This concept, the Big Bang Theory, is humanity's best scientific explanation for how the universe began and evolved. But this theory wasn't born in a flash. It took decades of debate, evidence, and serendipitous discoveries to piece it together. The story of the Big Bang Theory starts with Albert Einstein in the early 20th century. Einstein's theory of general relativity, published in 1915, described how gravity works on a cosmic scale, revealing that massive objects warp space and time around them. Yet, when applying his equations to the entire universe, Einstein was baffled. His equations seemed to suggest an expanding or contracting universe, which conflicted with the common belief at the time that the universe was static and unchanging. To align his theory with the steady-state idea, Einstein introduced a cosmological constant to force his equations into a model of a stable universe. Meanwhile, Georges Lemaitre, a Belgian priest and mathematician, saw something intriguing in Einstein's equations. In 1927, he proposed the bold idea that the universe wasn't static, but expanding. Lemaitre suggested that if we ran the universe's expansion backward, we'd reach a point where everything began, a primeval atom from which the universe burst into existence. At the time, this concept was radical and widely dismissed, even by Einstein himself. In the late 1920s, the American astronomer Edwin Hubble delivered groundbreaking observational evidence that would transform Lemaitre's hypothesis into a scientifically backed theory. Using the powerful telescopes at Mount Wilson Observatory, Hubble studied distant galaxies and found that they all appeared to be moving away from Earth. Even more astonishing, the farther a galaxy was, the faster it was receding. This phenomenon, now known as Hubble's law, pointed to an expanding universe. Hubble's observations showed that galaxies are not stationary, but are being pushed apart, suggesting that the universe itself is stretching. Hubble's findings gave credibility to the idea of a dynamic universe, yet the scientific community was divided. Skepticism remained, especially among those who held on to the idea of a steady-state universe, but evidence continued to pile up. One of the most compelling pieces of evidence for the Big Bang theory came in the form of an unexpected discovery in the 1960s. Physicists Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, testing a large antenna built for satellite communications. However, their work was plagued by an annoying hum of static noise that seemed to come from every direction. They tried everything to eliminate the noise, even going as far as cleaning pigeon droppings off the antenna, but the hum persisted. As it turned out, Penzias and Wilson had accidentally detected something groundbreaking: cosmic microwave background, CMB radiation. This faint glow of radiation, now understood as the afterglow of the Big Bang, was the thermal remnant of the universe's fiery birth. The CMB is a snapshot of the universe at around 380,000 years old, when it had cooled enough for atoms to form and photons to travel freely through space. This discovery was monumental. It provided a fossil of the early universe and was the smoking gun that validated the Big Bang theory. The Big Bang theory describes an event around 13.8 billion years ago when the universe began as an incredibly hot, dense point, often called a singularity. For reasons still unknown, this singularity began to expand, setting off the process of cosmic evolution. In the first moments after the Big Bang, the universe was a seething mass of particles, protons, neutrons, electrons, all too hot and energetic to form atoms. As the universe continued to expand and cool, these particles eventually combined, forming hydrogen and helium, the first atoms. In the first few 100 million years, slight variations in the density of matter led to the gravitational collapse of gas clouds, which formed the first stars and galaxies. Over billions of years, galaxies merged, stars were born and died, and complex structures formed, leading to the universe we observe today. To grasp the concept of an expanding universe, imagine a balloon with dots on its surface. Each dot represents a galaxy. As you blow up the balloon, the surface expands and the dots move away from each other. This is similar to how galaxies recede from each other as space itself stretches, though unlike the balloon, the universe expands in 3 dimensions, with galaxies moving apart in every direction. Another useful analogy is to think of a loaf of raisin bread rising in the oven. As the dough, representing space, expands, the raisins, representing galaxies, move away from each other. Importantly, it's not that the raisins themselves are moving through the dough. Rather, the dough itself is expanding and carrying the raisins along with it. This expansion isn't happening within pre-existing space. The creation of space itself is the essence of the Big Bang. The Big Bang theory is the cornerstone of modern cosmology, providing a framework to understand the evolution of the universe from its infancy to today. Yet, as much as we know, many mysteries remain. Scientists still seek to understand what triggered the Big Bang. The theory also doesn't explain what happened before this event, or what lies beyond our observable universe. Additionally, discoveries in the late 20th and early 21st centuries, such as dark matter and dark energy, suggest that our understanding of the cosmos is incomplete. Dark matter, which doesn't emit or interact with light, seems to hold galaxies together, while dark energy is accelerating the universe's expansion. These components make up most of the universe, yet they remain largely mysterious, leading scientists to wonder if an even deeper, more comprehensive theory of the cosmos awaits discovery. The Big Bang theory stands as one of the most profound scientific insights into our origins. By observing the universe's expansion and listening to the cosmic hum of background radiation, scientists have pieced together a story that traces our existence back to an ancient, fiery beginning. This theory transforms the universe from a static backdrop into a dynamic, evolving entity with a beginning, a middle, and possibly an end. And while the Big Bang Theory answers some of humanity's biggest questions, it leaves us with others, new frontiers for exploration, as we continue to seek the truth of our cosmic origins. The standard model of particle physics. Imagine if the universe were like an enormous Lego set, with each structure around us, stars, planets, humans, and even the air, constructed from tiny blocks, each with unique properties. The standard model of particle physics is like the instruction manual for these blocks, identifying the basic pieces that compose everything in the universe and the forces that hold them together. But the journey to this manual wasn't straightforward. It was the result of decades of groundbreaking experiments, brilliant theories, and an ongoing effort to decode the language of nature at its most fundamental level. The discovery of the standard model didn't happen in a single moment or by a single scientist. It began in the late 19th and early 20th centuries as physicists tried to make sense of the smallest components of matter. J.J. Thomson's discovery of the electron in 1897 showed that atoms were not indivisible, as once thought, but contained even smaller parts. Later, in 1911, Ernest Rutherford's gold foil experiment revealed the atomic nucleus, a dense center surrounded by electrons. These discoveries kicked off a wave of research that led to the realization that atoms were not fundamental at all. They were built from even tinier particles. Throughout the early 20th century, scientists uncovered several mysterious particles, and by the 1930s, the proton and neutron were identified as the building blocks of atomic nuclei. But these discoveries raised questions. Were protons and neutrons fundamental, or did they also contain smaller parts? What forces held them together? As physics progressed, quantum mechanics and special relativity laid the groundwork for understanding particles at tiny scales and high speeds. In the 1950s and 1960s, the development of particle accelerators, huge machines that could smash particles together at high speeds, allowed scientists to observe phenomena they'd never seen before. Every collision seemed to reveal new particles, from pions to muons to strange quarks. There were so many new discoveries that physicists jokingly called it a particle zoo. It was during this particle explosion that scientists began looking for a unifying theory that could organize these particles and describe their interactions. This search led to the Standard Model, a theoretical framework combining three of nature's four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. One of the breakthrough ideas in the Standard Model came from Murray Gell-Mann in 1964, who proposed the concept of quarks. Quarks are elementary particles that combine to form protons, neutrons, and other particles known as hadrons. Just like letters in an alphabet can combine in various ways to form words, quarks combine in different combinations to form the particles we observe in nature. Gell-Mann initially proposed three types of quarks: up, down, and strange, which explained many of the particles scientists were observing. With quarks, the idea of a fundamental building block was revived, but there was more to understand. In the Standard Model, there are actually 6 types of quarks: up, down, charm, strange, top, and bottom. These quarks combine in various ways to make protons and neutrons, among other particles. Quarks are bound together by the strong force mediated by particles called gluons, which act as the glue holding quarks together inside protons and neutrons. The Standard Model also explains how particles interact through fundamental forces. Besides quarks, the Standard Model includes leptons, like the familiar electron, and force-carrying particles known as bosons. Each force has a corresponding boson that carries the force. For example, photons carry the electromagnetic force, allowing charged particles to interact. The W and Z bosons are responsible for the weak nuclear force, which governs radioactive decay. Gluons mediate the strong force that binds quarks together in atomic nuclei. These discoveries gradually came together to form the Standard Model, but one important piece was missing: mass. While the Standard Model successfully explained the fundamental particles and their interactions, scientists were puzzled about how particles acquire mass. In 1964, physicists Peter Higgs and others proposed the existence of a field, now called the Higgs field, which pervades all of space. Particles interacting with this field would acquire mass, similar to how a ball rolling through water moves slower than one rolling through the air. The existence of the Higgs field implied a new particle, the Higgs boson. For decades, the Higgs boson was theoretical. It had to be there according to the Standard Model, but no one had observed it. Finally, in 2012, the Large Hadron Collider, LHC, in Switzerland provided enough energy to detect the Higgs boson, confirming a central prediction of the Standard Model. One way to understand the Standard Model is to imagine a huge, invisible web that connects everything in the universe. The web is made up of particles that interact with each other through exchanges of invisible messenger particles. For example, if you and a friend toss a ball back and forth, the ball can represent a force, say the electromagnetic force, and by throwing it, you're interacting. The Standard Model explains how particles toss these messengers, like photons or gluons, to experience forces. Another analogy is to think of quarks as building blocks that come in different flavors or types. Just as a sandwich could be made from different ingredients, particles like protons and neutrons are formed from different combinations of quarks, held together by gluons. This recipe of quarks, gluons, and force carriers forms the basis of everything around us. The Standard Model is remarkably successful, describing nearly every known particle interaction and enabling predictions that have stood up to experimental testing. However, it's not a complete theory. The model doesn't include gravity, and it doesn't explain dark matter and dark energy mysterious components that make up most of the universe's mass and energy. There's also the question of why there are precisely 6 quarks and 6 leptons, or why particles have the masses they do. The Standard Model of particle physics is a crowning achievement of modern science, encapsulating our understanding of the universe's fundamental particles and forces. It is the blueprint for the microcosmic world, capturing everything from the tiniest quarks to the interactions that shape the cosmos. And while it answers many questions, it leaves the door open to deeper mysteries, encouraging physicists to continue exploring, discovering, and refining the story of what our universe is made of and how it all fits together. Hawking radiation. Imagine black holes as cosmic monsters devouring everything that crosses their path, including light. For centuries, they were thought of as the ultimate cosmic traps. Once something fell into a black hole, it was gone forever. However, in the early 1970s, a young physicist named Stephen Hawking challenged this idea with a radical discovery. Black holes could actually emit energy, and over time, they could even disappear completely. This groundbreaking idea, known as Hawking radiation, transformed our understanding of black holes and raised profound questions about the nature of the universe. To understand how Hawking arrived at his theory, we need to look at the backdrop of the 20th century physics landscape, dominated by 2 seemingly incompatible theories: Einstein's general theory of relativity and quantum mechanics' general relativity. Explains how massive objects warp the fabric of space and time, forming gravitational fields, while quantum mechanics describes the behavior of particles on an incredibly small scale. Yet black holes challenge both theories, sitting at the intersection where gravity becomes so intense that quantum effects can no longer be ignored. In the early 1970s, Hawking, a young physicist at Cambridge University, began investigating the properties of black holes using these 2 theories. Black holes were thought to only grow by absorbing matter and energy, and were otherwise inert. But quantum mechanics hinted at something different happening at the event horizon, the boundary beyond which nothing, not even light, can escape. To develop his theory, Hawking turned to the strange, often counterintuitive world of quantum mechanics, particularly the idea of quantum fluctuations. In the quantum world, empty space isn't truly empty. It's a seething, energetic vacuum where pairs of particles and antiparticles spontaneously appear and annihilate each other. These particles typically pop into existence, interact briefly, and then disappear, leaving no trace behind. However, Hawking proposed that when these pairs of particles form near the event horizon of a black hole, something unusual might happen. Sometimes, instead of annihilating each other, one particle could fall into the black hole, while the other escapes into space. In this case, the escaped particle would appear as radiation, visible from a distance. This radiation escaping from the black hole became known as Hawking radiation. Hawking realized that as this radiation continued to be emitted, it would carry energy away from the black hole. Over time, this energy loss would cause the black hole to lose mass, a process known as black hole evaporation. If this process continues long enough, the black hole could, in theory, completely evaporate, disappearing into a burst of energy. This was a revolutionary concept. Before Hawking's work, black holes were thought to be eternal. Hawking radiation showed that black holes could actually die, fundamentally changing the way we think about these cosmic objects. It also suggested that black holes weren't just one-way traps. They had a way of releasing energy back into the universe. The discovery of Hawking radiation didn't just add a new chapter to black hole physics, it also forced physicists to confront deep questions about information in the universe. In quantum mechanics, information about the state of a system is preserved over time, meaning we could theoretically trace back the history of any particle. But if black holes could emit radiation and eventually evaporate, what would happen to all the information that fell into them? This paradox, known as the information paradox, has puzzled physicists for decades. If the information within a black hole is lost forever, it would contradict the principles of quantum mechanics. If it somehow survives, we would need new physics to explain how. To this day, scientists are still grappling with these questions, and the study of Hawking radiation remains a cornerstone of efforts to reconcile general relativity with quantum mechanics. Imagine a bustling city with a central recycling plant that never lets any waste escape. For years, it's believed that any item that goes into this plant is permanently destroyed. But then, a scientist discovers that, under certain conditions, some of the waste particles at the plant's edge actually escape. Even more astonishing, as these particles continue to escape, the recycling plant itself begins to shrink and eventually disappears. This surprising turn of events is analogous to Hawking's insight. Black holes, once thought to be cosmic traps, could actually lose mass over time through radiation and ultimately even cease to exist. Hawking's discovery of black hole radiation made him a celebrity in the physics world and beyond. It provided a glimpse into the quantum workings of black holes and brought physicists a step closer to understanding how the universe's most powerful forces interact. Today, Hawking radiation is considered one of the great theoretical breakthroughs of 20th century physics. It has inspired countless research efforts aimed at understanding black holes, quantum gravity, and the nature of space and time. Directly observing Hawking, radiation is practically impossible. The radiation is incredibly faint, far weaker than the cosmic background radiation left over from the Big Bang. For most black holes, the process of evaporation would take far longer than the current age of the universe. However, scientists have designed experiments on Earth to mimic aspects of Hawking radiation using analog systems like sound waves in certain materials, hoping these experiments will give insights into the behavior of black holes. Hawking radiation stands as a monumental leap in our understanding of black holes. It's a reminder that even the most mysterious entities in the universe aren't beyond human comprehension. Stephen Hawking's insight showed that black holes aren't eternal prisons, but dynamic objects that interact with the universe in complex ways. Through Hawking's discovery, we gained a clearer view of the cosmos and set the stage for future breakthroughs as scientists continue to explore the mind-bending mysteries of space, time, and the fundamental nature of reality. Superconductivity and superfluidity. In the early 20th century, as scientists began to experiment with temperatures close to absolute zero, the lowest possible temperature around minus 273.15 degrees Celsius or 0 Kelvin, they discovered strange and mysterious properties in materials that defied conventional physics. Two of the most intriguing phenomena they encountered were superconductivity and superfluidity. These effects, which occur in certain materials when they reach extremely low temperatures, opened up a new realm in physics and continue to inspire breakthroughs across science and technology. The story of superconductivity begins in 1911 with Dutch physicist Heike Kamerlingh-Onnes at the University of Leiden. Onnes was a pioneer in the study of cryogenics, specializing in reaching ultra-low temperatures. In 1908, he became the first person to successfully liquefy helium, achieving temperatures just a few degrees above absolute zero. This achievement allowed him to test how materials behaved in such cold conditions. One of the key experiments Onnes conducted was on mercury, a familiar metal known to conduct electricity fairly well at room temperature. But as he cooled the mercury closer to absolute zero, something astonishing happened. At a temperature of 4.2 Kelvin, 268.95 degrees Celsius, the mercury's electrical resistance, the usual hindrance that causes energy loss in the form of heat, suddenly dropped to zero. In other words, the mercury allowed electric current to flow without any resistance at all. This was the first documented observation of superconductivity. To understand how groundbreaking this discovery was, consider an everyday analogy. Normally, when electricity flows through a wire, some energy is lost as heat because of resistance. This is like water flowing through a pipe with friction. Some of the water's energy dissipates as it rubs against the walls of the pipe. But superconductors are like perfectly frictionless pipes for electricity. In a superconductor, an electric current could theoretically flow forever without losing any energy. This property holds extraordinary potential for energy-efficient power grids, MRI machines, particle accelerators, and even maglev trains. But what exactly causes this strange effect? Scientists would spend decades unraveling the mystery of superconductivity. It wasn't until 1957 that American physicists John Bardeen, Leon Cooper, and Robert Schrieffer proposed the BCS theory to explain the phenomenon. They suggested that at ultra-low temperatures, electrons in a superconductor form pairs, called Cooper pairs, which move through the material in a coordinated manner that prevents energy loss from resistance. These pairs can slide through the atomic lattice of the material without being scattered, enabling zero resistance flow. Superfluidity, discovered a couple of decades later, shares an eerie resemblance to superconductivity, but with a twist. It occurs in liquids instead of solids. In the 1930s, Soviet physicist Pyotr Kapitsa and American physicists John Allen and Don Messener observed a startling behavior in liquid helium when it was cooled to 2.17 Kelvin. Below this temperature, liquid helium transitioned into a phase with zero viscosity, meaning it could flow without any resistance whatsoever. Kapitsa coined this phenomenon superfluidity. Imagine a glass of water where if you stirred it, the water would continue to spin indefinitely. This defies our everyday experience with fluids, which always lose energy due to friction and eventually come to a standstill. Superfluid helium, however, can climb up walls, seep through the tiniest of cracks, and maintain a perpetual flow in a closed loop without any external energy input. Superfluidity baffled scientists because it seemed to contradict all known laws of fluid dynamics. It turned out that this strange state of matter could be explained by quantum mechanics, particularly the idea of Bose-Einstein condensation. In simple terms, when helium atoms reach super cold temperatures, they behave more like waves than particles, overlapping and moving in perfect harmony as a single quantum state. This collective behavior allows the helium atoms to flow without losing energy to viscosity. The discoveries of superconductivity and superfluidity have had profound effects on science and technology. Superconductors, for example, have made possible some of the most powerful magnets in existence. These magnets are used in MRI machines to generate high-quality images of the human body, and in particle accelerators, like the Large Hadron Collider, to probe the fundamental particles of the universe. The zero-resistance property also makes superconductors ideal for high-speed maglev trains, which can levitate and move without friction, potentially revolutionizing transportation. Superfluidity, while still more confined to theoretical and experimental realms, has had significant implications in understanding quantum mechanics and the behavior of matter at extreme conditions. The study of superfluid helium, in particular, has provided insights into quantum turbulence and has inspired the exploration of other exotic states of matter, such as Bose-Einstein condensative and atomic gases. Consider a regular liquid as a group of people walking through a crowded hallway. Each person must adjust their pace to avoid bumping into others, leading to an overall slow and chaotic movement. But in the case of a superfluid, it's as if all the people were suddenly in perfect harmony, colliding without any collisions, almost as if they were moving as one. This is similar to how atoms behave in a superfluid state, moving collectively without any friction. Similarly, for superconductors, imagine electrons in a conductor like cars on a busy road, where each car occasionally gets slowed down by bumps and turns, representing resistance. In a superconductor, however, all cars move in pairs, coordinated so perfectly that they encounter no obstacles and can drive endlessly without losing speed. This frictionless movement explains why superconductors are so remarkable. The discoveries of superconductivity and superfluidity opened a window into the strange, quantum-dominated world of ultra-cold physics, challenging our intuitions and broadening our understanding of matter. These phenomena not only demonstrate the fascinating behaviors that emerge at extremely low temperatures, but also provide valuable applications in technology and fundamental science. As scientists continue to experiment with these states, including efforts to achieve superconductivity at higher temperatures, the possibilities for energy efficiency, medical technology, and our grasp of the quantum world grow ever more promising. The anthropic principle. The anthropic principle is a philosophical framework that tries to answer one of the most profound questions humanity has ever asked. Why does the universe appear to be finely tuned for life? The term anthropic refers to humans, and the principle essentially asks why our universe has the exact physical conditions that allow conscious beings to exist and observe it. Developed and formalized in the latter half of the 20th century, the anthropic principle has become a major topic in both physics and philosophy, influencing debates about cosmology, quantum mechanics, and even the existence of parallel universes. The story begins in the early 20th century when physicists began discovering the fundamental forces and constants that govern our universe, such as the speed of light, gravitational strength, and the charge of the electron. Physicists noticed that if any of these constants were even slightly different, the universe as we know it couldn't exist. Stars wouldn't form, atoms wouldn't bond, and life would be impossible. This led to a realization. Our universe seemed to be perfectly tuned for the existence of life, almost like a cosmic symphony where every note and pitch is precisely calibrated for harmony. Physicists in the 1960s and 1970s, including Brendan Carter, a British cosmologist, began to explicitly formulate what became known as the anthropic principle. Carter introduced this idea in 1973 during a conference celebrating the 500th birthday of Nicholas Copernicus. Carter argued that the universe's parameters aren't randomly configured. Instead, they appear biophilic, conducive to life. The anthropic principle comes in two main forms: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. 1. Weak anthropic principle, WAP. This version simply states that the universe must have properties compatible with life because we are here to observe it. In other words, the fact that we observe a life-friendly universe is not surprising because if the universe didn't allow life, we wouldn't be here to notice. The weak anthropic principle is more of a tautology. It doesn't explain why the universe has these properties, only that it must, given our existence. 2. Strong anthropic principle, SAP. The strong anthropic principle goes a step further, suggesting that the universe's properties are not just accidentally compatible with life, but that they somehow require or are destined to produce observers. This implies a deeper reason behind the universe's design, almost hinting at purpose or intentionality, though this notion remains controversial. Imagine you walk into a kitchen and find a cake baking in the oven, filled with the exact ingredients that make it both delicious and structurally sound. This cake has the perfect amount of flour, sugar, eggs, and other ingredients to produce a fluffy and flavorful dessert. If any ingredient were slightly off, the cake would collapse or taste terrible. Now, you might wonder, why does this cake have the precise ingredients needed to make it delicious? The anthropic principle would suggest that the cake had to have these specific conditions. Otherwise, it wouldn't be there to be observed as a cake at all. In the same way, our universe appears to be made up of just the right ingredients to allow conscious beings to observe it. But why it has these ingredients is where the mystery deepens. In the late 20th century, the anthropic principle became a central point of discussion in physics and cosmology, especially as theories about the multiverse gained traction. The multiverse theory proposes that there might be an enormous or even infinite number of universes, each with its own unique set of physical laws and constants. In this framework, the anthropic principle can be explained by probability. Out of countless universes, we happen to be in one where the constants allow for life, just by chance. The anthropic principle has also played a crucial role in the development of string theory and quantum mechanics. Some interpretations of quantum mechanics, for instance, suggest that the universe doesn't settle into a single state until it is observed. This ties in intriguingly with the anthropic principle, as it implies that our observation has an active role in defining the universe's parameters. The anthropic principle has not been without controversy. Some physicists and philosophers argue that it's not really a scientific principle because it doesn't provide testable predictions. Rather, it seems more like a philosophical argument. Critics say it's a cop-out explanation for the universe's fine-tuning, avoiding the search for deeper underlying laws. Others, however, see it as an essential aspect of modern cosmology. Supporters argue that the anthropic principle helps prevent scientists from pursuing unnecessary explanations for phenomena that are merely preconditions for our existence. For example, instead of asking why the gravitational constant has its exact value, one could simply say, if it were different, we wouldn't be here to ask. In recent years, the anthropic principle has continued to inspire new scientific ideas. Physicist Leonard Susskind, a key proponent of the multiverse theory, has suggested that the anthropic principle could help explain the cosmological constant problem. The cosmological constant, which relates to the universe's expansion, is precisely tuned to a value that allows galaxies to form and life to develop. Susskind and others argue that the multiverse theory combined with the anthropic principle might explain why our universe has this exact value. Another notable figure, the British physicist Stephen Hawking, was both intrigued by and skeptical of the anthropic principle. He recognized its utility in understanding why the universe allows for life, but he was cautious about attributing purpose to the universe, preferring explanations that could be grounded in mathematical laws and physical theories. The anthropic principle remains one of the most compelling and debated ideas in modern science. By focusing on the conditions necessary for life, it challenges our understanding of the universe and prompts us to ask whether there is a deeper reason behind these conditions. Whether viewed as a tautology, a guiding framework, or a hint of purpose, the anthropic principle forces us to reflect on our place in the cosmos. It's a reminder that the universe, with its intricate symphony of laws and constants, is both comprehensible and profoundly mysterious. And perhaps, just perhaps, it's tuned for us to observe, question, and explore. String theory. String theory is one of the most ambitious ideas in physics, aiming to be a theory of everything that could reconcile quantum mechanics and general relativity, two of the most fundamental, yet fundamentally different frameworks in modern physics. In its essence, string theory suggests that the most basic elements of the universe are not particles, like electrons or quarks, but tiny vibrating strings. Each string vibrates at a specific frequency, and the mode of vibration determines the properties of the particle it manifests as. It's as if the universe is an orchestra, with different instruments playing unique notes to create the complex melody of reality. String theory wasn't originally aimed at unifying physics. Its origins trace back to the 1960s, a time when physicists were wrestling with the mysteries of the atomic nucleus. In those days, they had discovered that particles called hadrons, like protons and neutrons, interacted in ways that were not fully understood. Italian physicist Gabriele Veneziano was exploring the unusual properties of these interactions when he stumbled upon a mathematical formula, later known as the Veneziano amplitude, that described the interactions of these particles surprisingly well. At the time, physicists didn't know why this formula worked. They only knew it seemed to describe reality accurately. It was in 1970 that Leonard Susskind, along with Holger Beck-Nielsen and Yukiro Nambu, found that Veneziano's mathematical formula could be visualized as describing a one-dimensional vibrating string. This was a paradigm shift. Instead of particles being treated as dimensionless points, they were now conceived of as tiny loops or segments of strings that could vibrate in various ways. When these strings oscillate, they give rise to different particles, much like how a single guitar string can produce different notes based on how it's plucked or tuned. As physicists began exploring the implications of string theory, they realized it offered a remarkable and unique perspective. It had the potential to unify all fundamental forces under one framework. However, early versions of string theory had limitations and inconsistencies. For instance, they predicted not 3 but 10 dimensions of space and time, 6 more than what we experience. This initially seemed absurd, but physicists soon learned that these extra dimensions could be compactified or curled up so tightly that we wouldn't perceive them in our everyday reality. As the theory developed, physicists began to explore ways to extend it further, giving birth to superstring theory in the 1980s. Superstring theory introduced the concept of supersymmetry, a proposed symmetry between particles that carry forces, like photons, and particles that make up matter, like electrons. Supersymmetry added stability to the equations, allowing physicists to develop more consistent models. Superstring theory was powerful and elegant, unifying all four fundamental forces: gravity, electromagnetism, strong nuclear force, and the weak nuclear force under a single overarching framework. For the first time, string theory appeared as a promising candidate for the long-sought theory of everything. To understand the basic idea behind string theory, imagine a guitar. Each string on a guitar can vibrate at different frequencies, producing different notes. In the same way, each string in string theory can vibrate at different frequencies, producing different fundamental particles. A string vibrating one way might appear as an electron, while another mode of vibration could make it behave like a photon. Just as a guitarist can create music by manipulating the strings, the universe plays these strings to create particles and forces, forming the intricate symphony of reality. During the mid-1980s, string theorists encountered a new puzzle. Instead of a single unified theory, they had 5 competing versions of string theory, each with different mathematical structures. This was frustrating, as physicists were looking for one cohesive theory to explain everything. But in the 1990s, Edward Witten, a leading theoretical physicist, proposed a new idea. These 5 string theories might actually be different expressions of a single, more fundamental theory. He called this the M theory, which added yet another spatial dimension, bringing the total to 11. Under M theory, strings were not the only fundamental objects. There were also multidimensional brains that could exist in different dimensions. The idea of brains opened up new avenues for understanding our universe, with one of the most intriguing possibilities being that our universe itself could be a 3-dimensional brain floating within a higher dimensional space. This concept suggested that other brains, or parallel universes, might exist alongside ours, leading to groundbreaking ideas about the multiverse. While string theory is mathematically elegant and conceptually beautiful, it's still largely theoretical, as it has yet to make predictions that can be directly tested in experiments. This lack of empirical evidence is one of the major criticisms against string theory. Some physicists argue that a theory that cannot be tested might fall outside the bounds of traditional science. However, supporters of string theory point out that it has provided crucial insights into the nature of black holes, entropy, and even the early moments of the Big Bang. Despite the challenges, string theory remains one of the leading candidates for a theory of everything, guiding physicists toward new mathematical tools and ideas. It has inspired thousands of researchers and has even influenced fields outside of physics, such as pure mathematics. String theory represents humanity's relentless pursuit of understanding the cosmos at the deepest level. It pushes the boundaries of what we know about space, time, and matter, suggesting that the very fabric of reality might be woven from tiny, vibrating strings. Though we may be far from confirming its predictions, string theory serves as a beacon in the quest to uncover the ultimate nature of the universe. Just as the early explorers charted unknown territories, string theorists venture into the abstract landscapes of mathematics and physics, driven by the hope that one day we may have a complete understanding of reality itself. Cosmic microwave background radiation. The discovery of cosmic microwave background, CMB, radiation ranks as one of the most profound breakthroughs in our understanding of the universe. This radiation provides a window back in time, offering scientists a glimpse of the universe as it was nearly 14 billion years ago, shortly after the Big Bang. But the story of how this faint glow of ancient radiation was discovered is one of unexpected finds and scientific curiosity, with roots in a quiet field in New Jersey and theories that emerged decades before. To understand what CMB radiation is, it helps to imagine the universe shortly after the Big Bang. Around 380,000 years post-Big Bang, the universe was a scorching, dense plasma, a thick, foggy soup of protons, electrons, and photons. Light, in the form of photons, was constantly scattering off particles in this plasma, unable to travel freely. Then, as the universe expanded, it cooled down to a temperature low enough for protons and electrons to combine and form neutral hydrogen atoms. This change allowed photons to move freely, filling the universe with light. This moment is known as the epoch of recombination, and the light from this time has been traveling through space ever since. Over billions of years, as the universe expanded further, the wavelengths of these photons stretched out, shifting into the microwave portion of the electromagnetic spectrum, creating what we now detect as the CMB radiation. Long before it was actually discovered, CMB radiation was predicted by theorists in the 1940s. Physicist George Gamow and his colleagues Ralph Alpher and Robert Herman were studying the implications of the Big Bang model and realized that if the universe had indeed begun in a hot, dense state, then there should be residual radiation from that initial phase. They calculated that this leftover radiation would have cooled down by now just a few degrees above absolute zero, and it would permeate all of space. However, this prediction did not immediately lead to experimental searches, and it would take 2 decades before anyone stumbled upon it. In the early 1960s, Arno Penzias and Robert Wilson, 2 radio astronomers at Bell Telephone Laboratories in New Jersey, were experimenting with a large horn antenna designed to detect faint radio signals for satellite communication. But their antenna picked up a mysterious noise they couldn't explain, a faint, persistent hum that seemed to come from every direction in the sky. Penzias and Wilson checked and rechecked their equipment, suspecting technical interference, or perhaps even interference from the nearby city. They cleaned out pigeon droppings from the horn, thinking that might be the cause, yet the noise persisted. It had no identifiable source and didn't vary with the time of day season or the direction in which they pointed the antenna. This static remained a puzzle until they heard about the work of Robert Dick and his team at Princeton University, who were working on the very prediction made by Gamow's team years earlier, the residual radiation from the Big Bang. When Penzias and Wilson reached out to Dick, he immediately recognized the significance of their findings. His team at Princeton had been searching for evidence of this background radiation, but they hadn't yet succeeded. Upon hearing about the static Penzias and Wilson had detected, Dick famously said, "Well, boys, we've been scooped." The signal Penzias and Wilson detected was precisely what Gamow, Alpher, and Herman had predicted, the faint residual radiation from the Big Bang, cooled and stretched into microwaves by the expansion of the universe. This was a monumental discovery, providing the first concrete observational evidence for the Big Bang theory. Following this discovery, the scientific community set out to study the CMB radiation in greater detail. In the 1990s, NASA launched the COBE, Cosmic Background Explorer satellite, which confirmed Penzias and Wilson's findings with much greater accuracy. COBE also found tiny fluctuations in the temperature of the CMB across the sky, variations that correspond to the small density differences in the early universe that would eventually grow to form galaxies, stars, and planets. These fluctuations were like a snapshot of the seeds of structure in the cosmos, allowing scientists to understand how the universe's large-scale structure developed. Later, even more advanced satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite provided even more detailed maps of the CMB. With these maps, scientists could measure the age, composition, and curvature of the universe with unprecedented precision. The CMB radiation became a cosmic blueprint, encoding information about the universe's infancy, composition, and eventual fate. Imagine shouting into a canyon and hearing an echo reverberate back to you. The CMB radiation is like an echo from the early universe, a faint but persistent hum that provides invaluable information about where we came from. Just as the echo reflects the original shout, the CMB radiation reflects the conditions of the early universe, stretched and softened by the vast distances it has traveled. This radiation fills the universe, providing us with a backdrop, a faint afterglow of creation that illuminates the origins of everything we know. The discovery of CMB radiation transformed cosmology. It provided a foundation for the Big Bang theory, allowing scientists to transition from speculative cosmological theories to a concrete model based on empirical evidence. It offered a way to see back to the earliest moments of time, to understand the universe's structure, and even predict its fate. For their groundbreaking work, Penzias and Wilson received the Nobel Prize in Physics in 1978, cementing their accidental discovery as one of the most significant scientific achievements of the 20th century. Today, the study of the CMB continues, with physicists probing it for insights into dark matter, dark energy, and other cosmic mysteries. The CMB radiation, once a mysterious noise on a radio antenna, has become a cornerstone of our understanding of the universe, forever changing the way we view our cosmic origins. Dark matter and dark energy. The discovery of dark matter and dark energy stands among the most intriguing, mysterious chapters in modern physics. These two invisible entities are believed to compose around 95% of the universe, yet they defy direct observation. Their existence was suggested not by sight, but by the strange, unexpected ways they influence the visible cosmos. The story of their discovery is a winding journey of curiosity, mathematical puzzles, and the persistence of scientists who noticed things in the universe weren't quite adding up. The search for dark matter began with a peculiar observation in the 1930s by Swiss astronomer Fritz Zwicky. Studying the Coma Cluster, a collection of galaxies bound together by gravity, Zwicky noticed something odd. The galaxies were moving far faster than they should have been if their observable mass was all that existed. According to Newton's laws, they should have flown apart at those speeds, yet they remained bound together. Zwicky theorized that there must be some kind of invisible, missing mass holding the galaxies together. He coined the term dunkle materie, or dark matter, to describe this unseen mass, which seemed to provide the gravitational glue binding galaxies in place. While Zwicky's theory was ahead of its time and largely overlooked for years, the idea of missing mass reemerged in the 1970s, thanks to the pioneering work of American astronomer Vera Rubin. Rubin was studying the rotation curves of individual galaxies, specifically how fast stars orbit around their galactic centers. According to established laws of physics, stars farther from the center of a galaxy should orbit more slowly than those closer in, much like planets around the sun. However, Rubin discovered that stars in galaxies rotated at nearly the same speed, regardless of their distance from the center. This uniform rotation implied that galaxies had far more mass than what was visible in the form of stars, gas, and dust. Like Zwicky, Rubin deduced that galaxies contained an enormous amount of unseen matter that provided the gravitational pull necessary to account for this rotation pattern. Her work offered compelling evidence for dark matter and transformed it from a fringe idea into one of the central questions in cosmology. While dark matter addresses the invisible mass holding galaxies together, dark energy addresses an entirely different mystery, the accelerating expansion of the universe. To understand dark energy, we need to jump forward to the 1990s, when two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to measure the rate of cosmic expansion. At the time, scientists expected the universe's expansion, which began with the Big Bang, to be slowing down due to gravity. After all, if galaxies and clusters are gravitationally attracted to each other, this pull should eventually decelerate the expansion of space itself. To test this theory, Perlmutter, Schmidt, and Rees's teams observed Type Ia supernovae, explosions of dying stars that act like standard candles due to their consistent luminosity, making them ideal for measuring cosmic distances. To their astonishment, the results showed the opposite of what they expected. Rather than slowing down, the universe was expanding faster. It was as if some unseen force was propelling galaxies apart, accelerating the expansion of space itself. This force was named dark energy, an enigmatic pressure countering gravity on a cosmic scale, responsible for pushing galaxies farther and farther away from each other. Imagine watching a play in a theater. The actors, lights, and props on stage are the visible matter we can observe, stars, galaxies, and everything we see in the universe. But for the play to run smoothly, there must be a team of stage managers, lighting coordinators, and directors working behind the scenes, influencing the production without being seen. Dark matter is like the set crew, moving the scenery, setting the stage, and ensuring everything holds together. Dark energy, on the other hand, is like a mysterious director making decisions that alter the play's pacing, creating a dynamic push that influences everything on the stage. In this analogy, dark matter holds galaxies and clusters together, while dark energy accelerates the expansion of the cosmic stage itself, increasing the distance between the galaxies as if constantly adding more space. Today, dark matter and dark energy remain two of the most significant mysteries in science. Dark matter appears to interact primarily through gravity, forming the invisible framework upon which galaxies and clusters are built. Despite decades of experiments, ranging from particle detectors deep underground to high-energy collisions in the Large Hadron Collider, scientists have yet to directly detect a dark matter particle. Current theories suggest it might be composed of exotic particles like WIMPs, weakly interacting massive particles, or axions. But without direct evidence, dark matter's nature remains speculative. Dark energy is even more elusive. Its nature is not fully understood, but one hypothesis links it to the cosmological constant that Albert Einstein once proposed in his equations of general relativity. Ironically, Einstein originally introduced the cosmological constant to keep the universe static, but later discarded it, calling it his biggest blunder when he learned the universe was expanding. In a strange twist, this cosmological constant has returned as a candidate explanation for dark energy. Understanding dark matter and dark energy is crucial because they affect everything from the shape and fate of the universe to the formation of galaxies and the distribution of cosmic structures. Dark matter explains why galaxies cluster in particular patterns, while dark energy hints at the ultimate fate of the universe. Will it continue to expand forever, ripping galaxies apart in a big rip? Or might it reach a balance where expansion halts? These questions depend largely on the behavior of dark energy, which remains one of the most tantalizing unknowns in cosmology. Research on dark matter and dark energy continues with ever-advancing technology. Telescopes like the James Webb Space Telescope and massive surveys like the Dark Energy Survey aim to gather clues about these cosmic mysteries. These tools allow scientists to map out the universe's structure with greater precision, looking for patterns and gravitational effects that could reveal the presence of dark matter or hint at the behavior of dark energy. Ultimately, dark matter and dark energy remind us of how much there is yet to discover. They point to gaps in our knowledge, urging scientists to explore, question, and push the boundaries of what we know. And though they may be invisible to us, their effects shape everything we see in the cosmos, connecting galaxies, influencing cosmic structure, and driving the expansion of the universe itself. The quest to understand them lies at the heart of modern physics, as we continue to unravel the hidden, powerful forces that sculpt the universe. Discovery of the Higgs boson. The discovery of the Higgs boson is one of the most celebrated achievements in modern physics, not just because it solved a long-standing puzzle, but because it represents a triumph of human ingenuity, engineering, and theoretical foresight. The story of the Higgs boson is one of persistence, spanning nearly half a century from its theoretical conception to its experimental confirmation, and it centers on a seemingly simple but incredibly important question: why do particles have mass? In the early 1960s, physicists were developing what we now know as the Standard Model of Particle Physics, a framework that would become a foundation for understanding the fundamental particles and forces. The Standard Model explained a lot, but it had a glaring problem. It could not account for the mass of particles without breaking key symmetries in nature, symmetries that are critical to how particles and forces interact. The equations predicted that particles like W and Z bosons, which mediate the weak force, should be massless, but experiments showed they were massive. Without an explanation for mass, the entire model was incomplete. This was where a group of theorists, including Peter Higgs, stepped in. In 1964, Higgs, along with other scientists like Robert Brute, Francois Englert, Gerald Guralnick, Carl Hagen, and Tom Kibble, proposed a radical solution, a new field, now known as the Higgs field. Higgs theorized that this field permeates the universe like an invisible molasses. As particles move through it, they interact with the field, which slows them down and gives them mass. Some particles, like photons, don't interact with this field and thus remain massless, while others, like the W and Z bosons, interact strongly with it and gain mass. To explain this visually, imagine a crowded room full of people. A person trying to cross the room encounters resistance from the crowd, which slows them down. This is akin to how particles acquire mass as they move through the Higgs field. This field is everywhere, and it interacts with particles based on specific properties, causing some to become massive, while others pass through unaffected. If this Higgs field existed, it would imply the existence of a unique particle, the Higgs boson, a quantum ripple in the field. Proving the existence of this particle became one of the great quests in particle physics. However, because of its predicted mass and the energy required to detect it, the Higgs boson was elusive, out of reach for many years. This set the stage for an unprecedented scientific endeavor, the construction of the Large Hadron Collider, LHC. The LHC, located near Geneva, Switzerland, is a massive underground particle accelerator operated by CERN, the European Organization for Nuclear Research. The LHC was designed to smash protons together at speeds near the speed of light, creating conditions so extreme that they could mimic the universe's state just after the Big Bang. In these collisions, particles break apart and interact, releasing massive amounts of energy. This process has the potential to produce heavy particles like the Higgs boson, if it exists. After years of planning and construction, the LHC began operations in 2008. Thousands of scientists and engineers from around the world collaborated on experiments specifically designed to search for the Higgs. These experiments, particularly the ATLAS and CMS experiments, were designed to detect and analyze the fleeting signs of particles produced in these high-energy collisions. Detecting the Higgs boson was no easy task. Scientists were looking for extremely subtle signs among a flood of other particle events. The Higgs boson itself decays almost immediately after it is produced, leaving behind signatures that are notoriously difficult to isolate from background noise. The data had to be filtered, analyzed, and reanalyzed to confirm any possible evidence of the Higgs. Finally, on July 4, 2012, scientists at CERN announced they had observed a particle consistent with the Higgs boson. Both the ATLAS and CMS experiments independently confirmed this result with a high degree of confidence. The discovery was hailed as a monumental breakthrough, providing the missing piece of the Standard Model and confirming the existence of the Higgs field, which imparts mass to particles. The announcement made headlines worldwide, and Peter Higgs himself, who was present at CERN that day, was visibly moved, overwhelmed by the realization of an idea he had proposed nearly 50 years earlier. The Higgs boson is sometimes called the God particle because it completes our understanding of the Standard Model, but it's more than just a theoretical milestone. The Higgs field is essential for explaining why the universe is structured as it is, with galaxies, stars, planets, and life as we know it. Without the mass generated by the Higgs field, particles wouldn't clump together to form atoms, let alone complex structures. The discovery of the Higgs boson has also opened new avenues in particle physics, providing clues that may one day help us understand mysteries like dark matter and gravity. To understand the Higgs field, imagine the universe as a vast canvas and particles as paintbrushes. The canvas has a slight resistance that affects how the paint flows. Depending on the thickness of the brush, some strokes glide easily, while others struggle against the resistance. The Higgs field is like that resistance on the canvas, determining how heavy each stroke appears. For particles in the universe, this field gives them mass, affecting how they move, interact, and combine to form everything we observe. The discovery of the Higgs boson was a crowning achievement, but it is also just the beginning. The properties of the Higgs boson itself may hold secrets to physics beyond the Standard Model, such as supersymmetry or extra dimensions. Today, physicists are probing the Higgs boson with greater precision, hoping to uncover deviations or peculiarities that could lead to new discoveries. In essence, the Higgs boson is a window into the deeper structure of reality. It reveals how particles acquire mass, why they come together to form matter, and what underpins the very fabric of the universe. The journey of its discovery is a testament to human curiosity, collaboration, and perseverance, and it serves as a reminder that, in physics, every answer leads to new, intriguing questions. Gravitational waves. Detection. Gravitational waves, ripples in the fabric of space-time itself, are one of the most fascinating and profound predictions of Einstein's theory of general relativity. For over a century, these waves were theorized but remained elusive, seemingly beyond our reach. Yet, in 2015, after decades of scientific pursuit, these invisible waves were detected for the first time, confirming one of the most profound predictions in physics. This discovery opened a new era in astrophysics, allowing us to listen to the universe in a completely new way. The concept of gravitational waves first arose from Albert Einstein's general theory of relativity, published in 1915. The theory revolutionized our understanding of gravity, not as a force between masses, but as the warping or curvature of space-time caused by the presence of mass and energy. Imagine space-time as a giant trampoline. When you place a heavy ball in the center, it causes the fabric to stretch and curve. Smaller objects, like marbles, roll toward the ball, following the curvature of the fabric. In the same way, planets and stars follow curved paths in the fabric of space-time. Einstein's equations predicted that massive objects, when they move, cause ripples in this fabric, gravitational waves. These waves are created when massive objects like black holes or neutron stars accelerate, particularly in events like mergers, where two massive objects collide and spiral into each other. However, Einstein himself wasn't certain that gravitational waves could ever be detected. The waves, if they existed, would be incredibly faint by the time they reached Earth, making their detection extraordinarily difficult. The idea that gravitational waves could be detected was captivating, but how could such faint disturbances in space-time be measured? The waves would stretch and compress space itself, but the effect on objects would be minuscule, far too small to be detected by ordinary instruments. Even if two black holes collided, the stretching and squeezing caused by the waves would alter distances by less than 1,000th of the size of a proton. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, an ambitious project born out of decades of work by physicists like Rainer Weiss, Kip Thorne, and Barry Barish. The LIGO experiment, which began in the 1990s, was designed to detect these subtle distortions in space-time by measuring the minute changes in the distance between two mirrors placed miles apart. LIGO works by using an interferometer, a device that measures changes in the distance between two mirrors along two perpendicular arms. A laser beam is split in two, with one part traveling down each arm. After reflecting off the mirrors, the beams are recombined. If a gravitational wave passes through the Earth, it causes a tiny distortion in the length of one arm of the interferometer, altering the pattern in which the laser beams recombine. This shift, though infinitesimally small, can be detected by extremely sensitive equipment. On September 14, 2015, LIGO achieved the unthinkable. At 9 hours 50 minutes and 45 seconds UTC, both LIGO detectors, one located in Hanford, Washington, and the other in Livingston, Louisiana, simultaneously recorded a signal that could only be explained by the passage of gravitational waves. The waves had been produced by the collision and merger of two black holes, each about 30 times the mass of the Sun, located roughly 1.3 billion light-years away. The signal, which lasted less than a second, showed a distinctive chirp, a rapid increase in frequency and amplitude as the black holes spiraled toward each other and merged. The event was so powerful that it released more energy in a fraction of a second than the combined energy output of all the stars in the observable universe. The energy released was in the form of gravitational waves that rippled across the universe and were detected by LIGO. This first detection of gravitational waves was a monumental moment in physics and astronomy. The confirmation of the waves not only verified Einstein's century-old prediction, but also opened a new window into the universe. The discovery was made by a team of scientists working together across the world, and it was an extraordinary validation of decades of hard work, ingenuity, and belief in a theory that had often been considered too speculative to test. The detection of gravitational waves has profound implications for our understanding of the universe. It allows us to hear the violent energetic events that occur far beyond the reach of traditional telescopes. Gravitational waves carry information about the most extreme environments in the universe, places where space-time is warped and where gravity is incredibly intense, such as black hole mergers, neutron star collisions, and supernovae. Before this breakthrough, astronomers were limited to observing the universe through electromagnetic radiation, light, radio waves, X-rays, and so on. But gravitational waves are a new kind of signal, one that reveals aspects of the universe that were previously hidden. These waves provide insights into the nature of black holes, the formation of galaxies, and the very fabric of space-time itself. For instance, since the detection of the first gravitational wave signal, LIGO has recorded multiple other events, such as neutron star mergers, which are especially important for understanding phenomena like gamma-ray bursts and the production of heavy elements like gold and platinum. Gravitational wave astronomy has become a vibrant field of research, and its future looks even brighter as more detectors come online around the world, such as the Virgo detector in Europe and future planned detectors like LISA, Laser Interferometer Space Antenna, which will operate in space. The discovery of gravitational waves has not only confirmed Einstein's predictions, but also challenged our understanding of the universe in ways we're still coming to terms with. It opens the door to new theories, new questions, and new kinds of observations. For example, one of the most exciting prospects is the potential to directly study the interiors of black holes, regions where no light can escape. Gravitational waves could allow us to peer into the heart of these cosmic giants, offering a new way to study one of the most enigmatic objects in the universe. Additionally, gravitational wave detection provides a powerful tool for testing the limits of Einstein's theory of general relativity. While the theory has passed every test thrown at it so far, the detection of gravitational waves gives physicists the chance to test its predictions in extreme environments where the usual laws of physics break down. Imagine you're standing by a calm lake, watching ripples form when a stone is thrown into the water. The ripples travel outward, carrying information about the disturbance in the water. In much the same way, gravitational waves travel through the fabric of space-time, carrying information about the most violent and energetic events in the universe, just as the ripples on the water tell you something about the object that caused them. Gravitational waves tell us about the cosmic events, black hole mergers, neutron-star collisions, that created them. Before 2015, gravitational waves were mere speculation. Now, they are a tool for exploring the universe in ways that were previously unimaginable. The discovery of gravitational waves marked the dawn of a new age of cosmic exploration, allowing us to listen to the universe in a way we never could before, revealing a deeper, more mysterious cosmos than we ever imagined. Exoplanet detection and implications for life. For centuries, humanity has looked up at the stars, pondering the existence of life beyond Earth. The idea of other worlds, perhaps similar to our own, teeming with life, has fueled science fiction stories and philosophical debates. Yet, for most of history, this was purely speculative. That is, until science began to answer the question with a resounding yes. The discovery of exoplanets, planets orbiting stars beyond our own solar system, has not only confirmed that the universe is filled with other worlds, but has also opened up profound possibilities for the existence of life elsewhere. But how did we find these distant planets, and what are the implications for life beyond Earth? The story of exoplanet discovery began relatively recently, with the first confirmed exoplanet found in 1992. However, the journey to this discovery was paved with years of scientific progress, starting from a theoretical framework and evolving with advances in technology. In the 1980s, astronomers began developing methods to detect planets around other stars. But detecting exoplanets is a tricky business. Stars are so bright and distant that any planets around them are often completely overshadowed. Astronomer Alexander Woljan and his colleague Piotr Mazur made the groundbreaking discovery of the first confirmed exoplanet, not around a regular star, but around a pulsar, a highly magnetized, rapidly rotating neutron star. The pulsar, named PSRB 1257+12, emitted regular pulses of radio waves, and its regularity allowed Woljan and Mazur to detect small gravitational wobbles caused by the presence of orbiting planets. This was a small but significant step. The planets were extremely unusual, small and rocky, with no potential for life, but they demonstrated that exoplanets could exist outside our solar system. Although the pulsar planets were a milestone, the real revolution in exoplanet detection came with the launch of the Kepler Space Telescope in 2009. Kepler was designed specifically to hunt for Earth-like planets in the habitable zone, the region around a star where conditions might be right for liquid water and potentially life to exist. Kepler's primary method of detecting exoplanets was the transit method. The idea is simple but ingenious. When a planet passes in front of its star, as seen from Earth, it blocks a tiny fraction of the star's light, causing a slight dimming. By measuring these dimming events precisely, astronomers can determine the size of the planet, its orbit, and even its composition. Because Kepler stared at a patch of sky for over 9 years, it observed thousands of stars, carefully measuring the subtle dimming effects caused by orbiting planets. In 2012, Kepler made an incredible announcement. It had identified over 2,300 potential exoplanets. Many of these were Earth-sized or smaller, and some were in the habitable zone of their stars. This was a game-changer. For the first time, we were not only finding exoplanets, but identifying potentially habitable worlds, planets that might host life in ways we had only previously dreamed of. The discovery of Kepler 22b, an exoplanet, in the habitable zone of its star, was one of the most exciting early finds. It's about 600 light-years away from Earth, but its discovery sent shockwaves through the scientific community, suggesting that planets in the habitable zone could be relatively common in our galaxy. As technology improved, so did our ability to detect a wider range of planets. By 2015, astronomers had discovered a staggering 1,000 confirmed exoplanets, and the discoveries have continued to accumulate at an even faster pace. Many of these planets are in unexpected places, challenging previous assumptions. For example, some exoplanets are much larger than Jupiter and orbit extremely close to their stars, while others are super-Earths, planets with masses larger than Earth, but smaller than Uranus or Neptune. Beyond the transit method, scientists have developed other techniques for finding exoplanets. The radial velocity method, also known as the Doppler method, detects the gravitational tug that a planet exerts on its parent star. As a planet orbits a star, it causes the star to wobble slightly. This wobble shifts the star's light toward the red or blue end of the spectrum, depending on whether the star is moving toward or away from Earth. By measuring these shifts, astronomers can detect the presence of planets, even without seeing them directly. Another method is direct imaging, which involves blocking out the light of a star to reveal the planets surrounding it. This technique is more challenging, but has provided fascinating results, especially in the case of young hot exoplanets that shine brightly in infrared light. The discovery of exoplanets raises one of the most profound questions of our time. Is there life out there? Given the vast number of planets in the universe, many of which share similarities with Earth, the possibility that life could exist elsewhere seems increasingly likely. In 2015, astronomers discovered Proxima b, a planet located in the habitable zone of the star Proxima Centauri, the closest star to our Sun. This discovery sparked widespread excitement as it's possible that Proxima b has liquid water on its surface, one of the key ingredients for life. While we can't say for sure if life exists on Proxima b, its discovery suggests that Earth-like conditions are not as rare as once thought. One of the most exciting aspects of exoplanet research is that it allows us to study planets in ways we couldn't before. For example, scientists are using spectroscopy to study the atmospheres of distant exoplanets. By analyzing the light that passes through or is reflected by an exoplanet's atmosphere, scientists can detect the presence of key molecules like water vapor, oxygen, or methane, molecules that could be associated with life. This technique, known as atmospheric characterization, is giving us our first glimpses of alien worlds and may one day help us identify planets that have the right conditions for life. The hunt for Earth-like planets, or Earth 2.0, continues to be one of the most exciting endeavors in modern science. While we have yet to find a perfect twin of Earth, the discovery of thousands of exoplanets, some of which lie in their star's habitable zone, gives us hope. In the coming decades, as telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope come online, we may be able to directly analyze the atmospheres of exoplanets in unprecedented detail. What does all of this mean for us? The discovery of exoplanets has shifted our perspective on the universe. It suggests that we are not alone in a barren cosmos, but part of a vast star-filled expanse teeming with possibilities. Whether we find life on an exoplanet or not, the search helps us understand our own planet, the conditions that make life possible, and our place in the universe. By exploring these distant worlds, we not only seek the potential for life beyond Earth, but also ask fundamental questions about existence itself. What makes a planet habitable? What role does life play in the grand cosmos? The discovery of exoplanets is a profound reminder that we are not isolated in the universe. We are part of an incredible cosmic experiment, one that is just beginning to reveal its secrets. Quantum computing and information theory. In the 1980s, physicist Richard Feynman famously said, "If you're not confused by quantum mechanics, you don't understand it." His statement encapsulates the oddness of the quantum world, where particles can exist in multiple states simultaneously, and where information behaves in ways that defy classical intuition. But this strange realm also holds the key to a breakthrough in computation and information theory that could revolutionize our world. This breakthrough is quantum computing, a concept that, at its heart, harnesses the unique properties of quantum mechanics to process information in entirely new ways. The idea of quantum computing emerged from the realization that classical computers, those powered by bits, might not be able to solve certain problems efficiently. Bits, the basic unit of classical information, can exist in one of two states, 0 or 1. While this binary system works for many tasks, it's not suitable for problems that require immense computational power, such as simulating the behavior of molecules at the quantum level or factoring large numbers for cryptography. In 1981, Feynman proposed a novel idea. Instead of relying on classical bits, why not exploit the power of quantum mechanics itself? Quantum mechanics is the branch of physics that deals with particles at the smallest scales, where phenomena like superposition, being in multiple states at once, and entanglement, instantaneous connections between particles, no matter the distance, occur. Feynman suggested that we could design a machine that harnesses these properties to simulate quantum systems far more efficiently than classical computers could. The seeds for quantum computing were planted in this moment. Feynman wasn't the only one thinking along these lines. In 1985, physicist David Deutsch of Oxford University took the next crucial step, creating a mathematical model for a quantum computer, which became known as the Deutsch model. His work laid the groundwork for understanding how a quantum computer could theoretically function. To understand how quantum computers work, we need to dive into two fundamental quantum phenomena: superposition and entanglement. Superposition. In the quantum world, particles like electrons don't just exist in one state at a time. They can exist in multiple states simultaneously. Imagine flipping a coin. It can either land heads or tails. But in the quantum world, the coin can be in a superposition of heads and tails at the same time until you observe it. Quantum computers exploit this ability, allowing a quantum bit or qubit to be both 0 and 1 simultaneously. This opens the door to processing vast amounts of information at once, vastly increasing the computational power compared to classical bits. Entanglement. When two quantum particles become entangled, their states are linked, no matter how far apart they are. If you measure one particle, you instantly know the state of the other, even if it's light years away. In quantum computing, entanglement allows qubits to work together in ways classical bits cannot, enabling quantum computers to solve complex problems exponentially faster than traditional computers. With the basic principles of quantum computing in place, the next step was to develop algorithms that could harness the power of qubits. In 1994, physicist Peter Shor made a groundbreaking contribution. He developed an algorithm that could factor large numbers exponentially faster than any known classical algorithm. This was a game changer because factoring large numbers is a core task in cryptography, specifically in RSA encryption, which is widely used to secure online communications. If a quantum computer could break RSA encryption, it would represent a monumental shift in the field of cybersecurity. Shortly after, in 1996, Love Grover developed an algorithm that could search unsorted databases faster than classical computers, a task that traditionally requires examining each entry one by one. Grover's algorithm demonstrated that quantum computers could provide speed-ups for a wide variety of tasks beyond number factoring, from optimization problems to machine learning. These developments sparked interest across both academia and industry, and the race to build a functioning quantum computer began in earnest. Building a quantum computer, however, is no simple feat. The fragile nature of quantum states, affected by factors like temperature, noise, and electromagnetic radiation, makes it incredibly challenging to create a stable qubit. Several approaches emerged to overcome these challenges, including trapped ions, superconducting circuits, and topological qubits. Trapped ions. In this approach, ions, charged atoms, are trapped using electromagnetic fields and manipulated with lasers. Each ion acts as a qubit, and their interactions are controlled by the laser pulses. This method has shown remarkable promise in lab experiments and has led to the development of small-scale quantum computers. Superconducting circuits. This approach involves using superconducting materials that can conduct electricity with zero resistance when cooled to extremely low temperatures. These circuits behave like tiny artificial atoms and can be used as qubits. Companies like IBM and Google have made significant progress with superconducting qubits, with Google's Sycamore processor famously achieving quantum supremacy in 2019 by solving a problem that would have taken a classical supercomputer thousands of years to complete. Topological qubits. A more speculative approach. Topological qubits are designed to be more resistant to error by encoding information in the topology of the quantum system. While this approach remains largely theoretical, it promises to solve one of the biggest challenges in quantum computing: error correction. While a fully functional large-scale quantum computer remains elusive, significant strides have been made in building quantum processors capable of solving specific problems. In addition to the breakthroughs in hardware, advances in quantum error correction, quantum communication, and quantum cryptography are being made at a rapid pace. Quantum computing's potential extends beyond just speed. It could unlock new solutions to complex problems in fields ranging from material science, designing new drugs or better solar panels, to artificial intelligence, creating more efficient machine learning models. For instance, quantum computers could simulate chemical reactions at the atomic level, something classical computers struggle to do. This could lead to breakthroughs in drug development, energy storage, and new materials that are currently beyond our reach. Today, companies like IBM, Google, and Microsoft are leading the charge to make quantum computing a practical reality. Startups like Rigetti Computing and IonQ are also pushing the envelope. Governments around the world are investing heavily in quantum research as the technology promises to reshape industries from finance to healthcare. But quantum computing also presents new challenges and questions. If quantum computers can break traditional encryption schemes, how can we protect our data? This is where quantum cryptography comes in, offering new ways to secure information through the principles of quantum mechanics itself. Ultimately, the discovery of quantum computing is still in its infancy, but its potential to change the world is vast. From solving problems too complex for even the fastest classical supercomputers to unlocking new technologies, quantum computing may be the next frontier in our understanding of the universe and in how we manipulate information to change the world. The theory of everything. Imagine trying to put together a jigsaw puzzle. Each piece represents a different aspect of the universe: the forces of nature, the behavior of matter, the structure of space and time. Now imagine that the pieces of the puzzle fit together perfectly, revealing a single unified picture that explains everything from the smallest particles of matter to the largest galaxies. This is the ultimate dream of physics. A theory of everything, TOE. A single framework that unifies all the forces of nature into one coherent explanation. For centuries, scientists have been working toward this elusive goal, and while it remains one of the greatest challenges in science, progress has been made. Let's take a journey through the history of the theory of everything, examining the discoveries that have brought us closer to this monumental understanding. In the early 20th century, physics was already fragmented into two main pillars. The first was classical mechanics, which explained the motion of objects in everyday life. The second was electromagnetism, the theory governing electric and magnetic forces, brilliantly formulated by James Clerk Maxwell in the 19th century. Maxwell's equations showed that light itself was an electromagnetic wave, linking electricity and magnetism in a beautiful unified theory. But then came a radical shift with the advent of quantum mechanics and general relativity, two ideas that redefined our understanding of the universe in very different ways. Quantum mechanics, developed in the early 20th century by pioneers like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, revealed that At the microscopic level, particles don't behave like solid objects. They act more like waves with probabilities and uncertainties. The concept of wave-particle duality and the uncertainty principle shattered the classical understanding of reality. General relativity, developed by Albert Einstein in 1915, gave us a new understanding of gravity. Einstein proposed that gravity isn't a force in the traditional sense, but rather a result of the warping of space-time by mass and energy. This was a far cry from Newton's classical theory of gravity, but it provided a more accurate description of the universe, especially in extreme conditions like black holes and the cosmos itself. These two theories, quantum mechanics and general relativity, were each incredibly successful in their respective domains. Quantum mechanics governed the microscopic world of atoms and particles, while general relativity described the behavior of massive objects like planets, stars, and galaxies. However, they didn't mix well. The two frameworks were fundamentally incompatible, and they couldn't explain everything. The first major step toward a theory of everything came in the mid-20th century, with the development of quantum field theory. QFT. QFT combines the principles of quantum mechanics with special relativity, and is the framework in which we understand the behavior of particles and forces. But what really brought things together was the discovery that three of the four fundamental forces of nature, electromagnetic force, weak nuclear force, and strong nuclear force, could be unified into a single framework. The standard model of particle physics is the culmination of this effort. It describes the particles that make up matter and the forces that govern them. The standard model successfully unified the electromagnetic and weak nuclear forces into the electroweak theory in the 1970s, earning physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg the Nobel Prize in Physics in 1979. In the 1980s, the discovery of the Higgs boson completed the model by explaining how particles acquire mass. The standard model, however, leaves a significant gap. It doesn't include gravity. Gravity is still described by Einstein's general relativity, and no one has yet figured out how to incorporate it into the framework of quantum mechanics. This is where the theory of everything comes into play. By the 1980s, the search for a theory of everything turned to the idea that everything in the universe could be explained by tiny vibrating strings. String theory suggests that the fundamental building blocks of the universe are not particles, but tiny one-dimensional strings that vibrate at different frequencies. These strings could explain the various particles and forces of nature as different vibrational modes of the same underlying entity. String theory offers a possible unification of quantum mechanics and general relativity because it provides a framework in which gravity can be naturally included alongside the other forces. In string theory, the force of gravity is mediated by a hypothetical particle called the graviton, a quantum particle that would be responsible for transmitting the gravitational force. By integrating gravity into the quantum framework, string theory could be the key to a theory of everything. However, string theory is still highly theoretical. It requires the existence of additional spatial dimensions beyond the familiar three: height, width, depth. In fact, string theory suggests there could be as many as 10 or 11 dimensions in total. These extra dimensions are not immediately observable because they are thought to be curled up at scales so small they cannot be detected with current technology. Despite its elegance and potential, string theory has yet to make testable predictions that could confirm its validity. It's also a highly mathematical and abstract framework, making it difficult to visualize or test in experiments. This has led some to criticize string theory for being too speculative, while others remain hopeful that it will eventually lead to a unified theory. While string theory remains the leading candidate for a theory of everything, it's not the only idea on the table. Another approach called loop quantum gravity attempts to combine quantum mechanics and general relativity without relying on the idea of strings. Instead, loop quantum gravity suggests that space-time itself is quantized, composed of discrete chunks or loops at the smallest scale. While this approach is still in its infancy compared to string theory, it has the advantage of being more directly related to Einstein's original equations of general relativity, without requiring extra dimensions or the highly abstract concept of strings. It is one of many theories being explored in the search for a complete theory of quantum gravity. So how close are we to a theory of everything? Despite the tremendous progress made over the past century, the final unification of all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, remains an open question. The search for a TOE is ongoing, with new developments in quantum mechanics, string theory, and quantum gravity emerging all the time. You see, one of the biggest challenges is that the scales at which quantum mechanics and general relativity operate are vastly different. Quantum mechanics governs the tiny scales of atoms and particles, while general relativity governs the vast expanses of the universe. Bringing these two together requires new mathematical frameworks and new ways of thinking about the fabric of reality itself. The journey towards a theory of everything is as much about the questions we ask as the answers we find. Whether string theory, loop quantum gravity, or some other theory ultimately holds the key, the quest for a unified theory is a testament to the curiosity and determination of humankind. It's a reminder that despite our current understanding of the universe, we are still only scratching the surface of its deepest secrets. In the end, the theory of everything is not just about understanding the universe, it's about comprehending our place within it. And that's a pursuit that will continue to inspire generations of physicists and dreamers alike. Extra dimensions and brain theory. Imagine you're living in a two-dimensional world, a flat plane like a piece of paper. You move in two directions, forward and backward, left and right. Now, imagine that you're suddenly told there are extra directions you can't see or experience, directions that go above and below the plane of your existence. These hidden dimensions might sound strange, but this is the idea behind extra dimensions in physics, a concept that challenges everything we know about space and reality itself. The notion that there might be more dimensions than the familiar three, height, width, and depth, has been a provocative idea in theoretical physics for over a century, but it wasn't until the late 20th century, with the advent of string theory and the exploration of brain theory, that the idea of extra dimensions started to take shape in a more formal and scientifically grounded way. The idea of extra dimensions isn't as new as it might seem. The first serious attempt to unify gravity with electromagnetism through extra dimensions came in the 1920s with the work of Theodor Kaluza and Oskar Klein-Kaluza, a German physicist, proposed that the force of gravity could be described by a fifth dimension, in addition to the familiar four of space and time. Klein, building on Kaluza's work, suggested that this extra dimension could be curled up at a very small scale, which is why we can't observe it. This idea, known as Kaluza-Klein theory, was a bold and imaginative attempt to unify the fundamental forces of nature, but it remained an abstract concept with no experimental support at the time. However, as the century progressed and quantum mechanics and relativity grew more established, the idea of extra dimensions would come to play a pivotal role in the development of string theory. In the 1980s, string theory emerged as a powerful framework that sought to unify the forces of nature. String theory proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings. These strings can vibrate in different modes, with each mode corresponding to a different particle. For string theory to work mathematically, it requires the existence of more than just the familiar three spatial dimensions and one time dimension. In fact, string theory suggests that there are 10 dimensions in total, 9 spatial dimensions, and one time dimension. These extra dimensions, however, are not immediately observable because they are thought to be compactified, curled up so small that they exist on scales far beyond the reach of current experiments. This concept of compactification, where extra dimensions are hidden from our direct observation, was a key element in making string theory a mathematically viable framework. As string theory developed, it wasn't just the idea of extra dimensions that caught physicists' attention. It was also the idea of brains, short for membranes. Brains are higher dimensional objects that can exist in these extra dimensions. While a point-like particle is zero-dimensional and a string is one-dimensional, brains can have multiple dimensions. For instance, a two-brain would be a two-dimensional object like a sheet. A three-brain would be a three-dimensional object like a cube, and so on. The key insight from brain theory developed in the 1990s as part of M-theory, a broader framework that includes string theory, is that our universe may itself be a three-brain embedded in a higher dimensional space. In this scenario, our familiar 3D world is confined to a brain, while extra dimensions and other brains might exist in a higher dimensional space. One of the striking implications of brain theory is that gravity might not be confined to our three-brain. According to string theory and brain models, gravity could leak into higher dimensions, which could explain why gravity is so much weaker than the other fundamental forces. If gravity spreads out into the extra dimensions, it would appear much weaker in our three-dimensional world compared to the forces of electromagnetism, the strong force, and the weak force. What does all this mean for our understanding of the universe? Extra dimensions and brain theory offer radical new ways of thinking about space, time, and the fundamental forces of nature. Here are a few key implications of these ideas. 1. Unification of forces. Extra dimensions provide a framework where the forces of nature could be unified. In string theory, the existence of extra dimensions helps explain the behavior of particles and forces, including gravity, in a single unified framework. This brings us closer to the dream of a theory of everything. A single theory that can explain all the forces of nature from the smallest particles to the largest cosmic structures. 2. Hidden realities. If there are extra dimensions beyond the ones we experience, this suggests the existence of hidden realms or realities that we cannot directly perceive. In the context of brain theory, our entire universe could be a three-dimensional brain, floating within a higher dimensional space. This raises the possibility of parallel universes, other brains that exist in the same higher dimensional space, but don't interact with ours in any observable way. 3. Dark matter and dark energy. Some physicists have speculated that extra dimensions and brains could help explain some of the greatest mysteries of modern physics, such as dark matter and dark energy. These invisible phenomena make up most of the mass and energy in the universe, yet we cannot detect them directly. If gravity spreads into higher dimensions, it could be interacting with hidden matter or energy in ways that we don't yet understand. 4. Cosmic evolution. Brain theory also has implications for the origins of the universe. One popular idea suggests that the Big Bang may have been the result of a collision between two brains. In this scenario, The universe we see today could be just one outcome of a much larger, more complex process involving higher dimensional objects. While extra dimensions and brain theory provide an elegant and mathematically rich framework, they are still speculative. We have yet to observe higher dimensional phenomena or directly detect brains. The idea of extra dimensions is tantalizing, but experimental evidence remains elusive. Some theories suggest that we may one day detect signs of extra dimensions through high-energy particle collisions or the study of cosmological phenomena. But for now, we are still in the realm of theoretical physics. As technology and experimental techniques improve, we may one day be able to test these ideas and uncover the hidden dimensions of our universe. Until then, the concept of extra dimensions and brains remains one of the most fascinating frontiers of theoretical physics, opening up new possibilities for understanding the fabric of reality itself. In the end, extra dimensions and brain theory offer a glimpse into a universe far more complex and mysterious than we could have ever imagined. They challenge our perceptions of space, time, and the very nature of existence, pushing the boundaries of our knowledge and inviting us to think beyond the limits of our three-dimensional experience. The multiverse theory. Picture a grand cosmic library, an infinite structure that houses every possible book you could imagine. Each book represents a different universe, each with its own unique set of rules, histories, and events. Some are similar to ours, with only subtle differences, while others are vastly different, governed by entirely different laws of physics. This library of books is the multiverse, a vast, ever-expanding collection of parallel universes that coexist alongside our own. The idea of the multiverse is one of the most mind-bending and controversial concepts in modern physics. It suggests that the universe we inhabit is not the only one that exists, but just one of many possible realities. But how did this idea come about? Let's trace its origins and explore how it has evolved over time. The first inklings of the multiverse can be traced back to the early 20th century, when the foundations of modern physics were being laid. The discovery of quantum mechanics and the development of cosmology introduced new ways of thinking about reality. In quantum mechanics, particles didn't follow predictable paths. Instead, their behavior seemed governed by probabilities. This led to the famous Copenhagen interpretation, which suggested that particles could exist in multiple states at once, until observed. But the real spark for the multiverse theory came from a seemingly unrelated development: the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. Everett's groundbreaking idea was that instead of the universe collapsing into one definitive state when we observe it, every possible outcome of a quantum event actually happens, just in separate, non-interacting branches of the universe. Imagine tossing a coin. Instead of the coin landing as heads or tails, both outcomes occur, but in different parallel universes. Each universe is its own branch, created by the different possible results of quantum events. This idea was revolutionary. It suggested that the universe we experience is just one of the infinite number of possible realities, each one existing in parallel. The many worlds interpretation provided a possible framework for understanding how the multiverse might exist, though it was at the time more of a mathematical curiosity than a testable theory. While Everett's many worlds interpretation planted the seeds of the multiverse theory, it was the work of cosmologists in the late 20th century that brought the idea closer to mainstream science. The advent of the inflationary model of the universe, developed by Alan Guth in the early 1980s, set the stage for the multiverse to emerge as a scientific theory. In simple terms, cosmic inflation is the idea that in the first moments after the Big Bang, the universe expanded exponentially at an incredibly rapid rate. This expansion stretched the fabric of space-time so quickly that small quantum fluctuations in the early universe could grow into the galaxies and structures we observe today. These fluctuations became the seeds of cosmic diversity. But what inflation also suggested was something far stranger. Regions of space could inflate at different rates, leading to different pockets of space-time, each evolving into its own universe with its own set of physical laws. This was the birth of the idea of eternal inflation, the notion that inflationary expansion didn't stop with our universe but continues indefinitely, creating an endless number of pocket universes or bubbles, each with its own distinct properties. This is one version of the multiverse theory, the bubble multiverse. In this scenario, the Big Bang is not a one-time event, but part of an ongoing process of universe creation, with each bubble universe having its own Big Bang and its own physical constants, such as gravity, the speed of light, and even the laws of physics. As the multiverse idea gained traction in cosmology, it also found a natural home in the world of string theory, a framework that attempts to unify all the forces of nature. String theory proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings exist in higher dimensions, beyond the familiar three dimensions of space and one of time. String theory suggests that there could be a vast landscape of possible solutions to the equations of the theory, each corresponding to a different set of physical laws. This idea is known as the string landscape. In this context, the multiverse is seen as a natural consequence of string theory's extra dimensions. There could be a vast number of different ways that the extra dimensions are compactified, curled up on tiny scales that we cannot observe. Each compactification could result in a different set of physical laws, creating a separate universe. The landscape of possible universes is so vast that, according to string theory, it's highly likely that other universes exist, each one with its own unique properties. In fact, some proponents of string theory argue that the multiverse is an unavoidable result of the theory itself. The constant creation of universes with different properties would explain the fine-tuning of the constants of nature, why the conditions of our universe seem so perfectly suited for life. If there are enough universes, then, by pure chance, some would have the right conditions for stars, planets, and even life to emerge. If the multiverse theory is correct, it raises profound questions about the nature of reality. Here are a few of the key implications. 1. The fine-tuning problem. One of the central mysteries of cosmology is why the constants of nature, like the strength of gravity or the mass of the electron, are so perfectly tuned to allow life to exist. The multiverse offers an explanation. In a universe with an infinite number of possibilities, some universes will have the right conditions for life by chance. 2. The nature of probability. If every possible outcome of every quantum event occurs in a separate universe, it challenges our understanding of probability and fate. The idea that everything that could happen does happen somewhere in the multiverse could have profound philosophical implications. 3. The limits of observation. One of the main challenges of the multiverse theory is that, in most versions, the other universes are forever beyond our reach. Since they don't interact with ours, we have no way of observing them directly. This raises the question of whether the multiverse is truly scientific or if it is simply a philosophical idea. Despite the tantalizing implications of the multiverse, it remains a controversial and speculative theory. There is as yet no direct evidence for the existence of other universes, and testing the idea is a monumental challenge. However, the concept of the multiverse continues to inspire new research in cosmology, quantum mechanics, and string theory. If we ever develop the tools to test the multiverse hypothesis, it would mark a new era in our understanding of the cosmos, one in which the universe we call home is no longer the only reality. Whether or not the multiverse exists, the idea forces us to confront some of the most profound questions about existence, reality, and the very nature of the cosmos itself. For now, the multiverse remains a tantalizing possibility, an idea that challenges the very fabric of reality and offers a glimpse into the unimaginable vastness of the cosmos. The information paradox in black holes. Imagine you're standing before a massive black hole, the most mysterious and powerful object in the universe. As you approach, you notice an oddity. Objects, light, even information about what falls into it, seem to disappear entirely, lost forever. But is that truly the case? Does information vanish, or does it somehow persist in ways we can't yet comprehend? This is the essence of the information paradox in black holes, one of the deepest puzzles in modern physics. To understand this enigma, we need to trace its origins, the discoveries that led to it, and the ongoing efforts to resolve it. The story of the information paradox begins with the legendary physicist Stephen Hawking in the 1970s. Until that point, black holes were mostly thought of as objects with such intense gravity that nothing, not even light, could escape their grasp. This point of no return is known as the event horizon, the boundary beyond which nothing can escape, not even information. However, Hawking's work would challenge this classical view. In 1974, Hawking made a stunning discovery. Black holes emit radiation. This radiation, now known as Hawking radiation, arises from quantum effects near the event horizon. It's as if the black hole is slowly leaking energy, and over time it can even cause the black hole to shrink and eventually evaporate completely. This revelation was groundbreaking, because it suggested that black holes weren't permanent. They could eventually vanish. But it was this discovery that also laid the foundation for the information paradox. According to the laws of quantum mechanics, information about the state of a system, whether it's the position of particles or the properties of energy, cannot be completely lost. Even if a black hole evaporates through Hawking radiation, the information contained within it should, in theory, be preserved. After all, quantum mechanics holds that information is always conserved, a principle that underpins much of our understanding of the universe. But here's the rub. If a black hole evaporates and disappears, taking all its mass and energy with it, where does the information go? The radiation emitted by the black hole doesn't seem to carry any information about the objects that fell into it. In fact, the radiation looks completely random. This creates a paradox. If the black hole evaporates and takes all the information with it, then information seems to be lost, violating a fundamental rule of quantum mechanics. Imagine you have a book with all the details of a particular object. You send the book into a black hole, and the book disappears beyond the event horizon. Normally, you'd expect that the information about the book would still exist, just in a form we can't observe. However, Hawking's theory suggests that the book's information could simply vanish when the black hole evaporates. In this scenario, it's as if the book was never written in the first place, completely erased. This problem struck at the very foundation of quantum theory, which relies on the principle that information is never truly lost. If black holes could erase information, it would imply that quantum mechanics is incomplete or even wrong in its most fundamental principle. This gave rise to what's known as the information paradox, the question of whether information that falls into a black hole is lost forever, or whether there's a deeper, more complex way in which it's preserved. The information paradox has sparked decades of debate among the world's leading physicists. Some have argued that the information is indeed lost, suggesting that our understanding of quantum mechanics and black holes might need to be revised. But many others, including Leonard Susskind and Juan Maldacena, have fiercely defended the principle of information conservation. They have proposed various solutions to the paradox, which suggests that information may be encoded in ways we don't fully understand. One of the most prominent proposals comes from the idea of holography. This theory suggests that the information about what falls into a black hole might not be lost, but instead could be stored on the event horizon itself in a two-dimensional form. According to the holographic principle, the information about a three-dimensional object can be encoded on a two-dimensional surface, just as a hologram captures the 3D image on a flat surface. In this view, the black hole's event horizon may contain all the information about what has fallen into the black hole, and that information may be retrievable through the radiation emitted by the black hole, although not in a form we can directly detect. Another intriguing idea involves firewalls. The black hole firewall hypothesis proposed by physicists like Alessandro Strominger and Samir Mathur suggests that the event horizon might not be a smooth, featureless boundary as traditionally thought. Instead, it might be a region of intense energy like a firewall that could destroy anything that crosses it. If this is true, it could offer a way to preserve the information, albeit by fundamentally altering our understanding of the event horizon and what happens when matter falls into a black hole. However, this solution is highly controversial, and it would require a major revision of how we understand the nature of space and time. As of now, the information paradox remains unsolved. The discovery of Hawking radiation fundamentally altered our understanding of black holes, but it also introduced one of the deepest conundrums in modern physics. Theoretical physicists continue to wrestle with the paradox, and new ideas are constantly emerging. Some believe that the resolution might require a complete theory of quantum gravity, an understanding of how quantum mechanics and general relativity work together at the most fundamental level, which is still an open question. In the meantime, experiments are being designed to probe the nature of black holes and their event horizons, especially through the study of gravitational waves and the use of more advanced observational tools. These could one day provide crucial evidence about whether information can truly escape a black hole, or if it is, in fact, lost forever. The information paradox challenges the very nature of reality itself, asking whether the universe adheres to the strict laws of quantum mechanics, or whether black holes represent an exception, an object where the rules of physics as we know them break down. Whether the information is lost or preserved, this paradox is a window into some of the deepest mysteries of the cosmos, a mystery that might one day unlock new insights into the nature of space, time, and the fabric of reality itself. For now, the paradox remains, tantalizingly unresolved, a testament to the complexity and wonder of the universe we are still trying to understand. Advances in nuclear fusion research. Nuclear fusion is the process that powers the stars, including our sun. It is the most efficient energy production method known to science, capable of producing massive amounts of energy by fusing light atomic nuclei, like hydrogen, into heavier elements, such as helium. For decades, scientists have been striving to replicate this process on Earth in the hopes of unlocking an almost limitless source of clean energy. But how far have we come in this quest? To understand the groundbreaking advances in nuclear fusion research, we need to trace the history of the field and explore the scientific breakthroughs that have shaped it. The story of nuclear fusion begins in the 1930s when physicists like Hans Bethe first unlocked the secrets of stellar fusion. Bethe's work revealed that stars, including our sun, produce energy by fusing hydrogen atoms into helium through a series of nuclear reactions. This process, known as the proton-proton chain reaction, releases an enormous amount of energy in the form of light and heat, sustaining the star's brightness and temperature. Bethe's insights were groundbreaking and set the stage for future work in nuclear fusion on Earth. But it wasn't until the 1950s that humans seriously began trying to replicate fusion as an energy source. During this period, the concept of nuclear fusion reactors, machines capable of fusing atoms and harnessing their energy, began to take shape. The first steps in this direction came through the development of magnetic confinement fusion, a method that uses powerful magnetic fields to contain hot plasma, a superheated, electrically charged gas, in a controlled environment long enough to sustain fusion reactions. The concept of magnetic confinement led to the development of the tokamak, a donut-shaped reactor designed to keep plasma at extremely high temperatures, millions of degrees Celsius, without it touching the walls of the containment vessel. In the early 1960s, Soviet physicists, including Andrei Sakharov and Lev Artsimovich, made significant progress by designing the first tokamak reactors, which were capable of achieving the high temperatures needed for fusion. However, despite their promise, these early reactors were not able to maintain stable conditions or generate more energy than they consumed. Fusion, at least on Earth, was still elusive. The core challenge was that the plasma inside a fusion reactor had to be heated to temperatures far beyond the melting point of any known material, about 100 million degrees Celsius, while also being held together long enough to allow fusion reactions to take place. No materials existed that could withstand this extreme heat. Despite these obstacles, the dream of nuclear fusion never died. In fact, the past few decades have witnessed extraordinary progress, particularly with the advent of newer technologies and international collaboration. One of the most significant advances came with the development of the International Thermonuclear Experimental Reactor, ITER, a project aimed at building the world's largest and most advanced fusion reactor. ITER, located in southern France, is a collaborative effort involving 35 nations, including the European Union, the United States, China, and Russia. The goal of ITER is to demonstrate that fusion can be a practical and sustainable energy source by achieving a net positive energy output, meaning that the energy produced by the fusion reactions is greater than the energy put into heating and maintaining the plasma. ITER's design is based on the tokamak, but with cutting-edge technologies that allow it to operate at temperatures and pressures that were previously unattainable. In 2021, ITER achieved an important milestone by completing the installation of its superconducting magnets, which will play a key role in generating the magnetic fields necessary to contain the plasma. These magnets, which are chilled to near absolute zero, are able to generate stronger magnetic fields than conventional magnets, enabling ITER to achieve the temperatures and pressures needed for fusion. While ITER is still under construction and will not be fully operational until the late 2020s, fusion research has made significant strides through other experimental reactors. In 2021, a breakthrough came from a much smaller fusion facility, the National Ignition Facility, NIF, in the United States. The NIF's approach to fusion differs from the tokamak in that it uses laser-induced fusion, a process called inertial confinement fusion. Here, ultra-intense lasers are focused on a tiny pellet of hydrogen fuel, compressing it to extremely high temperatures and pressures, simulating the conditions found at the core of stars. In 2021, NIF announced that it had achieved a world record for fusion energy output, producing nearly 1.9 megajoules of energy from a fusion reaction, a major step toward the goal of achieving ignition, a state where the energy produced by the fusion reaction exceeds the energy required to initiate it. This milestone was significant because it demonstrated that fusion can occur under controlled laboratory conditions, and the results are pushing the boundaries of what is possible in fusion research. However, researchers still face significant challenges before fusion can become a reliable source of energy. The next step for NIF and similar facilities is to scale up the process and improve efficiency, ensuring that the fusion reactions are sustained over longer periods and generate more energy than they consume. Looking to the future, the advances in fusion research present a tantalizing possibility: clean, virtually limitless energy. Unlike nuclear fission, which powers current nuclear reactors but produces radioactive waste, fusion doesn't create long-lived radioactive byproducts. Its fuel, mainly isotopes of hydrogen, such as deuterium and tritium, is abundant, with deuterium found in seawater, making it a potentially inexhaustible resource. However, challenges remain. The sheer scale of the technology required to achieve sustained, net positive fusion reactions is immense. The reactors must be capable of handling the extreme conditions needed to keep plasma hot and stable, and new materials must be developed that can withstand these conditions without degrading. Additionally, the cost of building and maintaining these reactors is still very high. Despite these challenges, the rapid pace of innovation in fusion research is incredibly promising. As governments and private companies continue to invest in fusion technology, the dream of harnessing the power of the stars may one day become a reality, providing humanity with a revolutionary energy source for the future. The work of physicists, engineers, and researchers around the world is laying the groundwork for a cleaner, more sustainable planet, powered by the same process that lights the night sky. For now, the race to achieve practical nuclear fusion continues, and every step forward in this field brings us closer to unlocking the greatest energy source known to science, one that could forever change the way we power our world. Imagine you just woke up, floating in the vast emptiness of space. No body, no Earth, no solar system, just your consciousness, your thoughts, and your memories. Everything you remember your childhood, your first love, what you had for breakfast this morning, might be nothing more than random arrangements of atoms creating false memories in a spontaneously formed brain. This is the Boltzmann brain paradox, and it's about to make you question everything you think you know about existence. In the late 1800s, physicist Ludwig Boltzmann was contemplating the nature of the universe and entropy, the tendency of all things to move from order to chaos. Think of it like your bedroom. It's much easier for your room to become messy than to spontaneously organize itself. The universe works the same way. But here's where things get strange. In an infinite universe with infinite time, anything that can happen, no matter how improbable, must happen eventually. Just as 1,000 monkeys typing for an infinite amount of time would eventually write Shakespeare, random atoms floating in space would eventually arrange themselves into meaningful patterns. Now consider two scenarios. Scenario 1. Our entire universe, with its billions of galaxies, countless stars, and all of human civilization, emerged from the Big Bang and evolved over 13.8 billion years to create your current experience. Scenario 2. A single brain with all the necessary neural connections to hold your current memories and consciousness spontaneously formed from random atoms floating in space. Here's the unsettling part. According to the laws of probability, Scenario 2 is vastly more likely. It requires far fewer atoms to arrange themselves in the right way to create a single thinking brain than it does to create our entire observable universe. Think of it like this. Imagine you're playing with Lego bricks in zero gravity. Which is more likely to happen if the bricks randomly collide, forming a small house or an entire city? The house, of course. Similarly, a single brain requiring fewer precise arrangements is more probable than an entire universe. But this leads us to an even deeper question. If Boltzmann brains are more likely than real universes, and if we assume we're experiencing reality right now, aren't we more likely to be Boltzmann brains than real people? Every memory you have, every person you've met, every experience you've lived through could be nothing more than the random firing of neurons in a cosmic accident. Some philosophers argue that this paradox reveals a fundamental flaw in our understanding of probability and the universe. Others suggest it might point to deeper truths about consciousness and reality. Perhaps we're all just thoughts in the mind of a greater consciousness, or perhaps our understanding of cosmic probability needs serious revision. As you drift towards sleep, consider this. Whether you're a Boltzmann brain floating in space or a conscious being in a vast universe, your experiences, thoughts, and consciousness are real to you in this moment. The paradox doesn't just challenge our understanding of reality, it invites us to appreciate the extraordinary mystery of consciousness itself. In the end, perhaps the most comforting thought is this. If you are a Boltzmann brain that just popped into existence, you'll never be able to prove it one way or the other. So you might as well enjoy the reality you're experiencing, whether it's real or not. Philosophical zombie. Picture yourself at a bustling cafe, and across the room, someone is reading, sipping coffee, glancing out the window. They look engaged, maybe even contemplative, like they're deeply experiencing the world around them. But here's the twist. What if that person isn't actually conscious? What if they don't have any inner experience, no thoughts, no emotions, no awareness, but simply act as though they do? In other words, what if they're a philosophical zombie? This mind-bending thought experiment, known as the philosophical zombie theory, poses a profound question. Could a creature exist that appears perfectly human, behaves exactly like us, but lacks any conscious experience? Philosopher David Chalmers introduced the term philosophical zombie in his discussions on consciousness and the hard problem of understanding it. This theory is a fascinating way to explore what consciousness is, and more importantly, why it exists. To better understand this idea, let's dive into the basics. Philosophical zombies look and act just like humans. They'd laugh at jokes, recoil from pain, and make decisions in seemingly thoughtful ways. But unlike humans, they wouldn't feel anything. Their reactions are all mechanistic, like a highly advanced robot programmed to simulate emotions without actually experiencing them. If you say something surprising, they might gasp, but this gasp wouldn't be accompanied by the inner sensation of shock or surprise. They're empty, devoid of subjective experience. The concept of philosophical zombies is important because it confronts a mystery at the heart of consciousness studies. Why do we have conscious experience at all? When we see something beautiful like a sunset, we don't just react to it physically. We experience a sense of awe. But why couldn't we just function without that awareness, responding like sophisticated machines? The question goes to the core of the hard problem of consciousness. What is the purpose of subjective experience? One way to approach this is through an analogy. Imagine you have two computers. One is programmed to perform calculations, and the other is programmed to produce a pleasant sound whenever it completes a task. The added sound doesn't change the function. It's just an extra sensory experience. Similarly, philosophers ask, could our conscious experience simply be a sound effect that isn't strictly necessary for survival or function? Let's apply this to a real-world scenario. Imagine a person Alex is walking in a forest and stumbles across a snake. Immediately, Alex's body reacts. Adrenaline surges, muscles tense, eyes focus on the threat. But here's the question. Does Alex's survival depend on actually experiencing fear? From a purely mechanical standpoint, all that's needed is a set of physical responses. A philosophical zombie could be programmed to step back, simulate fear, and run without actually experiencing any fear. The response would be identical, but the inner sensation, the thing that makes fear truly fear, would be missing. For philosophers like Chalmers, this idea raises the question of what consciousness really adds to our existence. Why do we feel fear rather than simply reacting to danger? Is consciousness just an evolutionary accident, or does it serve a deeper purpose? One of the biggest implications of the philosophical zombie theory is its challenge to physicalism, the view that everything about the mind can be explained by physical processes. If a creature can behave identically to a human without consciousness, this suggests that consciousness might be something extra that doesn't arise purely from physical interactions. It raises the possibility that consciousness is an independent phenomenon, something that can't be reduced to brain processes alone. This has led some to suggest that consciousness might belong to a realm beyond the physical, perhaps as a fundamental feature of the universe, akin to space or time. Others argue against the possibility of philosophical zombies, claiming that the act of behaving in a complex human way inherently requires consciousness. They contend that every reaction, every decision, and every interaction is so deeply intertwined with consciousness that separating them is impossible. In this view, philosophical zombies are a conceptual paradox, a thought experiment with no real grounding in how life or consciousness actually functions. What makes the philosophical zombie concept so compelling is how it taps into the mystery of our own awareness. We know we're conscious because we feel our thoughts, emotions, and experiences. But knowing what consciousness actually remains elusive. The philosophical zombie theory highlights the unique, almost magical quality of consciousness. It's something that can't be observed or measured from the outside. You could study a human brain in exquisite detail, understand every chemical reaction and neural pathway, and still have no insight into what that person experiences internally. This idea invites us to ponder. If consciousness could be removed from our existence without altering our behavior, what does that say about the nature of reality? Are we simply collections of reactions with the illusion of self-awareness layered on top? Or is consciousness the very essence of our being? The philosophical zombie theory also taps into something deeply existential. If a person could be devoid of inner life, yet still behave in every way like you or me, it raises questions about identity and authenticity. How do we know other people are conscious? How do we know we're not philosophical zombies ourselves, only thinking we're conscious because that's what we're programmed to believe? While these questions may sound fantastical, they speak to the heart of our deepest uncertainties about consciousness. Is there more to being alive than just existing and reacting, or is that all we truly are? The philosophical zombie forces us to confront this ambiguity, making it a profound and perhaps unsettling reflection on the mystery of our inner lives. In the end, whether philosophical zombies are possible or not, this thought experiment serves as a mirror, reflecting the complexity and wonder of our own conscious experience. It asks us to marvel at the fact that, in a universe filled with stars, atoms, and energy, there exists a phenomenon as strange and beautiful as the feeling of simply being at the butterfly dream paradox. Imagine a man lying under a tree, drifting off to sleep as the breeze rustles the leaves around him. He dreams that he's a butterfly, fluttering through the air, feeling the sunlight on his wings, experiencing the world in soft, vibrant colors. In this state, he is fully and completely a butterfly. He feels only the lightness of flying and the serenity of floating on the wind. Suddenly, he wakes up. Once again, a man. The experience fades, but a haunting question lingers. Was he a man dreaming he was a butterfly? Or is he now a butterfly dreaming he's a man? This ancient story, known as the butterfly dream paradox, is attributed to the Chinese philosopher Chuangzi, who lived around the 4th century BCE. Chuangzi's dream raises one of the most profound questions in philosophy. How can we know what is truly real? Are we certain of the reality we are in? Or could it all be an illusion, much like the way we perceive our dreams? Chuangzi's butterfly dream touches on a universal human experience, the vividness of dreams. Most people have experienced dreams that felt so real, so complete, that they briefly believed them to be their true reality. In those moments, we rarely question the authenticity of the dream world. Our mind creates narratives, sensations, and emotions that feel entirely genuine. It's only when we wake up that we realize we were in a different state altogether. This paradox invites us to consider whether there's a fundamental difference between dreams and waking reality. In the dream, Chuangzi was a butterfly. He experienced the world through its eyes, with its perspective and sensations. Upon waking, he found himself back as Chuangzi, a man. But if his perception was entirely altered in the dream, how could he be sure which experience was the true one? This leads us to question the nature of our own reality. Is there any infallible way to confirm that we are not, in fact, dreaming right now? Chuangzi's story also opens up questions about subjective reality, the idea that reality is not absolute, but perceived individually by each of us. What we see, hear, and feel is filtered through our minds, shaped by our beliefs, biases, and senses. In this sense, each person experiences a version of reality unique to themselves. Just as Chuangzi, when he was a butterfly, had an entirely different experience of the world, we might each be living in slightly different versions of reality based on our own perceptions. An analogy often used to illustrate subjective reality is a film projector. Each person's mind can be thought of as a projector, casting its own unique version of the movie of life onto a blank screen. The scene might be the same, but the interpretation, the colors, and the emotional resonance vary with each person watching. The butterfly dream paradox shares common ground with other philosophical questions about reality and existence. One famous example is Descartes' cogito, ergo sum, I think, therefore I am, which was Descartes' attempt to find a truth that could not be doubted. Descartes considered the possibility of being deceived by a powerful entity, but he concluded that his ability to doubt meant that he existed, at least as a thinking entity. However, even with this assurance, Descartes couldn't be sure of the nature of the external world. This paradox also mirrors ideas in Hindu philosophy, where the concept of Maya describes the world as an illusion, a veil that obscures the true nature of reality. Just as in Zhuangzi's dream, where the line between butterfly and man is blurred, Maya suggests that the line between reality and illusion may be indistinct. Both concepts challenge the certainty of our knowledge and the reliability of our perceptions. In modern philosophy, Zhuangzi's butterfly dream resonates with the brain in a vat thought experiment. Imagine a brain kept alive in a vat, wired to a supercomputer simulating sensory experiences. The brain would have no way of knowing it was in a vat. It would experience a full, rich world created by the computer. This scenario is often used to illustrate how reliant we are on our senses and perceptions, which can be manipulated or deceived. Just as the brain in a vat would accept the simulated world as reality, we might be accepting our own experiences without question. So, Zhuangzi's question lingers. If we cannot rely on our senses, how can we determine what is real? At its core, the butterfly dream paradox doesn't provide an answer. It leaves us with an open-ended question. And perhaps that's the point. Zhuangzi's philosophy often emphasizes the idea of going with the flow, accepting the uncertainty of life. Rather than seeking concrete answers, Zhuangzi encourages us to embrace the mystery of existence and live harmoniously within it. One of the lessons we might draw from the butterfly dream paradox is that reality, whether objective or subjective, is complex and multifaceted. Just as we sometimes take our dreams seriously while we're in them, it's possible that our perception of reality might be just one layer in a much larger tapestry. Zhuangzi invites us not to view this as a limitation, but as a source of wonder. There's a poetic beauty in the idea that we might all be butterflies, flitting from one dream to another, each one feeling as real as the last. And if reality is indeed a dream, Zhuangzi seems to suggest that we should not struggle to dissect it. Instead, perhaps we can savor each moment, like the butterfly savoring each flight, each flower, each patch of sunlight. After all, whether we are butterflies or humans, the experience of being, even if uncertain, might be the greatest mystery of all. In the end, Zhuangzi's butterfly dream paradox isn't about solving the question of what is real or fake. It's about appreciating the mystery of perception itself. It reminds us that reality is perhaps not just about what we see or touch, but about the ever-shifting dance of experiences that makes life so rich, strange, and beautiful. The temporal experience. Theory. Have you ever noticed how time seems to fly when you're having fun, yet crawls at a snail's pace during that last hour of work? This curious relationship with time brings us to one of the most fascinating aspects of human consciousness, the temporal experience theory, which explores how our minds perceive and process the passage of time. Think of time like water flowing through a river. While the actual flow rate remains constant, our experience of it varies dramatically based on where we're standing and what we're doing. This is the essence of temporal experience, the subjective way we perceive time's passage, often in stark contrast to its objective measurement. Let's dive deeper through a simple example. Remember your last vacation. Those beautiful days probably felt like they zipped by in moments. Yet think back to your childhood summers, they seem to stretch on endlessly. This isn't just nostalgia. It's a fundamental aspect of how our brains process temporal experience. The theory suggests that our perception of time isn't fixed like a metronome, but is instead highly malleable, influenced by several fascinating factors. The first is novelty. New experiences cause our brains to create more detailed memories, making time feel longer in retrospect. This explains why your first day at a new job feels longer than your 100th day. Your brain is working harder to process all the new information. Consider this. Researchers have found that time seems to speed up as we age. This isn't because our biological clocks run faster, but because we experience fewer novel situations. When you're 5 years old, everything is new. Each day brings unprecedented experiences, making time feel expansive. By the time you're 50, many experiences are routine, causing time to feel like it's rushing by. The theory also explains the holiday paradox, how vacations can feel quick while we're experiencing them, but long when we remember them. It's like your brain creates a detailed photo album of new experiences, making the memory feel rich and time-stretched, even though the actual experience might have felt brief. Emotion plays a crucial role, too. Time seems to slow down during dangerous or frightening situations. Think of how a near-miss accident seems to happen in slow motion. This is your brain switching to high alert mode, processing information more quickly, and creating an illusion of slowed time. It's like your mind's frame rate suddenly increasing, capturing more detail in each moment. But perhaps most fascinating is how our attention shapes temporal experience. When you're fully engaged in an activity, what psychologists call flow state time seems to disappear altogether. It's as if your consciousness temporarily steps outside the river of time. Conversely, when you're acutely aware of time's passage, like watching a clock during a boring meeting, each minute feels excruciatingly long. The theory has profound implications for how we live our lives. Understanding that novel experiences expand our perception of time suggests a solution to the feeling that life is rushing by. Seek out new experiences, learn new skills, visit new places. Each novel experience is like dropping a pebble in the river of time, creating ripples that slow its perceived flow. Moreover, this understanding can help us design our days more effectively. If we want time to feel richer and fuller, we might intentionally vary our routines, engage in new activities, or simply pay more attention to the present moment. It's like being both the photographer and the subject of your temporal experience. consciously choosing what to focus on and how to frame each moment. As you rest with these thoughts, consider how your own temporal experience shifts and changes. Notice how this very moment might feel different now that you're paying attention to it. Perhaps time isn't just something that happens to us, but something we actively participate in shaping through our attention, our choices, and our willingness to embrace new experiences. Remember, while we cannot control time's objective passage, we have remarkable influence over how we experience its flow. In understanding this, we gain a tool for making our finite time feel richer, fuller, and more meaningful. The egg theory. Imagine this. You're walking home after a long day, lost in thought, when suddenly everything goes dark. You blink, confused, and realize you're in a completely different place. There's no pain, no fear, just a gentle curiosity. A figure approaches, calm and knowing, and before you can even ask, they tell you you're dead. But rather than fading into the unknown, you're about to learn something extraordinary. This is the starting point of The Egg Theory, a thought-provoking story by Andy Weir, the author of The Martian. In a few hundred words, this theory proposes an idea about life, consciousness, and the nature of existence that has captivated millions of readers. The Egg Theory invites us to consider a radical, mind-bending concept. What if we are all the same soul, reincarnating across time, experiencing every single life in the history of humanity? You are not just you. You are also every person who has ever lived, is living, and will live. In this framework, every relationship, every conflict, every kindness is, in essence, a connection with yourself. At its heart, the Egg Theory explores the concept of universal oneness. In most spiritual traditions, there is an underlying idea that all beings are interconnected, that we're all part of a larger whole. The Egg Theory takes this a step further, suggesting that this unity is literal, that every person you encounter is in some way a different version of you. When you hold a door open for a stranger, you're showing kindness to yourself. When you argue with someone, you're actually struggling with an aspect of your own nature. This perspective has profound implications. If everyone you meet is another version of you, then every act of compassion, empathy, and forgiveness becomes an act of self-love. When viewed through this lens, the moral philosophy of treat others as you would want to be treated isn't just a guideline for polite behavior. It becomes a fundamental truth of existence. In Weir's story, the protagonist learns about this concept through a conversation with a being who may be God, or perhaps simply a higher form of consciousness. This being explains that Earth is essentially an egg where souls incubate. Life after life, they are reincarnated in different forms and circumstances, gradually learning, experiencing, and evolving. When every possible life has been lived, when every perspective has been understood, the soul will hatch from the egg, becoming something greater, perhaps even like this godlike figure. The God character implies that the purpose of life isn't about achieving individual greatness or accumulating material success. Instead, it's about gaining empathy, understanding, and wisdom. The journey isn't just about your life as you currently know it. It's about understanding the full range of human experience, from the heights of joy to the depths of despair. In the grand scheme, your current identity is only a single thread in a vast, interconnected tapestry. If everyone you encounter is another version of yourself, then empathy becomes more than an emotional response. It becomes a necessity. Think of it this way. If you were to experience every person's life, wouldn't it make sense to treat everyone with compassion? After all, their struggles and triumphs are, in this theory, your own. The Egg Theory encourages us to view human conflict, discrimination, and prejudice as misunderstandings within ourselves, a failure to recognize our shared consciousness. This idea reflects the principle of non-duality, a concept in many Eastern philosophies that emphasizes the illusion of separation. According to non-duality, the distinctions between you and me, us and them, are ultimately false, mere constructs of our minds. The Egg Theory takes this idea into a fictional, yet deeply insightful context. By suggesting that everyone is one soul, it challenges us to think beyond our individual boundaries and to see ourselves in others. The Egg Theory also touches on ideas found in Hinduism and Buddhism, where reincarnation and karma are key components. However, it deviates in its assertion of a single soul, rather than multiple. In Hinduism, the concept of Atman, or the individual soul, is part of Brahman, the universal soul. Buddhism teaches that the self is an illusion, and the journey is about dissolving the ego. The Egg Theory simplifies these ideas into a single, digestible concept, making it accessible for readers of all backgrounds. By envisioning every life as part of one soul's journey, it offers a unifying perspective that aligns with spiritual themes without requiring adherence to any specific belief system. Beyond spirituality, the Egg Theory also aligns with certain principles in quantum physics and consciousness studies. Some interpretations of quantum mechanics suggest that consciousness itself might be a fundamental element of reality, woven into the fabric of existence. While scientists haven't found any empirical basis for reincarnation or the existence of a universal consciousness, the Egg Theory offers a fictional yet fascinating thought experiment that bridges these scientific mysteries with human experience. So, how might our lives change if we truly embrace the Egg Theory? Imagine going through your day with the awareness that every interaction is, in a way, a conversation with yourself. Small annoyances like a rude cashier or an impatient driver might start to feel different. You may find yourself responding with understanding instead of frustration, thinking, this too is me, just in a different circumstance. Conflicts might take on new meaning as opportunities to reconcile with parts of yourself that you find difficult or uncomfortable. This doesn't mean that life becomes instantly easier, but it does encourage a mindset of patience and understanding. By internalizing the egg theory, you could foster a sense of peace, a feeling that no matter what happens, every experience is helping you grow and evolve. You're not just learning for yourself in this life, but for every future life, every future version of you. The egg theory may be a work of fiction, but its message lingers. It speaks to a longing we all have to feel connected, to transcend the barriers that separate us from each other. Whether or not we are all truly one soul, as the theory suggests, it reminds us that we have the capacity to expand our understanding, to embrace empathy, and to view life as a journey of growth and unity. The egg invites us to see the world as a place where every interaction, every relationship, every moment is part of a grander story, a story of learning, compassion, and connection across time and space. The Matrix. Imagine if one day you discovered that everything you know, the world, your relationships, even the very air you breathe, is part of an elaborate simulation. You're a character in a system that looks real, feels real, and even fools your own mind. Welcome to The Matrix, a thought experiment that explores the boundaries between reality, illusion, and control. While the Matrix concept became popular through the 1999 film, it has deep philosophical roots that question whether reality itself could be an illusion. The film might be fiction, but its questions about perception, technology, and existence resonate with some of the most intriguing ideas in philosophy and science. At its core, the Matrix theory asks, can we trust our perceptions? Everything we know about reality comes through our senses: sight, sound, touch, taste, and smell. But if our senses could be manipulated, would we even know? In a way, we're all plugged into a matrix of our own, our brains. Every experience, from the warmth of sunlight to the taste of food, is processed in the mind. The brain relies on electrical impulses and chemical signals, not unlike a computer processing code. But if these signals were intercepted and replaced with artificial ones, our brains might still interpret them as real. In the movie, humanity is trapped within a virtual construct, a world that only exists in their minds, while their physical bodies are imprisoned and used as batteries. This premise builds on an idea explored by philosophers like René Descartes, who proposed the possibility of an evil demon that could be deceiving us into believing in a false reality. Today, we might substitute Descartes' demon with advanced artificial intelligence, asking whether a machine could fool us just as easily. The Matrix concept has philosophical precedents going back thousands of years. One of the most well-known is Plato's allegory of the cave. Imagine prisoners chained inside a dark cave, facing a blank wall. They've been there since birth, so they've never seen the outside world. Behind them, a fire burns, and people pass in front of the fire, casting shadows on the wall. The prisoners see these shadows and hear echoes, and to them, this is reality. One day, a prisoner escapes and sees the world outside the cave, the sun, trees, rivers, and people. He realizes that the shadows he's known his whole life were just illusions. In Plato's allegory, the journey out of the cave is a journey toward knowledge and enlightenment, the realization that there is a reality beyond what we directly perceive. The Matrix updates this allegory for the digital age. Instead of shadows on a wall, humans in the Matrix experience a fully immersive illusion designed to keep them docile and unaware of their real situation. But the lesson remains the same. Breaking free from illusion requires questioning reality, a difficult task in a world where illusion feels as real as any physical sensation. The Matrix idea isn't just a fantasy for the screen. The concept has real-world proponents among philosophers and scientists who propose simulation theory, the idea that our universe could be an artificial simulation. The argument was famously put forward by philosopher Nick Bostrom, who suggested that advanced civilizations might create simulations so sophisticated that their inhabitants would believe they were real. If this were possible, and if such civilizations created many simulations, it could be statistically likely that we're living in one of them. Bostrom's theory doesn't claim to prove we're in a simulation, but it challenges us to consider the possibility. After all, if we already have virtual reality technology and are advancing AI, could it be only a matter of time before simulations are indistinguishable from the real world? If that's the case, then our very reality could be an advanced simulation controlled by beings or systems beyond our understanding. The Matrix also explores questions of free will and determinism. In the film, Neo is told he has a choice. Take the red pill to wake up to the real world, or take the blue pill to remain in the simulated comfort of the Matrix. This choice is symbolic, presenting a philosophical question that goes beyond the movie's plot. Do we have genuine freedom, or are our actions controlled by unseen forces? The Matrix implies that as long as we remain within the bounds of a controlled reality, our choices might be manipulated by the rules of that reality. This idea echoes deterministic philosophies, which argue that everything we do is the result of prior causes, our environment, biology, and the systems we're part of. In The Matrix, Neo's choice to rebel against his artificial reality symbolizes a struggle for autonomy and authenticity in a world that constantly shapes us. One of the most compelling aspects of The Matrix is its exploration of awakening. In philosophical terms, awakening is often seen as enlightenment, a moment of clarity where one sees reality as it truly is, free from illusions or biases. For Neo, taking the red pill is his awakening. He chooses to see the truth, however painful or disorienting it may be. The Matrix suggests that enlightenment isn't necessarily about finding new knowledge, but about questioning the knowledge we already have. This moment of awakening resonates with many spiritual traditions, from Buddhism's concept of enlightenment to Socrates' famous assertion that the unexamined life is not worth living. The red pill represents the willingness to question, to confront uncomfortable truths, and to risk leaving behind the comfort of familiar illusions. In our own world, the Matrix metaphor is often applied to modern life, where technology, media, and social structures can act as a kind of matrix of their own. Algorithms influence our choices, social media shapes our perceptions, and the pressures of consumer culture tell us what to value. Just as Neo breaks free from his simulated world, we are challenged to recognize the forces that influence us and to decide whether we accept or resist them. Ultimately, the Matrix leaves us with an open-ended question. How do we know what is real? And if reality could be manipulated, do we have the courage to seek the truth no matter the cost? The red pill symbolizes a universal human choice, the choice to seek truth and authenticity in a world that often presents comfortable illusions. For anyone who has ever wondered if there's more to life than what meets the eye, The Matrix is a powerful reminder that the journey to understand reality is as transformative as it is unsettling. And like Neo, we are all invited to take that leap, to wake up and to question the nature of the world we call home. The experience machine theory. Suppose a machine that can give you the perfect life. Every experience you've ever wanted, traveling the world, falling in love, achieving fame, could be yours at the push of a button. This isn't a fantasy. It's a thought experiment called the experience machine, proposed by philosopher Robert Nozick in 1974. He presented it as a challenge to a popular philosophical idea known as hedonism, which says that happiness or pleasure is the highest good and the only thing that truly matters in life. But here's the catch. Once you're plugged into the machine, you won't know you're inside it. Every experience will feel real, every sensation vivid, but it will all be artificial. The machine will stimulate your brain, making you feel like you're living the life of your dreams. So, would you choose to plug in? The experience machine presents a tantalizing question. If pleasure and happiness are the only things that truly matter, then why shouldn't we plug into the machine? If the machine can give us everything we desire and make us feel happy all the time, wouldn't that be the best possible life? But Nozick's point was to challenge this very assumption. By asking whether we'd plug in, he's asking us to consider what we value most in life. Is pleasure really the ultimate goal? Or do we also value authenticity, genuine relationships, personal growth, and the sense of accomplishment that comes from facing real challenges? Imagine being able to program your life experiences like a movie script. You could decide that tomorrow you'll wake up as a world-renowned artist or a successful entrepreneur. You could design a love story that's free from heartbreak or a career that's free from failure. This vision of a perfect, pleasure-filled existence seems like the ultimate escape from the hardships of reality. The machine offers a reality where there are no disappointments, no unfulfilled dreams, and no setbacks. Every moment would be crafted to maximize your happiness and eliminate all suffering. At first glance, it sounds like an easy choice. After all, who doesn't want happiness and pleasure? But Nozick argued that if we stop and think about it, many of us would hesitate to plug in. The machine strips away everything that makes life unpredictable, real, and uniquely ours. It gives us happiness, but it takes away the meaning that comes from real experiences, relationships, and personal achievements. Why would anyone hesitate to enter the experience machine? Nozick suggested that we value more than just feeling good. We want our experiences to be real. We don't just want the feeling of achieving something, we want to actually achieve it. There's a profound difference between the simulated feeling of climbing a mountain and the actual experience of struggling up each step, feeling the burn in your legs, and reaching the summit. In essence, Nozick believed that we crave authenticity. The idea of experiencing love, success, or adventure in a simulated reality might feel hollow because we know it's not genuinely happening. The love in the machine is programmed, the challenges are artificial, and the victories are predetermined. Without the possibility of failure, can success even hold real meaning? One of the things that the experience machine lacks is struggle. Real life includes challenges, setbacks, and pain, but these are also the moments where we grow, learn, and transform. Nozick's thought experiment touches on the idea that growth comes through overcoming real obstacles, not merely experiencing pleasure. Think about a story where the hero always succeeds, never faces any hardships, and wins every battle easily. It would quickly become a boring story, wouldn't it? In the same way, a life without real challenges might feel empty. The experience machine can give us pleasure, but it denies us the journey, the failures, and the lessons that make real achievements meaningful. Another issue with the experience machine is that it removes our sense of control. Once you're inside, the machine decides what happens. You've pre-programmed your life to bring you happiness, but you're no longer an active participant in it. Instead, you're simply receiving experiences, like a movie playing in front of your eyes. In real life, every decision we make shapes who we are, from the small choices to the life-altering ones. Being in the machine would mean giving up this autonomy, the freedom to make choices and to discover ourselves through them. In a way, this thought experiment reflects the human need for self-discovery. Real life offers surprises, unexpected turns, and opportunities for self-reflection. The machine, however, offers a closed loop of experiences that reflect only what you think you want, without the possibility of discovering something new. Nozick's experience machine raises profound questions about what makes life worth living. Are pleasure and happiness enough? Or do we need authenticity, struggle, autonomy, and growth to feel truly alive? The thought experiment doesn't give us a definitive answer, but it invites us to reflect on our own values. If we say we wouldn't plug into the machine, it might be because we value a life that's rich with the messiness and complexity of reality. We want relationships that are real, achievements that are earned, and a life that unfolds in ways we can't always control. The experience machine challenges us to define our own sense of purpose. In the end, it's not a question of whether the machine could give us happiness. It's about whether happiness alone would be enough for us to feel that we're truly living. The Library of Babel concept. Picture yourself at a library so vast, it contains every single book ever written, and every book that could ever be written. In its endless corridors, you'd find a text with the complete works of Shakespeare, but also countless near duplicates where every letter is off by one. Somewhere, there's a book that holds the exact description of your life from birth to this very moment, as well as countless others that detail versions of your life that you never lived. This is the Library of Babel, an idea conceived by the Argentine writer Jorge Luis Borges in 1941. In Borges's mind-bending short story, the Library of Babel is not just a literary device, but a philosophical concept that challenges our understanding of infinity, knowledge, and meaning. Imagine walking into this library. The shelves extend in every direction as far as the eye can see. Row after row, shelf after shelf, all filled with books that contain every possible arrangement of letters and punctuation. Borges imagined each book as 410 pages long, each page with a fixed number of letters. In such a library, there would be books that contain profound insights into the universe, mixed with books that are pure gibberish, and others that are almost right, but not quite. It's a powerful metaphor for human knowledge and the search for meaning in a vast and often incomprehensible universe. The library, with its infinite possibilities, is a paradox. It holds every truth, every answer, but it's also mostly noise, an overwhelming ocean of meaningless text. To truly understand the Library of Babel, we need to dive into the philosophical implications of infinity, randomness, and our search for meaning. Jorge Luis Borges was deeply fascinated by the nature of knowledge and the limits of human understanding. In his short story, The Library of Babel, he describes a universe that is, in fact, a library, an infinite array of hexagonal rooms, each filled with books that together contain every possible combination of letters. This library embodies infinity in the purest sense, a place where everything exists but almost nothing makes sense. The concept wasn't just a literary invention. It reflects questions that philosophers and mathematicians have pondered for centuries. How do we navigate an infinite realm of information? How do we find meaning in a universe that seems indifferent, where truth is hidden among countless falsehoods? Borges used the Library of Babel to push these questions to their limits. At the heart of the Library of Babel lies the concept of infinity. In an infinite library, every possible book exists, but so does every incorrect version of that book. Somewhere in this library there is a book that describes exactly how the universe works, down to the finest detail. But the vast majority of books are filled with random sequences of letters, making it nearly impossible to find anything meaningful. It's like looking for a needle in an endless stack of hay. This brings us to a profound philosophical point. In an infinite universe, even if all knowledge exists, most of it might be inaccessible or buried in noise. Imagine trying to find a single meaningful sentence in an ocean of nonsense. The Library of Babel suggests that even if every answer is out there, the vastness of possibilities makes finding it almost hopeless. The Library of Babel serves as a powerful analogy for the internet, where we have access to more information than ever before. Just like the library, the internet holds both profound truths and endless misinformation. We live in an age where knowledge is abundant, but distinguishing valuable information from irrelevant or misleading content is an enormous challenge. Borges foresaw this problem long before the digital age, hinting at the difficulty of finding meaningful insights amidst overwhelming noise. In Borges's library, the endless corridors of books are also a metaphor for the human quest for meaning. We are constantly searching for answers about ourselves, our place in the universe, and the nature of reality. But the Library of Babel warns us that even if we had access to infinite knowledge, much of it would still be incomprehensible or useless. One of the most fascinating aspects of Borges's library is how it reflects our deep-seated curiosity and desire to understand the universe. Even though the majority of books in the library are gibberish, the inhabitants of Borges's world are driven to explore, hoping to find just one book that contains a coherent answer. The librarians in Borges's story spend their lives searching for meaning, piecing together fragments of understanding from books that are often nonsensical. It's a journey that mirrors the human condition, our endless search for knowledge in a world that sometimes feels vast and unknowable. In this way, the Library of Babel resonates with the existentialist idea that we must create our own meaning in an indifferent universe. Just as the librarians search for purpose in an endless sea of information, we too search for meaning in a world that doesn't always offer clear answers. The Library of Babel challenges us to think about the nature of knowledge, randomness, and meaning. In its infinite shelves, every truth exists, but so does every falsehood, every meaningless sequence, and every possible version of every possible story. The library is both a paradise and a prison, offering the promise of infinite knowledge, but also confronting us with the impossibility of finding it. Through this concept, Borges reminds us that the pursuit of knowledge is not just about collecting facts or seeking definitive answers. It's also about navigating uncertainty, embracing the unknown, and finding value in the journey itself. Like the librarians of the infinite library, we are all searching for meaning, hoping to find coherence amidst the chaos. And perhaps in that search, we create our own purpose, turning a vast, incomprehensible universe into something personally meaningful. The Library of Babel, then, is a reflection of life itself, an infinite, bewildering expanse where we, the explorers, must find our own way through the shelves. The Infinite Hotel Paradox. Let's suppose there is a hotel with an infinite number of rooms. No matter how many guests arrive, there's always room for one more. This place isn't just a thought experiment. It's a fascinating way to explore the concept of infinity itself. First proposed by mathematician David Hilbert, the Infinite Hotel Paradox challenges our understanding of space, numbers, and what we think is logically possible. While it's impossible to build such a hotel in reality, thinking about it opens doors to understanding infinity in ways that are surprising and even a bit unsettling. Picture this. You arrive at Hilbert's Infinite Hotel, a grand structure that stretches beyond what the eye can see. The hotel's lobby is filled with guests checking in, yet every single room is already occupied. An infinite hotel with an infinite number of guests? That's a paradox in itself. How can there be a room for you if every room is full? Hilbert's Infinite Hotel confronts this with a clever twist. Since the hotel has infinite rooms, there's a way to make space for any newcomer. The solution seems straightforward, but opens up mind-bending implications about infinity and endlessness, challenging what we think is possible. So, you've arrived at the Infinite Hotel, and all the rooms are full. How can the manager accommodate you? Surprisingly, it's easy. The manager simply moves the guest in room 1 to room 2, the guest in room 2 to room 3, and so on, down the line. In other words, each guest is shifted over by one room. Now, room 1 is open, and you can check in. Even though the hotel was fully occupied, one more guest can always be accommodated in an infinite system. Schwa. This seemingly simple solution becomes more interesting when you realize that no matter how many guests arrive, this shifting method can accommodate all of them. If an infinite bus with an infinite number of passengers shows up, each guest in the hotel can be moved to double their room number, room 1 to room 2, room 2 to room 4, and so on, freeing up every odd-numbered room for the new arrivals. By shifting the guests in specific ways, the manager can find space for an infinite number of new guests, over and over again. At the heart of Hilbert's Infinite Hotel Paradox is the idea that infinity isn't one size fits all. In mathematics, some infinities are bigger than others, which sounds strange at first. For example, the set of all whole numbers, 1, 2, 3, is infinite, but the set of all real numbers, including fractions and decimals, between 0 and 1, is an even larger infinity. This concept, developed by mathematician Georg Cantor, challenges the notion of infinity as something singular and introduces us to the idea of countable and uncountable infinities. Hilbert's Hotel represents a countably infinite set because we can assign a room number to each guest in a sequence, 1, 2, 3. However, if guests started arriving who each needed infinite space, let's say each one represents a decimal between 0 and 1, there would be no way to fit them into the hotel without some rooms remaining empty. This distinction between types of infinity shows us that some infinities can contain other infinities, a concept both simple in theory but perplexing in its implications. Hilbert's Infinite Hotel helps us see that the rules governing infinity are unlike anything we encounter in the finite world. In everyday life, if every room in a hotel is full, there's no way to fit in another guest without kicking someone out. But in the Infinite Hotel, new rules apply, and these rules teach us about the possibilities and limitations of infinity. Infinity, as represented by Hilbert's Hotel, allows for endless possibilities. Yet this endlessness leads to paradoxes that challenge our fundamental understanding. For instance, if the hotel is always full, does that mean it's ever really empty? And if you keep adding guests, does the hotel actually grow? These questions are absurd, but they're also profound. They reveal the strange, counterintuitive ways infinity behaves when it's applied to practical scenarios. The Infinite Hotel Paradox is more than just a clever riddle. It has real implications for fields like mathematics, physics, and philosophy. In cosmology, for instance, the concept of an infinite universe brings up similar questions about space, matter, and the limits of our understanding. If the universe is infinite, can it ever be full? And if there's always room for more galaxies, stars, and planets, what does that mean for our place in the cosmos? In the realm of philosophy, the paradox raises questions about the nature of existence and reality. Just as Hilbert's Hotel can infinitely accommodate, does it mean that possibilities in life and thought are also infinite? Or does infinity suggest that there are no true limits, only constructs we impose upon the boundless? Hilbert's infinite hotel is a mind-bending concept, but it gives us a way to approach the unfathomable concept of infinity. By considering what it would mean to run a hotel with infinite rooms, we catch a glimpse into the vast, complex world of infinite sets, countability, and paradoxes that make up the world of higher mathematics. It's a thought experiment that stretches our minds beyond the finite limits we're used to, showing us that, in some realms, there truly is always room for one more. The next time you see a hotel with a no vacancy sign, you might just wonder what it would take to turn it into a place with infinite possibilities. A hotel where everyone is welcome, no matter how many guests arrive, in a place where the rules we know simply don't apply. The Fermi Paradox. You are standing on a quiet hilltop, looking up at a night sky splattered with stars. Some of these stars have their own planets, some of which might even look something like Earth. And in one of those far-off worlds, there might be beings looking up, just like you are. But if there's so much potential for life out there, then a question emerges, like an uninvited guest. Just, why haven't we heard from anyone yet? This question, this unsettling silence from the cosmos, is what the Fermi Paradox seeks to explore. It's named after physicist Enrico Fermi, who in the middle of a casual lunch in 1950 asked, "Where is everybody?" A simple question with implications as deep as the universe itself. The Fermi Paradox isn't just about the absence of little green men waving at us. It's about reconciling the high probability of extraterrestrial life with the eerie quiet that seems to surround us. To break it down, the paradox rests on a few fundamental ideas. First, that the universe is unbelievably vast, and second, that within this vastness there should be other intelligent civilizations. Statistically, given the age of the universe and the countless billions of stars and planets, it seems almost certain that intelligent life should have arisen elsewhere. And if these civilizations have had millions or even billions of years to develop, some of them should have advanced far beyond our current technological stage to the point where they could theoretically communicate with or even visit us. So, why silence? One possible answer lies in something called the Great Filter. Imagine that along the journey from simple life to advanced, spacefaring civilizations, there are immense hurdles or filters that most life forms don't survive. This Great Filter could be something behind us. Maybe life itself is incredibly rare, or maybe complex multicellular organisms are unlikely to arise. In that case, we might already be past the hardest part, and we're on our way to eventually making contact with other civilizations. But there's a darker possibility. What if the Great Filter lies ahead of us? Perhaps intelligent civilizations inevitably self-destruct, or face an unavoidable cosmic disaster. If that's the case, then the silence might be a warning rather than a mystery. Another theory speculates that advanced civilizations have simply chosen to stay silent, either to avoid drawing attention to themselves or to observe us without interference, as if we're a cosmic nature reserve. This idea is known as the zoo hypothesis, suggesting that more advanced beings might find us fascinating but primitive, worth studying but not worth interacting with directly. They're out there, but they're simply watching from afar, letting us evolve without interference. And then there's the possibility that we're looking in the wrong way, or perhaps listening on the wrong channels. Imagine tuning a radio to a specific station, but the broadcast is on a frequency we haven't even considered yet. Or perhaps their methods of communication are so advanced that they're invisible to us, like sending a letter to someone who only uses email. It could be that out in the universe, signals are flowing back and forth, but we simply don't have the means or the knowledge to detect them. For some, the answer to the Fermi Paradox might be that we are indeed alone, that Earth is the rare exception in a quiet cosmos. This idea, known as the rare Earth hypothesis, suggests that conditions like ours are so unique that it's unlikely they exist anywhere else. If true, then life as we know it might be a spectacular anomaly in the universe. In contemplating the Fermi Paradox, we're not just searching for life in distant star systems. We're seeking our place in the vast story of the universe. Are we a common chapter, one among many? Or are we the universe's only storytellers? The Fermi Paradox doesn't give us answers. It merely opens up the space for questions as deep and vast as the night sky. It challenges our assumptions and reminds us of the immensity of what we don't know, nudging us to look up with a bit more wonder and perhaps a hint of trepidation. The overview effect. Picture this. You are in space far above Earth, surrounded by the endless dark canvas of the cosmos, staring down at the blue and green sphere we call home. In this moment, you see no borders, no countries, no divisions, only a single interconnected planet floating in the infinite vastness. This profound shift in perspective is called the overview effect, an extraordinary and often life-changing experience reported by astronauts who've seen Earth from space. The overview effect is not simply the awe of a beautiful view. It's a transformative moment that alters the way one perceives humanity, nature, and even existence itself. Astronauts who experience it often describe an overwhelming sense of unity and interconnectedness, a feeling that every person, creature, and ecosystem on Earth is part of a single, fragile whole. But what exactly causes this change, and why does seeing Earth from space make such a dramatic impact on one's psyche? To explore these questions, we'll dive into the concept of the overview effect and unpack the lessons it offers for how we live on this planet. The term overview effect was first coined by space philosopher Frank White in the 1980s. In interviews with astronauts, White discovered that nearly all of them experienced a profound cognitive shift when observing Earth from orbit. He described this effect as a sudden realization that the world's political, religious, and cultural conflicts seemed trivial compared to the vastness of space and the fragile beauty of Earth. From space, Earth appears as a tiny, self-contained ecosystem without visible boundaries. In White's words, the overview effect catalyzes a sense of responsibility and empathy, encouraging individuals to become advocates for the preservation and care of our planet. One of the most famous instances of the overview effect occurred during the Apollo 8 mission in 1968. When astronauts captured the now iconic Earthrise photo. For the first time in history, humanity saw Earth from beyond its orbit, a beautiful and isolated orb in the endless blackness of space. This image became a powerful symbol for the environmental movement, as people around the world began to grasp the interconnectedness of Earth's ecosystems and the need to protect them. To understand why this experience resonates so deeply, let's use an analogy. Imagine living in a tiny town your whole life, thinking it's the entire world. Your perspectives, beliefs, and concerns are shaped by what happens within the borders of this town. But then, one day, you climb to the top of a nearby mountain, and from this vantage point, you can see dozens of other towns, forests, and rivers stretching out into the horizon. Suddenly, the issues that seem so pressing in your town feel smaller, and you realize you're part of a much larger landscape. In a way, the overview effect is like climbing that mountain, except instead of seeing neighboring towns, you see all of humanity united on a single isolated planet. Astronauts often say that the overview effect permanently alters their priorities and sense of purpose. The experience tends to foster a deep sense of stewardship toward Earth and a desire to promote peace, unity, and environmental protection. Dr. Edgar Mitchell, an Apollo 14 astronaut, described it as an instant global consciousness that emerged from seeing the interconnectedness of all life on Earth. He said, "You develop an intense dissatisfaction with the state of the world and a compulsion to do something about it." Mitchell went on to become an advocate for environmental causes and dedicated his life to promoting sustainable practices. The overview effect also prompts philosophical questions about identity and existence. From the perspective of space, the boundaries that divide nations, races, and religions disappear, leaving only one shared home. This profound unity challenges the way people typically define themselves, encouraging a more expansive sense of identity. It pushes individuals to see themselves as Earthlings, rather than by national or cultural labels, emphasizing a shared humanity rather than divisions. The lessons of the overview effect reach far beyond astronauts. They are relevant to every person on Earth. Although most of us won't have the chance to view Earth from space, we can still tap into this mindset. By looking at images of Earth from space, exploring nature, and learning about the interconnectedness of ecosystems, we can foster a similar sense of unity and responsibility. The overview effect calls on us to shift from thinking in terms of me to we, recognizing that our actions impact everyone and everything on this delicate, life-supporting planet. In an age when environmental issues, political conflicts, and social divides seem more pressing than ever, the overview effect reminds us of the bigger picture. Earth is our shared home, and its well-being is inextricably tied to our own. Embracing this perspective can inspire us to take actions that reflect care, empathy, and responsibility toward all living beings and the planet itself. By understanding the overview effect, we don't just gain insight into the mindset of astronauts, we gain a powerful reminder of what unites us. It's a call to action for everyone to live with greater consciousness and compassion, knowing that we are all, in the grand expanse of the universe, passengers on the same fragile spaceship. The spotlight effect theory. Picture yourself walking into a crowded cafe. You've just spilled a few drops of coffee on your white shirt. Your heart races, and suddenly it feels like every single person in that cafe is staring at you, judging you, noticing that small brown stain that seems to be screaming for attention. In your mind, you become the center of a spotlight that doesn't actually exist. This, dear listeners, is the spotlight effect theory, our tendency to overestimate how much other people notice about us, both our failures and our triumphs. Think of it as wearing a pair of glasses that magnifies how visible we think we are to others, when in reality, everyone else is wearing their own pair, focused on themselves. The term was coined by psychologists Thomas Gilovich and Kenneth Savitsky in 1999, but the phenomenon has been part of human experience for as long as we've had self-consciousness. In their groundbreaking study, they asked college students to wear an embarrassing T-shirt, one with a large picture of Barry Manilow, into a room full of their peers. Before entering, the students predicted that about half of the people in the room would notice their shirt. In reality, only about 25% did. Why does this happen? Imagine you're the director of your own life's movie. You're always at the center of your own experience. Every thought, every emotion, every minor embarrassment plays out on your personal main stage. But here's the beautiful truth. Everyone else is the director of their own movie too. While you're worrying about that small coffee stain, they're probably consumed by their own narratives, their own concerns, their own spotlight effects. Let's explore this deeper through another story. Sarah, a public speaker, once gave a presentation where she stumbled over her words for a brief moment. For days afterward, she was convinced that this tiny mistake had ruined her entire speech and that everyone remembered it. But when she asked audience members later, most couldn't even recall the stumble. They remembered her insights, her presence, but not the small imperfection that had seemed so glaring to her. The spotlight effect teaches us something profoundly liberating. We are both more and less important than we imagine, more important in our own internal world, less important in everyone else's. This isn't because others don't care about us, but because they're caught up in their own spotlight effects, their own internal movies. Think about how this knowledge might free you. That awkward moment in the meeting? Most people have already forgotten it. That mismatched outfit you wore last week? It likely registered for mere seconds in others' minds, if at all. The spotlight effect is like a magnifying mirror. It shows us our flaws in high definition, but no one else is looking through that same mirror. Understanding this can be incredibly liberating. It doesn't mean we should stop caring about how we present ourselves or what we contribute to the world. Rather, it invites us to be more compassionate with ourselves, to understand that our perceived spotlight is often just that, perceived. As you drift towards sleep tonight, consider releasing yourself from your self-imposed spotlight. Remember that just as the stars in the night sky shine, without worrying who's watching, you too can move through life with less self-consciousness and more self-acceptance. The spotlight effect is merely an illusion of our minds, and in recognizing it, we find a kind of freedom, the freedom to be imperfectly, beautifully human. The Barnum effect. You have a great need for others to like and admire you, yet you tend to be critical of yourself. While you have some personality weaknesses, you are generally able to compensate for them. You have considerable unused capacity that you have not turned to your advantage. How accurate does this description feel to you? Do you find yourself nodding along, thinking how perfectly it captures your personality? If so, you've just experienced the Barnum effect, a fascinating psychological phenomenon where we accept vague, general personality descriptions as uniquely specific to ourselves, when in reality they could apply to almost anyone. Named after P.T. Barnum, the legendary showman who famously said, "There's a sucker born every minute." The Barnum effect is like a mirror that shows us what we want to see. Imagine walking into a hall of mirrors at a carnival. Each mirror seems to show you something unique and personal, but in reality, they're all showing slightly different versions of the same reflection. Let me share a revealing story. In 1948, psychologist Bertram Fourier conducted an intriguing experiment. He gave his students a personality test and told them they would each receive a unique personality analysis. A week later, he gave each student what they believed was their personalized analysis. The students rated the accuracy of their analysis on a scale of 0 to 5, with an average score of 4.26, meaning they found it highly accurate. But here's the twist. Every student received exactly the same analysis. This effect explains why horoscopes feel so personally relevant, why fortune tellers seem mysteriously accurate, and why personality tests can feel so revealing. It's like being handed a key that seems perfectly shaped for your lock, only to discover it's a master key that opens many doors. First, there's our natural tendency toward confirmation bias. Like a detective who's already decided on the culprit, we actively look for evidence that confirms what we want to believe about ourselves. Second, these statements often contain what psychologists call double-headed statements. You can be outgoing and sociable, but sometimes you prefer quiet solitude. It's like describing water as both wet and capable of being frozen. Both are true, but they seem contradictory. Think about social media personality quizzes. Which ancient god are you? Or what's your spirit animal? They work because they tap into this effect, providing descriptions broad enough to fit anyone but specific enough to feel personal. It's like wearing a one-size-fits-all garment that's been cleverly marketed as custom-tailored. But understanding the Barnum effect isn't about becoming cynical. Rather, it's about developing a more nuanced understanding of how we perceive ourselves and how we process information about our personalities. It's like having a map that shows not just where we are, but also the optical illusions along the way. The real magic lies in recognizing that while we all share common human experiences and traits, our individual stories and choices make these universal experiences uniquely our own. Yes, we might all experience anxiety about the future, but your specific dreams and fears are still uniquely yours. As you rest with this knowledge, consider how this understanding might change how you interpret personality descriptions, horoscopes, or even compliments. Perhaps true self-knowledge isn't found in vague, universal statements, but in the specific, concrete experiences that shape our individual journeys. The Mandela effect. The Mandela effect. A fascinating phenomenon where large groups of people share the same false memories, remembering events or details differently from what historically occurred. It's as if we're all reading from slightly different versions of reality script. The term was coined by Fiona Broome in 2009 when she discovered that thousands of people, like herself, clearly remembered Nelson Mandela dying in prison in the 1980s. But here's the reality twist. Mandela was actually released from prison in 1990 and passed away in 2013. This shared false memory was so widespread and vivid that it sparked a deeper investigation into this curious phenomenon of collective misremembering. Think of memory like a massive library where each book is written by thousands of different authors simultaneously. Sometimes these authors inadvertently influence each other's stories, creating a blend of fact and fiction that becomes accepted as truth. It's like a game of telephone played not with words, but with memories, spanning across millions of minds. Let's explore some of the most compelling examples. Remember the beloved Monopoly Man. Many of us can picture him clearly with his top hat, suit, and monocle. Yet, he never had a monocle that's a detail our collective consciousness somehow invented. Or consider the famous logo of Fruit of the Loom. Countless people remember a cornucopia behind the fruit, but it was never there. It's as if we're all remembering a painting that was never painted. But why does this happen? Cognitive scientists suggest several fascinating explanations. First, there's the concept of confabulation, our brain's tendency to fill in gaps in our memory with details that make logical sense. Like an artist touching up a faded photograph, our minds add details that seem like they should be there. Then there's the power of social reinforcement. When we share memories with others who remember things the same way, it strengthens our conviction in these false memories. It's like a group of friends all agreeing on the details of a shared experience, even if those details aren't quite accurate. Some theorists have proposed more exotic explanations, suggesting parallel universes or glitches in the matrix. While these theories might seem far-fetched, they speak to our deep human need to make sense of shared experiences that don't quite align with reality. The Mandela effect teaches us something profound about the nature of memory and shared human experience. Our memories aren't like perfect digital recordings, they're more like impressionist paintings, capturing the feeling and essence of moments rather than exact details. Each time we recall a memory, we're not accessing the original file, but rather recreating it anew, sometimes with subtle alterations. Perhaps the most beautiful aspect of the Mandela effect is how it connects us. These shared false memories become part of our collective cultural tapestry, reminding us that even in our misrememberings we're united. It's like we're all looking at the same stars, but seeing slightly different constellations. As you drift towards sleep, consider your own memories. How many might be slightly different from reality? And does it matter? Perhaps what's most important isn't the perfect accuracy of our memories, but the shared human experience. They represent the stories we tell ourselves and each other about the world we inhabit together. The Baader-Meinhof phenomenon. Have you ever bought a new car and suddenly started seeing that exact model everywhere? Or learned a new word, only to find it popping up in every book you read? If so, you've experienced the Baader-Meinhof phenomenon, also known as the frequency illusion, a fascinating quirk of human consciousness that makes us notice things more often once they've captured our attention. Imagine your mind as a vast ocean of information, with countless fish swimming by every moment. Usually, most of these fish pass unnoticed, but when something catches your attention, let's say a bright yellow fish, suddenly you start noticing yellow fish everywhere. They haven't actually become more numerous, you've just become more attuned to their presence. This phenomenon got its unusual name in 1994 when a newspaper reader noticed the term Baader-Meinhof twice in short succession and mentioned this coincidence to others. Ironically, people then began noticing the phrase Baader-Meinhof everywhere, perfectly demonstrating the very effect it described. The science behind this phenomenon involves two distinct cognitive processes working in harmony. The first is selective attention, which is like having a mental spotlight that automatically illuminates certain things once they've caught our interest. The second is confirmation bias, our tendency to notice and remember instances that confirm our expectations while overlooking those that don't. Let me share a story that illustrates this beautifully. Sarah, an art student, learned about a relatively obscure artistic technique called chiaroscuro, the use of strong contrasts between light and dark. In the following weeks, she began noticing chiaroscuro everywhere, in photography magazines, movie posters, even in the way sunlight fell across her kitchen table. The technique hadn't suddenly become more prevalent. Her brain had simply created a new filter through which to view the world. This effect goes beyond simple pattern recognition. It reveals something profound about how our consciousness shapes our reality. Consider how many times you'd walk down your street without noticing the bird songs, only to have them become unmissable once someone points them out. The birds were always there, singing their songs, but they existed outside your conscious awareness. The Baader-Meinhof phenomenon reminds us that our perception of reality is not a perfect mirror of what exists, but rather a carefully curated experience shaped by our attention and expectations. It's as if our consciousness is a skilled DJ, mixing and amplifying certain frequencies while letting others fade into the background. This phenomenon has practical implications too. Marketers understand that once you notice their product, you'll start seeing it everywhere, creating an illusion of ubiquity. Politicians know that once they plant an idea, supporters will begin noticing evidence that confirms it everywhere they look. Even in our personal lives, when we learn about a new concept or theory, we often find evidence of it in unexpected places. But there's also something beautiful about this quirk of consciousness. It reminds us that the world is infinitely richer and more detailed than we typically notice. Each shift in our attention reveals new layers of reality that were always there, waiting to be discovered. It's like having access to countless radio stations, but only being able to tune into a few at a time. Understanding the Baader-Meinhof phenomenon can make us more mindful of how our attention shapes our experience. It invites us to wonder, what else might we notice if we shifted our attention just slightly? What other patterns and connections are waiting to be discovered in the rich tapestry of our daily experience? As you drift towards sleep, consider what patterns your mind might be amplifying right now, and what new awareness tomorrow might bring. Remember that each day holds infinite potential for discovery, even in the most familiar surroundings. The beauty of this phenomenon lies not just in understanding it, but in recognizing how it enriches our experience of the world, making each day a potential adventure in perception and awareness. The philosophical razor of Hanlon. Never attribute to malice that which can be adequately explained by stupidity. These words, known as Hanlon's razor, might sound harsh at first, but they contain a profound wisdom that could transform how you view the world and the people around you. Imagine you're waiting for an important email from a colleague. Hours pass, then days. Your mind begins weaving elaborate theories. They're deliberately ignoring me. They're trying to sabotage my project. They must be talking behind my back. But then you discover the truth. They simply typed your email address incorrectly. This simple scenario perfectly illustrates Hanlon's razor in action. This philosophical principle, named after Robert J. Hanlon, though its origins trace back much further, serves as a powerful mental tool like a sharp blade that cuts through our tendency to assume the worst in others' motives. Think of it as a pair of special glasses that help you see the world more clearly, filtering out the distortions of paranoia and suspicion. Let's delve deeper through a story. Sarah, a software developer, once spent weeks believing her team member was deliberately undermining her code contributions. She crafted elaborate theories about professional jealousy and workplace politics. The reality? Her colleague was struggling with undiagnosed ADHD and was making genuine mistakes while trying his best to keep up with the workload. The moment Sarah applied Hanlon's razor, her entire perspective shifted from antagonism to empathy. But why do we so readily jump to assuming malice? The answer lies in our evolutionary history. Our ancestors survived by being hypervigilant about others' intentions. Those who assumed the rustling in the bushes was a predator rather than the wind were more likely to survive. We've inherited this cautious mindset, but in our modern world, it often leads us astray. The beauty of Hanlon's razor lies in its practical applications. In the workplace, it can transform toxic environments into collaborative spaces. In relationships, it can prevent unnecessary conflicts and foster understanding. In daily life, it can reduce stress and anxiety by offering simpler, less sinister explanations for others' actions. Consider these common scenarios. A friend doesn't respond to your text. Before assuming they're angry with you, consider that they might be overwhelmed with work or family obligations. A driver cuts you off in traffic. Instead of assuming they're being deliberately rude, consider that they might be distracted by a personal emergency. A service worker seems unfriendly. Rather than taking it personally, consider that they might be dealing with personal challenges you know nothing about. However, Hanlon's razor isn't about naivety or dismissing genuine malice when it exists. Think of it as a first-line diagnostic tool, not an absolute rule. It's about making incompetence or ignorance our first hypothesis, rather than our last resort. The principle also contains a deeper truth about human nature. Most people aren't plotting and scheming their way through life. They're just trying their best to navigate their own challenges, often making mistakes along the way. This realization can be incredibly liberating, as it frees us from the exhausting task of constantly analyzing others' hidden motives. Perhaps most profoundly, Hanlon's razor invites us to extend to others the same grace we hope they'll extend to us when we make mistakes. After all, haven't we all been on the other side, having our momentary lapses or oversights misinterpreted as intentional slights? As you rest with this wisdom, consider how many of your current frustrations might look different through the lens of Hanlon's razor. How might your relationships change if you replaced suspicion with curiosity and assumed confusion before malice? In doing so, you might find yourself living in a world that seems less hostile and more human. A world where mistakes are just mistakes and where understanding comes before judgment. This simple philosophical tool, when properly applied, doesn't just change how we see others. It transforms how we experience the world itself, making it a less threatening and more comprehensible place to exist. Occam's razor principle. Imagine you're walking through a garden and hear hoofbeats. Which is more likely, that it's a horse or that it's a zebra wearing a saddle while being ridden by a unicorn? This whimsical example introduces us to one of philosophy's most powerful thinking tools, Occam's razor, the principle that states, entities should not be multiplied beyond necessity, or in simpler terms, the simplest explanation is usually the best one. Named after William of Occam, a 14th century Franciscan friar, this philosophical razor isn't about finding the easiest answer. It's about finding the answer that requires the fewest assumptions. Think of it as a mental pruning tool, cutting away unnecessary complications to reveal the most likely truth. Let's explore this through a story. A detective arrives at a crime scene where a jewelry store has been robbed. She finds two possible explanations. First, a professional thief with years of experience used specialized tools to crack the safe. Second, a team of international spies coordinated with aliens using advanced technology to teleport the jewels away, while simultaneously erasing security footage and hypnotizing the guards. Even though the second explanation might be more exciting, Occam's razor guides us toward the first, simpler explanation. But why does simplicity often lead to truth? Imagine building a house of cards. The taller and more complex you make it, the more likely it is to collapse. Each additional card, or in our case, each additional assumption increases the chances of the whole structure falling apart. Similarly, complex explanations require more things to be true simultaneously, making them statistically less likely to be correct. This principle revolutionized scientific thinking. Before Copernicus, astronomers created incredibly complex models to explain planetary motion, adding circle upon circle to match their observations. Then Copernicus suggested a simpler explanation. What if the planets, including Earth, just orbited the Sun? This elegant solution, though controversial at the time, proved far more accurate than its complicated predecessors. However, Occam's razor comes with an important caveat. It's a guiding principle, not an absolute rule. Sometimes the truth is complex. Think of quantum physics, where the reality of subatomic particles often seems stranger than fiction. The key is that even in these cases, we should only add complexity when simpler explanations fail to account for all the evidence. In our daily lives, Occam's razor can be an invaluable tool for decision-making and problem-solving. When your phone stops working, start with checking if it's charged before assuming it's been hacked by cybercriminals. When a friend doesn't show up for coffee, consider that they might have forgotten before concluding they've been kidnapped by a secret organization. This principle also teaches us something profound about human nature. We often prefer complex, dramatic explanations because they seem more meaningful or interesting. There's something almost disappointing about simple truths. Yet, finding beauty and simplicity in the elegant, straightforward explanation can be deeply satisfying. Consider how this applies to everyday situations. A strange light in the sky? Before assuming aliens, consider aircraft or satellites. A mysterious illness? Check common causes before fearing rare diseases. Unexpected success at work? Your hard work might be the simpler explanation than luck or conspiracy. Occam's razor doesn't just help us find truth, it helps us find peace of mind. By favoring simpler explanations, we can avoid the anxiety that comes from imagining elaborate worst-case scenarios. It's a reminder that sometimes the truth isn't hiding in complexity, but standing in plain sight, waiting for us to notice its elegant simplicity. Now, as you drift towards sleep, consider how this principle might illuminate your own life. How many of your worries rest on complicated assumptions? How many problems might have simpler solutions than you've imagined? In embracing Occam's razor, we might find not just clearer thinking, but a clearer path through life itself. Remember, in a world that often celebrates complexity, there's profound wisdom in seeking simplicity. The truth, more often than not, doesn't need elaborate embellishments, it simply needs to be recognized. The lottery of birth theory. Imagine for a moment that before you were born, you were handed a cosmic lottery ticket. This ticket would determine not just who you would be, but where you would be born, to whom, in what era, in what circumstances, and with what opportunities. This is the lottery of birth theory, a profound philosophical concept that challenges our notions of merit, justice, and human destiny. Consider this. You didn't choose to be born in your country, to your parents, with your genetic predispositions, or in this particular century. You didn't select your native language, your early education, or the cultural values that shaped your formative years. Everything that forms the foundation of who you are began with a roll of cosmic dice. Think of it like arriving at a theater where a play is already in progress. You didn't choose the script, the setting, or your role. You simply found yourself on stage, expected to perform. Some are born onto a stage with bright lights and a supportive audience, while others enter a dimly lit corner with far fewer resources at their disposal. This theory carries profound implications for how we view success, failure, and human potential. Warren Buffett himself acknowledged this when he spoke of winning the ovarian lottery, being born male, white, and in America during the 20th century, with access to opportunities that most of human history never knew. He recognized that his success, while requiring skill and effort, was built upon a foundation he neither earned nor chose. Let's explore this through a thought experiment. Imagine a child born in a remote village without electricity, clean water, or access to education. Now imagine another child born into a wealthy family in a developed nation with access to the best schools, healthcare, and opportunities. Both children might possess equal innate potential, but their life trajectories will likely differ dramatically due to circumstances entirely beyond their control. The theory challenges our traditional narratives about merit and achievement. While personal effort, dedication, and choices matter tremendously, they operate within the boundaries set by our birth lottery. It's like being dealt cards in a poker game. While skill affects how you play them, the initial deal significantly influences your chances of winning. This understanding has revolutionary implications for how we view social justice and human society. If our station in life is largely determined by factors beyond our control, what does this but mean for our obligations to one another? How should this influence our policies, our judgments, and our treatment of those less fortunate? Consider education. A child born in Silicon Valley to tech executive parents will have vastly different educational opportunities than one born in a war-torn region or impoverished community. Neither child earned their starting position, they simply won or lost a lottery they never entered. The theory also invites us to examine privilege not as something to feel guilty about, but as something to acknowledge and potentially use to benefit others. If you've won aspects of the birth lottery, perhaps your privilege carries a responsibility to help create opportunities for those who didn't. This perspective can foster both humility and empathy. When we truly internalize that we didn't choose our starting circumstances, it becomes harder to judge others for theirs. The theory suggests that "there but for the grace of fortune go I" isn't just a saying. It's a fundamental truth about human existence. Yet this theory isn't meant to promote fatalism or dismiss personal responsibility. Rather, it's about understanding the complex interplay between circumstance and choice. We may not choose our starting point, but we can choose what to do with what we're given. As you contemplate this theory, consider how it might change your view of others, the homeless person on the street, the refugee seeking asylum, or the child born into wealth and privilege. Each is playing with cards they were dealt, in a game they didn't choose to enter. This understanding can lead to a more compassionate and equitable worldview, where we recognize that our achievements and failures exist within a broader context of fortune and circumstance. It reminds us that while we can't control where we start in life, we can control how we treat others who started differently. How? The Capgras delusion theory. Imagine coming home one evening and looking at your loved one's face, their smile, their eyes, their familiar features, but something feels terrifyingly wrong. While they look identical to your loved one, you're gripped by an unshakable feeling that they're actually an imposter, a perfect duplicate who has somehow replaced the real person you know. This isn't the plot of a science fiction movie. This is the reality for people experiencing the Capgras delusion, one of the most fascinating phenomena in the realm of human consciousness and perception. First described by Joseph Capgras, a French psychiatrist in 1923, this rare psychological condition reveals profound insights about how our minds construct reality and recognize the people we love. He first observed it in a woman who was convinced that multiple identical-looking imposters had replaced her husband. What makes this delusion so intriguing is that it challenges our basic understanding of how we recognize faces and form emotional connections. To understand the Capgras delusion, let's explore how our brain typically recognizes faces. Imagine your brain as a sophisticated security system in an art museum. There are two parallel pathways, one for visual recognition, like security cameras identifying a visitor's face, and another for emotional response, like sensors detecting if this visitor belongs here. In normal face recognition, these two systems work in perfect harmony. But in Capgras delusion, something remarkable happens. The visual system works perfectly. Patients can see and recognize every detail of their loved one's face. However, the emotional pathway becomes disconnected. It's as if the security camera recognizes the visitor, but the emotional sensor doesn't trigger the usual warm, familiar feeling of recognition. This disconnect creates a profound paradox in the mind. Think about looking at a photograph of someone you love. You recognize them instantly, but you don't feel the same emotional warmth as when you see them in person. The Capgras delusion is like being stuck in this state, permanently recognizing but not feeling the emotional connection, leading the mind to create an explanation. This must be an imposter. The implications of this condition reach far beyond clinical interest. It raises profound questions about consciousness, identity, and the nature of human connections. How much of our recognition of loved ones depends on pure visual input, and how much relies on the invisible threads of emotional connection? What does it mean to truly know someone? Some philosophers and neuroscientists suggest that the Capgras delusion offers us a window into the complex machinery of consciousness. It shows us that our experience of reality isn't a simple unified process, but rather a delicate dance between different systems in our brain, each contributing to our sense of what's real and familiar. Consider for a moment. Every time you recognize a loved one, your brain performs an incredible feat of integration, matching visual patterns with emotional memories, creating that seamless feeling of familiarity we take for granted. When this integration fails, as in Capgras delusion, we glimpse how fragile yet remarkable our perception of reality truly is. The Capgras delusion teaches us something profound about human consciousness. Our sense of reality, our recognition of loved ones, and our feeling of connection to others isn't a simple, single process, but a beautiful symphony of different mental systems working in harmony. When this harmony is disrupted, it reveals just how complex and mysterious our experience of consciousness truly is. As you drift closer to sleep, consider how many intricate processes are working together right now in your mind, creating your unique experience of reality, your recognition of the world around you, and your connection to those you love. The Uncanny Valley Theory. Here's a soothing yet insightful script for the Uncanny Valley Theory. Have you ever felt an inexplicable sense of unease when looking at a highly realistic robot or a CGI human character that's almost but not quite perfect? That subtle feeling of discomfort, that creeping sensation that something isn't quite right, you're experiencing what robotics professor Masahiro Mori called the Uncanny Valley, a fascinating phenomenon that tells us as much about human psychology as it does about technology. Imagine walking through a toy store. You see a simple cartoon-like stuffed bear. It's clearly artificial, yet it brings a smile to your face. Next to it is a wooden doll again, clearly not human, but charming in its simplicity. But then you encounter something different. A hyper-realistic humanoid doll with almost perfect skin texture, nearly natural eye movements, and an almost human smile. Suddenly, that warm feeling disappears, replaced by a subtle but distinct feeling of unease. You've just descended into the Uncanny Valley. The theory suggests that as artificial creations become more human-like, our emotional response to them becomes increasingly positive, but only up to a point. When these creations become too close to human, yet still noticeably artificial, our comfort suddenly plunges into what we call the valley, a deep drop in emotional response, marked by feelings of unease or even revulsion. Think of it like climbing two mountains with a valley between them. The first mountain represents our increasing comfort with artificial things as they become more human-like, from simple robots to cartoons to more sophisticated animations. But just before reaching perfect human likeness, we tumble into the valley. Only by crossing this valley, achieving either complete human likeness or deliberately staying less realistic, can we reach the second peak of comfort and acceptance. But why does this valley exist? Some scientists believe it's deeply rooted in our evolutionary history, a protective mechanism that helped our ancestors avoid sick or dead members of their species. Others suggest it's connected to our fundamental sense of human identity and our innate ability to detect when something isn't quite right. Consider how a symphony orchestra works. When all instruments play perfectly in tune, the music is beautiful. If one instrument is slightly out of tune, our ears immediately detect this discordance, even if we can't explain exactly what's wrong. The uncanny valley works similarly. Our brains are exquisitely tuned to detect these subtle out-of-tune elements in human appearance and behavior. The implications of the uncanny valley reach far beyond robotics and animation. It raises profound questions about human nature itself. What makes us human? How do we recognize humanity in others? Where do we draw the line between artificial and authentic? In our modern world, as technology increasingly tries to replicate human characteristics, the uncanny valley becomes more relevant than ever. From virtual influencers to AI-powered chatbots, we're constantly navigating this delicate balance between artificial and human connection. Perhaps most fascinating is how the uncanny valley reflects our own self-image. Like a mirror showing us what we're not, these almost human creations help us understand what we truly are. Each feeling of discomfort in the valley is really a reminder of the countless subtle elements that make us uniquely human. The microscopic movements, the imperfect perfections, the authentic irregularities that no artificial creation has yet perfectly captured. As you rest and drift closer to sleep, consider how your own mind navigates this valley every day, instantaneously processing countless signals to recognize what is authentically human. In our increasingly digital world, perhaps the uncanny valley isn't just a theory about robots and animations. It's a window into our own humanity, helping us understand what makes us uniquely, imperfectly, beautifully human. The uncanny valley reminds us that in our quest to create perfect replicas of human life, we've discovered something profound about the nature of humanity itself sometimes. It's our very imperfections that make us perfect. The philosophical concept of Yugen. Imagine standing at the edge of a vast ocean at twilight, watching the sun slowly sink below the horizon. As darkness gently falls, you catch a glimpse of wild geese disappearing into a clouded moon. There's a feeling that washes over you, something profound, yet impossible to fully capture in words. This mysterious deep awareness of the universe's beauty and mystery is what Japanese aesthetics calls Yugen, perhaps one of the most elegant and elusive concepts in all of philosophical thought. Yugen literally translates to mysterious profundity. But like many profound concepts, its true meaning lies beyond simple translation. It's the feeling you get when you realize that the universe is far more mysterious and beautiful than we could ever fully comprehend. Think of Yugen as reading a book where the most important story lies between the lines. It's not in what you see, but in what you sense exists just beyond your perception. Imagine walking through an ancient forest. You see the sunlight filtering through the leaves, creating dancing shadows on the ground. Yugen isn't in the leaves or the light themselves. It's in the subtle suggestion that there's something more, something deeper, something just beyond our grasp. To understand Yugen better, consider these moments. The way your heart feels when you look up at the stars and truly comprehend their distance. The sensation of watching autumn leaves fall and suddenly understanding the cyclical nature of existence. The feeling of hearing a wind chime in the distance and wondering about all the stories the wind could tell. In traditional Japanese arts, Yugen manifests in different ways. In poetry, it's the power of suggestion rather than explicit statement. In painting, it's the empty space that speaks as loudly as the brushstrokes. In theater, it's the pregnant pause between actions that holds the deepest meaning. But Yugen isn't just an artistic concept, it's a way of seeing the world. Modern physics tells us that the universe is stranger and more mysterious than we could have imagined. Dark matter, quantum entanglement, the vast expanses of space, these scientific discoveries echo what the ancient Japanese understood through Yugen, that the most profound truths often lie just beyond our direct perception. Consider how Yugen might apply to human consciousness itself. Just as we can never directly see the wind, but only its effects on leaves and water, we can never directly observe consciousness, but only its manifestations in thought and behavior. This parallel suggests that Yugen isn't just a poetic idea, but a fundamental truth about how we experience reality. Think of Yugen as similar to watching a boat disappear over the horizon. The mystery isn't in the boat's disappearance itself, but in the suggestion of countless unseen journeys continuing beyond our view. It's the understanding that while we can't see what lies beyond, we can feel the vastness of what might be there. In our modern world of instant information and constant connectivity, Yugen reminds us of the value of mystery. It suggests that true wisdom lies not in knowing everything, but in being aware of how much we don't know. It's found in those moments when we stop trying to understand everything and simply allow ourselves to be moved by the profound mystery of existence. As you drift toward sleep, consider the Yugen. In this very moment, the mysterious process of consciousness transitioning to dreams, the countless thoughts and memories floating just below the surface of awareness, the profound complexity of your own existence. Like a moon partially hidden by clouds, the most beautiful aspects of life are often those we can sense but never fully grasp. In embracing Yugen, we learn that some things are more beautiful precisely because they cannot be fully understood, like the space between stars, the depth of human emotion, or the peaceful transition from wakefulness to dreams. The philosophical concept of Ma. Take a deep breath, and now slowly exhale. In that pause between your breath, that perfect moment of stillness you've just experienced, what Japanese philosophy calls Ma. It's not just empty space or silence. It's the powerful interval where meaning itself resides. Ma teaches us that emptiness isn't nothing. It's everything. Imagine a conversation with someone you love. What makes it meaningful isn't just the words spoken, but the thoughtful pauses between them. These aren't empty gaps, they're pregnant with meaning, anticipation, and understanding. This is Ma in its most human form. In Japanese, Ma is written with a character that shows the sun peeking through an open gate. Like sunlight streaming through a doorway, Ma is the space that allows brilliance to enter our lives. It's not the absence of something, but rather the presence of possibility. Think of music for a moment. A beautiful melody isn't just about the notes being played, it's about the precise spacing between those notes. Without these intervals, we wouldn't have music at all. We'd have noise. In the same way, Ma suggests that life's meaning often resides not in the events themselves, but in the spaces between them. In traditional Japanese architecture, Ma manifests in the thoughtful arrangement of rooms and gardens. Consider the tokonoma, an empty alcove in a traditional Japanese home. To Western eyes, it might appear to be wasted space. But in the philosophy of Ma, this emptiness serves as a vessel for possibility, a space where imagination and meaning can dwell. Ma appears everywhere in daily life, though we rarely notice it. The moment before sunrise when the world holds its breath. The space between reaching for someone's hand and touching it. The silence after a profound question. The emptiness of a canvas before the first brushstroke. In our modern world, we often try to fill every moment, every space, every silence. We check our phones during elevator rides, play background music during quiet moments, scroll through social media in waiting rooms. But Ma reminds us that these empty spaces aren't meant to be filled, they're meant to be experienced. Think of Ma like the white space in a beautiful piece of calligraphy. The empty space isn't a blank void, it's an active element that gives the black ink its power and meaning. Without this space, the characters would blur together, losing their clarity and impact. Ma teaches us about the art of timing in life. Just as a skilled comedian knows the perfect pause before a punchline, Ma suggests that all of life has its own natural rhythm of fullness and emptiness. It reminds us that sometimes doing nothing is doing something very important indeed. In meditation practices, Ma manifests as the space between thoughts, that moment of pure awareness before the next thought arises. It's in these spaces that we often find our deepest insights and most profound peace. As you lie here, drifting toward sleep, notice the Ma in your own experience, the quiet space between your thoughts, the peaceful interval between your breaths, the gentle transition between wakefulness and dreams. Ma reminds us that emptiness is never truly empty. Like a vessel that's useful because of its hollow center, or a window that serves its purpose through its openness, the apparent nothingness in our lives might actually be everything we need. It teaches us that sometimes the most meaningful moments are the ones where nothing seems to be happening at all. As you rest in this moment, allow yourself to appreciate the Ma in your own life, the beautiful empty spaces that give shape and meaning to all the fullness around them. For it's in these precious intervals that we often find our deepest peace, our clearest insights, and our most profound connections to the essence of being. The philosophical concept of wabi-sabi. Look at your hands for a moment. Notice the tiny imperfections, the slight asymmetry of your fingers, the unique patterns in your skin, perhaps some scars that tell stories of your past. In these supposed flaws, you're witnessing what Japanese philosophy calls wabi-sabi, the profound beauty of imperfection, impermanence, and incompleteness. It's a concept that challenges our modern obsession with perfection and invites us to see beauty in the most unexpected places. Imagine an ancient ceramic bowl, cracked and repaired with gold. This is kintsugi, the physical embodiment of wabi-sabi. Instead of hiding the cracks, they're highlighted with precious metal, suggesting that it's the imperfections that make something truly valuable. The bowl isn't beautiful despite its cracks, it's beautiful because of them. Wabi originally meant the loneliness of living in nature, remote from society, while sabi-ji referred to the autumn of life, the lean and withered beauty of age. Together, they've evolved to describe a profound appreciation for the imperfect, rustic, and melancholy aspects of existence. Think of wabi-sabi like an old wooden bench in a garden. Over years, the wood has weathered, its surface textured by rain and sun. Moss grows in its crevices, and the grain has become more pronounced. To a mindset focused on perfection, this bench needs replacement, but through the lens of wabi-sabi, it has only grown more beautiful with time, each mark and weathering telling a story of its journey through seasons. Wabi-sabi appears in countless forms. The asymmetrical leaves of a naturally grown plant, the gentle wear on well-loved books, the patina on old copper, the wrinkles around smiling eyes, the handmade pottery with visible fingerprints, the worn stones of ancient temples. In our age of filters, Photoshop, and carefully curated social media, wabi-sabi offers a revolutionary perspective. It suggests that our attempt to achieve perfection is misguided, not because perfection is too lofty a goal, but because imperfection is actually more beautiful and meaningful. Consider how wabi-sabi might apply to human relationships. Like an old marriage that has weathered storms and grown stronger through challenges, or a friendship that's more meaningful because of the difficulties it has overcome. These aren't perfect relationships, they're real ones, and that makes them far more precious. In traditional Japanese aesthetics, wabi-sabi manifests in rough ceramics, uneven glazes, simple tea houses, and modest gardens. But its wisdom extends far beyond aesthetics. It's a worldview that accepts the fundamental truth of existence. Nothing lasts, nothing is complete, and nothing is perfect. Think of wabi-sabi as nature's truth revealed in objects and experiences. A perfect sphere exists only in mathematics in nature. Everything is slightly askew, weathered, and in constant transition. This isn't a flaw in the universe, it's the very essence of reality. Wabi-sabi reminds us that we are not meant to be perfect, complete, or permanent. Like the changing seasons, the weathered stones, and the aging trees, our beauty lies in our transience and our flaws. Each wrinkle, scar, and imperfection is not a flaw to be corrected, but a story to be honored. As you drift toward sleep, remember that like this moment, imperfect, incomplete, and impermanent, you too are perfectly imperfect, exactly as you should be. In embracing wabi-sabi, we find a deeper peace, one that comes not from achieving perfection, but from accepting and celebrating the beauty of life exactly as it is. Mono no aware. Picture yourself sitting beneath a cherry tree in full bloom. As you watch, a soft breeze stirs and a single petal breaks free, dancing slowly through the air before settling on the ground. In that moment, you feel something, a sweet sadness, a gentle ache, a bittersweet awareness that this perfect moment is already passing. This is mono no aware, wu no I, with a poignant awareness of the transience of all things. The term literally translates to the pathos of things, but its meaning runs far deeper. It's the emotional awareness that everything in life, every smile, every sunset, every cherished moment is fleeting. Yet rather than being a source of sadness, this awareness makes these moments even more precious. Think of looking through old photographs. There's a certain tenderness in seeing faces younger, places changed, moments long past. That feeling isn't quite nostalgia, nor is it purely sadness. It's mono, no aware, the gentle ache of being human and aware of time's passing. Imagine holding a handful of sand. The tighter you try to grasp it, the more quickly it slips through your fingers. Mono no aware teaches us not to clutch desperately at moments, but to appreciate them precisely because they're slipping away. It's the understanding that impermanence doesn't diminish beauty. It creates it. We experience mono, no aware in countless ways. The last day of summer vacation, a child's outgrown clothes, the changing of seasons, the end of a perfect evening with friends. In Japanese culture, the cherry blossom holds special significance precisely because of its ephemeral nature. The flowers bloom for just a few days each year, their brief appearance and inevitable falling away serving as a perfect metaphor for life itself. Their beauty isn't diminished by their briefness, it's enhanced by it. Mono no aware differs from simple sadness or melancholy. It's not about mourning what's lost, but about finding beauty in the very fact that nothing lasts. It suggests that impermanence isn't a flaw in the universe, it's what gives life its depth and meaning. In our modern world of digital permanence and instant replay, mono no aware reminds us that real life happens only once. Each sunset is unique, each laugh unrepeatable, each moment a singular gift that will never come again exactly the same way. This concept teaches us about love too. When we truly love someone, we're acutely aware that our time together is finite. This awareness doesn't make love sad. It makes it more precious, more worthy of our full attention and gratitude. Mono no aware invites us to live more fully by accepting life's transient nature. It suggests that our awareness of impermanence can lead not to despair, but to a deeper appreciation of beauty and a more profound capacity for love and gratitude. As you drift towards sleep, remember that this very moment with its unique combination of thoughts, feelings, and sensations will never come again exactly this way. And that's what makes it perfect. Like a cherry blossom carried on the wind, each moment is more beautiful because it's fleeting. The glass child syndrome. Imagine a family photograph where one child seems to fade into the background, like light passing through glass. They're present, yet somehow transparent, bearing the weight of being simultaneously visible and unseen. This is the essence of what we call the glass child syndrome, a profound psychological phenomenon that affects siblings of children with special needs or chronic conditions. The term glass child was coined by Alicia Arenas, who grew up as the sibling of a child with special needs. She describes glass children as those who watch life happen through a transparent wall, seeing everything, feeling everything, but often going unnoticed in the intensity of their family situation. Think of a garden where one plant requires constant attention, special care, and extra resources to survive. While the gardener's dedication is necessary and beautiful, the other plants must learn to grow in whatever light filters through. They become resilient, but they also become transparent, like glass. Glass children often develop remarkable characteristics: extraordinary empathy at a young age, advanced emotional intelligence, strong self-reliance. Imagine holding two glasses, one visibly cracked and requiring careful handling, the other seemingly perfect and sturdy. The world naturally focuses on protecting the cracked glass, while the sturdy one is expected to need no special care. But glass, no matter how strong it appears, still needs gentle handling and attention. These children often develop what psychologists call precocious maturity, growing up too fast, too soon. Like a greenhouse plant forced to bloom early, they develop survival mechanisms that are both impressive and poignant. To the glass children listening, your transparency isn't invisibility. Your strength isn't invulnerability. Your maturity isn't a barrier to needing support. Like a prism that appears clear, yet contains all the colors of the rainbow, you hold depths that deserve to be seen and understood. If you're a glass child, know that your experiences have shaped you, but don't define you. Like light passing through a prism, your challenges can transform into unique strengths and profound wisdom. The glass child syndrome reminds us that sometimes the most resilient among us are the ones who appear the strongest. It teaches us to look more carefully at those who seem to need us least, to listen more attentively to those who complain the least, and to remember that strength, like glass, can be both remarkable and fragile. As you drift toward sleep, remember that being transparent doesn't make you invisible. Like the most beautiful glass art, your experiences have created patterns of light and shadow that make you uniquely precious and worthy of attention. The philosophical parking lot theory. Have you ever noticed how when you're desperately searching for a parking spot, it seems impossible to find one, but the moment you give up and decide to leave, several perfect spots appear? This seemingly mundane experience reveals a profound truth about human psychology and the nature of desire. Welcome to the philosophical parking lot theory. This theory isn't just about parking spaces, it's a metaphor for life's most persistent paradox. The way our desperate desire for something often becomes the very thing that prevents us from obtaining it. When we grip too tightly, what we seek seems to slip through our fingers. Imagine yourself circling a busy parking lot. Each loop increases your anxiety, your frustration growing with every filled space. Your mind becomes fixated on finding the perfect spot. In this state of desperate seeking, you might miss perfectly good spaces because they don't match your ideal, or you might be too tense to smoothly maneuver into an available spot when you do find one. First, the law of inverse effort. The harder you try to find something, the more it eludes you. This isn't just about parking spots. Think about trying to fall asleep, finding love, or achieving happiness. Often, the more desperately we pursue these things, the further they seem to drift away. Second, the paradox of attachment. When we become too attached to a specific outcome, we become blind to other possibilities. Like a driver fixated on finding a spot near the entrance, we might miss multiple suitable spaces slightly further away. Third, the liberation of surrender. The moment we truly let go of our desperate search, our perception shifts. We become more relaxed, more aware, and ironically, more likely to find what we're looking for. Think of it like trying to see a star in the night sky. If you look directly at it, it might seem to disappear. But when you relax your gaze and look slightly to the side, suddenly the star becomes visible. This is called averted vision in astronomy, but it applies to many aspects of life. This theory connects deeply with ancient wisdom traditions. Buddhists speak of non-attachment, Taoists of wu-wei, effortless action, and Stoics of accepting what we cannot control. The parking lot becomes a modern meditation on these timeless truths. The theory suggests a profound truth. Sometimes our greatest obstacle isn't external circumstances, but our own desperate desire for control. Like a tightly clenched fist that cannot receive anything new, a mind fixated on one specific outcome becomes blind to other possibilities. As you rest here, notice how this principle might apply to sleep itself. The more we try to force ourselves to sleep, the more elusive it becomes. But when we relax and let go of the need to sleep, we create the very conditions that allow sleep to arrive naturally. The philosophical parking lot theory reminds us that sometimes the best way forward is to ease our grip on what we seek. It suggests that life's gifts often come not through force of will, but through a delicate balance of intention and surrender. As you drift toward sleep, remember that like finding the perfect parking spot, some of life's most sought-after experiences come not when we chase them desperately, but when we create the space for them to appear naturally. The Codex Seraphinianus theory. Imagine you're holding a beautifully bound, thick, mysterious book in your hands. Its cover is adorned with intricate symbols, and as you open it, you're greeted by a series of surreal images. A strange plant morphing into a chair, fish swimming through rainbow-colored clouds, and people merging with their surroundings in bizarre ways. Every page is filled with an unfamiliar language, one no one has ever been able to decode. Welcome to the world of the Codex Seraphinianus, a book that has puzzled readers and scholars since its creation in the late 1970s. The Codex Seraphinianus, created by Italian artist and architect Luigi Serafini, is perhaps one of the most enigmatic works of our time. The book resembles an encyclopedia and is filled with detailed illustrations of an imaginary world, each accompanied by text written in a bizarre, indecipherable script. Although it's been nearly 50 years since its creation, no one has cracked its language or unlocked its meaning, leading to countless theories about its purpose and message. The Codex's contents evoke a powerful sense of curiosity and wonder, not unlike the feeling we get from childhood fairy tales or fantasy novels. Just as Alice fell down the rabbit hole into Wonderland, readers of the Codex are transported into a surreal alien landscape where the usual rules of reality don't apply. There are familiar elements, plants, animals, cities, but they're all distorted, twisted into forms that challenge our perceptions of the real world. In many ways, the Codex Seraphinianus embodies the human fascination with the unknown. We often seek to understand, categorize, and make sense of things. But what happens when something resists explanation? The Codex invites us into a world where we must accept mystery and ambiguity, embracing the strange and the unknowable. Some scholars suggest that this is precisely its point. It's a book that defies understanding, serving as a metaphor for the limits of human knowledge. One of the most compelling aspects of the Codex is its elaborate script. Serafini created a flowing, looping text that looks like a language but isn't recognizable to any known linguistic system. Over the years, many have tried to decode it, analyzing letter frequencies and structures, but no one has succeeded in translating a single word. The text appears to be consistent, as if governed by grammatical rules, and this has led some to believe it could indeed be a language, or perhaps a pseudo-language, meant to mirror the way we interpret symbols. Some have suggested that the Codex's language serves as a mirror of our own experience with communication. Imagine, for example, an alien stumbling upon an English dictionary for the first time. They might recognize patterns and letters, but be completely unable to understand the meanings. The Codex's language could be a reminder of how foreign, even cryptic communication can be, particularly in cultures we don't fully understand. It taps into our experience of outsiderness, of being presented with symbols we can't decipher, yet sense are significant. The illustrations in the Codex seem designed to provoke thought rather than to inform. Unlike most encyclopedias, which offer straightforward information, the Codex presents images that are surreal, whimsical, and at times unsettling. Serafini's drawings blend elements from natural history, architecture, and the human body, turning them into dreamlike scenes that can be interpreted in countless ways. There are hints of familiarity. The pages might show plants, animals, or people, but they are never exactly what we expect. This artistic choice may be Serafini's way of demonstrating the flexibility and subjectivity of interpretation. Just as we can all look at the same piece of abstract art and walk away with different impressions, the Codex offers each reader a unique experience. One person may see a metaphor for human transformation. Another might see commentary on technology and nature. In this way, the Codex Seraphinianus almost invites readers to become creators themselves, constructing their own meanings and narratives as they navigate its pages. Another compelling theory is that the Codex is a critique of our obsession with categorization and order. Think of an encyclopedia. It's a reference book intended to provide clear, factual information, but the Codex takes this format and fills it with ambiguity and fantasy, as if to remind us of the limitations inherent in human knowledge. In creating a text that resists categorization, Serafini may be hinting that the world isn't always as understandable as we'd like it to be. Life, like the Codex, contains mysteries that can't always be decoded or reduced to neat definitions. This sense of ambiguity resonates with the philosophy of absurdism, where the search for meaning meets the inherent meaninglessness of the universe. Much like Albert Camus's asterisk myth of Sisyphus, in which Sisyphus endlessly pushes a boulder up a hill only for it to roll back down, readers of the Codex are engaged in a quest to understand something that defies understanding. It's a journey without a destination, an intellectual exercise that invites us to explore without expecting concrete answers. Ultimately, the Codex Seraphinianus isn't just a strange book. It's an experience that challenges us to think differently. In a world where we crave explanations and clarity, the Codex offers something rare, an invitation to embrace the unknown. It reminds us that not all mysteries are meant to be solved, and that sometimes the beauty of art and life lies in the unanswered questions. By letting go of our need to decipher its language and images, we can begin to appreciate the Codex as it is, a surreal, immersive art piece that mirrors the wonder and mystery of existence itself. Like a dream, it slips away when we try to grasp it, leaving us with only the feeling that we've glimpsed something beyond words.
The Beginning of Infinity. This book by David Deutsch is one of the rare, life-changing works that completely reshapes the way you see reality. Once you grasp its ideas, you may never think about knowledge, progress, or even the future in the same way again. At its core, the book argues that progress is limitless. Every major breakthrough in science, philosophy, and society stems from one simple fact. Problems are solvable. There is no fundamental barrier to knowledge, only unanswered questions waiting to be explored. Deutsch dismantles the idea that we will ever reach a point where everything is known, showing instead that the quest for knowledge is infinite. One of the book's most powerful ideas is that knowledge doesn't merely accumulate, it evolves. Weak explanations are replaced by stronger ones, and this ongoing process fuels scientific discovery, moral progress, and even political freedom. Deutsch emphasizes that this isn't automatic. Civilizations that embrace open-ended inquiry flourish, while those that resist change stagnate. This book forces you to rethink reality. It argues that we are not passive observers of the universe, but active participants shaping its future through our understanding. Whether in physics, democracy, or even art, progress is always possible, if we commit to rational thinking and the relentless pursuit of truth. The theory of everything. Some ideas are so powerful that once you understand them, they change the way you see everything. your past, your future, even your place in the universe. The Theory of Everything by Stephen Hawking is one such book. It doesn't just explain the cosmos, it reshapes your understanding of existence itself. Hawking takes us on an extraordinary quest to understand the forces that shape our reality. He unravels the evolution of the cosmos, from the explosive birth of the Big Bang to the formation of galaxies, stars, and planets. But this book isn't just about what happened, it's about why it happened, and what it means for the ultimate fate of the universe. At the heart of Hawking's work is a profound question. Can we find a single theory that explains everything? He explores the two pillars of modern physics, Einstein's theory of relativity, which governs the vast cosmic scale, and quantum mechanics, which rules the microscopic world. These two frameworks, though incredibly successful, seem to contradict each other. Bridging this gap is the holy grail of physics, the elusive theory of everything. Hawking breaks down complex ideas with astonishing clarity, making the vast mysteries of black holes, space-time, and quantum uncertainty feel within reach. He challenges us to rethink concepts like the nature of time, suggesting that it might not be as linear or absolute as we assume. He also explores the possibility of a multiverse, where infinite versions of reality could coexist beyond our perception. But what makes the Theory of Everything truly transformative is not just its scientific depth, it's the way it forces us to confront our place in the cosmos. Are we insignificant specks in an indifferent universe? Or do we have a role in uncovering its deepest truths? Hawking's work suggests that understanding reality is not just a pursuit for scientists, it's a pursuit for all of us. Because once you grasp the grand design of the universe, the way you see your own existence will never be the same again. The Selfish Gene, Richard Dawkins's. The Selfish Gene is a book that changes how you see life itself. It doesn't just explain evolution, it redefines it, shifting the focus from species and individuals to something far more fundamental, genes. Dawkins argues that genes, not organisms, are the true driving force of evolution. Life is not designed for the survival of the fittest individual, but for the replication of the most successful genes. Every trait, instinct, and behavior we see in nature exists because it has helped genes persist across generations. This idea transforms our understanding of why creatures behave the way they do, from altruism to aggression, cooperation to competition. Even selfless acts, Dawkins explains, often serve the hidden agenda of genetic survival. One of the book's most eye-opening concepts is that evolution is not guided by intention or purpose. Genes do not want to spread. They simply do, through an endless trial and error process where only the most effective replicators endure. This shift in perspective reveals the deep logic behind life's complexity, from the tiniest microbes to human societies. Yet, The Selfish Gene is not a cynical book. In fact, it shows that even in a world driven by genetic competition, cooperation and kindness can emerge as evolutionary strategies. It forces you to question long-held beliefs about identity, purpose, and even free will. Reading this book is like lifting a veil on the hidden mechanics of existence. It is a fundamental, mind-expanding work, one that leaves you seeing life and yourself in an entirely new way. Once you grasp its message, you may never think about nature, evolution, or human behavior the same way again. What It's Like to Be a Bat. This book by Thomas Nagel challenges everything we think we know about consciousness. We assume that science will eventually explain the mind, but Nagel argues that no amount of physical data, no brain scans, no chemical breakdowns, can ever truly capture what it feels like to be another conscious being. And to prove his point, he asks a simple but unsettling question. What is it like to be a bat? Bats navigate the world through echolocation, a form of perception so different from ours that we can only describe it in vague metaphors. No matter how much we study the bat's brain or its behavior, we can never experience the world as a bat does. This, Nagel argues, reveals the limits of a purely scientific, materialist view of consciousness. While we can break down the brain into neurons and signals, there remains an unbridgeable gap between objective facts and subjective experience, what philosophers call qualia. This is the essence of the mind-body problem. How can physical processes give rise to the richness of experience? Nagel's argument raises difficult questions about the nature of thought and perception. If consciousness is more than just computation and chemistry, can it ever be fully explained? Could a machine ever truly think and feel? Or will there always be something missing? And if every conscious being has an inner world that we can never access, what does that mean for how we understand and relate to others? What It's Like to Be a Bat doesn't give us easy answers. Instead, it forces us to confront the fact that consciousness is still one of the greatest unsolved mysteries of existence. Man's search for meaning. When everything is taken from you, your home, your freedom, even your name, what remains? In the depths of suffering, when survival seems impossible, does life still have meaning? Viktor Frankl's Man's Search for Meaning is not just a book, it is a testimony to the resilience of the human spirit. and a guide to finding purpose even in life's darkest moments. Frankl was not a detached observer of suffering. He was a prisoner in Auschwitz, subjected to unimaginable cruelty and loss. Yet, in the midst of it all, he made a remarkable discovery. Survival was not just about strength or luck. Those who endured longest were often the ones who held on to a sense of purpose, whether it was the memory of a loved one, the dream of unfinished work, or the belief that their suffering had meaning. They had something that kept them going. From this experience, Frankl developed logotherapy, a school of thought that argues meaning is the primary driving force of human life. Unlike Freud's focus on pleasure or Nietzsche's emphasis on power, Frankl's insight was different. If a person has a why to live, they can endure almost any how. Even in the most brutal conditions, we always have one freedom left, the freedom to choose our response to suffering. This book is not comforting. It is challenging. It does not offer simple answers, nor does it promise happiness. Instead, it presents a truth that can change your life. Suffering is unavoidable, but within it, we can still find purpose. The question it leaves you with is inescapable. What meaning have you given to your life? Once you confront that, you may never see the world or yourself the same way again. The myth of Sisyphus. Life offers no explanations, no grand design, no built-in purpose. So why do we keep going? The Myth of Sisyphus by Albert Camus is a fearless confrontation with this unsettling reality, forcing us to question whether existence itself is an act of defiance. Rather than offering comforting answers, Camus challenges us to stare into the void and decide for ourselves. Is life still worth living when stripped of illusions? At the heart of Camus's philosophy is the concept of the absurd, the fundamental contradiction between our relentless search for meaning and the universe's indifferent silence. Unlike other philosophers who attempt to resolve this tension through faith or reason, Camus insists that we must embrace it. To illustrate this, he turns to the Greek myth of Sisyphus, condemned to roll a boulder up a hill for eternity, only to watch it roll back down each time. His struggle is endless, devoid of victory or escape. But does that make his existence meaningless? Camus argues that Sisyphus is not a tragic figure, but a rebellious one. In accepting his fate without seeking false hope or resignation, he finds a strange form of liberation. He is fully aware of the absurdity of his condition, yet he chooses to persist. And in that persistence, he reclaims his freedom. One must imagine Sisyphus happy, Camus writes, not because his suffering is erased, but because he has embraced it without illusion. This philosophy extends beyond myth into our daily lives. We chase careers, relationships, ambitions, hoping they will provide lasting fulfillment. Yet time and again, we find ourselves in the same existential loop, pushing our own metaphorical boulders uphill. The absurd is not an abstract concept, it is the reality of being human. But instead of succumbing to despair, Camus challenges us to revolt, not through resignation or escape, but by living fully, without expecting the universe to justify itself. The Myth of Sisyphus is not a book of comfort. It is a book of defiance. It does not offer meaning, but demands that we create our own. In embracing the absurd, we reclaim our power. And in that moment of realization, existence is no longer a burden, it becomes a choice. Meditations, Marcus Aurelius. Meditations is not just a book, it is a rare and intimate look into the mind of a ruler grappling with the weight of the world. Written as personal reflections during his reign as Roman emperor, it was never meant for public reading, yet it has become one of the most powerful guides to inner strength, resilience, and self-mastery ever written. At its core, Meditations teaches a lesson that can reshape your life. You cannot control the world, only your response to it. Pain, misfortune, and injustice are inevitable, but how you react determines your character. Aurelius urges us to meet adversity with calm, to see obstacles not as misfortunes, but as opportunities for growth. A disciplined mind, he insists, is stronger than any hardship. This philosophy, rooted in Stoicism, teaches that suffering often comes not from events themselves, but from how we interpret them. By training the mind to see things as they are, without fear, anger, or self-pity, we gain control over ourselves. External chaos no longer dictates our inner peace. Meditations is not abstract theory. It is a practical manual for life. It reminds us that wealth, power, and recognition are fleeting, but virtue and wisdom endure. In a world driven by ego, distraction, and anxiety, Aurelius's words are a call to live with purpose, integrity, and clarity. The wisdom in these pages is not meant to be admired, it is meant to be applied. Those who embrace its lessons will find themselves steadier, less shaken by life's turbulence, and more at peace with whatever comes their way. The real question is, are you ready to master yourself? The Diary of a Young Girl, Anne Frank's. The Diary of a Young Girl is more than a historical document. It is a window into the soul of a teenager whose voice refuses to be silenced by time. Trapped in hiding during one of history's darkest moments, Anne transforms her fear and isolation into something extraordinary, a deeply personal, honest, and heartbreaking account of hope in the face of despair. Through her diary, we witness not just the horrors of war, but the inner world of a young girl searching for meaning, love, and identity. She writes with stunning clarity about human nature, injustice, and the resilience of the human spirit. Even as she endures unimaginable fear, she refuses to let hatred consume her. Instead, she believes in the goodness of people, even when the world around her suggests otherwise. What makes this book life-changing is its raw intimacy. Anne is not just a historical figure, she is a voice that feels strikingly familiar. A reminder of lost innocence, unfulfilled dreams, and the fragility of life. Her words challenge us to reflect on our own existence. How do we respond to adversity? What do we take for granted? And what kind of world do we leave behind? But perhaps the most haunting aspect of Anne's diary is what it leaves unsaid. The dreams that will never be realized, the life that was unjustly cut short. Her words end, but history continues. It is a stark reminder of what was lost, but also of the responsibility we carry to create a world where such tragedies never happen again. This is not just the story of one girl. It is a testament to the power of words, the endurance of hope, and the cost of hatred. Long after you turn the final page, Anne's voice lingers, a whisper from history, asking you to remember, to feel, and most of all, to never let such darkness return. The untethered soul. Most people go through life without ever questioning the voice in their head, the endless stream of thoughts, doubts, and fears that dictate their every move. But what if you could step outside of that mental noise and experience a completely different way of being? In The Untethered Soul, Michael Singer offers a path to breaking free from the invisible chains of your own mind, revealing how true peace comes not from controlling life, but from surrendering to it. At its core, this book reveals a profound truth. You are not your thoughts, not your worries, not even your pain. You are the one who watches it all unfold. But most people never realize this because they are trapped in an endless cycle of inner chatter, reacting to every fleeting emotion as if it defines them. Singer shows how this mental noise is the root of suffering, and how learning to detach from it can lead to a life of true peace. The key to freedom, he explains, is surrender. By letting go of the constant need to control everything, you open yourself to a higher state of being, one where fear no longer dictates your choices, where inner turmoil gives way to boundless joy. It's not about denying emotions, but about allowing them to pass through without clinging to them. Singer takes you beyond conventional self-help advice. He doesn't promise quick fixes or temporary relief. Instead, he reveals a path to a radically different way of living, one where you are no longer at war with your own mind. He invites you to step outside your mental prison and experience life as it truly is, vast, limitless, and free. Most people will continue to live inside their own self-imposed limitations, believing they are the voice in their head. But for those who truly listen to the message of the untethered soul, a different reality becomes possible. One where you are no longer trapped in the storm of your thoughts, but watching it from a place of complete stillness. The question is, are you ready to let go? The Critique of Pure Reason, Immanuel Kant's. The Critique of Pure Reason is one of the most profound and challenging works in philosophy, one that reshapes how we understand knowledge, reality, and the limits of human thought. It is a book that does not merely provide answers, but forces you to question the very foundation of what you believe to be true. At its core, Kant challenges the assumption that human reason can grasp reality as it truly is. He argues that our minds do not passively receive information from the world, but actively shape it. Space, time, and causality, concepts we take for granted, are not inherent features of the universe but structures imposed by our own perception. We do not see things as they are. We see them as our minds allow us to perceive them. This realization has staggering implications. If our understanding of the world is always filtered through these mental structures, then there are limits to what we can ever truly know. Kant draws a bold line between what can be understood through experience and what lies forever beyond our grasp, the realm of pure reason. Metaphysical debates about the existence of God, free will, and the nature of the soul, he argues, are attempts to reach beyond what human cognition is capable of comprehending. But this is not a message of despair. It is one of clarity. By recognizing the boundaries of knowledge, we gain a deeper appreciation for what we can truly understand. Kant's work frees us from intellectual illusions and forces us to confront the true scope of human thought. It is a book that forever changes the way you think, replacing naive certainty with a rigorous and humbling awareness of reality itself. Once you engage with Kant's ideas, the world will never seem as simple again. The mind is not just a tool for discovering truth. It is the lens that defines what truth even means. Sapiens, humans rule the world, But not because we are the strongest or the fastest. What truly sets us apart is our ability to create and believe in shared stories, fictions that shape our societies, drive our progress, and define our reality. In Sapiens, Yuval Noah Harari uncovers the hidden forces behind human history, revealing how myths of money, religion, and nations turned a once ordinary species into the most powerful force on Earth. Harari reveals that our success is not due to raw intelligence or physical strength, but to our unique ability to create and believe in shared myths. Money, religion, nations, human rights, none of these exist in nature, yet they shape our world more than anything tangible. This ability to cooperate on a massive scale has allowed Homo sapiens to build civilizations, wage wars, and reshape the planet itself. But our progress has come at a cost. The agricultural revolution may have allowed larger populations to thrive, but it also locked humans into grueling labor and rigid social hierarchies. Industrialization brought convenience, but also alienation. Each leap forward has raised new questions. Have we really gained freedom, or have we only traded old chains for new ones? Harari doesn't just recount history, he dismantles our assumptions. He forces us to see our world as it truly is, built on fragile agreements shaped by forces we rarely question. And as artificial intelligence, biotechnology, and automation advance, we must ask, are we still in control of our destiny, or are we on the verge of becoming obsolete? Understanding the past is not just about history, it is about clarity. Sapiens forces us to see the invisible structures guiding our lives, the illusions we take for reality, and the patterns that repeat over centuries. In doing so, it leaves us with an unsettling yet liberating realization. The way the world works is not inevitable, and if we created it, we can change it. Cosmos. There was a time when humanity looked up at the night sky and saw only mystery. Today, we understand more than ever about the vastness of the cosmos, yet the questions remain just as profound. How did we get here? What forces shaped the universe? And what does it all mean for us? Carl Sagan's Cosmos is not just a book about space. It's an exploration of our place in the grandest story ever told. At its heart, Cosmos is about perspective. Sagan traces the origins of the universe, the formation of galaxies, the birth of our planet, and the emergence of life. But beyond the science, he asks deeper questions. What does it mean to exist in such a vast and ancient cosmos? How did human civilization arise from the dust of dead stars? And what will become of us as we reach toward the future? Sagan's vision is both breathtaking and unsettling. He reveals how small and insignificant we are in the grand scale of the universe, yet he also shows that our ability to understand it is nothing short of miraculous. He warns against ignorance, superstition, and the dangers of self-destruction, urging us to embrace reason, curiosity, and a shared responsibility for our fragile planet. But perhaps the most powerful message of Cosmos is its reminder that science is not just a collection of facts. It is a way of thinking, a candle in the dark against the vast unknown. It challenges us to see knowledge as an ongoing journey, not a destination. This book leaves you with more than just information. It gives you a new way of seeing reality. It reminds us that while we are small, we are also capable of great understanding. And in that understanding, we may just find our greatest purpose. The Republic, Plato's. The Republic is not just a book about politics. It is a deep and relentless exploration of justice, power, and the very nature of reality. It is a work that forces you to confront fundamental questions about society and the human condition, challenging everything you assume about morality, leadership, and knowledge. At its core, the Republic examines what it means to build a just society. Through Socrates' dialogues, Plato dismantles flawed ideas of justice and argues that true justice is not about power or personal gain, but about the harmony of individuals fulfilling their rightful roles. He introduces the concept of the philosopher king, an enlightened ruler guided by wisdom rather than ambition, questioning whether democracy, with its susceptibility to ignorance and manipulation, can ever lead to true justice. But the Republic goes far beyond politics. In the famous allegory of the cave, Plato suggests that most people live in ignorance, mistaking shadows for reality. True knowledge, he argues, requires breaking free from illusion and seeking a deeper understanding of the world. This idea has shaped philosophy for centuries, influencing everything from existential thought to modern psychology. The book also explores the nature of the soul, arguing that just as a well-ordered society requires harmony, so too does the human mind. He divides the soul into three parts: reason, spirit, and desire, emphasizing the importance of self-mastery. Without reason guiding the soul, both individuals and societies fall into chaos. To read The Republic is to question the very structure of the world you live in. It forces you to ask whether your beliefs are truly your own, or mere reflections of society's influence. It is not just a book, it is an intellectual awakening, one that compels you to seek truth, justice, and wisdom beyond the illusions of everyday life. Once its ideas take hold, you may never see the world the same way again. Gödel, Escher, Bach. Douglas Hofstadter's Gödel, Escher, Bach is a masterpiece that defies traditional categories. It is a journey through mathematics, art, and music. Yet at its core, it is a profound meditation on the nature of consciousness, self-reference, and meaning itself. This book does not just teach, it transforms the way you think. At its heart lies the concept of strange loops, self-referential systems that arise in everything from mathematical logic to human thought. Hofstadter explores how Kurt Gödel's incompleteness theorems shattered the foundations of mathematics, proving that no formal system can ever be complete. He connects this to the paradoxical art of M.C. Escher, whose drawings depict impossible realities, and the music of Johann Sebastian Bach, whose compositions contain intricate self-referential structures. But the true brilliance of Gödel, Escher, Bach is how it links these ideas to the very essence of human consciousness. Hofstadter suggests that our sense of self, our I, is not a fixed entity, but an emergent phenomenon arising from layers of self-reference in the brain. He draws parallels between machine intelligence, neural networks, and the recursive patterns of thought, raising profound questions about whether artificial intelligence could ever develop true self-awareness. The book does not offer simple answers. Instead, it challenges you to think in entirely new ways. It blends logic with creativity, playfulness with rigor, and philosophy with science. The journey through its pages is both exhilarating and humbling, revealing hidden connections between disciplines that seem worlds apart. Gödel, Escher, Bach is not just a book you read. It is a book that reads you, reshaping your perception of thought, creativity, and what it truly means to be alive. Once you grasp its ideas, your understanding of the mind, mathematics, and the fabric of reality itself may never be the same again. The World as Will and Representation. Arthur Schopenhauer's The World as Will and Representation is a staggering exploration of existence, perception, and suffering. It is a book that forces you to confront the unsettling truth about reality. Beneath the world of appearances lies an unstoppable, blind force, the will. This primal drive, according to Schopenhauer, is the essence of all life, compelling us to chase desires that can never truly be satisfied. Every action, every ambition, every craving is merely an expression of this ceaseless force, ensuring that contentment remains forever out of reach. At the heart of this work is the idea that reality is not an objective structure, but a projection shaped by our minds. The world we see is merely a representation, a filtered version of something deeper and far more irrational. Schopenhauer argues that human existence is defined by an endless cycle of striving, where the fulfillment of one desire only gives birth to another, trapping us in perpetual suffering. Yet, Schopenhauer does not leave us without escape. He suggests that through art, aesthetic contemplation, and the suppression of desire, we can transcend the will's control and achieve a form of inner peace. Music, in particular, he claims, provides a direct glimpse into the essence of existence, offering a temporary reprieve from the struggles of life. He also explores themes of compassion and asceticism as paths to liberation, foreshadowing ideas found in Eastern philosophies like Buddhism. This is not a book that offers comforting illusions. It is a book that forces you to see the world for what it truly is. Schopenhauer's vision is haunting, yet strangely illuminating. To read The World as Will and Representation is to step beyond ordinary perception and into a radical, unsettling truth. Few books will challenge your understanding of life as profoundly as this one. The Doors of Perception. We think we see the world as it truly is. But what if our perception is nothing more than a dim, restricted version of reality? In The Doors of Perception, Aldous Huxley embarks on a radical exploration of human consciousness, documenting his experience with mescaline and the mind-altering revelations that followed. What he discovers is both astonishing and unsettling. Our everyday awareness is not the full picture, but a narrow sliver of something far more expansive. Huxley argues that the brain functions as a filtering system, stripping away the overwhelming depth of reality so that we can focus on survival. Psychedelics, he suggests, temporarily disrupt this filter, allowing us to perceive the world in its raw, unmediated brilliance. Ordinary objects become luminous and deeply significant. The distinction between self and surroundings begins to blur. Colours, textures, and sounds take on an almost divine intensity. For Huxley, these altered states are not hallucinations, but glimpses into a greater truth, one that art, religion, and mysticism have long sought to capture. But this book is not just about psychedelics, it is about the nature of perception itself. Huxley challenges us to reconsider the way we interpret reality, suggesting that our normal consciousness is shaped by language, habit, and cultural conditioning. If our minds operate with blinders on, what else might we be missing? The Doors of Perception is not just a memoir, it is an invitation to question the limits of the human mind. Huxley's insights are as provocative as they are transformative, urging us to see beyond the ordinary and embrace the possibility that reality is far more mysterious than we ever imagined. Once you begin to see through these doors, there is no turning back. The big picture. What if everything, your thoughts, emotions, and sense of self, is nothing more than the intricate dance of particles obeying physical laws? In the big picture, Sean Carroll takes us on a profound journey through science and philosophy, challenging us to rethink existence itself. This is not just a book about physics. It is an exploration of meaning, consciousness, and the very nature of reality. Carroll introduces a framework he calls poetic naturalism, the idea that while the universe is governed by strict physical laws, our experiences, values, and sense of purpose emerge naturally from its complexity. He tackles some of the deepest questions we can ask. What is reality made of? How did life arise from lifeless matter? Is consciousness merely an illusion? Through clear and compelling storytelling, Carroll weaves together quantum mechanics, thermodynamics, and evolutionary biology to show how everything we know fits into the grand structure of the cosmos. One of the book's most striking arguments is its rejection of dualism, the belief that the mind or soul exists separately from the physical world. Instead, Carroll argues that consciousness is a product of intricate material processes, making supernatural explanations unnecessary. He also explores free will, morality, and the search for meaning, showing that while the universe does not dictate purpose, we have the power to create it ourselves. Ultimately, the big picture is about more than just understanding the laws of nature. It is about what it means to be human. Carroll replaces comforting illusions with awe-inspiring truths, offering a perspective that is both humbling and empowering. For those ready to challenge their assumptions, this book will change not only how they see the universe, but how they live within it. Fooled by Randomness. Nassim Nicholas. Taleb's Fooled by Randomness is a wake-up call to anyone who believes success is solely the result of skill, intelligence, or hard work. This book dismantles our illusions of control, revealing how chance, luck, and randomness shape our lives far more than we like to admit. Taleb explores the hidden role of probability in everything, from financial markets to personal achievements. He shows how we fall for survivorship bias, mistakenly attributing success to talent while ignoring the countless others who failed under the same conditions. The world, he argues, is not as predictable as we think, and our minds are wired to see patterns where none exist. We crave explanations, weaving stories of cause and effect, even when outcomes are largely determined by randomness. This book also forces us to question the way we make decisions. Are we truly in control, or are we just reacting to randomness disguised as certainty? Taleb warns against overconfidence, reminding us that even the most sophisticated models can crumble under the weight of the unknown. He critiques the financial world's illusion of predictability, where traders and investors often mistake lucky streaks for skill, until an unforeseen event wipes them out. But Fooled by Randomness is not a pessimistic book. It's an empowering one. Once we recognize the role of chance, we can make better decisions, become more skeptical of empty predictions, and develop a mindset that thrives in uncertainty. Instead of chasing illusions of certainty, we learn to embrace probabilities, understanding that resilience and adaptability matter more than false confidence. This book is not just about probability. It's about seeing reality as it truly is. It shifts your perception of success, failure, and decision-making in ways that will permanently alter how you view the world. Behave. This book by Robert Sapolsky is an extraordinary deep dive into the science of human behavior, tackling one of the most complex questions of all. Why do we do what we do? This book unravels the intricate web of biology, psychology, and culture that shapes every decision we make, from moments of kindness to acts of violence. It dismantles the illusion that we act in isolation, showing instead that every choice we make is the culmination of influences stretching back seconds, years, and even millennia. Sapolsky takes us on a journey through time, starting with the milliseconds before an action occurs, how neurons fire, how hormones surge, before stepping back to explore the deeper roots of behavior. What happened in the preceding hours to shape our emotions? How did childhood experiences wire our responses? And how did evolutionary pressures millions of years ago craft the instincts we take for granted? He reveals how genetics and environment intertwine, breaking down the simplistic debate of nature versus nurture. Instead, he paints a picture of human nature that is complex, unpredictable, and deeply interconnected. But Behave isn't just about science, it's about understanding ourselves on a deeper level. By exploring the hidden forces behind morality, prejudice, and aggression, Sapolsky forces us to reconsider concepts like blame and free will. Are we truly in control, or are we just the sum of countless biological and environmental influences? And if so, what does that mean for ethics, justice, and how we treat one another? This book doesn't just explain human nature, it challenges you to rethink it. By the time you finish, you won't see yourself, or others, the same way again. Behave doesn't just inform, it transforms the way you perceive human actions, leaving you with a newfound awareness of the invisible forces shaping every aspect of life. How to create a mind. Intelligence is humanity's defining trait, yet we barely understand how it works. What if we could not only unravel its mysteries but also replicate it? In How to Create a Mind, Ray Kurzweil takes on this challenge, arguing that the future of artificial intelligence depends on unlocking the secrets of our own brains. His vision is audacious. If we can reverse engineer human cognition, we are on the verge of building machines that can think, learn, and perhaps even become conscious. Kurzweil presents a compelling theory. The brain operates as a hierarchical pattern recognition system, constantly predicting, analyzing, and refining information. This mechanism is what allows us to learn, adapt, and create, and it's precisely this structure that he believes can be replicated in artificial intelligence. If we can reverse engineer the brain, he suggests, we are on the verge of creating machines that not only think but learn, innovate, and perhaps even develop consciousness. But this book isn't just about AI, it's about what it means to be human. What is self-awareness? Can machines truly experience emotions, or is intelligence just an advanced form of pattern processing? If artificial minds surpass human intelligence, will they enhance our abilities or render us obsolete? Kurzweil argues that the line between biology and technology is blurring, and soon we may not just create AI, we may merge with it, redefining intelligence itself. Rather than fearing this future, Kurzweil invites us to embrace it. Intelligence is not a fixed trait, it evolves, and whether through biology or silicon, the pursuit of knowledge and creativity will continue. If he's right, the age of artificial minds is not just approaching, it's inevitable. And when it arrives, we may have to redefine what it means to be alive. The Rational Optimist. Doomsayers have been predicting the downfall of civilization for centuries, yet history tells a different story, one of progress, innovation, and rising prosperity. In The Rational Optimist, Matt Ridley argues that despite today's widespread pessimism, humanity is not on the brink of collapse, but on an extraordinary upward trajectory. The secret to this relentless progress? Our unique ability to exchange ideas, goods, and knowledge, driving innovation and lifting societies to new heights. Ridley traces the evolution of human prosperity, dismantling the idea that scarcity and disaster are inevitable. He shows how trade, open markets, and free societies have historically fostered creativity and problem-solving, enabling civilizations to overcome everything from food shortages to environmental crises. Rather than being a species doomed by its own success, humanity thrives by adapting, cooperating, and sharing solutions across generations. Critics claim modern civilization is in decline, pointing to wars, economic instability, and climate change. But Ridley counters that these challenges, like those before them, are surmountable. From advances in medicine to improvements in global living standards, the evidence suggests that human well-being is at an all-time high. The world is far from perfect, but data, not fear, reveals a clear trend of progress. More than just a defense of optimism, The Rational Optimist is a call to rethink how we view the future. Are we trapped in a cycle of negativity, blind to the steady march of progress? By questioning the apocalyptic narratives that dominate headlines, Ridley challenges us to see the world not as it is feared to be, but as it truly is, a place of extraordinary potential and continuous growth. The Fabric of Reality. Reality is not what it seems. In The Fabric of Reality, David Deutsch offers a bold new way of understanding the universe, one that fuses quantum physics, evolution, computation, and epistemology into a single, unified framework. He argues that these disciplines are not isolated but are deeply interconnected, forming the foundation of everything we know and everything we have yet to discover. At the core of the book is a revolutionary idea: knowledge creation is the driving force of progress. Deutsch contends that human advancement isn't random, it is the result of our ability to generate better explanations, refine them, and expand our understanding. This principle doesn't just apply to science. It underpins technology, civilization, and even the survival of our species. Perhaps the most mind-bending concept Deutsch defends is the many worlds interpretation of quantum mechanics. He argues that parallel universes are not just theoretical speculation, but an inevitable consequence of quantum theory. Every decision, every event, and every possibility unfolds across an infinite number of realities. This challenges everything we think we know about existence, consciousness, and the very nature of choice. But The Fabric of Reality isn't just a book about physics, it's an intellectual upheaval. It forces us to rethink what it means to understand anything at all. Deutsch doesn't just describe the universe, he invites us to participate in the ongoing quest to explain it. By the time you finish, you may no longer see knowledge as a mere tool, but as the fundamental force shaping reality itself. Thus Spoke Zarathustra. Friedrich Nietzsche's Thus Spoke Zarathustra is not just a book. It is a challenge, a confrontation with everything you believe about morality, purpose, and the future of humanity. Written in a poetic and prophetic style, it delivers Nietzsche's most powerful ideas, forcing the reader to wrestle with uncomfortable truths and profound possibilities. The book follows Zarathustra, a solitary thinker who returns from the mountains to share a radical message with mankind. He declares that God is dead, not as a rejection of spirituality, but as an urgent wake-up call. The old foundations of morality and meaning have crumbled, and humanity must now forge its own path. If we are to move forward, we must break free from inherited beliefs and take responsibility for shaping our own destiny. At the heart of Zarathustra's teachings is the concept of the Übermensch, the higher being who rises above fear, conformity, and mediocrity. The Übermensch does not seek external validation, but creates meaning from within, embracing struggle and transformation as necessary for true greatness. This figure is not born, but forged through resilience, self-overcoming, and a radical affirmation of life. Nietzsche also presents the haunting idea of eternal recurrence, a thought experiment that forces you to consider whether you are living a life worth repeating endlessly. If every moment, every choice, had to be relived forever, would you welcome that fate or be horrified by it? This question is not meant to paralyze, but to inspire, to push you toward a life so fulfilling that you would choose it again and again. This is not a book that leaves you unchanged. It is a challenge to rise above complacency, to create meaning in a world without guarantees, and to step boldly into the role of architect of your own existence. The problems of philosophy. How do we know anything at all? Can we trust our senses? Or is reality something far different from what it appears to be? In The Problems of Philosophy, Bertrand Russell dissects these fundamental questions, guiding us through the uncertainties that underpin human knowledge. This is not just a book about philosophy. It's an invitation to rethink the very nature of truth, perception, and understanding. Russell begins with skepticism, asking whether we can ever be certain of anything. Our senses tell us that a table is solid, but physics reveals it is mostly empty space. A stick in water appears bent, yet we know it remains straight. If our perceptions can mislead us so easily, how can we be sure of anything? Through clear and engaging reasoning, Russell explores the distinction between appearance and reality, the nature of matter, and the limits of empirical knowledge. He then turns to logic and abstract thought, showing how philosophy helps us move beyond sensory experience to grasp deeper truths. Drawing from great thinkers like Descartes, Hume, and Kant, he unpacks the nature of belief, the foundations of reasoning, and the ways we construct knowledge itself. Yet The Problems of Philosophy is not an argument for despair. It is a defense of intellectual curiosity. Russell shows that while absolute certainty may be unattainable, the search for truth is what drives human progress. Philosophy, he argues, does not give us final answers, but teaches us how to think critically, embrace uncertainty, and appreciate the beauty of unanswered questions. This book is an essential guide for anyone seeking to sharpen their mind and challenge their assumptions about reality. The Conspiracy Against the Human Race. Most books try to comfort you, to assure you that life has meaning. Thomas Ligotti's The Conspiracy Against the Human Race does the opposite. It stares directly into the void and dares you to do the same. This is not just a book. It is a bleak but unflinching meditation on the horror of consciousness itself. Ligotti argues that self-awareness is not a gift, but a cruel mistake of evolution. Unlike other creatures that live without questioning their existence, humans are burdened with the knowledge of their own mortality, the futility of their struggles, and the inescapable nature of suffering. We are, in his view, puppets who have become aware of our own strings, trapped in a reality that offers no inherent purpose, only the illusion of meaning to keep us going. Drawing from the philosophy of Arthur Schopenhauer, the cosmic horror of H.P. Lovecraft, and the darkest corners of literature, Ligotti dismantles the comforting narratives that shield us from despair. He suggests that optimism is not wisdom but a biological trick, a delusion that keeps us from seeing the world for what it truly is, indifferent, empty, and grotesquely absurd. But this book is not about nihilism for its own sake. It is a challenge, an invitation to strip away illusions and confront reality as it is. Whether you reject Ligotti's conclusions or find them disturbingly resonant, one thing is certain. Once you have read The Conspiracy Against the Human Race, you cannot unread it. When breath becomes air. At what point does a life stop being about the future and start being about the present? When Breath Becomes Air is the devastating yet profoundly illuminating memoir of Paul Kalanithi, a neurosurgeon whose promising career is abruptly cut short by terminal lung cancer. One day, he is the doctor saving lives. The next, he is the patient fighting to hold on to his own. Faced with the knowledge that his time is running out, Kalanithi embarks on a journey not just to understand death, but to redefine what it means to truly live. With a sharp, philosophical mind and the heart of a poet, Kalanithi reflects on the nature of mortality, the pursuit of meaning, and the intersection of science and the human spirit. As he transitions from healer to patient, he grapples with impossible questions. If life is short, what makes it worth living? How do we measure a meaningful existence? These reflections, drawn from his experiences in medicine, literature, and his own suffering, create a deeply personal, yet universally resonant meditation on life's fragility. But this book is not just about dying, it's about embracing the time we have. Even as his body fails him, Kalanithi chooses to keep moving forward, returning to work, writing, becoming a father. His words remind us that meaning is not found in how long we live, but in how deeply we engage with life. When Breath Becomes Air is not simply a memoir, it is a wake-up call to appreciate every moment. It leaves readers with a haunting yet beautiful truth. In the face of death, we can either surrender or choose to live with purpose until our final breath. The elegant universe. Reality is not what it seems. Beneath the familiar world of stars, atoms, and forces lies a hidden framework so bizarre it defies common sense. In the elegant universe, physicist Brian Greene takes us on a mind-expanding journey through space, time, and the deepest structures of reality. If you've ever questioned what the universe is truly made of, this book will shatter your expectations and leave you awestruck by the sheer complexity of existence. At the heart of Greene's exploration is string theory, a revolutionary idea that suggests the universe's fundamental building blocks are not particles, but minuscule vibrating strings. These strings, oscillating in dimensions beyond human perception, may hold the key to uniting the two great pillars of modern physics: Einstein's theory of relativity, which explains the grand structure of the cosmos, and quantum mechanics, which governs the chaotic world of the subatomic. For decades, these theories have stood in contradiction, but string theory offers a potential bridge, a single framework that could explain everything. But the elegant universe isn't just about equations. It challenges our understanding of reality itself. Space and time may not be fundamental, but emergent properties of a deeper, hidden order. The universe may contain extra dimensions curled up beyond our perception, or even parallel worlds governed by unseen forces. Greene's lucid explanations transform these mind-bending concepts from abstract mathematics into tangible ideas, making them feel just within reach. This book is more than a lesson in physics. It's an invitation to see the universe through new eyes. Once you glimpse the elegant structure beneath existence, your sense of reality will never be the same again. The first 3 minutes. Before there were galaxies, before there were stars, before there was even light, the universe was a dense, seething cauldron of energy. In the first 3 minutes, physicist Steven Weinberg takes us back to this unimaginable moment, unraveling the story of how everything we see today emerged from the chaotic aftermath of the Big Bang. If you have ever wondered how something arose from nothing, or why the cosmos exists in its present form, this book offers answers that will forever change your perspective on reality. Weinberg masterfully guides us through the staggering events that unfolded in the universe's infancy, where temperatures soared to incomprehensible levels, particles formed and annihilated in an instant, and the fundamental forces of nature began their intricate dance. Within a fraction of a second, the groundwork for galaxies, stars, and life itself was laid. By reconstructing these fleeting moments, he reveals the precise and delicate physics that made our existence possible. But this book is more than a scientific account. It is a reminder of how fragile and extraordinary reality truly is. Weinberg connects the latest discoveries in cosmology with profound philosophical questions, showing how the universe's earliest moments hold clues not only to our origins, but also to its ultimate fate. His writing does more than educate. It inspires awe, forcing us to confront the sheer vastness of the forces that shaped us. In the end, the first 3 minutes is not just about the beginning of time. It is an invitation to see the universe through new eyes. Once you grasp the cosmic forces that brought everything into being, you may never look at the night sky the same way again. The Origin of Species. Few books have reshaped our understanding of life as profoundly as The Origin of Species by Charles Darwin. It is not just a scientific work, it is a revelation, a fundamental shift in how we perceive nature, ourselves, and the forces that shape all living things. Darwin unveils a simple yet astonishing truth. Life is not static, nor was it designed in its present form. Instead, species evolve through a slow and relentless process, natural selection. In every generation, small variations arise. Some of these traits offer an advantage, helping organisms survive and reproduce. Over immense spans of time, these tiny changes accumulate, giving rise to new species, while others fade into extinction. This idea shattered centuries of belief in fixed, unchanging life forms. It revealed a world driven not by chance or divine intervention, but by an elegant, natural process, one that explains the astonishing diversity of life. Everything, from the tiniest bacteria to towering trees and intelligent beings, is connected through this endless cycle of adaptation and change. Darwin did not just propose a theory. He provided overwhelming evidence, gathered through years of observation and research. Fossils, geographical distribution, embryology, all pointed to the same conclusion. Life is a constant work in progress. Reading. The Origin of Species is like opening your eyes to the hidden forces shaping the natural world. It challenges you to see life differently, not as a fixed design, but as a masterpiece of gradual transformation. This book is more than history. It is the foundation of modern biology, and a reminder that change is not only possible, but inevitable. Understanding its message alters the way you see nature, humanity, and your own place in this ever-evolving world. The Inflationary Universe. This book by Alan Guth is a radical rethinking of the origins of everything. It takes one of the deepest mysteries in cosmology, the birth of the universe, and transforms it with a groundbreaking theory that reshapes our understanding of time, space, and existence itself. If you've ever questioned what came before the Big Bang, or how the universe expanded into the vast cosmic web we see today, this book will make you rethink reality from the ground up. At its core, Guth's inflation theory solves problems that baffled scientists for decades. How did the universe grow so uniformly, despite the randomness of quantum mechanics? Why does space appear so flat when gravity should have curved it long ago? The answer lies in an almost inconceivably rapid expansion, an instant of exponential inflation, stretching the universe from subatomic scales to cosmic proportions in a fraction of a second. But the implications go far beyond the Big Bang. Inflation suggests that our universe may be just one of many, part of an endless multiverse, where new universes are constantly bubbling into existence. This idea challenges everything we think we know about reality, hinting that what we see is only a tiny fragment of an unimaginably vast cosmic landscape. More than a scientific theory, the inflationary universe is a testament to human ingenuity, the ability to peer into the deep past and decode the mechanisms that gave rise to everything. It is a book that forces you to question your assumptions about time, space, and the fundamental nature of reality itself. And once you grasp its ideas, you may never think of the universe the same way again. A Universe from Nothing. Lawrence Krauss's book, A Universe from Nothing, is a daring exploration of one of the most fundamental questions in existence. Why is there something rather than nothing? If you've ever struggled with the idea of how the universe could arise without a creator, this book delivers an answer rooted in the laws of physics, one that is as unsettling as it is awe-inspiring. Krauss dismantles the assumption that nothing is truly empty. In the quantum world, empty space is never truly void. It seethes with energy, constantly producing and annihilating particles. The universe itself, he argues, could have emerged from this quantum nothingness, driven by the forces of physics alone. In this view, the cosmos is not the product of divine intervention, but a natural consequence of how reality operates at its most fundamental level. But this book goes far beyond just explaining origins. Krauss takes us through the stunning discoveries of modern cosmology, the accelerating expansion of the universe, the nature of dark energy, and the ultimate fate of everything. He paints a picture of a cosmos that is not only stranger than we imagine, but stranger than we can imagine. This is not just a book about science, it is a book about shifting perspectives. It challenges our deepest assumptions about existence and forces us to confront a reality where the universe requires no external cause, where something can and does emerge from nothing. And once you absorb these ideas, the very concept of existence will never feel the same again. What is life? Erwin Schrödinger's What is Life? Is a daring attempt to bridge physics and biology, seeking to answer one of the most profound questions of existence. What makes life different from inanimate matter? In this small yet monumental work, Schrödinger lays the groundwork for modern molecular biology, forever changing our understanding of life itself. At the heart of the book is the idea that life operates within the laws of physics, yet defies the chaotic tendencies of the universe. Schrödinger introduces the concept of negative entropy, explaining how living organisms maintain order by extracting energy from their surroundings. This insight would later influence the discovery of DNA's structure, providing a theoretical foundation for the genetic code. But what is life? Goes beyond biology. Schrödinger questions whether life's essence can be reduced to mere physical and chemical interactions, or if something deeper is at play. He explores the implications of quantum mechanics in biological processes, an idea that remains controversial, yet continues to inspire research in fields like quantum biology, artificial intelligence, and consciousness studies. The book also challenges our understanding of free will and determinism. If the molecules within us obey strict physical laws, where does human agency fit in? Is life simply an inevitable outcome of physics, or is there something irreducible about living systems? Schrödinger's ideas push the boundaries of what we consider possible, daring us to look at life from an entirely new perspective. This is not just a book about science, it is a philosophical challenge. It forces you to confront the very nature of existence and question whether life is simply a complex arrangement of molecules or something more profound. What is life? Does not hand you answers. It dares you to think beyond the boundaries of conventional wisdom. Once its ideas take hold, they linger, reshaping the way you perceive not only biology, but the very fabric of reality. Being in time. Most people move through life without ever truly questioning what it means to exist. But what if everything you take for granted, your sense of self, your understanding of time, your relationship with the world, was built on assumptions you've never examined? In Being in Time, Martin Heidegger dismantles our everyday understanding of existence. forcing us to confront the deepest and most unsettling question of all. What does it mean to be? This book is not just philosophy. It's an intellectual earthquake, shaking the very foundations of how we understand reality and ourselves. Heidegger introduces the concept of Dasein, the unique mode of being that defines human existence. Unlike objects that simply exist, humans are aware of their existence, constantly interpreting their place in the world. He argues that we are not isolated minds observing reality from a distance, but beings fundamentally shaped by our experiences, culture, and relationships. At the heart of his analysis is time. Our past shapes our present, and our awareness of death casts a shadow over everything we do. Heidegger challenges us to stop living inauthentically, conforming to societal expectations, and instead embrace the finite nature of life with full awareness. This book is dense, complex, and often frustrating, but its impact is undeniable. Heidegger's insights have influenced existentialism, psychology, literature, and even artificial intelligence. He forces us to ask, are we truly living, or just passing time? Being and time does not offer easy answers, but it will leave you with a deeper, more profound awareness of your own existence. After reading it, even the simplest moments, walking through a city, watching the sunset, take on a new, almost sacred significance. Life is fleeting, and Heidegger urges you to wake up before it's too late. The pleasure of finding things out. The greatest joy in life might not be in knowing, but in discovering. The Pleasure of Finding Things Out is a brilliant collection of reflections by Richard Feynman, a physicist whose boundless curiosity and deep love for learning made him one of the most extraordinary thinkers of the 20th century. More than just a book on science, this work is a passionate defense of intellectual honesty, critical thinking, and the relentless pursuit of truth. It is an invitation to see the world through the eyes of a man who never stopped questioning, never stopped wondering, and never stopped delighting in the mysteries of the universe. Feynman's essays and interviews span a wide range of topics: science, education, philosophy, and even the art of problem solving. He reveals how true scientific thinking is not about memorizing facts, but about learning how to ask the right questions. With characteristic wit and clarity, he dismantles common misconceptions, explains the beauty of scientific inquiry, and highlights the dangers of dogma and blind faith. His insights extend beyond physics, touching on the importance of doubt, the necessity of failure, and the sheer joy of uncovering how things work. Whether he is discussing the atomic bomb, the Challenger disaster, or his own adventures in safe-cracking and bongo playing, Feynman's infectious enthusiasm makes every idea come alive. At its core, this book is about the thrill of discovery, the sheer, uncontainable excitement of understanding something new. Feynman reminds us that curiosity is not just for scientists. It is a way of life, a mindset that keeps the world endlessly fascinating. Reading this book is not just an intellectual exercise, it is an awakening, a reminder that the universe is filled with wonder, waiting to be explored by those bold enough to ask, why? Guns, germs, and steel. Why did some civilizations rise to global dominance while others remained marginalized? In Guns, Germs, and Steel, Jared Diamond dismantles the notion that history unfolded the way it did because of inherent differences in intelligence or ability between peoples. Instead, he reveals a deeper, more unsettling truth. Geography, environment, and chance shaped the fate of civilizations. Diamond traces how access to domesticable plants and animals allowed some societies to develop agriculture early, freeing them from the limitations of hunting and gathering. This surplus of food led to the rise of complex societies, technological innovation, and written language, advantages that would later allow certain civilizations to dominate others. But the most unexpected force of conquest wasn't just weapons or strategy, it was disease. Societies with long histories of farming lived in close proximity to domesticated animals, inadvertently developing immunity to deadly pathogens. When European explorers set sail, they unknowingly carried diseases like smallpox and measles, devastating indigenous populations who had no immunity. This book forces us to rethink the forces behind historical power imbalances. It challenges the idea that success is purely a product of intelligence or hard work, revealing how deep-rooted environmental factors played a decisive role in shaping the modern world. It also raises pressing questions about inequality today. How much of our present reality is shaped by the past in ways we rarely consider? Guns, Germs, and Steel is more than just history. It's a revelation. It forces you to confront the hidden structures that have shaped civilization, changing the way you see the world forever. Our Mathematical Universe. This Max Tegmark's book presents a radical and astonishing idea. Reality itself is not just described by mathematics, it is mathematics. This is not just a book about numbers and equations, it is a deep exploration of the nature of existence, consciousness, and the ultimate structure of reality. Tegmark argues that everything we perceive, from the smallest particles to the largest galaxies, is part of a vast mathematical structure. The laws of physics, rather than being arbitrary, emerge naturally from the fundamental principles of mathematics. This leads to one of the most mind-bending conclusions in modern science. We may live in a multiverse, an infinite collection of parallel realities, where every possible version of events plays out. In some of these universes, you might not exist at all, while in others, an entirely different version of you could be living a different life. But our mathematical universe is more than just an abstract theory. It forces us to reconsider what it means to be conscious beings in a seemingly cold mathematical world. If reality is pure mathematics, then what is free will? What is meaning? Are we simply patterns within an eternal, unchanging equation? The implications of this idea stretch beyond physics, touching on philosophy, identity, and the very foundations of what we call reality. Tegmark's ideas are both unsettling and awe-inspiring. This book challenges the way we understand the universe, pushing us beyond our intuitive assumptions about reality. Whether or not you accept his conclusions, the questions he raises will stay with you long after you finish reading. To engage with our mathematical universe is to confront the possibility that everything, our lives, our choices, even the universe itself, is part of an intricate, eternal, mathematical tapestry. It is a book that reshapes how you think about existence itself. The problems of philosophy. How do we know anything at all? Can we trust our senses? Or is reality something far different from what it appears to be? In The Problems of Philosophy, Bertrand Russell dissects these fundamental questions, guiding us through the uncertainties that underpin human knowledge. This is not just a book about philosophy. It's an invitation to rethink the very nature of truth, perception, and understanding. Russell begins with skepticism, asking whether we can ever be certain of anything. Our senses tell us that a table is solid, but physics reveals it is mostly empty space. A stick in water appears bent, yet we know it remains straight. If our perceptions can mislead us so easily, how can we be sure of anything? Through clear and engaging reasoning, Russell explores the distinction between appearance and reality, the nature of matter, and the limits of empirical knowledge. He then turns to logic and abstract thought, showing how philosophy helps us move beyond sensory experience to grasp deeper truths. Drawing from great thinkers like Descartes, Hume, and Kant, he unpacks the nature of belief, the foundations of reasoning, and the ways we construct knowledge itself. Yet The Problems of Philosophy is not an argument for despair. It is a defense of intellectual curiosity. Russell shows that while absolute certainty may be unattainable, the search for truth is what drives human progress. Philosophy, he argues, does not give us final answers, but teaches us how to think critically, embrace uncertainty, and appreciate the beauty of unanswered questions. This book is an essential guide for anyone seeking to sharpen their mind and challenge their assumptions about reality. The order of time. Time feels like the one constant in our lives, unstoppable, universal, and absolute. But what if everything we believe about time is wrong? In The Order of Time, physicist Carlo Rovelli dismantles our deepest assumptions about time's nature, revealing a reality far stranger than we ever imagined. Rovelli takes us on a journey through Einstein's relativity and quantum mechanics, showing that time is not a rigid flow, but a shifting, fluid entity. A clock on a mountain runs faster than one in a valley. The distinction between past and future begins to blur. And at the most fundamental level of physics, time may not even exist in the way we experience it. But this book is not just about science. It's about how these discoveries reshape our understanding of existence. If time is not an absolute force, what does that mean for our memories, our choices, and the meaning we assign to our lives? Rovelli argues that time is not something external. It's something we create, a way of making sense of an ever-changing universe. Reading The Order of Time is like stepping outside the framework of reality itself. It challenges you to rethink not just time, but the way you experience every moment of your life. And once you grasp its revelations, the world and your place in it will never look the same again. Complexity. The world around us is bursting with complexity. Weather patterns shift unpredictably, cities grow without a master plan, and intelligence emerges from networks of simple neurons. But what if all of this intricate order arises from the same underlying principles? Melanie Mitchell's Complexity reveals the hidden laws that govern the most sophisticated systems in nature, technology, and human society. At its core, complexity science challenges the traditional, reductionist way of understanding reality. Instead of breaking things down into isolated parts, it looks at how patterns, self-organization, and adaptation emerge when simple elements interact. Ant colonies, immune systems, financial markets, none are centrally controlled, yet all display intelligence and resilience far beyond their individual components. Mitchell takes you through the revolutionary insights of pioneers like John von Neumann, Alan Turing, and Stuart Kauffman, showing how complexity science bridges fields as diverse as physics, biology, and artificial intelligence. She explores the mathematics of chaos, the power of networks, and the eerie parallels between evolution and machine learning, revealing that the principles of complexity might hold the key to unlocking artificial consciousness itself. But the real impact of this book lies in how it shifts your perception of the world. It forces you to rethink how change happens, not through top-down design, but through emergence, adaptation, and feedback loops shaping everything from civilizations to the human mind. In the end, complexity is more than just a scientific exploration. It's a new way of seeing reality. Once you grasp its ideas, you begin to notice the unseen connections in everything, from the smallest cell to the largest economy. And with that realization, the world never looks the same again. Consciousness explained. What if everything you think you know about consciousness is wrong? What if your sense of self, the inner voice narrating your life, the unified experience of being you, is nothing more than a grand illusion? In Consciousness Explained, philosopher and cognitive scientist Daniel Dennett challenges our deepest assumptions about the mind, dismantling traditional theories and replacing them with a radically new understanding of human consciousness. This is not just another book on the mind. It's an intellectual revolution that redefines what it means to be aware, to think, and to experience reality. At the heart of Dennett's argument is the idea that consciousness is not a single, centralized entity, but a complex, decentralized process. He introduces the multiple drafts model, which suggests that our thoughts and perceptions are not processed in a linear fashion by a central command center, but are instead the result of countless competing and interacting neural processes. What we call conscious experience is merely the brain's best attempt at making sense of this chaotic system, crafting a coherent but ultimately deceptive narrative. There is no Cartesian theatre where everything comes together, just a continuous stream of interpretations, none of which is privileged as the definitive reality. Dennett's work has profound implications, not just for philosophy, but for fields as diverse as neuroscience, artificial intelligence, and even ethics. If consciousness is a construct rather than a fundamental essence, what does that mean for free will, personal identity, and our understanding of morality? Consciousness. Explained forces us to confront the uncomfortable possibility that our inner world is far less solid than we imagine. And yet, rather than diminishing the wonder of human experience, Dennett's insights reveal the astonishing complexity of the brain, a machine that, in trying to understand itself, creates the illusion of being something more, the hero with 1,000 faces. Why do myths from different cultures, separated by vast distances and centuries, tell the same fundamental story? The Hero with 1,000 Faces by Joseph Campbell reveals that at the heart of every great myth, legend, and even modern storytelling lies a single structure: the hero's journey. Campbell dissects this universal pattern, showing how heroes across time undergo the same cycle: an ordinary life disrupted by a call to adventure, trials that force them to grow, and a triumphant return, forever changed. From the ancient epics of Gilgamesh and Odysseus to the stories of Buddha, Jesus, and even modern cinematic legends like Luke Skywalker, Campbell unveils the deep psychological truths behind humanity's most enduring tales. This book is more than an academic study of mythology. It's a guide to understanding our own lives. We are all on a hero's journey, facing challenges, setbacks, and moments of transformation. Campbell argues that myths serve as roadmaps for personal growth, helping us navigate the uncertainties of existence. The archetypes he describes are not just literary devices. They reflect something fundamental about human nature, the way we interpret meaning, and how we evolve as individuals. Few books change the way you see not only stories, but life itself. The Hero with 1,000 Faces does just that. It forces you to recognize the patterns in your own journey, and compels you to embrace transformation, struggle, and self-discovery. Once you see the world through Campbell's lens, you'll never look at myths, movies, or even your own experiences the same way again. The Man Who Mistook His Wife for a Hat. What happens when the mind no longer perceives reality as it should? The Man Who Mistook His Wife for a Hat, by Oliver Sacks, takes readers deep into the mysteries of the human brain, exploring bizarre and often heartbreaking neurological disorders that challenge our understanding of perception, identity, and consciousness. Through a series of real patient cases, Sacks reveals how damage to the brain can distort memory, strip away fundamental aspects of personality, and even alter the way a person experiences the world. The title itself refers to a man who, due to a rare neurological condition, could no longer recognize faces and objects correctly, mistaking his wife for a hat. But this is just one of many astonishing stories. There is a man who can no longer form new memories, a woman who suddenly loses all sense of her own body, and patients whose minds are trapped in perpetual repetition, reliving the same moments again and again. Sacks presents these cases not as medical curiosities, but as profound lessons on what it means to be human. Each disorder reveals the brain's astonishing complexity, and more importantly, how our sense of self is deeply tied to its intricate workings. Yet, for all the tragedy found in these cases, there is also resilience. Sachs does not merely document neurological failures. He celebrates the human spirit's ability to adapt. Some patients find ways to navigate their strange conditions, proving that identity is more than just neural pathways. It is something that persists, even when the brain betrays us. This book forces readers to question the nature of reality, the fragility of the mind, and the very foundations of selfhood. It is not just a collection of medical mysteries. It is an exploration of what makes us who we are. Quantum Enigma. What if reality isn't as solid as it seems? Quantum Enigma by Bruce Rosenblum and Fred Kuttner takes you to the heart of one of the greatest mysteries in science, the bizarre, mind-bending nature of quantum mechanics. More than just equations and experiments, this book forces you to confront a truth that defies common sense. The mere act of observation alters reality itself. At the core of this enigma lies the famous double-slit experiment in which particles behave like waves when unobserved but like solid objects when measured. This isn't just an abstract puzzle for physicists. It suggests that consciousness and physical reality are somehow entangled in a way we don't yet understand. Could the mind play a fundamental role in shaping the universe? That's the disturbing, exhilarating possibility that Quantum Enigma dares to explore. The authors, both physicists, present the science in a clear, compelling way, while refusing to brush aside the deeper implications. If quantum mechanics governs everything at the smallest level, does it hint at something deeper about human consciousness? Does it challenge the idea of an objective reality? These questions go beyond physics, touching philosophy, free will, and even the nature of existence itself. This book doesn't offer easy answers, but it forces you to see the universe differently. If the foundations of reality are this strange, what does that mean for us? Quantum Enigma is more than just a book. It's an invitation to step beyond the limits of ordinary thinking and embrace the true, unsettling nature of the cosmos. The body keeps the score. Imagine carrying an invisible wound, one that doesn't heal with time but lingers in the body, reshaping the way you think, feel, and experience the world. The Body Keeps the Score by Bessel. Van der Kolk is a revolutionary exploration of trauma, revealing how deeply past suffering imprints itself on the mind and body. Trauma isn't just a memory. It's a living force that alters brain function, disrupts emotions, and even rewires the nervous system. For those who have endured abuse, war, neglect, or loss, the scars don't just exist in the past. They manifest in anxiety, depression, chronic pain, and self-destructive behaviors. Van der Kolk, a leading psychiatrist in trauma research, takes readers on a journey through the latest neuroscience and psychological insights, exposing how traumatic experiences reshape the brain's fear circuitry, dull the ability to feel joy, and sever connections between the rational and emotional mind. He explores how traditional talk therapy often falls short in addressing these deeply ingrained wounds and introduces groundbreaking treatments that help trauma survivors reclaim their lives. From yoga and meditation to EMDR, eye movement desensitization and reprocessing, and neurofeedback, the book presents a new understanding of healing, one that engages both mind and body. More than just a study of trauma, The Body Keeps the Score is a guide to resilience. It illuminates the path toward recovery, proving that while trauma can trap people in cycles of pain, healing is possible. By bridging science, personal stories, and innovative therapies, this book challenges us to rethink mental health and recognize that the body itself holds the key to reclaiming peace. Once you understand how trauma reshapes the self, you will never look at human suffering or healing the same way again. The end of everything. The universe will not last forever. Every star, every galaxy, and every force that shapes reality is on borrowed time. In The End of Everything, astrophysicist Katie Mack takes us on a gripping journey to the ultimate fate of the cosmos, exploring the shocking ways it all might end. While we often marvel at the universe's vastness, this book asks a more unsettling question. How does it all disappear? Mack unpacks 5 scientifically plausible scenarios for the universe's demise, each more mind-bending than the last. Will everything be torn apart in a big rip as dark energy accelerates space to its breaking point? Will the cosmos slowly freeze in a heat death, where all motion ceases and nothing interesting ever happens again? Perhaps the universe will collapse in a big crunch, only to be reborn in a cycle of endless destruction and creation. And then, there's the most chilling possibility of all, vacuum decay, an unpredictable event that could erase everything in an instant, rewriting the very laws of physics. But The End of Everything is not a story of doom. It's a celebration of cosmic curiosity. By contemplating the end, we gain a deeper appreciation for the present, for the fleeting beauty of existence, and for the incredible fact that we are here to witness it at all. The universe may have an expiration date, but while it lasts, we have the privilege of understanding it. And once you glimpse reality through this perspective, your place in the cosmos will never feel the same again. The Varieties of Scientific Experience. Carl Sagan's The Varieties of Scientific Experience is a profound meditation on the intersection of science, philosophy, and the human search for meaning. It challenges us to confront the vastness of the cosmos, not with fear, but with a deep sense of wonder. If you've ever questioned humanity's place in the universe, this book will take you on a journey that reshapes your understanding of existence itself. At its heart, the book explores the tension between science and religion, arguing that true spirituality is not found in dogma, but in the awe-inspiring truths uncovered by scientific inquiry. Sagan dismantles our Earth-centric perspective, reminding us that we are a mere speck in an unfathomably large universe. Yet this realization should not diminish us. Instead, it should inspire humility, curiosity, and a commitment to reason over superstition. Through a sweeping exploration of astronomy, evolution, and the nature of intelligence, Sagan invites us to contemplate the possibility of extraterrestrial life, the fragility of our planet, and the ethical responsibility that comes with knowledge. He warns against the dangers of scientific illiteracy, emphasizing that only through rational thinking can humanity navigate the challenges ahead. But perhaps the book's greatest power lies in its ability to replace existential dread with cosmic perspective. It reminds us that science is not cold or impersonal. It is a deeply human pursuit, filled with wonder and beauty. It does not diminish the mystery of existence, but enriches it, offering a way to find meaning not in myths, but in the grandeur of reality itself. Once you see the universe through Sagan's eyes, the world will never feel small again. Meditations on First Philosophy. What if everything you believe, everything you see, hear, and feel was a lie? How can you be sure the world around you isn't just an illusion? Meditations on First Philosophy by René Descartes is one of the most groundbreaking works in the history of thought, stripping away every assumption to find a foundation of absolute certainty. With relentless skepticism, Descartes embarks on an intellectual journey that reshapes our understanding of reality, knowledge, and existence itself. At the core of this work is Descartes' method of doubt. He questions everything, his senses, his memories, even the existence of the physical world, because they can all be deceived. What if a powerful, malicious demon were manipulating his perceptions? Is there anything that cannot be doubted? From this radical skepticism, he arrives at a single, undeniable truth. Cogito, ergo sum. I think, therefore I am. No matter how much he doubts, he cannot doubt that he is thinking, and thus, he must exist. This revelation becomes the bedrock upon which he rebuilds his understanding of reality. From this foundation, Descartes seeks to prove the existence of God and the separation between mind and body. He argues that our ability to conceive of perfection suggests the existence of a perfect being, and that our minds, capable of reason and introspection, must be distinct from the material world. His ideas gave rise to modern philosophy, influencing everything from science to artificial intelligence. But Meditations is more than an abstract exercise in logic. It's a personal, almost spiritual reckoning with the nature of human existence. Descartes forces us to confront the uncomfortable idea that much of what we assume to be true could be a deception, whether by our own minds or by some external force. Yet, through this radical skepticism, he finds a path to certainty, providing a method of rigorous thinking that remains profoundly influential. Whether or not one accepts his conclusions, engaging with Descartes' Meditations is like stepping into a mental battlefield, one where the stakes are nothing less than reality itself. The botany of desire. What if plants have shaped human civilization as much as we have shaped them? In The Botany of Desire, Michael Pollan challenges our traditional view of nature by revealing a strikingly reciprocal relationship between humans and plants. We often think of domestication as something we impose on the natural world, but what if apples, tulips, marijuana, and potatoes have used us just as much as we have used them? Pollan presents a compelling argument. Plants, through their evolutionary brilliance, have adapted to fulfill human desires, sweetness, beauty, intoxication, and control, ensuring their survival and expansion across the globe. Each chapter of the book explores one of these desires through the lens of a specific plant. The apple represents sweetness, tracing its journey from the wild forests of Kazakhstan to orchards worldwide, where its diversity has been tamed by human cultivation. The tulip embodies beauty, demonstrating how a single flower could incite economic hysteria in 17th century Holland. Marijuana represents intoxication, raising profound questions about why humans seek altered states and how plants have evolved potent chemical defenses that double as sources of human pleasure. Finally, the potato symbolizes control, illustrating how our dependence on monocultures, like the genetically uniform potato crops that led to the Irish famine, reveals the risks of manipulating nature too aggressively. This book transforms the way we see the natural world, showing that our relationship with plants is not one of simple dominance, but of deep interconnection. Pollan's insights force us to reconsider our place in nature, not as masters of it, but as co-evolutionary partners in a vast, intricate system. In The Botany of Desire, he reminds us that by shaping the plants we cultivate, we are also shaping ourselves, our diets, our economies, and even our consciousness. The mind of God. Is the universe the result of mere chance? Or is there an underlying order guiding its existence? The Mind of God by Paul Davies takes readers on a profound journey through science, philosophy, and theology to explore one of humanity's greatest questions. Does the universe have a purpose? Davies begins by examining the astonishing precision of the physical laws that govern reality. The fundamental constants of nature, such as gravity and electromagnetism, are so finely tuned that even the slightest variation would make life impossible. Is this precision the product of blind luck, or does it point to a deeper design? He explores theories from quantum mechanics, relativity, and cosmology, revealing how modern physics brushes against profound philosophical ideas. Could mathematics be the language of the cosmos? Do the laws of physics suggest a deeper intelligence, or is consciousness itself a fundamental part of reality? Unlike many books on science and religion, The Mind of God does not argue for a traditional deity. Instead, it challenges us to consider whether the universe possesses an intrinsic order that transcends human understanding. Davies engages with ideas from Einstein, Gödel, and Hawking, questioning whether our search for ultimate meaning is itself woven into the fabric of existence. This book will leave you questioning everything you thought you knew about reality. It bridges the gap between scientific inquiry and existential wonder, pushing you to rethink the nature of existence itself. Whether you believe in a divine creator or a self-organizing cosmos, The Mind of God will challenge your perspective and expand your understanding of the universe in ways few books can. Thinking Fast and Slow, Daniel Kahneman's. Thinking Fast and Slow reveals a startling truth about our minds. We are not as rational as we think. Every decision we make, whether choosing a meal, making an investment, or even forming our beliefs, is influenced by two distinct thinking systems. System 1 is fast, intuitive, and emotional. It helps us react instantly, but often leads to errors. System 2, on the other hand, is slow, deliberate, and logical, yet it is lazy and easily influenced. Kahneman shows how these two systems interact, shaping our judgments in ways we rarely notice. Through decades of groundbreaking research, he exposes the cognitive biases that distort our perception, such as the availability heuristic, where we overestimate the importance of easily recalled information, and loss aversion, which makes us fear losses more than we value equivalent gains. These biases explain why we make impulsive choices, trust flawed memories, and fall for illusions of confidence. More importantly, they reveal why even experts and policymakers make irrational decisions with far-reaching consequences. But understanding these biases is not just an academic exercise, it is a profound tool for self-awareness. Once we recognize the hidden forces influencing our thoughts, we can make smarter financial choices, improve negotiations, and resist manipulative tactics in marketing and politics. The book challenges us to think more critically, question our assumptions, and slow down when it matters most. This is not just a book about psychology. It's a guide to seeing reality more clearly. By grasping how our minds truly work, we gain the power to make better decisions, avoid costly mistakes, and take control of our own thinking. From eternity to here, we live our lives bound by time, moving from past to future without ever questioning why it works that way. But what if time isn't as straightforward as it seems? What if the rules that govern our everyday experience are just a small piece of a much deeper mystery? Sean Carroll's From Eternity to Here unravels one of the biggest questions in physics. Why does time have a direction at all? At the heart of Carroll's exploration is the concept of entropy, the idea that disorder always increases. This simple principle, rooted in the second law of thermodynamics, explains why ice melts, why stars burn out, and why we can never truly reverse time. But the real question is, why did the universe begin in such a low-entropy, highly ordered state? To answer this, Carroll dives into the nature of space-time, black holes, and even the possibility of parallel universes. Could our universe be just one bubble in an infinite multiverse? Could time itself emerge from deeper, timeless laws of physics? This book is more than just a lesson in cosmology. It is an invitation to rethink everything we assume about reality. If time is not as fixed as we believe, then our notions of past, present, and future are up for debate. The implications stretch beyond science, forcing us to reconsider our place in the grand unfolding of the cosmos. What if time isn't something we move through, but something we create through our understanding? After reading From Eternity to Here, you may never look at a ticking clock the same way again. Enlightenment Now. This book by Steven Pinker is a bold defense of progress in an age filled with cynicism and despair. At a time when the world feels increasingly chaotic, this book delivers a powerful message. Humanity is not in decline. We are living in the most prosperous, healthy, and peaceful era in history. With a vast array of data, Pinker dismantles the common belief that the world is getting worse, proving that Enlightenment values, reason, science, and humanism have steadily propelled civilization forward. The book spans a vast range of topics, from life expectancy and education to poverty reduction, and technological advancement. Pinker demonstrates how, despite the headlines that suggest otherwise, violence is declining, diseases are being eradicated, and more people than ever before have access to knowledge and opportunity. He argues that these improvements are not accidents, but the direct result of rational thinking, liberal democracy, and scientific progress. Yet enlightenment now is not just about presenting hopeful statistics. It is a call to responsibility. Progress is not automatic, nor is it guaranteed. The forces of ignorance, tribalism, and anti-scientific thinking still threaten to undermine human advancement. Pinker warns against romanticizing the past and urges readers to embrace critical thinking, innovation, and evidence-based policies to ensure that progress continues. This book forces you to reconsider the way you view the world. It dismantles the illusion that humanity is doomed and replaces it with a compelling case for optimism. An optimism rooted not in blind faith, but in facts. Enlightenment now is not just an argument for progress. It is a manifesto for those who believe in reason, truth, and the potential for a better world. Once you see the world through Pinker's lens, despair becomes harder to justify, and hope becomes an intellectual necessity. Flow. There are moments in life when time seems to disappear, when every action flows seamlessly into the next, and when we feel completely alive and immersed in what we're doing. This rare and elusive state, known as flow, is the key to deep fulfillment, creativity, and peak performance. In Flow, the psychology of optimal experience, Mihaly Csikszentmihalyi explores the science behind this phenomenon and reveals how we can harness it to live richer, more meaningful lives. Flow occurs when we engage in activities that challenge us just enough to keep us fully focused, but not so much that they become overwhelming. Whether in sports, art, work, or even everyday tasks, this state brings a profound sense of enjoyment and mastery. The book details the conditions necessary for flow: clear goals, immediate feedback, and a balance between skill and challenge. When these elements align, we enter a state where self-consciousness fades, distractions disappear, and we perform at our highest potential. The implications are profound. By structuring our lives to create more opportunities for flow, we can cultivate happiness not through external rewards, but through the sheer joy of deep engagement. But flow is more than just a guide to personal fulfillment. Csikszentmihalyi challenges us to rethink our relationship with work, leisure, and even relationships. A life driven by passive consumption, endless scrolling, mindless entertainment, leaves us feeling empty. But when we actively shape our experiences, turning even ordinary moments into opportunities for deep engagement, life transforms. This book is a wake-up call. Happiness isn't something we find, but something we create through how we focus our attention. And once we master flow, we don't just live, we thrive. The Emperor's New Mind. Is the human mind just a biological computer, or is there something deeper, something beyond the reach of algorithms? In The Emperor's New Mind, physicist Roger Penrose challenges the dominant view that consciousness can be replicated by artificial intelligence, arguing instead that human thought operates on principles not yet understood by science. Penrose takes us on a journey through physics, mathematics, and philosophy, examining everything from Gödel's incompleteness theorems to the paradoxes of quantum mechanics. He argues that if consciousness were purely computational, it would be subject to the same logical limitations as machines. However, human intuition, creativity, and understanding seem to transcend these constraints, suggesting that something profoundly different is at play. At the heart of his argument lies quantum mechanics, particularly the mysterious nature of wave function collapse. Penrose speculates that the fundamental processes of consciousness might be tied to quantum effects occurring in the brain, an idea that remains controversial, but deeply thought-provoking. If true, it would mean that the mind is not just a program running on the hardware of the brain, but something woven into the very fabric of reality itself. This book forces you to rethink the nature of thought, intelligence, and even free will. If Penrose is right, then AI may never truly replicate human consciousness, not because of technical limitations, but because the mind itself operates on principles we have yet to discover. The Emperor's New Mind isn't just a book about physics or philosophy. It's a challenge to everything we assume about what it means to be human. Why we sleep. What if the single most powerful tool for a healthier, sharper, and longer life was something you're neglecting every night? Why We Sleep by Matthew Walker is a groundbreaking exploration of one of the most mysterious, yet essential biological functions: sleep. In a world that glorifies productivity and late-night work, Walker makes a compelling case that sleep is not a luxury, but a biological necessity, as vital as food and water. The consequences of sleep deprivation are staggering, affecting everything from memory and emotional stability to immune function and lifespan. Walker reveals how sleep enhances learning, creativity, and problem-solving, while a lack of it increases the risk of heart disease, Alzheimer's, obesity, and even cancer. He explains the two main forces governing our sleep: the circadian rhythm, which aligns with the day-night cycle, and sleep pressure, which builds throughout the day. He also dives into the different sleep stages, particularly the critical roles of deep sleep and REM sleep in repairing the body and processing emotions. One of the book's most eye-opening insights is the effect of modern society on sleep. Artificial light, caffeine, and erratic schedules have dramatically reduced the amount and quality of rest we get. Walker warns that even minor sleep deficits accumulate over time, leading to irreversible cognitive and physical damage. He dismantles the myth that we can catch up on sleep, showing that lost sleep is lost forever. This book is more than a call to sleep longer. It is a wake-up call to rethink our priorities. It challenges us to see sleep as the foundation of our well-being, not an afterthought. After reading Why We Sleep, you'll never look at bedtime the same way again. Rare Earth. We assume the universe is brimming with intelligent life, that Earth is just one of many worlds where evolution has played out. But what if we're wrong? In Rare Earth, Peter Ward and Donald Brownlee argue that complex life may be far more uncommon than we think, perhaps so rare that we are utterly alone. The book challenges the idea that the cosmos should be teeming with civilizations, pointing to a series of extraordinary circumstances that made Earth uniquely habitable. A perfectly placed moon to stabilize our climate, a gas giant like Jupiter to shield us from cosmic collisions, a precise sequence of mass extinctions and evolutionary leaps. Even plate tectonics, which reshapes continents and cycles nutrients, may be an essential factor that most planets never develop. Ward and Brownlee's argument is both unsettling and awe-inspiring. If intelligent life is vanishingly rare, what does that say about our place in the universe? Are we a cosmic accident, a fragile exception in an otherwise barren void? Or does our uniqueness make existence even more meaningful? Rare Earth isn't just about astrobiology, it's a humbling reflection on the sheer improbability of our existence. If Earth is one of the only homes for intelligence in the universe, then every moment of life here becomes even more precious. In the vast silence of space, we may be the only ones who can truly appreciate it. The interpretation of dreams. Every night, as you close your eyes and drift into sleep, another world awakens, one filled with strange symbols, forgotten memories, and impossible realities. What if these dreams weren't just random images, but messages from the depths of your own mind? In the interpretation of dreams, Sigmund Freud unveils his groundbreaking theory that dreams are the hidden language of the unconscious, revealing desires, fears, and conflicts buried beneath our waking awareness. This book didn't just change how we view dreams, it revolutionized our understanding of the human psyche itself. Freud argues that dreams serve as a gateway to the unconscious, a realm where repressed thoughts and emotions find expression in disguised forms. He introduces the idea of wish fulfillment, suggesting that even the most bizarre dream imagery is rooted in unfulfilled desires, often stemming from childhood. Using detailed case studies, he deciphers dream symbols, showing how the mind reshapes forbidden impulses into cryptic narratives. He also outlines the mechanisms of dream work, condensation, displacement, and symbolic representation, demonstrating how the unconscious mind distorts raw emotions into surreal but meaningful stories. More than just a psychological theory, the interpretation of dreams is a bold exploration of what it means to be human. It challenges us to question how much of our behavior is dictated by forces beyond our awareness. By decoding our dreams, Freud believed, we could unlock the unconscious mind, bringing buried emotions to light and ultimately achieving deeper self-understanding. Whether or not you accept all of Freud's conclusions, his insights laid the foundation for modern psychology, shaping everything from therapy to art and literature. After reading this book, you may never see your dreams or yourself the same way again. The extended phenotype. What if genes don't just shape the bodies of the creatures that carry them, but also reach beyond shaping the world itself? In the extended phenotype, Richard Dawkins challenges our understanding of evolution by proposing a radical idea. An organism's phenotype, the physical expression of its genes, is not limited to its own body. Instead, it extends into the environment, influencing structures, behaviors, and even other creatures in ways that serve the survival of its genes. This perspective reshapes how we see life, from the tiniest parasites to the grand engineering of beaver dams. Dawkins builds on the gene-centered view of evolution, arguing that natural selection does not operate on individuals or species, but on genes themselves. These genes, in their relentless drive for survival and replication, express themselves not only through an organism's body, but through the modifications it makes to its surroundings. A spider's web, a bird's nest, even the way a parasite manipulates its host. These are not random acts of nature, but extensions of the genetic blueprint, honed over millions of years to maximize reproductive success. One of the book's most striking ideas is how this theory explains the eerie precision with which parasites alter host behavior. A parasitic worm that compels an ant to climb a blade of grass, making it easy prey for a grazing mammal, is not just an anomaly of nature. It is an example of a gene's influence stretching beyond the body of the parasite itself. These phenomena reveal that evolution's true unit of selection is not the organism, but the replicating gene, using all means necessary to ensure its continuity. The extended phenotype forces us to reconsider what it means to be an individual in the first place. If genes exert their power far beyond the bodies they inhabit, then life itself is a vast network of genetic influence, sculpting the world in ways we are only beginning to understand. The universe in a nutshell, the deepest secrets of the universe, black holes, time travel, extra dimensions, can be unraveled in the palm of your hand. In The Universe in a Nutshell, Stephen Hawking distills the cutting-edge theories of physics into a breathtaking journey through space, time, and the fundamental nature of reality itself. This book is not just an exploration of the cosmos, it is an invitation to rethink everything we thought we knew about existence. Hawking masterfully navigates the frontiers of modern physics, introducing concepts that stretch the limits of human imagination. He builds upon Einstein's theory of relativity and quantum mechanics, explaining how they collide in the extreme environments of black holes and the Big Bang. He discusses the possibility of parallel universes, higher dimensions beyond our perception, and even the tantalizing idea that time itself may not be as rigid as we believe. With clarity and wit, he walks us through the mind-bending implications of string theory, M theory, and the search for a theory of everything, a single, unifying framework that could explain the entirety of existence. Unlike traditional science books, The Universe in a Nutshell is filled with stunning illustrations that bring these abstract ideas to life, making it accessible even to those without a background in physics. Yet its impact goes far beyond the scientific. It challenges us to grapple with the vastness of the cosmos and our fleeting place within it. This book is a gateway to the deepest mysteries of the universe, offering a glimpse into the profound beauty and complexity of reality. Reading it is like standing at the edge of infinity, peering into a realm where the ordinary rules of existence no longer apply. It is a reminder that, despite our smallness, the human mind is capable of grasping the most extraordinary truths of the cosmos. Nicomachean Ethics. What does it mean to live a good life? In Nicomachean Ethics, Aristotle embarks on one of the most profound explorations of human purpose, virtue, and happiness ever written. He doesn't offer rigid moral rules, but instead provides a guide for cultivating character, making wise choices, and achieving true fulfillment. At the heart of his philosophy is the concept of eudaimonia, often translated as flourishing or the highest good, which is not merely pleasure or wealth, but a deeply meaningful life rooted in virtue. Aristotle argues that virtue is not something we are born with, nor is it a set of abstract ideals. Instead, it is a habit, one that must be practiced through action and refined by reason. He introduces the golden mean, the idea that every virtue lies between two extremes. Courage, for example, is the balance between recklessness and cowardice. He believes that moral excellence is achieved by developing these virtues through experience, self-reflection, and a commitment to reason. Unlike fleeting pleasures, true happiness arises from living in alignment with our highest potential, continuously striving for wisdom and ethical integrity. But Aristotle does not stop at personal ethics. He sees human beings as inherently social creatures, arguing that a good life is not lived in isolation, but in a well-ordered society. Friendship, justice, and civic engagement are not just accessories to happiness, they are essential to it. By cultivating strong moral character and engaging in meaningful relationships, we create not only a better life for ourselves, but a better world for those around us. The Nicomachean Ethics is more than just philosophy. It is a roadmap for becoming the best version of ourselves. It challenges us to ask, what kind of person do I want to be? And more importantly, what kind of life is truly worth living? The sickness unto death. The worst kind of suffering may not be physical pain, but a sickness of the soul, one that most people don't even realize they have. In The Sickness Unto Death, Søren Kierkegaard argues that the greatest torment is not death itself, but despair, an internal, silent crisis that eats away at a person's very existence. Unlike a sickness of the body, this illness is far more insidious because it is rooted in the nature of selfhood itself. Kierkegaard sees the self as a tension between the finite and the infinite, the earthly and the eternal. To exist fully, one must properly relate to oneself and to God. But when this relationship is broken, despair emerges. He outlines different forms of despair. Some people are unaware they are in despair, living in ignorance or distraction. Others are painfully conscious of their condition, but feel powerless to change it. The deepest form of despair, however, is the rejection of one's true self, a refusal to align with the higher purpose of existence. This, he claims, is the ultimate sickness, the sickness unto death. Yet, there is a way out. Unlike the fatal despair Kierkegaard describes, the solution lies in embracing faith, not as blind obedience, but as the recognition of a deeper, transcendent truth. True freedom comes not from worldly success, nor from self-reliance, but from surrendering the ego and accepting one's dependence on something greater. Only then can a person reconcile their fragmented self and escape the abyss of despair. More than a philosophical treatise, The Sickness Unto Death is a haunting diagnosis of the modern soul. It forces us to confront an unsettling question. Are we truly living? Or are we merely avoiding the truth of who we are? The fabric of the cosmos. Everything you thought you knew about space, time, and reality might be incomplete, maybe even wrong. In The Fabric of the Cosmos, Brian Greene unravels the hidden nature of the universe, revealing a reality far stranger than common sense suggests. From the fluidity of time to the eerie possibility of parallel worlds, this book forces us to reconsider our most basic assumptions about existence itself. Greene explores the nature of space, not as an empty backdrop, but as an active, dynamic entity that can bend, ripple, and even vanish. Einstein's theory of relativity shattered the classical idea of time as fixed and universal, showing instead that it stretches and contracts depending on speed and gravity. But modern physics takes this even further. Quantum mechanics challenges the very fabric of cause and effect, with particles that can exist in multiple places at once or influence each other instantly across vast distances. The book also delves into one of the greatest mysteries in physics, the nature of time. If the laws of physics treat past, present, and future as equally real, why do we experience time as a one-way flow? Greene investigates whether time is an illusion, a product of human perception rather than an intrinsic feature of the universe. Meanwhile, string theory suggests that reality consists of far more than the three spatial dimensions we perceive. Hidden dimensions may hold the key to unifying all of physics. At its core, The Fabric of the Cosmos reveals that the universe is not just stranger than we imagine, but perhaps stranger than we can imagine. It challenges our grip on reality, forcing us to confront a cosmos that operates on principles more bizarre than any science fiction. Except in this case, it's all real. The telltale brain. Everything that makes you you, your thoughts, your creativity, your sense of self, may be the result of hidden patterns firing within the folds of your brain. In The Telltale Brain, neuroscientist V.S. Ramachandran embarks on a fascinating journey into the human mind, revealing how our brains construct reality, generate emotions, and even give rise to the elusive concept of consciousness. Through groundbreaking research and captivating case studies, this book offers a radical new understanding of what it means to be human. At the heart of Ramachandran's work is the idea that the brain is a master of adaptation and illusion. He explores the strange and often unsettling world of neurological disorders, people who feel phantom limbs after amputation, patients who deny that one side of their body belongs to them, and individuals who experience mirror-touch synesthesia, physically feeling sensations that happen to others. These anomalies, far from being mere curiosities, expose the brain's hidden mechanisms. They show how perception is not a passive process, but an active construction, where the mind fills in gaps, makes assumptions, and crafts a seamless experience of the world. One of the book's most profound revelations is how our brains are wired for creativity and metaphor. Ramachandran delves into the neurological basis of art and aesthetics, explaining how certain visual patterns evoke deep, emotional responses. He also explores the evolutionary leap that allowed humans to develop language, self-awareness, and culture, abilities that set us apart from any other species. Reading The Telltale Brain is like stepping behind the curtain of reality itself, seeing the hidden machinery that governs every thought and feeling. It leaves you with a profound sense of wonder and an unsettling realization. The mind is both more fragile and more astonishingly powerful than we ever imagined. The structure of scientific revolutions. Science doesn't progress the way we think it does. In The Structure of Scientific Revolutions, Thomas Kuhn shatters the conventional view of scientific progress as a steady accumulation of knowledge. Instead, he argues that science moves through disruptive, paradigm-shifting revolutions that completely redefine how we see the world. These revolutions don't happen smoothly. They emerge when old theories break down, forcing a radical shift in thinking. Once you understand this, you'll never see science the same way again. Kuhn's key idea is the paradigm shift, a fundamental change in the basic assumptions of a scientific field. Normal science operates within an accepted framework, solving puzzles and refining existing theories. But when anomalies accumulate, when evidence no longer fits, the entire framework is questioned. Suddenly, what once seemed certain becomes obsolete, and a new paradigm takes its place. Think of how Copernicus replaced the Earth-centered universe, or how Einstein overturned Newtonian physics. These weren't just small adjustments, they were complete transformations in our understanding of reality. More unsettling is Kuhn's claim that scientific truth isn't discovered in a straightforward, objective manner. Instead, science is shaped by human perspectives, social influences, and historical contexts. A new paradigm isn't necessarily more true in an absolute sense. It simply becomes the new lens through which scientists interpret data. This means that what we consider truth is, in part, a product of our collective mindset, not just raw facts. The structure of scientific revolutions doesn't just change how we think about science, it changes how we think about knowledge itself. It forces us to question whether progress is as objective as we believe and reveals the deep, often invisible forces that shape the way we understand the world. Being and nothingness. What if the greatest burden of human existence is also its greatest freedom? In Being and Nothingness, Jean-Paul Sartre delivers a profound exploration of what it means to be human, what it means to exist in a world without predetermined meaning, where consciousness itself is both a gift and a curse. This book is not just a philosophical treatise, it is an existential awakening, forcing us to confront the unsettling reality that we are condemned to be free. Sartre argues that human existence is defined by a fundamental divide, being in itself and being for itself. Objects, like a rock or a chair, simply exist. They are what they are. But human beings are different. Our consciousness introduces a dimension of negation, of nothingness, allowing us to imagine possibilities beyond what we are in the present. This is both liberating and terrifying, because it means that we alone are responsible for shaping our identity. There is no external force, no divine plan to dictate who we must become. We are free, and that freedom is absolute. But with freedom comes anguish. We long for stability, for a fixed identity, yet every attempt to define ourselves through career, relationships, or social roles is ultimately a self-deception. Sartre calls this bad faith, the act of pretending we are bound by circumstances, denying our radical freedom. A waiter who insists he is just a waiter, a lover who clings to an unchanging idea of their partner. These are examples of people avoiding the burden of choice. By exposing the illusions we create to avoid responsibility, Being and Nothingness forces us to confront the raw truth of existence. It is an unsettling yet empowering realization. Life has no inherent meaning except for what we choose to give it. And in that void, in that nothingness, lies our greatest power, the power to become whoever we dare to be. The logic of scientific discovery. Everything you believe about scientific truth might be wrong. The Logic of Scientific Discovery by Karl Popper challenges the very foundation of how we understand knowledge, offering a revolutionary approach to the philosophy of science. Rather than viewing science as a steady accumulation of proven facts, Popper argues that true scientific progress comes not from verification, but from falsification, the relentless testing of ideas to expose their weaknesses. This shift changes everything, redefining how we separate real science from mere speculation. At the heart of Popper's argument is the concept of falsifiability. A theory, no matter how elegant or widely accepted, is only scientific if it can be tested and potentially proven false. This principle directly opposes the classical view that science advances by accumulating evidence to confirm theories. Instead, Popper shows that the strength of a theory lies in its ability to withstand rigorous attempts to disprove it. This is why genuine scientific ideas evolve over time, not because they are proved right, but because weaker theories are continuously discarded in favor of stronger ones. Popper's ideas hold profound implications for fields beyond science. His philosophy dismantles dogmatic thinking and demands intellectual humility. It warns against blindly accepting ideas just because they seem to fit the evidence. In an age where misinformation spreads rapidly, Popper's method teaches us to question, test, and refine our understanding of reality rather than passively accepting what seems true. Ultimately, the logic of scientific discovery is not just about science, it's about thinking itself. It equips us with the tools to separate reason from ideology, skepticism from cynicism, and progress from illusion. To embrace Popper's philosophy is to embrace a world where truth is never final but always within reach, so long as we dare to challenge it. The Blind Watchmaker. If life is so complex, so intricately designed, how could it possibly emerge without a designer? This question has puzzled thinkers for centuries, but in The Blind Watchmaker, Richard Dawkins presents a compelling answer: evolution by natural selection. With striking clarity, he dismantles the illusion of purposeful creation, revealing that the breathtaking complexity of life arises not from a guiding hand, but from a mindless yet astonishingly effective process. Dawkins begins by challenging the idea that complexity requires intent. Many assume that intricate biological structures, like the eye or the wing, must have been consciously designed because their components work together with such precision. But evolution, he argues, builds complexity incrementally, step by step, through countless tiny variations. Each beneficial change is preserved and refined over generations, creating organisms that appear as if they were designed, yet without a designer. This process, acting over millions of years, is the blind watchmaker of nature. Using vivid examples, Dawkins illustrates how natural selection sculpts life in ways that seem almost magical. He explains how simple replicating molecules, through competition and gradual improvement, gave rise to the dazzling diversity of species we see today. He also tackles common misconceptions, such as the idea that evolution is random, clarifying that while mutations may be chance occurrences, selection itself is anything but random. Ultimately, the blind watchmaker reshapes how we see life itself. It replaces the comforting notion of intentional creation with something even more extraordinary, the realization that mindless natural forces, acting over vast stretches of time, can produce forms of unimaginable complexity. Evolution is not just a theory, it is the story of how everything that lives came to be, and in understanding it, we gain a deeper appreciation for the true marvel of existence. The phenomenology of spirit, your entire understanding of reality, your sense of self, your beliefs, your perception of the world, is not a fixed truth, but a journey. In the phenomenology of spirit, G.W.F. Hegel takes us on a profound intellectual odyssey, showing that consciousness is not static, but unfolds through a dynamic process of self-discovery. This book is not just a work of philosophy, it is an invitation to witness the evolution of human thought itself, from the simplest awareness to the deepest self-realization. At the core of Hegel's masterpiece is the idea that knowledge and self-awareness emerge through struggle. He introduces the famous master-slave dialectic, a concept that reveals how identity is shaped by recognition from others. Two beings encounter each other, each seeking dominance. One submits, the other rules, but in doing so, the master ironically becomes dependent on the slave for validation. This tension is not just a social dynamic, it is a metaphor for the way all ideas and identities develop through contradiction and resolution. Hegel also presents the concept of the dialectic, a process where ideas collide, challenge each other, and give rise to something new. Every stage of consciousness contains its own limitations, and through confronting those limits, thought evolves. From sensory experience to reason, from morality to absolute knowledge, the journey of spirit is one of constant transformation. The self does not simply find truth, it must actively become it. Reading. The phenomenology of spirit is like watching the universe wake up to itself. It is a book that demands patience, but in return, it offers a vision of reality as a living, unfolding process. One in which every struggle, every contradiction, and every moment of doubt is not an obstacle, but a necessary step toward greater understanding. Practical ethics. Doing what feels right isn't always what's truly ethical. In Practical Ethics, Peter Singer forces us to confront some of the most difficult moral questions of our time, challenging assumptions about life, death, and our responsibilities toward others. His approach isn't based on tradition or emotion, but on a strict, logical framework that asks, how can we maximize well-being and minimize suffering? The answers are often unsettling, but they demand our attention. At the core of Singer's argument is utilitarianism, the idea that ethical decisions should be based on their consequences. He applies this principle to real-world issues, dismantling conventional morality with uncompromising logic. Should we prioritize human lives over animal suffering when we have no rational justification for doing so? Is it ethical to spend money on luxuries while millions starve? If we can prevent immense suffering with minimal personal sacrifice, are we morally obligated to do so? Singer doesn't just ask these questions. He answers them with a clarity that makes evasion nearly impossible. Perhaps most controversial is his discussion of life and death. Singer challenges deeply held beliefs about abortion, euthanasia, and the value of human life itself. Rather than accepting rigid moral doctrines, he urges us to evaluate each situation based on reason and compassion. His arguments are provocative, sometimes uncomfortable, but always deeply thought-provoking. Practical Ethics is not a book that offers easy answers. It's one that forces you to think differently about everything. It strips away sentimentality and exposes the raw logic of moral responsibility. If taken seriously, its ideas demand action, making it one of the rare books that doesn't just change how you think, it changes how you live. The demon-haunted world. Imagine living in a world where truth is indistinguishable from illusion, where superstition rules over reason, and where critical thinking is drowned out by fear and deception. In the demon-haunted world, Carl Sagan offers a beacon of clarity in an age of misinformation, urging us to embrace science as our best defense against ignorance and manipulation. This book is not just about science. It is about how to think, how to question, and how to navigate a world teeming with both wonders and falsehoods. Sagan explores the human tendency to believe in the irrational, from alien abductions to conspiracy theories, and explains why such beliefs persist, even in the face of contradictory evidence. He argues that our minds, wired for pattern recognition and storytelling, are vulnerable to deception. But rather than dismissing these tendencies outright, he seeks to understand them, showing how our fascination with the unknown can either lead us toward enlightenment or trap us in self-imposed illusions. At the heart of the book is the baloney detection kit, a set of logical tools designed to help us separate fact from fiction. With simple yet powerful reasoning techniques, Sagan teaches us how to scrutinize claims, demand evidence, and resist the allure of pseudoscience. He champions skepticism, not as cynicism, but as a way to approach the world with curiosity, open-mindedness, and intellectual integrity. In an era where misinformation spreads faster than truth, the demon-haunted world remains more relevant than ever. Sagan's words remind us that science is more than just knowledge. It is a way of thinking, a method of survival, and perhaps our last best hope for a future governed by reason rather than fear. The better angels of our nature. For most of human history, violence was an unavoidable part of life. Wars, executions, slavery, and cruelty were woven into the fabric of existence, seemingly as natural as the air we breathe. But what if the story of humanity is not one of unending brutality, but of remarkable progress toward peace? In The Better Angels of Our Nature, Steven Pinker presents a sweeping, deeply researched argument that violence has been steadily declining for centuries, contrary to what the news and popular perception might suggest. And more importantly, he explains why this decline has happened and what it means for our future. Drawing from history, psychology, and neuroscience, Pinker examines the forces that have driven humanity away from its violent past. He highlights 5 key historical shifts: the rise of organized states, the spread of commerce, the empowerment of women, the expansion of literacy, and the development of reason-based thinking. These forces, he argues, have led to a world in which wars are less frequent, murder rates have plummeted, and once common atrocities, such as public executions and slavery, are now nearly unthinkable. Pinker does not deny that violence still exists, nor does he suggest that progress is inevitable. But through extensive data and compelling historical narratives, he shows that the human capacity for empathy, cooperation, and rationality has played a critical role in shaping a more peaceful world. The book challenges deep-seated beliefs about human nature, offering a vision of history that is not just a record of suffering, but a testament to our ability to change. In a time when fear and pessimism dominate public discourse, The Better Angels of Our Nature forces us to step back and see the bigger picture. The trajectory of history is not one of despair, but of hope, a powerful reminder that our choices today can shape an even better tomorrow. The Brothers Karamazov. Few novels have captured the full spectrum of human nature as profoundly as The Brothers Karamazov. Dostoevsky's final masterpiece is not merely a story, it is a philosophical battlefield where faith and doubt, love and hatred, freedom and responsibility collide. It is a book that does not just ask questions, but forces the reader to grapple with them, unsettling even the firmest convictions. At its heart, the novel follows the lives of the Karamazov brothers, Dmitri, Ivan, and Alyosha, each representing a different facet of the human soul. Dmitri is driven by passion and impulse, Ivan by intellect and reason, and Alyosha by faith and compassion. Their father, the hedonistic and manipulative Fyodor Karamazov, is a man ruled by base desires, and his murder sets off a chain of events that brings these opposing forces into stark relief. Through this gripping family drama, Dostoevsky weaves profound meditations on morality, free will, and the existence of God. One of the novel's most famous passages, The Grand Inquisitor, presents a chilling argument about human nature's preference for security over freedom, challenging the foundations of religious belief. Meanwhile, Ivan's struggle with the problem of evil, how a just God could allow suffering, remains one of the most unsettling moral dilemmas in literature. Yet, amidst these weighty questions, the novel is also deeply human, filled with moments of redemption, suffering, and raw emotion that feel startlingly real. What makes The Brothers Karamazov truly life-changing is its refusal to offer simple answers. It forces the reader to wrestle with contradictions, to face the uncomfortable truths of existence, and ultimately, to seek meaning in a world that often feels beyond comprehension. It is not a book to be merely read. It is a book to be lived with, argued over, and revisited, its questions echoing long after the final page is turned. Collapse. Civilizations do not last forever. No matter how powerful, advanced, or seemingly indestructible, history has shown time and time again that societies can crumble, sometimes swiftly, sometimes over centuries, but always with consequences that reshape the world. In Collapse. How societies choose to fail or succeed, Jared Diamond embarks on an extraordinary journey through history to uncover the reasons why some civilizations thrive while others vanish. The lessons he uncovers are not just historical curiosities, they hold urgent relevance for the fate of our own world today. Diamond meticulously examines societies that fell into ruin, from the deforestation that doomed Easter Island to the soil erosion that undermined the Norse settlements of Greenland. He reveals patterns of environmental mismanagement, political short-sightedness, and social inequality that, when left unchecked, spelled catastrophe. But Collapse is not merely a story of doom, it is also a study of resilience. Diamond contrasts failed civilizations with those that adapted to crises, such as Japan's Edo period, where sustainable forestry saved the nation from ecological disaster. The key distinction: some societies made the right choices, others did not. A particularly haunting message emerges from the book. The greatest threats to civilization are often self-inflicted. Many societies failed not because of inevitable external forces, but because they ignored warning signs, overexploited resources, and clung to traditions that no longer served them. Sound familiar? Diamond warns that the same destructive patterns are at play today, Climate change, deforestation, water scarcity, and economic inequality all echo the mistakes of past civilizations. Collapse is more than history. It is a wake-up call. Diamond forces us to ask, will we be the next failed civilization, or will we learn from history before it is too late? The answer, he argues, is in our hands. Zen and the art of motorcycle maintenance. Some journeys take you across landscapes, others take you deep into the mind. Zen and the art of motorcycle maintenance is both. What begins as a simple road trip evolves into an exploration of philosophy, self-discovery, and the pursuit of meaning. Robert Pirsig's book is more than a travelogue. It is a meditation on how we engage with the world, how we define value, and how we reconcile the rational with the intuitive. At the core of this book is the concept of quality, a force that defies strict definition, yet permeates everything we do. Pirsig challenges the conventional divide between science and art, reason and feeling, and shows how true understanding comes from seeing them not as opposites, but as complementary ways of knowing. Through the lens of motorcycle maintenance, he reveals that even the most mechanical tasks can become acts of deep engagement if approached with care and presence. It is not just about fixing machines, it is about cultivating a way of life that finds beauty in precision and meaning in effort. Yet beneath its philosophical depth, the book is also a personal story of a father and son traveling together, of a man haunted by his past self, and of the human struggle to find coherence in a world that often feels divided. Pirsig's narrative pulls the reader into an intellectual adventure that is both thrilling and unsettling, forcing us to question how we think, what we value, and what it truly means to live well. Few books have the power to reshape one's perspective, but Zen and the art of motorcycle maintenance does just that. It is a call to approach life with both thoughtfulness and passion, to see meaning where others see routine, and to embrace a philosophy that turns even the simplest acts into something profound. The Ancestor's Tale. Picture traveling back through time, not just centuries or millennia, but billions of years, retracing the steps of life itself to its very origins. The Ancestor's Tale by Richard Dawkins is no ordinary journey. Inspired by the Canterbury Tales, Dawkins leads us on a pilgrimage to meet our most ancient ancestors, unveiling the breathtaking story of evolution in reverse. With each step, we encounter the common ancestors we share with other species, from chimpanzees to fish, to the first single-celled organisms that sparked the chain of life. At the heart of the book is a profound realization: all life on Earth is connected. Dawkins masterfully demonstrates how the vast diversity of species emerged from a single shared lineage, guided by the forces of natural selection. He explains the intricate genetic evidence that reveals the branching patterns of evolution, showing how even the most seemingly unrelated creatures are linked by common descent. Along the way, he dismantles common misconceptions about evolution, replacing them with an awe-inspiring vision of life as a vast, interwoven tapestry. But this book is not just about science. It is about perspective. It forces us to see ourselves not as the pinnacle of evolution, but as one fleeting moment in a story far older and more intricate than we can fully comprehend. The tale is not just about us, it is about the entire web of life, and how every organism, past and present, is part of the same grand narrative. By the end of this journey, the world looks different. A simple tree, a bird in flight, or even the microbes within us are no longer just living things, but echoes of an ancient past. The Ancestor's Tale reminds us that to understand who we are, we must first understand where we came from. A story written not in ink, but in the very fabric of our DNA. The Tao of Physics. For centuries, science and spirituality have been seen as opposing forces, one rooted in cold, hard logic, the other in mystery and intuition. But what if they were not so different after all? In the Tao of Physics, Fritjof Capra makes a bold and mesmerizing claim: the discoveries of modern physics echo the wisdom of ancient Eastern philosophy. This is not just a book about science or religion. It is about the fundamental nature of reality itself. Capra takes us on a journey through the strange and counterintuitive world of quantum mechanics and relativity, showing how the principles of modern physics, interconnectedness, paradox, and uncertainty mirror the teachings of Taoism, Buddhism, and Hinduism. He explains how subatomic particles do not exist as isolated entities, but as part of an inseparable web of relationships, much like the Buddhist concept of dependent origination. The dual nature of light, which behaves both as a wave and a particle, finds an eerie parallel in the yin-yang duality of Taoism. Even the elusive void at the heart of quantum theory resonates with the Buddhist notion of emptiness, not as nothingness, but as a space of infinite potential. But the Tao of Physics is more than just an intellectual exercise. It is a challenge to the way we see the world. Capra argues that the mechanistic, reductionist view of Western science is incomplete. missing the deep unity that both physicists and mystics describe in their own languages. His message is clear. To understand the cosmos, we must embrace both reason and intuition, logic and wisdom, science and spirit. This book is an invitation to see beyond rigid categories and open our minds to a deeper, more holistic reality. It dares us to consider that the universe is not just a machine, it is a dance, a rhythm, a living expression of something far greater than we ever imagined. The power of now. Your mind is constantly pulling you into the past, or pushing you toward the future, reliving old regrets, worrying about what's next, chasing happiness that always seems just out of reach. But what if everything you seek, peace, clarity, even enlightenment, has been within you all along, hidden in the one place you rarely look, the present moment? In The Power of Now, Eckhart Tolle presents a radical yet simple truth. The key to a fulfilled life is learning to fully inhabit the now. Tolle argues that most suffering is not caused by external circumstances, but by our identification with the mind's endless stream of thoughts. We become trapped in narratives of fear, resentment, and longing, mistaking them for reality. By stepping back from this mental noise and observing it without attachment, we can break free from the grip of the ego, the false self that thrives on dissatisfaction and separation. The present moment, he explains, is the only reality that truly exists. Everything else, the past and future, is an illusion constructed by the mind. The book offers practical methods for awakening to this realization. Tolle emphasizes mindfulness, deep presence, and surrendering to what is, rather than resisting life as it unfolds. He describes how accessing this state of awareness dissolves anxiety, deepens relationships, and reveals an inner stillness that has always been there. He draws from spiritual traditions, but his message transcends religion. It is a universal guide to finding freedom from suffering. Reading The Power of Now is more than an intellectual exercise. It is an experience that challenges the way you perceive yourself and the world. If taken seriously, its insights have the potential to dismantle the very foundation of stress, fear, and self-doubt, leaving in their place a profound sense of peace and presence that cannot be shaken. The Stranger. What if life had no meaning, no grand purpose, no deeper reason for our existence? Would anything really change? The Stranger by Albert Camus is a haunting confrontation with the absurd, a story that forces us to question everything we assume about life, morality, and human nature. It follows Meursault, an ordinary man whose indifference to the world unsettles those around him. He does not cry at his mother's funeral. He does not pretend to feel emotions he does not have. And when he commits a senseless act of violence, society does not just judge his crime, it judges his very existence. At its core, The Stranger is an exploration of the absurd, the idea that human beings search for meaning in a universe that offers none. Meursault is not a villain, nor is he a hero. He simply is. He does not conform to societal expectations, and because of this, he becomes an outcast. His trial is less about his actions and more about his refusal to fake emotions, his unwillingness to pretend that life has meaning when he sees none. The world condemns him not because he is evil, but because he does not play by its unspoken rules. But The Stranger is not a book of despair. In the final moments before his execution, Meursault reaches a profound acceptance of life as it is. Raw, meaningless, and yet strangely liberating. He realizes that without illusions, without false hope, he is truly free. His story is not just a rejection of meaning, but a defiant embrace of existence itself. Camus does not offer easy answers. He holds up a mirror and asks, "What do you see?" And perhaps the most unsettling part is that in Meursault's indifference, in his raw and unfiltered view of the world, we might just catch a glimpse of ourselves. The mystery of consciousness. What is consciousness? It is the most intimate, undeniable fact of existence. We are aware, we think, we feel. Yet, despite centuries of philosophical inquiry and scientific progress, the nature of consciousness remains one of the greatest unsolved mysteries. In The Mystery of Consciousness, John Searle takes on this profound enigma, challenging both materialist reductionism and mystical explanations, guiding the reader through the debate with precision, wit, and intellectual depth. At its core, the book seeks to answer a deceptively simple question. How can subjective experience arise from mere biological processes? Searle critiques the dominant theories of mind, from artificial intelligence advocates who claim consciousness is nothing more than complex computation, to dualists who argue that the mind is independent of the physical world. He dismantles the notion that consciousness is an illusion, asserting instead that it is an irreducible feature of reality, one that must be explained rather than dismissed. Through sharp reasoning and thought-provoking examples, Searle introduces his theory of biological naturalism, proposing that consciousness is both caused by and realized in the brain's physical structure, much like liquidity emerges from the molecular interactions of water. He rejects the idea that a machine, no matter how complex, could ever be truly conscious unless it possesses the same biological mechanisms as a living brain. The significance of the mystery of consciousness lies in its ability to reframe the debate, cutting through jargon and ideological biases to reveal the real questions at stake. It forces us to confront the limits of human understanding. Are we even capable of grasping the true nature of consciousness? Searle doesn't provide easy answers, but he leaves the reader with a deeper appreciation of the mind's complexities and the intellectual courage to keep questioning. The Prince. Power is rarely won by virtue alone. It is seized, maintained, and wielded with cunning, strategy, and sometimes ruthless pragmatism. The Prince, Machiavelli's infamous treatise on power, strips away the illusions of morality in politics and exposes the raw mechanics of leadership. Written during a time of political upheaval in Renaissance Italy, this book is not just a guide for rulers. It is a timeless examination of human nature, ambition, and the forces that shape history. Machiavelli does not concern himself with how leaders should behave, but with how they must behave to maintain control. He argues that a ruler cannot afford to be bound by conventional morality. Rather, they must be adaptable, feared when necessary, and willing to deceive when the situation demands it. He famously states that it is better to be feared than loved, if one cannot be both, because fear is a more reliable tool for maintaining power. He warns against excessive cruelty, but also against naive kindness, which can lead to downfall. Yet, The Prince is more than a handbook for tyranny. It is a brutally honest exploration of the harsh realities of governance, showing that power is not sustained by ideals alone, but by strategic action. Machiavelli champions the idea of political realism, the belief that effective leadership requires a deep understanding of both human psychology and the unpredictability of fate. He emphasizes the importance of appearing virtuous, while being willing to act decisively behind the scenes. What makes The Prince so powerful is its unsettling relevance. Whether in politics, business, or daily life, Machiavelli's insights remain as sharp as ever. He forces us to confront uncomfortable truths about power, influence, and survival, challenging us to see the world not as we wish it to be, but as it truly is. The birth of tragedy. Why do we create art? What hidden forces drive the most profound expressions of human creativity? In The Birth of Tragedy, Friedrich Nietzsche offers a bold and revolutionary answer. Art emerges from the eternal struggle between two opposing forces, the Apollonian, representing order, reason, and harmony, and the Dionysian, embodying chaos, passion, and raw instinct. Through this lens, Nietzsche reinterprets the origins of Greek tragedy, revealing it as more than just entertainment, but as a powerful reflection of the human condition itself. Nietzsche argues that the greatest works of art arise from the balance of these two forces. The Apollonian provides structure, beauty, and clarity, while the Dionysian injects vitality, ecstasy, and the awareness of life's tragic nature. In ancient Greece, tragedy flourished because it embraced both, offering audiences a glimpse into the chaos of existence while still providing a sense of meaning. But Nietzsche laments that this delicate balance was lost, particularly with the rise of Socratic rationalism, which elevated reason above all else and suppressed the primal, life-affirming power of the Dionysian. This loss, Nietzsche contends, extends beyond art. It marks a fundamental shift in Western culture. By prioritizing reason at the expense of instinct, society has alienated itself from the deeper, more intuitive truths of existence. He suggests that reclaiming the Dionysian spirit is essential for rekindling the creative energy that gives life its fullest expression. Only by embracing both the ordered and the chaotic aspects of existence can humanity transcend the sterility of pure logic and rediscover the profound beauty of existence. At its core, The Birth of Tragedy is a call to reawaken the primal artistic spirit within us all. It challenges us to see art not as mere decoration, but as a vital force, one that holds the power to reconnect us with the deepest truths of life itself. The singularity is near. There is a moment in the future when everything will change, when human intelligence will merge with artificial intelligence, when biology will be rewritten by technology, and when the very nature of life itself will be transformed. In The Singularity is Near, futurist Ray Kurzweil presents a bold and meticulously reasoned vision of this coming revolution, arguing that we are racing toward an era of unimaginable progress, driven by the exponential growth of technology. At the heart of Kurzweil's argument is the idea that technological advancement is not linear, but accelerating. Computing power, artificial intelligence, biotechnology, and nanotechnology are evolving at an ever faster pace, leading to a moment, the singularity, when machines will surpass human intelligence. But rather than viewing this as a dystopian nightmare, Kurzweil sees it as an opportunity, a future in which humans transcend biology, merging with AI to become something more than we ever thought possible. Immortality, limitless intelligence, and an existence unbound by traditional constraints may no longer be science fiction, but an inevitable next step. Kurzweil supports his claims with detailed projections and historical data, showing how past technological revolutions, from the printing press to the internet, were just early signs of this accelerating trend. He explores how AI will reshape industries, how nanobots could repair and enhance our bodies at the cellular level, and how brain-computer interfaces might allow human consciousness to exist beyond the biological brain. The book forces us to ask profound questions. What does it mean to be human? How will society adapt to intelligence beyond its control? And are we prepared for a world where the line between organic life and machine intelligence dissolves? More than a prediction, the singularity is near is a challenge to rethink the future. Not as something that will happen to us, but as something we have the power to shape. If Kurzweil is right, the choices we make today will determine whether we become obsolete or evolve into something greater than we ever imagined. The Analects. What does it mean to live a good life? How can one cultivate wisdom, virtue, and harmony in a world of chaos? The Analects, a collection of the teachings and conversations of Confucius, has guided philosophers, rulers, and ordinary people for over 2,000 years. More than just a historical text, it is a profound blueprint for ethical living, offering timeless lessons on morality, leadership, and self-cultivation. At its core, the Analects teaches that true wisdom is not found in abstract theories, but in the way we treat others, the discipline we cultivate within ourselves, and the sense of duty we uphold towards society. Confucius emphasizes the concept of ren, a deep sense of humanness, compassion, and benevolence. He argues that virtue is not innate, but must be actively practiced through daily actions, from respecting one's parents to leading with integrity. Social harmony, he insists, does not come from rigid laws, but from individuals embodying moral excellence. In his view, a great leader does not rule through force, but through virtue, inspiring others to follow naturally. This idea of governance through moral example remains just as relevant in today's world, where power is too often wielded without responsibility. Yet the Analects is not just about leadership, it is about the inner life of the individual. Confucius teaches that wisdom begins with self-awareness. He warns against arrogance, encourages constant learning, and urges people to seek improvement rather than perfection. His words push us to ask, are we living with integrity? Are we fulfilling our responsibilities to others? Are we striving to be better than we were yesterday? Though written in ancient China, the wisdom of the Analects transcends time and culture. It reminds us that character is destiny and that true fulfillment is not found in wealth or power, but in the pursuit of virtue and understanding. The Black Swan. Imagine if everything you thought you knew about risk, prediction, and success was wrong. What if the most important events in history, those that shape economies, revolutions, and even your own life, were completely unpredictable? In The Black Swan, Nassim Nicholas Taleb dismantles our illusions of certainty, arguing that the most significant changes in the world are driven not by what we can foresee, but by rare, unexpected events that defy conventional wisdom. A black swan is an event that is highly improbable, massively impactful, and only seems obvious in hindsight. From the rise of the internet to financial crashes, from the 9/11 attacks to the emergence of billion-dollar companies, history is shaped not by steady, predictable progress, but by sudden, game-changing shocks. The problem? Humans are wired to see patterns, to believe we can anticipate the future based on the past. But in a world of randomness and complexity, our forecasts are little more than comforting illusions. Taleb exposes how experts, economists, and decision-makers routinely fail because they rely on flawed models that ignore these unpredictable shocks. Worse, we rewrite history after the fact, convincing ourselves that these events were inevitable. The reality, however, is far messier. He argues that instead of trying to predict black swans, we must learn how to survive and even thrive in a world dominated by uncertainty. This means embracing anti-fragility, building systems and mindsets that gain from disorder rather than being shattered by it. The Black Swan is more than a book about randomness. It is a call to change how we think about the world. It forces us to acknowledge the limits of knowledge, abandon false confidence, and prepare for the unexpected. In doing so, it doesn't just explain uncertainty, it teaches us how to live within it. The gene, an intimate history. What if the blueprint of who you are, your traits, your health, your very identity, was hidden within microscopic strands of information? The Gene, an intimate history by Siddhartha Mukherjee is a sweeping journey through the science of genetics, unraveling the profound forces that shape human life. From the earliest theories of inheritance to the cutting-edge breakthroughs of modern gene editing, this book explores not only the science behind our DNA, but also the ethical and philosophical questions it raises. Mukherjee traces the history of genetics back to Gregor Mendel's pea plant experiments, which first revealed patterns of inheritance. He then moves through the 20th century discoveries of DNA's structure and function, highlighting key moments like Watson and Crick's double helix model and the groundbreaking sequencing of the human genome. Yet this is not just a scientific chronicle, it is an intimate story, one that intertwines history with deeply personal reflections on mental illness in Mukherjee's own family, illustrating the complex and often unpredictable role genes play in human destiny. One of the book's most powerful ideas is how genes are not just passive carriers of information, but dynamic players in evolution, disease, and identity. Mukherjee explores how genetic mutations drive both diversity and disorder, how nature and nurture interact, and how the ability to manipulate genes raises profound moral dilemmas. With CRISPR and gene therapy now within reach, humanity stands on the brink of an era where we can rewrite the very code of life. But should we? The Gene is not just a book about biology. It is a reflection on what it means to be human. It forces us to confront the extraordinary power we wield over life itself, and challenges us to consider the responsibility that comes with such knowledge. The wealth of nations. What makes a nation truly prosperous? Is it gold locked away in vaults, or is it something far more dynamic, something woven into the very fabric of human interactions? The Wealth of Nations by Adam Smith is not just a book about economics, it is a revelation about how the world works. Written in 1776, yet still strikingly relevant today, this monumental work laid the foundation for capitalism and changed the way we understand markets, trade, and prosperity itself. At the heart of Smith's argument is the idea of the invisible hand, the notion that when individuals act in their own self-interest, they unintentionally contribute to the greater good of society. A baker does not provide bread out of charity, but because he wishes to earn a living. Yet in doing so, he feeds the community. This natural order, Smith argues, creates a self-regulating system where supply, demand, and competition drive efficiency and innovation. Unlike rigid, government-controlled economies, free markets encourage growth by allowing individuals the freedom to pursue their own success. But Smith does not advocate for unchecked greed. He warns of monopolies, corruption, and excessive government interference, all of which can strangle economic progress. He champions the division of labor, showing how specialization, each worker focusing on a specific task, leads to increased productivity and wealth. A pin factory, for instance, can produce far more when tasks are divided among workers, rather than attempted by one person alone. This principle, seemingly simple, underpins the explosive rise of industrial economies. More than 2 centuries later, The Wealth of Nations remains a cornerstone of economic thought. It is not just a book for economists. It is for anyone who wants to understand why some nations thrive while others struggle, and how human ingenuity, when set free, can shape the destiny of civilization itself. The Righteous Mind. Why do good people disagree so fiercely about politics, religion, and morality? Why do our moral convictions feel so obvious to us, yet utterly incomprehensible to those on the other side? In The Righteous Mind, social psychologist Jonathan Haidt unravels the deep psychological forces that shape human morality, revealing that our moral reasoning is not as rational as we like to believe. Instead of carefully weighing facts and logic, we are guided by instinctive, emotional responses. Intuition first, reasoning second. Haidt introduces the concept of the moral foundations theory, which identifies 6 fundamental moral instincts: care, fairness, loyalty, authority, sanctity, and liberty. Liberals, conservatives, and libertarians do not just disagree on policies, they prioritize these moral values differently, leading to profound misunderstandings. Liberals emphasize care and fairness, focusing on harm and equality. Conservatives balance all 6 values, placing more weight on loyalty, authority, and sanctity. Libertarians, meanwhile, elevate liberty above all else, distrusting authority in favor of individual freedom. These moral matrices explain why political and ideological debates often feel like people speaking different moral languages. But Haidt goes even further, showing that our moral instincts are not just cultural, but deeply rooted in evolution. Morality did not emerge to help individuals seek truth. It evolved to strengthen group cohesion, helping societies survive. This tribal nature of morality means we are hardwired to favor our side and distrust outsiders, which fuels political polarization and cultural divisions. Yet, by understanding this, we can begin to bridge the gaps that divide us. The Righteous Mind is not just a book about moral psychology. It is a blueprint for understanding human conflict. If we recognize the invisible forces shaping our moral judgments, we can step beyond blind partisanship and engage with others in a way that fosters true understanding rather than endless division. The moral landscape. Your entire understanding of morality, what is right, what is wrong, what makes a good life, may not be just a matter of opinion. In The Moral Landscape, neuroscientist Sam Harris argues that morality is not the domain of religion or philosophy alone, but something science can, and must, examine with the same precision as medicine or physics. If human well-being can be measured, then moral truth is not relative. It is something we can discover. Harris dismantles the common belief that morality is purely subjective, showing that human flourishing is grounded in measurable realities. Just as physical health depends on nutrition and biology, well-being depends on psychological and social conditions that science can study. He argues that some actions, policies, and cultures objectively promote human happiness, while others increase suffering. A society that values education, freedom, and human rights is not just better in an abstract sense, It is demonstrably superior to one that enforces oppression and ignorance. He introduces the idea of a moral landscape, where peaks represent societies or ways of living that maximize well-being, while valleys represent those that cause unnecessary suffering. The problem, he argues, is that religious dogma, moral relativism, and political ideology often blind us to these objective moral facts. Instead of relying on tradition or divine command, we should turn to evidence-based reasoning to determine the best ways to structure laws, policies, and social norms. By merging science and morality, the moral landscape forces us to reconsider the foundation of our ethical beliefs. If moral progress can be objectively measured, then it is not just an abstract goal, it is a responsibility. 21 lessons for the 21st century. What does it take to survive the 21st century? In a world where technology evolves at breakneck speed, where artificial intelligence, climate change, and geopolitical instability redefine the rules of existence, how do we make sense of it all? 21 Lessons for the 21st Century by Yuval Noah Harari is a piercing examination of the challenges that will shape our future. Unlike Sapiens, which looks at humanity's past, or Homo Deus, which speculates about the distant future, this book is a call to action for the present. It forces us to confront the defining issues of our time, from the rise of fake news and mass surveillance to the collapse of meaning in an era of automation. Harari organizes the book into 21 distinct lessons, covering politics, technology, war, religion, and education, among other pressing concerns. He warns that liberal democracy is no longer the unchallenged global force it once was, as nationalism and authoritarianism gain momentum. He argues that AI and biotechnology will not just reshape economies, but also redefine what it means to be human. With algorithms making more decisions on our behalf, will free will become obsolete? With machines replacing workers, what happens to economic stability? These are not distant possibilities, they are unfolding before us right now. Yet Harari is not just sounding the alarm. He offers a roadmap for navigating uncertainty. He emphasizes the importance of critical thinking, adaptability, and the ability to filter truth from misinformation. He challenges us to rethink outdated educational systems and embrace lifelong learning in a world where knowledge itself is constantly shifting. Above all, he argues that clarity, not blind optimism or fear, is our best weapon in an age of overwhelming complexity. In the end, 21 Lessons for the 21st Century is a wake-up call, urging us to engage with the forces shaping our world before they shape us. It does not offer easy answers, but it provides the intellectual tools needed to survive and perhaps even thrive in the decades ahead. The road to reality. What if the deepest secrets of the universe could be laid out before you, revealing an intricate web connecting the tiniest particles to the vast fabric of space-time? In The Road to Reality, renowned physicist Roger Penrose takes readers on a breathtaking journey through the mathematical foundations and physical laws that define our reality. This is not just a book about physics. It is an invitation to glimpse the profound structure of existence itself. Penrose begins by introducing the essential mathematical tools needed to navigate the cosmos, from complex numbers to manifolds and tensors. These are not just abstract concepts. They are the language of reality, the very framework through which we understand the universe. Building upon this foundation, he unpacks the great revolutions of modern physics, Einstein's relativity, the bizarre probabilities of quantum mechanics, and the deep conflicts that arise when these theories collide. He grapples with paradoxes that challenge our understanding, such as the incompatibility between the smoothness of spacetime and the uncertainty of quantum particles, and questions whether our current models are truly complete. What sets The Road to Reality apart is its fearless critique of mainstream physics. Penrose challenges widely accepted interpretations of quantum mechanics, proposing his own ideas on wave function collapse and even speculating on the role of consciousness in measurement. He explores alternative frameworks, including twistor theory, a mathematical approach he developed to rethink the fundamental nature of space and time. Unlike many popular science books, which simplify or speculate wildly, Penrose's work remains deeply rigorous, demanding intellectual engagement while rewarding readers with a richer, more nuanced understanding of the cosmos. For those willing to follow its challenging path, The Road to Reality is more than just an exploration of physics. It is an invitation to stand in awe of the mathematical harmony that governs the universe. The myth of Sisyphus. Life offers no explanations, no grand design, no built-in purpose. So why do we keep going? The Myth of Sisyphus by Albert Camus is a fearless confrontation with this unsettling reality, forcing us to question whether existence itself is an act of defiance. Rather than offering comforting answers, Camus challenges us to stare into the void and decide for ourselves. Is life still worth living when stripped of illusions? At the heart of Camus's philosophy is the concept of the absurd, the fundamental contradiction between our relentless search for meaning and the universe's indifferent silence. Unlike other philosophers who attempt to resolve this tension through faith or reason, Camus insists that we must embrace it. To illustrate this, he turns to the Greek myth of Sisyphus, condemned to roll a boulder up a hill for eternity, only to watch it roll back down each time. His struggle is endless, devoid of victory or escape. But does that make his existence meaningless? Camus argues that Sisyphus is not a tragic figure, but a rebellious one. In accepting his fate without seeking false hope or resignation, he finds a strange form of liberation. He is fully aware of the absurdity of his condition, yet he chooses to persist. And in that persistence, he reclaims his freedom. One must imagine Sisyphus happy, Camus writes, not because his suffering is erased, but because he has embraced it without illusion. This philosophy extends beyond myth into our daily lives. We chase careers, relationships, ambitions, hoping they will provide lasting fulfillment. Yet time and again, we find ourselves in the same existential loop, pushing our own metaphorical boulders uphill. The absurd is not an abstract concept, it is the reality of being human. But instead of succumbing to despair, Camus challenges us to revolt, not through resignation or escape, but by living fully, without expecting the universe to justify itself. The myth of Sisyphus is not a book of comfort, it is a book of defiance. It does not offer meaning, but demands that we create our own. In embracing the absurd, we reclaim our power. And in that moment of realization, existence is no longer a burden, it becomes a choice. The Master and His Emissary, the way we understand the world may be fundamentally broken. In The Master and His Emissary, Ian McGilchrist presents a groundbreaking exploration of the human brain and its far-reaching consequences for society. This is not just another book about left brain versus right brain. It is an urgent warning that civilization itself is being shaped, and perhaps distorted, by the dominance of one hemisphere over the other. McGilchrist argues that the brain is divided into two distinct modes of perception. The right hemisphere, the master, sees the world as a rich, interconnected whole, embracing nuance, meaning, and the complexity of human experience. The left hemisphere, the emissary, focuses on categorization, abstraction, and control, reducing reality to a set of manipulable parts. Both are essential, but something has gone terribly wrong. Over centuries, the left hemisphere has seized power, narrowing human vision, prioritizing efficiency over wisdom, and eroding our ability to engage with the world in a deeply meaningful way. This imbalance, McGilchrist suggests, is reflected everywhere. In modern science, which often reduces life to mechanical processes. In politics, which prioritizes rigid ideologies over human complexity. And in technology, which isolates us from lived experience. By overvaluing analysis and disregarding intuition, we have built a society that is increasingly fragmented, disconnected, and unable to grasp the full depth of existence. This is not just a theory, it is a call to awareness. Understanding the battle between these two ways of knowing may be the key to reclaiming a more balanced, meaningful life. The Master and His Emissary challenges us to see beyond our intellectual blind spots, urging us to restore the harmony that has been lost. The question is, will we listen before it's too late? The denial of death. We spend our lives building, striving, and searching for meaning, yet beneath it all lurks a truth we refuse to fully confront. We are going to die. In The Denial of Death, Ernest Becker delivers a staggering revelation. Human civilization itself is built on the unconscious fear of mortality. Every belief system, every ambition, and even our very sense of self is, in some way, an attempt to escape the unbearable awareness of our own impermanence. Becker argues that while we share a biological existence with animals, we are unique in our ability to reflect on our mortality. This awareness creates an unbearable contradiction. We are creatures who yearn for significance, yet we are finite, fragile, and destined to be forgotten. To cope, we construct symbolic worlds that promise transcendence. Whether through religion, art, nationhood, or even the pursuit of wealth and status, we seek ways to convince ourselves that we matter, that our existence has meaning beyond the grave. Yet this denial of death is both our greatest strength and our deepest flaw. It drives us to create, to achieve, to love, but it also fuels fanaticism, war, and a desperate need to prove that our chosen path is the correct one. Becker explores how human beings latch onto cultural immortality projects, attempts to outlive our physical selves through legacy, ideology, or heroism. The tragedy, however, is that no illusion can fully shield us from the truth. The more we deny death, the more it controls us. But if we accept this truth, what then? Becker does not offer easy comfort, but he does hint at a path forward. A life lived with courage, one where we acknowledge our insignificance, yet strive to create meaning anyway. Not as a shield against death, but as an act of defiance in the face of it. The age of surveillance capitalism. There was a time when our personal thoughts, habits, and desires were our own. That time is over. In the age of surveillance capitalism, Shoshana Zuboff exposes the hidden economic system that has transformed human experience into a raw material for profit. In this new age, the most valuable resource isn't oil or gold. It's you. Zuboff traces how tech giants, led by companies like Google and Facebook, pioneered a radical shift in capitalism. Unlike traditional businesses that profit by selling goods or services, surveillance capitalists extract behavioral data, your clicks, searches, locations, and even emotions, then use it to predict and manipulate your future actions. Every app, every website, and every smart device is a silent observer, feeding a system designed to control human behavior at scale. The book reveals how this new power dynamic has eroded privacy, freedom, and democracy itself. Companies no longer just respond to our needs, they shape them, nudging us toward decisions that maximize their profits. Algorithms determine what we see, what we buy, and even how we vote. The result is an invisible architecture of influence, one that exploits psychological vulnerabilities to keep us engaged, addicted, and predictable. Yet Zuboff argues, this is not an inevitable future. Surveillance capitalism is not a law of nature. It is a choice made by corporations and governments, one that can be challenged and reversed. But to do so, we must first recognize the reality we live in. This book is not just a warning, it is a wake-up call. It forces us to confront an uncomfortable truth. In the digital age, freedom will not be lost in one sweeping moment. It will disappear click by click unless we fight to reclaim it. The information. Before humanity tamed fire, built cities, or sent rockets into space, we did something far more fundamental. We communicated. In the information, James Gleick unravels the astonishing history of how information has shaped civilization, from the earliest spoken languages to the digital age that now defines our world. But this is not just a history of communication. It is the story of how information itself, as a measurable and powerful force, has transformed reality. Gleick begins by tracing the origins of language, writing, and the first methods of recording knowledge. From the invention of the alphabet to the printing press, each leap forward in communication has reshaped human thought, accelerating progress in ways our ancestors could never have imagined. But the book's most profound insight comes with the realization that information is not just something we create. It is a fundamental structure of the universe. Mathematics, genetics, quantum mechanics, and even consciousness itself can be understood as systems of information processing. One of the book's most striking revelations is how the modern world is built upon a hidden revolution, the rise of information theory. The work of Claude Shannon, the father of digital communication, introduced a new way of thinking about knowledge, reducing language, images, and even DNA to binary code. This breakthrough paved the way for computers, artificial intelligence, and the vast networks that now define our existence. Every message we send, every search we make, every decision we take is part of an invisible web of information that connects, influences, and shapes us in ways we barely comprehend. In the end, the information is not just about history. It is about what it means to live in an age where data is more abundant than ever. As we drown in an ocean of signals, the question is no longer how we communicate, but whether we truly understand the power of the information that now defines our reality. The sixth extinction, the greatest catastrophe in Earth's history, is not being caused by an asteroid, a supervolcano, or an ice age. It is being caused by us. The Sixth Extinction by Elizabeth Kolbert is a sobering, meticulously researched account of how human activity is driving the planet toward an unprecedented biological crisis. Unlike the 5 previous mass extinctions, which wiped out vast swathes of life due to natural disasters, this one is unfolding at the hands of a single species, ours, and the consequences will be unlike anything the Earth has ever seen. Kolbert takes the reader on a global journey, from the rainforests of the Amazon to the Great Barrier Reef, chronicling the decline of species in real time. She examines how climate change, habitat destruction, and ocean acidification are accelerating extinction rates to levels unseen in millions of years. Through gripping narratives, she introduces us to scientists on the front lines, uncovering chilling evidence that we are not just altering ecosystems, we are permanently rewriting the story of life itself. One of the book's most unsettling revelations is that even small disruptions can trigger cascading effects across entire ecosystems. Amphibians, once among the most resilient creatures on Earth, are vanishing due to an unstoppable fungal plague spread by human travel. Coral reefs, the cradles of marine biodiversity, are crumbling as the oceans absorb more carbon dioxide than they have in millions of years. Even species we take for granted, birds, insects, mammals, are disappearing at rates hundreds of times higher than normal. The pattern is undeniable. Human progress has become the driving force of destruction. Kolbert does not offer false hope or easy solutions. Instead, she presents a stark, unflinching truth. We are shaping the future of the planet in ways we barely comprehend. Whether humanity will recognize its role in this crisis before it is too late remains an open question. But the sixth extinction leaves no doubt. This is a turning point in Earth's history, and we are the ones writing its next chapter. The vital question: life is not just a product of chemistry, it is shaped by energy. In The Vital Question, biochemist Nick Lane takes on one of the deepest mysteries in science: why life is the way it is. While we understand the building blocks of life, DNA, proteins, and cells, the question of how simple molecules first sparked into complex organisms remains unanswered. Lane argues that the key is energy, specifically the flow of energy that sustains life at its most fundamental level. At the heart of the book is a bold theory. Life emerged from deep-sea hydrothermal vents, where chemical gradients provided the energy needed to transform simple molecules into self-replicating life forms. More than just a new take on abiogenesis, Lane's argument explains why life on Earth evolved in the incredibly specific way it did, why cells have membranes, why complex life relies on mitochondria, and even why aging and death are inevitable. One of Lane's most profound insights is how energy flow dictated the transition from simple bacteria to the complex eukaryotic cells that make up all animals and plants. Unlike bacteria, which remained small and simple for billions of years, eukaryotes broke free from evolutionary stagnation due to their acquisition of mitochondria, tiny power plants that supercharged their metabolism and enabled the explosion of complexity. This energy revolution set the stage for everything from multicellular life to consciousness itself. The Vital Question doesn't just explain life, it reshapes our understanding of what life must be, both on Earth and beyond. If energy flow determines biology, then the search for extraterrestrial life must focus not just on water and chemistry, but on the conditions that allow energy to shape complexity. This book challenges everything we assume about existence, making us question not only how life began, but what it truly means to be alive. The order of time. Time feels like the one constant in our lives, unstoppable, universal, and absolute. But what if everything we believe about time is wrong? In The Order of Time, physicist Carlo Rovelli dismantles our deepest assumptions about time's nature, revealing a reality far stranger than we ever imagined. Rovelli takes us on a journey through Einstein's relativity and quantum mechanics, showing that time is not a rigid flow, but a shifting, fluid entity. A clock on a mountain runs faster than one in a valley. The distinction between past and future begins to blur. And at the most fundamental level of physics, time may not even exist in the way we experience it. But this book is not just about science. It's about how these discoveries reshape our understanding of existence. If time is not an absolute force, what does that mean for our memories, our choices, and the meaning we assign to our lives? Rovelli argues that time is not something external. It's something we create, a way of making sense of an ever-changing universe. Reading The Order of Time is like stepping outside the framework of reality itself. It challenges you to rethink not just time, but the way you experience every moment of your life. And once you grasp its revelations, the world and your place in it will never look the same again. The hidden reality. What if the universe you see, the stars, the galaxies, even the fabric of space and time, is just one of countless others? In The Hidden Reality, physicist Brian Greene takes us on a mind-expanding journey into the frontier of modern physics, where the concept of a multiverse is not just science fiction, but a serious possibility. If true, this idea would upend our very understanding of existence, forcing us to reconsider what it means to be part of reality itself. Greene explores multiple theories that suggest our universe may be just one among many. Some arise from the mathematics of quantum mechanics, where every possible outcome of an event could be realized in separate, branching universes. Others emerge from string theory, which posits extra spatial dimensions hidden beyond our perception, dimensions that could house entire parallel worlds. Cosmology, too, offers its own evidence. If space is infinite, then somewhere, far beyond our cosmic horizon, there may be an exact copy of you, reading this very sentence. But the book does more than just present wild possibilities. It methodically walks through the science that makes them plausible. Greene explains how inflationary cosmology suggests endless universes bubbling into existence, and how holographic principles hint that our three-dimensional reality might be a mere projection of a deeper, underlying structure. Through clear and engaging language, he transforms mind-bending physics into an intellectual adventure, making us question the very nature of existence. If reality is far more vast and complex than we ever imagined, what does that mean for our place within it? The Hidden Reality invites us to step beyond the boundaries of what we once thought possible, challenging us to see the universe and ourselves in an entirely new way.
The story of Homo sapiens began 300,000 years ago in prehistoric Africa, during a time when the world was unpredictable and survival was uncertain. Our ancestors were one of many human species sharing the planet, yet only Homo sapiens endured. How did we survive while others vanished? What allowed us to adapt to an ever-changing environment? To answer these questions, we must look further back in time. Around 6 million years ago, our evolutionary journey began when early hominins, upright walking ancestors, split from the last common ancestor we shared with chimpanzees. Evolution is rarely simple, and over millions of years, multiple human-like species emerged. Among them were Homo habilis, one of the first toolmakers, and Homo erectus, who spread from Africa into Europe and Asia. Yet, Homo sapiens would follow a distinct path. Our species wasn't just defined by physical traits, but by remarkable mental capabilities. The human brain developed as an engine for problem-solving, abstract thought, and collaboration. These abilities gave rise to language, symbolic thinking, and cultural practices that allowed us to connect and innovate. Early evidence of this transformation can be seen in tools, cave art, and even burial rituals, markers of a species beginning to think beyond survival. Homo sapiens also differed physically. Our bodies were lean and built for endurance, which allowed us to thrive in diverse environments, from Africa's open savannas to more challenging climates encountered during migrations. Unlike our Neanderthal cousins, who were robustly built for Ice Age Europe, we relied on adaptability and ingenuity to overcome obstacles. Our species wasn't alone in the world. For tens of thousands of years, Homo sapiens shared the planet with other human species, including Neanderthals in Europe and Denisovans in Asia. These interactions were not purely competitive. Genetic evidence shows moments of interbreeding. Today, traces of Neanderthal and Denisovan DNA remain in modern humans, a legacy of these ancient encounters. Migration was a turning point in our history. Around 60,000 to 100,000 years ago, small groups of Homo sapiens began leaving Africa, spreading gradually across the globe. As they moved into new and often harsh environments, they adapted with remarkable creativity, crafting tools, clothing, and strategies to survive. From the frozen tundras of Siberia to the dense forests of Southeast Asia, early humans demonstrated an unparalleled ability to adjust to their surroundings. Around 40,000 years ago, something extraordinary occurred, a burst of cultural and technological innovation. This period saw the creation of intricate cave art, musical instruments, and advanced tools. These developments weren't just practical, they hinted at a growing ability for abstract thought, storytelling, and deeper social connections. These advancements strengthened communities and laid the foundation for more complex societies. Despite these successes, other human species began to disappear. By 40,000 years ago, Neanderthals were extinct, followed by Denisovans and other hominins. Why did Homo sapiens survive when others didn't? It was likely a combination of factors: our adaptability, ability to cooperate, and luck. The journey of Homo sapiens is one of survival, innovation, and transformation. Each challenge we faced shaped our species, refining the traits that define us today. By understanding our past, we gain a clearer picture of how we came to dominate the planet and continue to adapt to the challenges of an ever-changing world. The rise of early civilizations marks a pivotal turning point in human history. This transformation wasn't a single event, but a gradual process unfolding over thousands of years across diverse regions. It began when humans transitioned from nomadic hunter-gatherer groups to settled communities, establishing cities, governments, and systems of writing. This shift laid the groundwork for agriculture, politics, trade, technology, and the arts. One of the primary drivers of civilization was the development of agriculture. Around 10,000 years ago in the Fertile Crescent, a region encompassing parts of modern-day Iraq, Syria, and Turkey, humans began cultivating crops and domesticating animals. The area's climate and geography were ideal for growing staples like wheat and barley. For the first time, communities could produce surplus food, enabling them to settle in one place and form permanent settlements. Agriculture also demanded keen observation of seasonal cycles, giving rise to early systems of knowledge and record-keeping. Over time, these practices evolved into writing systems, such as cuneiform in Mesopotamia, used to track grain stores and transactions. The organization required for farming also spurred the development of governance, as growing populations needed leaders to manage resources, settle disputes, and defend against threats. Mesopotamia, often called the cradle of civilization, offers a vivid example of this evolution. Along the Tigris and Euphrates rivers, the Sumerians built cities like Uruk, complete with sophisticated architecture and monumental temples called ziggurats. Sumerian society was hierarchical, with kings and priests at the top, followed by merchants, artisans, farmers, and slaves. This specialization allowed people to focus on crafts, trade, and administration, leading to innovations like the wheel and law codes, such as the famous Code of Hammurabi. Similarly, ancient Egypt thrived along the Nile River. The Nile's predictable flooding deposited nutrient-rich silt, supporting abundant agriculture and acting as a natural highway for trade and communication. Egyptian civilization was highly centralized under powerful pharaohs, who were regarded as both kings and gods. Their construction of monumental pyramids demonstrated their authority and left enduring legacies. In the Indus Valley, the Harappan civilization displayed remarkable urban planning. Cities like Harappa and Mohenjo-Daro featured grid-like streets, advanced drainage systems, and standardized weights and measures, reflecting a highly organized society. Though much about the Harappans remains unknown, their engineering achievements and trade networks connected them with other civilizations like Mesopotamia. Meanwhile, in China, early civilizations flourished along the Yellow River. The Shang dynasty, one of China's earliest, advanced metallurgy with intricate bronze work and established a complex social structure. Early Chinese writing and the concept of the mandate of heaven, where a ruler's authority was seen as divinely ordained, shaped Chinese governance for centuries. These early civilizations shared common challenges, managing resources, defending against threats, and organizing increasingly complex societies. Trade routes linked them, facilitating the exchange of goods, technologies, and ideas. Such networks not only enriched these societies, but also laid the foundations for an interconnected world. The rise of civilizations was shaped by geography, resources, and human ingenuity. Yet, as these societies grew, they faced challenges: internal conflicts, invasions, and environmental changes. Despite these difficulties, humanity continued to adapt, innovate, and build the foundations of modern civilization. The Sumerians and Mesopotamia. The Sumerians, inhabitants of ancient Mesopotamia, are widely regarded as pioneers of human civilization. Mesopotamia, meaning the land between two rivers, lay between the Tigris and Euphrates rivers in modern-day Iraq. This fertile region, often called the Fertile Crescent, was the cradle of some of humanity's most transformative innovations. Thriving from around 4500 BCE to 1900 BCE, the Sumerians profoundly shaped early societies through advances in writing, governance, city building, and trade. Central to Sumerian civilization was the concept of the city-state, an independent political unit that redefined social organization. Unlike empires governed by central authorities, each Sumerian city-state, such as Ur, Uruk, and Eridu, had its own ruler, patron deity, and identity. Uruk, often regarded as one of the world's first true cities, reached a population of approximately 50,000 at its peak, setting the stage for urban life as we know it. The invention of cuneiform writing is among the Sumerians' most enduring legacies. Initially developed for recording economic transactions, cuneiform evolved to document laws, myths, hymns, and historical events. Writing not only streamlined administrative functions, but also preserved the Sumerian culture for future generations. The Epic of Gilgamesh, one of the earliest known works of literature, provides insights into their worldview and values, revealing a sophisticated spiritual and cultural life. Religion permeated every aspect of Sumerian society. Each city-state was devoted to a patron deity, and the Sumerians believed their gods controlled all aspects of existence, from natural phenomena to human affairs. Towering ziggurats served as both religious and administrative hubs, symbolizing the connection between heaven and earth. Priests played central roles in society, mediating between the gods and the people. Sumerian religious principles also influenced their legal systems. The Code of Ur-Nammu, the oldest known legal code, predates the Code of Hammurabi and emphasized justice through compensation rather than retribution. The codification of laws marked a transition from tribal customs to organized governance, reflecting the increasing complexity of Sumerian society. Agriculture was the backbone of Sumerian civilization, sustaining growing populations and fostering societal growth. By developing an advanced irrigation system, they harnessed the Tigris and Euphrates rivers to offset the region's irregular rainfall. This enabled the cultivation of staple crops such as barley, wheat, and dates. Agricultural surpluses supported population growth and societal specialization, allowing individuals to focus on crafts, trade, and governance. Trade played a crucial role in the Sumerian economy. While Mesopotamia was fertile, it lacked essential resources like timber, metals, and stone. To acquire these, the Sumerians established extensive trade networks that stretched to the Indus Valley and the eastern Mediterranean. These networks facilitated the exchange of goods such as textiles, grain, and crafted items for copper, gold, and other valuable resources. This interconnected trade system was an early precursor to global commerce. Despite shared cultural and religious practices, Sumerian city-states often competed for dominance over the region's fertile plains. These rivalries are documented in the Sumerian king list, which records the reigns of rulers and shifts in political power. Figures like Gilgamesh, who became legendary through epic poetry, exemplify the enduring impact of these early leaders. The decline of Sumerian civilization was gradual, driven by external pressures from neighboring peoples such as the Akkadians and Amorites. The rise of the Akkadian Empire under Sargon the Great in the 24th century BCE marked the beginning of the end for Sumerian independence. However, the Sumerians' cultural and technological achievements persisted, influencing successor civilizations like the Babylonians and Assyrians. The Sumerians laid the foundation for key aspects of modern civilization, including writing, law, organized religion, urbanization, and trade. Their innovations transformed Mesopotamia into a hub of cultural and technological progress, shaping the trajectory of human history. Their legacy, rooted in ingenuity and adaptability, continues to resonate in the modern world. Egypt and the Pharaohs. Ancient Egypt, with its monumental pyramids, majestic temples, and powerful rulers, stands as one of the most remarkable civilizations in human history. At its heart was the pharaoh, a leader revered not only as a political figure, but also as a living deity. For over 3,000 years, this civilization thrived along the Nile River, leaving behind an enduring cultural and architectural legacy. The Nile was the lifeblood of Egypt, its annual floods depositing nutrient-rich silt that enabled the cultivation of abundant crops. This agricultural bounty sustained the economy and fostered the growth of a highly sophisticated society. Flanked by vast deserts, the Nile provided both sustenance and protection, allowing Egypt to develop a unique culture centered on prosperity, spirituality, and centralized governance. The pharaoh held a dual role, embodying both temporal power and divine authority. Regarded as the intermediary between the gods and the people, the pharaoh's responsibilities extended beyond governance to maintaining cosmic harmony, or ma'at, a principle symbolizing truth, balance, and order. Monumental projects like the pyramids were more than grand tombs. They were profound expressions of the pharaoh's divine status and his eternal journey to the afterlife. Ma'at was central to Egyptian life, and the pharaoh was its ultimate guardian. Upholding Ma'at required ensuring justice, maintaining the Nile's fertility, and honoring the gods through rituals and grand construction projects. Failure to preserve Ma'at was believed to invite chaos, or isfet, jeopardizing the natural and social order. This belief unified the people and reinforced the authority of the pharaoh. Among Egypt's many rulers, Ramses II, or Ramses the Great, stands as one of the most iconic. During his reign in the New Kingdom, Ramses expanded Egypt's territory through military campaigns and commissioned grandiose building projects. The temples of Abu Simbel, carved into southern cliffs, exemplify his architectural legacy and devotion to the gods. His long rule brought stability and prosperity, solidifying Egypt's status as a dominant ancient power. In contrast, Hatshepsut, one of Egypt's few female pharaohs, is celebrated for her contributions to trade, architecture, and the arts. Ruling in the 15th century BCE, she revitalized trade routes, bringing wealth and resources to Egypt, and oversaw the construction of magnificent structures like her mortuary temple at Deir el-Bahari. Often depicted wearing the traditional regalia of a male pharaoh, including the ceremonial false beard, Hatshepsut challenged traditional notions of leadership and left an indelible mark on Egyptian history. Another notable ruler was Akhenaten, known for his radical religious reforms in the 14th century BCE. He introduced monotheism, focusing worship on Aten, the sun disk, and relocated the capital to Amarna. This departure from centuries of polytheistic tradition caused cultural and religious upheaval. After his death, his reforms were reversed and his monuments defaced, but his reign remains a fascinating episode in Egyptian history. His son, Tutankhamun, is best remembered for restoring traditional practices and for the discovery of his richly adorned tomb. The construction of the pyramids remains one of ancient Egypt's most enduring achievements. Built during the Old Kingdom, structures like the Great Pyramid of Giza exemplify the Egyptians' mastery of engineering, mathematics, and organization. Commissioned by Pharaoh Khufu, the Great Pyramid stands as a testament to the immense resources and labor mobilized under his rule, symbolizing the pharaoh's divine authority and his passage to the afterlife. The pharaohs ruled a society deeply rooted in religion, order, and the promise of an eternal afterlife. They were warriors, builders, and divine stewards responsible for safeguarding their people and maintaining the balance of the cosmos. Their legacy endures not only in the temples and monuments that dot the modern Egyptian landscape, but also in their contributions to human history. The timeless allure of ancient Egypt lies in its extraordinary achievements, profound spirituality, and the enduring stories of its rulers, whose influence continues to captivate the world. The Indus Valley Civilization. The Indus Valley Civilization, one of the earliest cradles of human civilization, remains a mysterious yet captivating chapter in history. Flourishing from around 3300 BCE to 1300 BCE along the fertile banks of the Indus River in modern-day Pakistan and northwest India, this civilization, also known as the Harappan Civilization, was remarkable for its advanced urban planning, impressive architecture, and extensive trade networks. However, much about it remains unknown, particularly its undeciphered script, which continues to intrigue scholars. One of the most striking features of the Indus Valley Civilization was its sophisticated urban design. Unlike many early civilizations ruled by centralized monarchies or religious elites, the cities of the Indus Valley were meticulously planned in grid-like patterns. Prominent urban centers such as Mohenjo-daro and Harappa featured streets intersecting at right angles, reflecting a high level of governance and organizational ability. This advanced approach to city planning predates similar developments in later civilizations like ancient Rome. The civilization's emphasis on sanitation further underscores its ingenuity. Homes in Harappa and Mohenjo-daro were equipped with wells, bathrooms, and a sophisticated drainage system that channeled wastewater away from residential areas. This focus on hygiene and public health was unprecedented at the time and marked the Indus Valley as one of the most advanced urban societies in the ancient world. Another remarkable feature was the uniformity of bricks, weights, and measures found across the civilization. Bricks used in construction were standardized in size, and weights and measures were consistent across various settlements. This suggests centralized regulation and coordination over a vast area, enabling efficient construction and trade. Trade played a vital role in the prosperity of the Indus Valley civilization. Archaeological evidence indicates extensive internal and external trade networks connecting the civilization to regions such as Mesopotamia, modern-day Iran, and Afghanistan. Seals bearing Indus Valley symbols have been found in Mesopotamia, indicating a robust exchange of goods, including textiles, metals, and gemstones. This thriving trade contributed significantly to the civilization's wealth and longevity. Despite the lack of monumental temples or centralized religious structures, the artifacts left behind suggest a rich spiritual life. Figurines, seals, and other relics point to possible fertility and nature worship. The famous Pashupati seal, depicting a seated figure surrounded by animals, is thought by some scholars to represent a precursor to Hinduism or the early god Shiva, hinting at a connection between Indus spiritual practices and later Indian traditions. One of the greatest mysteries of the Indus Valley civilization is its undeciphered script. Numerous inscriptions on seals, pottery, and tablets have been discovered, but without a bilingual text like the Rosetta Stone, the script remains unreadable. This has left key aspects of their society, politics, religion, and daily life, largely unknown, fueling speculation and debate among researchers. The decline of the Indus Valley civilization is another enigma. By 1300 BCE, major cities like Harappa and Mohenjo-daro were abandoned, and the region experienced a significant population decline. Theories about this decline range from environmental changes, such as river drying or flooding, to the migration or invasion of Indo-Aryan peoples. Some scholars suggest that the gradual degradation of the river system disrupted agriculture, while others posit that internal, social, or infrastructural challenges contributed to the collapse. Despite its decline, the legacy of the Indus Valley civilization persisted. Its innovations in urban planning, trade, and possibly spiritual traditions influenced subsequent societies in the Indian subcontinent. The civilization stands as a testament to humanity's early capabilities in creating organized, thriving communities. In summary, the Indus Valley civilization showcases the ingenuity of early human societies in governance, engineering, and commerce. Its meticulously planned cities, advanced sanitation systems, and extensive trade networks highlight a society that was well ahead of its time. Yet the unresolved mysteries of its script, beliefs, and collapse continue to make it one of the most enigmatic civilizations in history. With each new archaeological discovery, we move closer to understanding this remarkable chapter of human development. Ancient China and the dynasties. Ancient China is a vast and intricate tapestry of history, defined by the rise and fall of dynasties that shaped both Chinese civilization and global history. Spanning thousands of years, China's dynastic period is marked by extraordinary achievements in philosophy, science, technology, and governance, making it one of the most enduring and influential civilizations in the world. The story begins with the Xia dynasty, traditionally regarded as China's first dynasty. However, much of its history is steeped in legend, with limited archaeological evidence to confirm its existence. Ancient texts like the Shujing Book of Documents credit the Xia with laying the foundations of Chinese civilization, including early agriculture and bronze working. While its influence remains debated, the Xia occupies an important place at the intersection of myth and history. The Shang dynasty is the first historically verified Chinese dynasty, known for its advancements in bronze metallurgy, the development of writing, and a highly organized political system. Archaeological discoveries, including elaborate bronze vessels and inscribed oracle bones, provide insight into Shang society. Oracle bones, used for divination, reveal the importance of ancestor worship and the central role of spirituality in governance and daily life. Following the Shang, the Zhou dynasty became the longest-lasting dynasty in Chinese history. The Zhou introduced the Mandate of Heaven, a doctrine that legitimized rulers as divinely chosen but held them accountable for just governance. This concept shaped Chinese political thought for millennia, linking the ruler's moral integrity to their right to govern. The Zhou era also saw the emergence of China's most influential philosophical systems: Confucianism, Taoism, and legalism. Confucianism, founded by Confucius, emphasized social harmony, moral integrity, and filial piety as guiding principles for both rulers and citizens. Taoism, attributed to Laozi, advocated living in harmony with the Tao, the natural way of the universe, through simplicity and humility. Legalism, on the other hand, championed strict laws and harsh punishments, asserting that strong state control was necessary to maintain order. These philosophies profoundly shaped Chinese governance, culture, and society. The transition to the Qin dynasty marked a dramatic shift in Chinese history. Under Qin Shi Huang, China was unified for the first time under a centralized imperial system. The Qin standardized weights, measures, and writing, facilitating administration and communication. Major construction projects, including the early Great Wall, aimed to protect against northern invasions. However, Qin Shi Huang's rule was characterized by authoritarianism, including the infamous burning of books and suppression of dissent. His harsh policies unified China, but also led to rebellion, hastening the dynasty's fall shortly after his death. The Han dynasty followed, ushering in one of China's golden ages. Expanding upon the Qin's foundation, the Han consolidated centralized governance and officially adopted Confucianism as state ideology. This period saw significant territorial expansion and the opening of the Silk Road, which connected China to the West, facilitating cultural and economic exchanges. The Han era was marked by technological and cultural advancements, including the invention of paper, advancements in medicine, and astronomical discoveries. After the Han collapsed, China entered the Three Kingdoms period, a time of political fragmentation and war. Despite the instability, this era became legendary in Chinese folklore, immortalized in the novel Romance of the Three Kingdoms. Subsequent dynasties, including the Sui and Tang, restored unity and contributed uniquely to China's development. The Tang dynasty is often regarded as China's second golden age. It was a period of immense cultural flourishing, territorial expansion, and economic prosperity. Poetry, painting, and ceramics reached unparalleled heights, and the capital, Chang'an, became a cosmopolitan hub of trade and cultural exchange, attracting visitors from across Asia and the Middle East. Ancient China's dynastic cycle continued for centuries, with each dynasty leaving its mark on Chinese civilization. From the foundational Xia to the flourishing Tang, each era contributed to the development of one of the world's most enduring cultures. The innovations and philosophies that emerged during this period shaped not only China, but also the broader course of human history. The Greek city-states and democracy. The Greek city-states, or poleis, were not just communities. They were vibrant experiments in governance, culture, and innovation. Picture a world where towering marble temples overlooked bustling marketplaces, where philosophers debated under olive trees, and where citizens gathered to vote on matters that would shape their collective destiny. These independent city-states, scattered across the sparkling waters of the Aegean, were united by a shared language and culture, yet fiercely distinct in their identities. Among them, Athens stands as the birthplace of democracy, a bold and fragile experiment that forever changed how humanity viewed power and participation. Unlike the sprawling empires of Persia or Egypt, the Greek polis were intimate and self-contained, each with its own government, military, and customs. Some, like Sparta, were fiercely militaristic, ruled by oligarchies where discipline and strength reigned supreme. Athens, however, charted a radically different course, laying the groundwork for democracy, a revolutionary idea that power could rest in the hands of the people. But this wasn't democracy as we know it today. It was an evolving experiment, riddled with imperfections, yet brimming with the promise of something extraordinary. In the early days, Athens was anything but democratic. Imagine a city dominated by noble families, where the poor toiled under crushing debts and inequality ran rampant. This tension gave rise to reformers who dared to reimagine the system. Solon, one of Athens' first visionaries, abolished debt slavery, a practice where citizens were forced into servitude for unpaid debts. He redistributed wealth and empowered more Athenians to participate in civic life, planting the seeds for change. Though his reforms stopped short of democracy, they set the stage for what was to come. The true turning point arrived with Cleisthenes, often called the father of Athenian democracy. In a moment of bold innovation, Cleisthenes broke the grip of aristocratic families by reorganizing the political system. He created new districts called dems, mixing citizens from different regions to foster unity and weaken traditional power structures. Imagine a world where power wasn't inherited but earned through participation, a world where ordinary citizens, regardless of their family name, could have a voice in governance. Cleisthenes' reforms laid the foundation for the most radical idea of the time, that governance could belong to the people. Athenian democracy, however, came with limitations. Women, slaves, and non-citizens were excluded, and even among male citizens, wealth and status often dictated who could fully participate. Yet the idea of direct citizen involvement was transformative. Picture the ecclesia, a great open-air assembly where citizens gathered to debate matters of war, law, and trade. Every voice mattered, and every decision was made collectively, a stark contrast to the monarchies and empires of the ancient world. The Boule, a council of 500 citizens chosen by lot, ensured that governance wasn't monopolized by the elite. This emphasis on equality before the law, or isonomia, became a defining feature of Athenian democracy. But democracy's critics were never far away. Philosophers like Plato saw its potential for chaos, warning that unchecked power by the masses could lead to mob rule. Aristotle, though more sympathetic, questioned whether democracy could balance expertise with popular will. These critiques resonate even today as modern democracies grapple with similar challenges. Athenian democracy was tested and ultimately undone by war. The Peloponnesian War, a brutal conflict between Athens and Sparta, shattered the city's strength and unity. Picture a city battered by siege, its once proud walls breached, its democratic institutions crumbling under internal strife and external pressure. Yet, even as Athenian democracy faded, its legacy endured. The story of the Greek city-states is one of experimentation, ambition, and resilience. They were laboratories of ideas that would ripple across time, influencing the Renaissance, the Enlightenment, and the birth of modern democracies. Athens, with all its imperfections, dared to imagine a society where power didn't rest solely in the hands of kings, but in the collective will of its people. That bold vision continues to inspire, reminding us that democracy, though fragile, remains one of humanity's greatest achievements. The Persian Empire, one of history's most expansive and influential civilizations, stretched from the edges of Europe to the heart of Asia. Its rise reshaped the ancient geopolitical landscape, blending conquest with diplomacy and governance with cultural tolerance. At its height, this vast empire united a tapestry of peoples and traditions under a sophisticated administrative system, leaving a legacy that still echoes through the corridors of history. The story begins with Cyrus the Great, the visionary founder of the Persian Empire. In the mid-6th century BCE, Cyrus, a member of the Achaemenid dynasty, overthrew the Medes and forged an empire that quickly encompassed vast territories, including Mesopotamia and Babylon. But Cyrus was more than a conqueror. He was a unifier. Unlike rulers who imposed their will with cruelty, Cyrus practiced a revolutionary policy of tolerance and inclusion. When he captured Babylon in 539 BCE, he not only spared its population, but also respected its customs and religions, earning him admiration as both a liberator and a leader. One of Cyrus's most remarkable achievements was the creation of the Cyrus cylinder, often regarded as the world's first declaration of human rights. This clay artifact chronicles how Cyrus restored religious sanctuaries and allowed displaced peoples, such as the Jews, to return to their homelands. His humane policies are celebrated in the Hebrew Bible, where he is hailed as a liberator who allowed the rebuilding of the temple in Jerusalem. Cyrus's leadership blended power with humanity, laying the foundation for an empire built on trust as well as strength. Cyrus's successors expanded the empire's boundaries and refined its governance. Darius I, who reigned nearly 40 years later, was a master administrator who transformed the empire into a well-oiled machine. To govern its vast and diverse territory, Darius divided the empire into 20 provinces, or satrapies, each overseen by a satrap, or governor. This system allowed for local autonomy while maintaining centralized control. He also introduced a standardized currency and developed an extensive road network, including the renowned Royal Road, a 1,500-mile artery connecting Sardis in the west to Susa in the east. This infrastructure fostered trade, communication, and cohesion across the empire's vast lands. Darius's reign, however, was not without strife. In 499 BCE, the Ionian Revolt erupted as Greek city-states in Asia Minor resisted Persian control, igniting the Greco-Persian Wars. These conflicts would intensify under Darius's son, Xerxes I, leading to iconic battles such as Marathon, Thermopylae, and Salamis. Despite their superior resources and armies, the Persians were ultimately thwarted by the unity and determination of the Greek city-states, halting their westward expansion and marking a turning point in ancient history. Beyond its military and administrative prowess, the Persian Empire was a beacon of cultural diversity. Its rulers embraced the languages, religions, and customs of its many peoples, fostering an environment of coexistence. The imperial capitals of Persepolis and Susa stood as architectural marvels, blending styles from Egypt, Mesopotamia, and India into a visual testament to the empire's multicultural identity. Zoroastrianism, the empire's dominant religion, introduced ideas of dualism, moral choice, and the eternal struggle between good and evil, concepts that later influenced Judaism, Christianity, and Islam. However, the empire's golden age began to wane in the 4th century BCE. Internal rebellions, administrative corruption, and a series of weak rulers eroded its strength. The fatal blow came from Alexander the Great, the Macedonian king whose military genius overwhelmed Persia's defenses. In a series of decisive battles, including Issus and Gaugamela, Alexander dismantled the once mighty empire. The fall of Persepolis in 330 BCE marked the end of Persian dominance, as Alexander absorbed its vast territories into his own expanding realm. Despite its collapse, the Persian Empire's influence endured. Its administrative practices and infrastructure became blueprints for future empires, including the Hellenistic states and the Roman Empire. Its model of governance, which balanced centralized power with local autonomy and cultural tolerance, set a precedent for ruling diverse populations. Persian art, architecture, and literature continued to inspire the regions it once ruled, ensuring that its legacy lived on. The Persian Empire was more than a political entity. It was a crossroads of cultures, ideas, and innovation. It bridged the ancient worlds of the Near East, Europe, and Asia, fostering exchanges that shaped civilizations for centuries. Balancing conquest with diplomacy, tradition with progress, and authority with tolerance, the Persian Empire remains a testament to the heights humanity can achieve through unity and vision. Its story is not just one of power, but of profound influence, a legacy that continues to shape the world today. Rise and Fall of the Roman Empire. The rise and fall of the Roman Empire is one of the most compelling stories in world history, a tale of power, conquest, politics, and eventual decline that spanned over 1,000 years. From a small city-state along the banks of the Tiber River to a sprawling empire that controlled much of Europe, North Africa, and the Middle East, Rome's story is one of both human ambition and fragility. The lessons of its triumphs and failures continue to resonate today. Rome's rise began humbly. Founded in 753 BCE, according to legend by the twin brothers Romulus and Remus, Rome started as a small kingdom. However, it wasn't until the establishment of the Roman Republic in 509 BCE that its true path to greatness was set. The Republic was built on a system of checks and balances designed to prevent the rise of a single ruler, with elected magistrates, a senate, and popular assemblies guiding the government. This structure, although imperfect and prone to corruption, gave Rome a stability that allowed it to grow. Through a combination of military prowess, shrewd diplomacy, and relentless ambition, Rome began to expand. The conquest of Italy was the first step, but the Punic Wars, 264-146 BCE, against Carthage truly marked Rome's arrival as a major power. By the end of these wars, Rome had destroyed Carthage and gained control of significant territories in Spain, Sicily, and North Africa. The Roman legions, disciplined and well-organized, became the most feared military force in the Mediterranean world. As Rome expanded, it absorbed more than just territory. It incorporated different cultures, technologies, and ideas. The Roman military system allowed conquered peoples to join its ranks, and many of Rome's greatest generals and leaders hailed from regions far from the Italian peninsula. This inclusiveness was one of Rome's greatest strengths, allowing it to bind together a vast and diverse empire. However, the expansion of the Republic also sowed the seeds of its eventual transformation into an empire. With great territorial gains came vast wealth, which widened the gap between the Roman elite and the lower classes. Political corruption, landlessness among the poor, and the rise of powerful military generals like Julius Caesar set the stage for civil wars. The assassination of Caesar in 44 BCE, rather than preserving the Republic, led to its collapse. In 27 BCE, Caesar's adopted heir, Augustus, formerly Octavian, established the Roman Empire, marking the start of an era that would bring Rome to its zenith. Under Augustus, the Roman Empire entered a period of relative peace and stability known as the Pax Romana, Roman peace. Lasting roughly 200 years, this era saw the consolidation of Roman rule across vast territories. The empire was now a mosaic of cultures, religions, and peoples, stretching from Britain in the west to Egypt and Syria in the east. Roman law, architecture, engineering, and culture spread throughout these lands, laying the foundations for much of Western civilization. Rome's infrastructure was one of its greatest achievements. Roads, aqueducts, and bridges built during the empire's height were marvels of engineering, and many still stand today. The Roman legal system, too, was advanced for its time, establishing principles like innocent until proven guilty that are still central to modern legal thought. The cities of the empire, from Londinium, modern-day London, to Antioch, reflected Roman urban planning, with public baths, forums, and amphitheaters becoming centers of civic life. However, even during the Pax Romana, the seeds of decline were present. The empire was vast, and managing it was an immense challenge. Corruption among officials, economic instability, and the growing power of the military over civilian life began to erode the stability that Augustus had built. By the 3rd century CE, Rome faced increasing internal strife and external pressure from barbarian groups like the Goths and Vandals. The eventual fall of Rome is a complex story, with historians pointing to a combination of internal weaknesses and external pressures. Internally, the Roman economy suffered from inflation, heavy taxation, and a reliance on slave labor, which stifled innovation and economic growth. The empire was also politically unstable, with a revolving door of emperors, many of whom were installed by the military rather than by any legitimate process. In 284 CE, Emperor Diocletian attempted to address these issues by dividing the empire into eastern and western halves, believing it would be easier to manage. While the Eastern Roman Empire, later known as the Byzantine Empire, would endure for another 1,000 years, the Western Roman Empire continued to crumble. By the 4th and 5th centuries CE, Rome faced an onslaught of invasions from various Germanic tribes. The Huns, led by the infamous Attila, pushed these tribes westward into Roman territory, where they sought refuge, but often turned against their Roman hosts. The Visigoths sacked Rome in 410 CE, a devastating blow to the city that had once seemed invincible. In 476 CE, the last Roman emperor of the West, Romulus Augustulus, was deposed by the Germanic chieftain Odoacer, marking the traditional date of the fall of the Western Roman Empire. Although the fall of the Roman Empire is often viewed as the end of the classical world and the beginning of the Middle Ages, its legacy lived on. The Eastern Roman Empire, or Byzantine Empire, continued to flourish for centuries, preserving Roman law, culture, and Christian tradition. Meanwhile, the Western world, though fragmented, would continue to be deeply influenced by Rome. Rome's legal system, architecture, and engineering became cornerstones of European development. Latin, the language of the Romans, evolved into the Romance languages and remained the language of scholarship and religion for centuries. The idea of a united Europe under a single ruler, as Rome had once been, would continue to inspire future empires and leaders. In the end, the story of Rome is one of both incredible human achievement and inevitable decline. It serves as a reminder that even the greatest powers are vulnerable to internal weaknesses and external pressures, a lesson that continues to resonate in modern times. The birth of Christianity. The origins of Christianity, one of the most influential religions in history, can be understood as a profound social, cultural, and historical phenomenon. Emerging from the turbulent world of first-century Judea, Christianity began as a small Jewish sect and over centuries evolved into a global religion that reshaped the political and cultural landscapes of the ancient world and beyond. Its rise, while often seen through a theological lens, is equally remarkable as a story of human society grappling with power, identity, and meaning. First-century Judea, a Roman-occupied province, was a complex and volatile society. The Jewish population lived under Roman taxation and governance, which frequently clashed with their own religious traditions and aspirations for autonomy. At the heart of Jewish identity was the expectation of a Messiah, a savior foretold in their scriptures who would liberate them from oppression. This belief intersected with a broader environment of social unrest, as many groups resisted Roman rule or sought ways to adapt to it. Within Judaism itself, there were competing factions. The Pharisees emphasized strict adherence to Jewish law, the Sadducees controlled temple worship, the Zealots advocated violent rebellion, and the Essenes withdrew from mainstream society to live in ascetic purity. These divisions reflected the diverse ways in which people responded to the challenges of their time. Into this fragmented world came Jesus of Nazareth, a charismatic preacher and healer. His life, teachings, and the movement he inspired would spark one of the most significant transformations in human history. While much about Jesus' life remains debated, historical evidence suggests he was a Galilean Jew who lived during a time of great social and political upheaval. His teachings, preserved in the Gospels and early Christian writings, focused on themes of love, forgiveness, and humility. He also spoke of the kingdom of God, a concept interpreted by many as a call for moral and spiritual renewal rather than political revolution. Jesus' message was notable for its inclusivity. He interacted with marginalized individuals, prostitutes, tax collectors, and lepers, and challenged social hierarchies. This approach appealed to those disillusioned with the rigid structures of Jewish law and Roman rule. His growing popularity, however, alarmed both religious leaders and Roman authorities, who saw him as a potential disruptor of the fragile social order. In approximately 30 CE, Jesus was executed by crucifixion, a Roman method of punishment reserved for political dissidents and criminals. Crucifixion was not merely a means of execution, it was a public spectacle designed to deter rebellion and humiliate the condemned. From a historical perspective, Jesus' death should have marked the end of his movement, as had been the case for many other would-be messiahs. However, what followed was unprecedented. Jesus' followers claimed he had risen from the dead, an event they referred to as the resurrection. This claim, regardless of its theological interpretation, became the foundation of the Christian movement. It transformed Jesus from a local preacher into a figure of divine significance and galvanized his followers to spread his teachings. The early followers of Jesus, later called Christians, were initially a small Jewish sect. They believed that Jesus' message fulfilled Jewish prophecy, but redefined salvation as a universal promise for all humanity, not just the Jewish people. This shift allowed Christianity to appeal to a much broader audience. A pivotal figure in this transformation was Paul of Tarsus, a former Pharisee who converted to Christianity after a dramatic experience he interpreted as a vision of Jesus. Paul became one of the movement's most effective organizers and thinkers, traveling across the Roman Empire and establishing Christian communities. His letters, later canonized as part of the New Testament, articulated key theological ideas and helped shape Christianity into a coherent and adaptable belief system. Christianity spread rapidly, particularly among urban populations in the Roman Empire. Its teachings resonated with the poor and disenfranchised, offering hope, community, and a sense of purpose. Early Christian communities were notable for their mutual support, including care for the sick and poor, which contrasted with the often impersonal and hierarchical nature of Roman society. The Roman state initially viewed Christianity with suspicion. Christians' refusal to participate in traditional Roman religious practices, including emperor worship, was seen as a threat to social cohesion. Periodic persecutions sought to suppress the movement, but these often had the opposite effect. Martyrdom, the public execution of Christians who refused to renounce their faith, became a powerful symbol of conviction and inspired others to join the movement. The turning point for Christianity came in the early 4th century with Emperor Constantine. According to historical accounts, Constantine converted to Christianity after a vision before a crucial battle. In 313 CE, he issued the Edict of Milan, legalizing Christianity and ending centuries of persecution. By aligning himself with Christianity, Constantine recognized its growing influence and used it to unify the empire. In 380 CE, Emperor Theodosius declared Christianity the official religion of the Roman Empire. What had begun as a marginalized sect in a remote province had, in less than 4 centuries, become the dominant religion of one of history's most powerful empires. The integration of Christianity into Roman governance and culture marked a profound shift, transforming both the religion and the empire. Christianity's rise reshaped the ancient world. It introduced new ideas about human dignity, compassion, and the moral obligations of rulers, which influenced Western thought for centuries. The Christian Church became a central institution in medieval Europe, preserving knowledge, shaping art and philosophy, and serving as a unifying force during times of political fragmentation. From a scientific perspective, the success of Christianity can be understood as a product of its adaptability and universal appeal. Its message was flexible enough to transcend cultural boundaries and resonate with diverse populations. Its organizational structure allowed it to survive and thrive under varying political conditions. And its ability to provide meaning and community in a complex and often harsh world gave it a resilience that few movements could match. In summary, the rise of Christianity is not only a religious story, but also a human one, a story of how ideas, institutions, and social dynamics converge to create movements that transform societies. By examining its growth through the lens of history and sociology, we gain a deeper understanding of how this once small sect became a cornerstone of global civilization. The Islamic Golden Age. The Islamic Golden Age, spanning roughly from the 8th to the 14th century, stands as one of the most extraordinary periods of intellectual, scientific, and cultural flourishing in human history. During this time, the Islamic world became a vibrant hub of innovation and discovery, blending knowledge from diverse civilizations and creating a legacy that shaped the course of global progress. From advancements in science and medicine to groundbreaking contributions in philosophy, mathematics, and the arts. This era laid the foundation for much of the intellectual revival that later defined the European Renaissance. The Islamic Golden Age began under the Abbasid Caliphate, particularly during the reigns of visionary leaders like Al-Mansur and Al-Mamun, who established Baghdad as a center of learning and culture. At the heart of this intellectual movement was the House of Wisdom, a legendary library and academy in Baghdad where scholars from across the known world gathered to translate, study, and expand upon the knowledge of ancient civilizations, including Greek, Persian, Indian, and Egyptian texts. Unlike many rulers who sought power through conquest alone, the Abbasid caliphs recognized that knowledge was a form of power. Their support for scholarship was deeply rooted in Islamic teachings, which emphasized the pursuit of knowledge as a divine act. The Quran and the sayings of Prophet Muhammad encouraged learning, inspiring an age of unprecedented intellectual curiosity and exploration. Cities like Baghdad, Cairo, and Cordoba became bustling centers of knowledge, drawing scholars, scientists, and philosophers from all corners of the Islamic world and beyond. The Islamic Golden Age made remarkable contributions to medicine, bridging ancient traditions with new discoveries. Physicians like al-Razi, known as Razas in the West, revolutionized clinical practices, emphasizing careful observation and evidence-based diagnosis. His comprehensive medical encyclopedia, Al-Hawi, became a cornerstone of medical education in both the Islamic world and medieval Europe. Ibn Sina, or Avicenna, further elevated the field with his monumental work, The Canon of Medicine. This encyclopedic text synthesized Greek, Roman, and Islamic medical knowledge, offering insights into anatomy, pharmacology, and treatment methods. It introduced groundbreaking diagnostic techniques and served as a standard reference in European universities for centuries, influencing medical practice well into the Renaissance. Mathematics flourished during this period, with scholars making significant advances that continue to shape modern disciplines. Al-Khwarizmi, often referred to as the father of algebra, introduced foundational concepts in his book Kitab al-Jabr, from which the term algebra is derived. His work also popularized the decimal system and the concept of zero, tools essential for modern mathematics and engineering. Astronomy, closely tied to mathematical advances, saw tremendous progress. Scholars like al-Battani refined trigonometric calculations and improved methods for predicting celestial events, knowledge that proved crucial for navigation and religious practices, such as determining the direction of Mecca. Al-Biruni accurately calculated the Earth's circumference centuries before European explorers confirmed it, while Al-Tusi developed planetary models that prefigured Copernicus's heliocentric theory. Philosophy thrived as Islamic scholars engaged with the works of ancient Greek thinkers like Plato and Aristotle. Al-Kindi, Al-Farabi, and Ibn Rushd, Averroes, sought to reconcile reason and faith, grappling with questions about existence, ethics, and the nature of the universe. Ibn Rushd, in particular, became a pivotal figure in transmitting Aristotle's philosophy to Europe, where his ideas influenced medieval scholasticism, and thinkers like Thomas Aquinas. The philosophers of the Islamic Golden Age didn't merely preserve ancient knowledge, they expanded it, challenging established ideas and introducing new perspectives. Their respect for reason and empirical inquiry became hallmarks of the era, fostering a spirit of intellectual openness that transcended religious and cultural boundaries. One of the era's most enduring contributions was its role in preserving the intellectual heritage of antiquity. During a time when much of the classical world's knowledge risked being lost, Islamic scholars translated works by luminaries such as Euclid, Galen, and Hippocrates into Arabic. These translations were not mere copies. Scholars critiqued, annotated, and expanded upon these texts, creating a dynamic body of knowledge that would later be reintroduced to Europe through Latin translations. This effort wasn't limited to science and philosophy. Literature and poetry flourished as well, with works like 1001 Nights blending moral lessons with imaginative storytelling. Persian poets like Rumi explored themes of love, unity, and spirituality, crafting verses that continue to inspire readers worldwide. The achievements of the Islamic Golden Age did not remain confined to the Islamic world. Through Spain, particularly the city of Cordoba, and institutions like the School of Translators in Toledo, Arabic texts were translated into Latin, sparking a revival of intellectual activity in Europe. These translations introduced Europe to the scientific methods, mathematical theories, and philosophical ideas of Islamic scholars, laying the groundwork for the Renaissance. Figures like Leonardo da Vinci and Copernicus indirectly benefited from the insights of Islamic thinkers, who had built upon and preserved the knowledge of antiquity. The scientific revolution that followed in Europe owes much to the transmission of this intellectual heritage. The decline of the Islamic Golden Age began in the 14th century, driven by political fragmentation, the Mongol invasions, and internal strife. The sacking of Baghdad by the Mongols in 1258 dealt a devastating blow to the cultural and intellectual vibrancy of the Islamic world. However, the contributions of this era endured, shaping the development of science, medicine, and philosophy for centuries. The Islamic Golden Age serves as a testament to the power of curiosity, collaboration, and the exchange of ideas. It reminds us that knowledge knows no borders and that progress often emerges from the meeting of diverse cultures and perspectives. The achievements of this remarkable era continue to inspire, offering a vision of what humanity can accomplish when it values learning and creativity. The Byzantine Empire. The Byzantine Empire, often overshadowed by its Roman predecessor, stands as one of history's most enduring and influential civilizations. Spanning over 1,000 years, from 330 CE, when Emperor Constantine the Great established Constantinople as the empire's capital. To its fall in 1453 to the Ottoman Turks, the Byzantine Empire was a bastion of resilience, intellect, and culture. Its story is one of strategic ingenuity, religious transformation, and profound influence, shaping both the ancient and modern worlds. At the core of the Byzantine Empire was Constantinople, a city strategically perched on the Bosporus Strait, where Europe meets Asia. This prime location made it a crossroads of commerce and culture, controlling vital trade routes between the Mediterranean and the Black Sea. Constantinople became a vibrant hub of wealth and influence, its marketplaces filled with goods from distant lands and its coffers enriched by trade tolls. The city's defenses were legendary. Encircled by massive walls that seemed impenetrable, Constantinople repelled countless sieges over the centuries. For nearly a millennium, it stood as the shining jewel of the Byzantine Empire, its skyline dominated by the magnificent Hagia Sophia. With its awe-inspiring dome and intricate mosaics, the Hagia Sophia wasn't just an architectural marvel. It was a symbol of Orthodox Christianity and Byzantine ingenuity. One of the Byzantine Empire's most defining features was its role in shaping Christianity. In the 4th century, Emperor Constantine legalized Christianity with the Edict of Milan, setting the stage for its rise as the state religion. Over time, Byzantium became the spiritual heart of Orthodox Christianity, distinct from its Western counterpart. The Great Schism of 1054 formalized this division, separating the Eastern Orthodox Church from the Roman Catholic Church and solidifying Byzantium's unique religious identity. Orthodox Christianity deeply influenced Byzantine culture. Monasticism flourished, with communities like Mount Athos becoming centers of spirituality and learning. Byzantine icons, stylized religious artworks, were revered as sacred windows to the divine, central to Orthodox worship and spirituality. These icons, adorned with gold and vivid colors, reflected the Byzantine emphasis on symbolism and transcendence. The reign of Emperor Justinian IV, 527-565 CE, marked a golden age for the Byzantine Empire. Determined to restore the glory of the Roman Empire, Justinian launched ambitious military campaigns under his brilliant general Belisarius, temporarily reclaiming parts of North Africa, Italy, and Spain. These conquests symbolized a fleeting revival of Roman dominance. However, Justinian's most enduring legacy lay not in warfare, but in law. His Corpus Juris Civilis, body of civil law, was a monumental codification of Roman law that streamlined centuries of legal traditions. This legal masterpiece became the foundation of Byzantine jurisprudence and influenced legal systems in Europe, shaping the development of civil law in modern states. Justinian also left his mark on architecture. The Hagia Sophia, commissioned during his reign, stood as a testament to Byzantine engineering and artistic brilliance. Its immense dome seemed to float above the heavens, inspiring awe in all who entered. The Byzantine Empire was a melting pot of Greco-Roman traditions and Eastern influences, forging a unique cultural identity. Its art, characterized by shimmering mosaics and religious iconography, reflected a fusion of realism and spirituality. Unlike Western art, which often aimed for lifelike depictions, Byzantine art prioritized conveying divine truths and spiritual presence. Education and scholarship thrived. Byzantine scholars preserved and expanded upon the works of ancient Greek philosophers like Plato and Aristotle, safeguarding knowledge that might have otherwise been lost during Europe's tumultuous Middle Ages. This intellectual tradition later found its way to the Islamic world and eventually back to Europe, sparking the Renaissance and shaping modern thought. The Byzantine Empire's longevity can be attributed to its innovative military strategies and diplomatic acumen. One of its most famous weapons was Greek fire, a mysterious incendiary substance that could burn even on water, giving the Byzantines a formidable advantage in naval battles. The empire's armies, including the elite Varangian Guard, fearsome warriors of Norse and Anglo-Saxon origin, were highly trained and fiercely loyal. Equally important was the Byzantine mastery of diplomacy. Leaders skillfully played rival powers against one another, forging alliances, arranging strategic marriages, and using cunning negotiation to avoid unnecessary wars. This ability to balance force with diplomacy allowed Byzantium to survive for centuries, even as Western Europe descended into feudal chaos. Despite its resilience, the Byzantine Empire faced relentless challenges. The Fourth Crusade in 1204 was a devastating blow. Originally intended to reclaim Jerusalem, the Crusaders turned their attention to Constantinople, sacking the city and dividing its wealth. For decades, Constantinople remained under Latin control, and even after the Byzantines recaptured it, the empire was weakened beyond repair. By the 14th century, the Ottoman Turks emerged as a powerful force, steadily encroaching on Byzantine territory. In 1453, under Sultan Mehmed II, the Ottomans launched a final siege of Constantinople. Despite fierce resistance, the city fell, marking the end of the Byzantine Empire. The fall of Constantinople was a watershed moment, symbolizing the end of the medieval era and the rise of the Ottoman Empire. Though the Byzantine Empire fell, its influence endures. Its preservation of Greek and Roman knowledge laid the intellectual foundation for the Renaissance. Byzantine religious traditions continue to shape Orthodox Christian nations like Russia, Greece, and Serbia. Its art and architecture, from mosaics to domed cathedrals, remain celebrated as pinnacles of human creativity. The Byzantine Empire was more than a bridge between the ancient and modern worlds. It was a civilization that forged its own identity, blending East and West into a unique cultural mosaic. Its story is one of resilience, adaptation, and profound influence, a testament to the enduring power of culture and intellect. Even centuries after its fall, Byzantium's legacy continues to illuminate the paths of history. The feudal system in medieval Europe. The feudal system was the framework of medieval European society, a web of interdependence that governed land, power, and daily life for centuries. It emerged in the wake of the Roman Empire's collapse, when Europe fractured into a mosaic of territories ruled by local warlords. In the absence of centralized authority, survival depended on mutual obligations, an intricate human chain where kings, lords, knights, and peasants each played their part. Imagine a massive puzzle, each piece vital to the whole, yet each shaped by its unique role. After the fall of Rome in the 5th century, chaos reigned. Without the stability of Roman governance, marauding invaders, economic decline, and constant threats made life unpredictable. Local rulers, often warlords with armies, seized control of fragmented regions, offering protection in exchange for allegiance. This arrangement soon evolved into a formalized system. Feudalism. Land, or fiefs, became the currency of power granted by kings or powerful lords in exchange for loyalty and military service. Unlike modern ownership, this land was not held outright, but loaned under strict conditions, forming the backbone of a society rooted in land-based wealth. Feudal society resembled a pyramid. At the top sat the king, theoretically owning all the land. Beneath him were the powerful lords and barons, who were granted vast estates in return for their allegiance. These lords further subdivided their land to knights, who pledged to defend their domains. At the base of the pyramid were the peasants and serfs, who toiled on the land to sustain the entire system. This hierarchy was bound by a network of mutual obligations. The king granted protection and authority to the lords provided knights to fight for the king, and the peasants worked the land to feed everyone above them. The daily life of a serf, the backbone of this system, was grueling and unrelenting. Though not slaves, serfs were tied to the land, unable to leave without their lord's permission. They worked the fields from sunrise to sunset, plowing, planting, and harvesting crops. In return, they were promised protection from invaders, a critical assurance in an era marked by frequent raids and violence. Serfs paid their lords with a portion of their harvest, performed additional labor on the lord's personal lands, and faced taxes and fees for using communal resources like mills or ovens. Though their lives were marked by hardship, the feudal system offered them a semblance of stability in an otherwise perilous world. Above the serfs stood the knights, the armored enforcers of feudal law. Trained from boyhood in the arts of combat, horsemanship, and weaponry, knights were both warriors and symbols of feudal values. Their loyalty to their lord was cemented through ceremonies of fealty, where they knelt and swore an oath of service. Knights didn't merely fight, they embodied the chivalric ideal, bravery in battle, protection of the weak, and devotion to God. Though the reality often fell short of the ideal, chivalry offered a moral framework that upheld the feudal order. The lords, who ruled over their fiefs, held both economic and judicial power. They oversaw their estates, managed disputes, and ensured the productivity of their lands. Yet they too were vassals, bound by oaths of loyalty to kings or more powerful overlords. This web of vassalage created a chain of interdependence, with each link reinforcing the other. The bond of fealty was sacrosanct. Breaking it was seen as a grave betrayal that could upend the delicate balance of power. At the pinnacle of this hierarchy stood the king, a figure of ultimate authority, but often limited by the realities of his dependence on the loyalty of his vassals. While the king technically owned all the land, his power relied on the cooperation of the lords who governed vast territories on his behalf. A weak king could find his authority undermined by ambitious barons, while a strong king could unify his realm and wield significant influence. Feudalism wasn't just about survival. It was also about order. The system provided a structured response to the chaos of the early medieval period, creating a predictable framework of mutual obligations. Yet this rigidity also sowed the seeds of its eventual decline. By the 14th century, shifts in economics, technology, and society began to unravel the feudal web. The Black Death devastated Europe's population, creating labor shortages that empowered serfs to demand better conditions or freedom. Trade expanded, and the rise of towns and cities shifted wealth and power away from rural manors. Meanwhile, the invention of gunpowder and professional armies diminished the military role of knights, eroding one of feudalism's central pillars. Centralized monarchies began to eclipse the power of feudal lords, consolidating authority in the hands of kings and paving the way for nation-states. By the time of the Renaissance, feudalism had largely faded, replaced by economies and societies driven by trade, urban centers, and monetary wealth. Yet feudalism's influence persisted. Its hierarchical structure shaped European societies for centuries, leaving echoes in notions of loyalty, service, and governance. The concepts of mutual obligation and duty that defined feudal relationships can still be seen in modern legal systems and cultural traditions. Feudalism was more than a social order. It was a response to the challenges of its time, creating a network of interdependence in a fragmented world. The feudal system may seem distant, a relic of a bygone era, but it remains a testament to humanity's ability to adapt and organize in the face of adversity. Its legacy is woven into the fabric of Western civilization, offering insights into the foundations of modern society. Feudalism was a world built on trust, loyalty, and the shared need for survival, a system that thrived in the chaos and gave shape to the medieval world. The Crusades. The Crusades were a sweeping and turbulent saga of faith, ambition, and conflict that shaped medieval Europe and the Middle East for centuries. These religious wars primarily fought between European Christians and Muslim forces over control of the Holy Land, particularly Jerusalem, were anything but simple. Spanning from 1096 to the late 13th century, the Crusades were driven by a mix of piety, political maneuvering, and personal ambition. They left behind a legacy of cultural exchange, economic growth, and enduring animosities that continue to shape the world today. The stage was set in the 11th century, a time of upheaval and opportunity. Europe was fragmented into feuding kingdoms, while the Muslim world, though often divided, controlled Jerusalem, a city sacred to Christians, Jews, and Muslims alike. Against this backdrop, Pope Urban II issued a fiery call to arms at the Council of Clermont in 1095. His words electrified Europe, framing the campaign as a holy mission to reclaim Christian lands and promising spiritual rewards, even eternal salvation, to those who joined. This rallying cry unified disparate factions under a common cause, igniting a fervor that swept through knights, nobles, and peasants alike. The First Crusade, launched in 1096, was both a staggering success and a brutal testament to the complexities of the movement. Tens of thousands of crusaders embarked on a grueling journey across Europe and the Middle East, driven by faith, the lure of adventure, and the hope of eternal glory. Their march was marked by starvation, disease, and conflict, but they pressed on. In 1099, they achieved the unthinkable, the capture of Jerusalem. Yet their victory came at a terrible cost. Historical accounts describe a massacre of Muslim and Jewish inhabitants that left the city drenched in blood, setting the tone for centuries of interfaith tension. The Crusaders established Christian states, known as the Crusader states, to maintain their foothold in the Holy Land, but these territories would remain fragile and contested. The initial triumph of the First Crusade was difficult to replicate. In 1147, the Second Crusade was launched in response to the Muslim recapture of Edessa, one of the Crusader states. Despite immense resources and support, the campaign ended in failure, plagued by poor leadership, disunity among European forces, and the strategic resilience of Muslim defenders. The stark contrast between the triumph of the First Crusade and the debacle of the Second highlighted the unpredictability and complexity of these conflicts. The Third Crusade, beginning in 1189, brought together some of the most legendary figures of the medieval world. It was sparked by the recapture of Jerusalem by Saladin, the charismatic and brilliant Muslim leader who united much of the Islamic world against the Crusaders. Facing him were Europe's most powerful monarchs, including Richard the Lionheart of England. The rivalry between Richard and Saladin became the stuff of legend, marked by epic battles and mutual respect. While Richard achieved notable victories, he ultimately failed to retake Jerusalem. Instead, a truce was brokered in 1192, allowing Christian pilgrims access to the city while leaving it under Muslim control. A bittersweet conclusion to a campaign marked by heroism and heartbreak. The Fourth Crusade, launched in 1202, revealed the shifting motivations and moral complexities of the Crusades. Initially intended to reclaim Jerusalem, the Crusaders instead turned their sights on Constantinople, the capital of the Byzantine Empire. Driven by political intrigue and financial pressures, they sacked the city in 1204, looting its treasures and leaving a once mighty Christian ally in ruins. This betrayal deepened the rift between the Roman Catholic and Eastern Orthodox churches and marked a dramatic departure from the original goals of the Crusades. While the Crusades ultimately failed to establish lasting Christian control over the Holy Land, their impact reverberated far beyond the battlefield. The movement opened up new trade routes and facilitated the exchange of goods, ideas, and technologies between Europe and the Middle East. European crusaders encountered advanced Muslim knowledge in medicine, mathematics, and astronomy, sparking intellectual curiosity that would help lay the groundwork for the Renaissance. Spices, textiles, and other luxuries from the East flowed into European markets, transforming economies and cultures. However, the Crusades also left deep scars. The violence committed in the name of faith entrenched animosities between Christians and Muslims that persisted for centuries. Jewish communities in Europe were frequently targeted by crusaders en route to the Holy Land, leading to horrific massacres and fueling anti-Semitism. The sacking of Constantinople fractured Christendom, creating divisions that remain evident today. The Crusades also reshaped European society. Many feudal lords who joined the campaigns never returned, allowing kings to consolidate power and lay the foundations for centralized monarchies. The experience of large-scale warfare led to innovations in military tactics and castle construction, while the cultural exchanges of the era enriched art, literature, and intellectual life. Ultimately, the Crusades were far more than a clash of religions. They were a complex web of human motivations and consequences. What began as a singular call to reclaim sacred lands evolved into a series of campaigns driven by a mix of faith, greed, ambition, and desperation. The Crusades remind us of the power of ideas to inspire extraordinary feats and devastating atrocities, and of the ways in which ideals can be both a guiding light and a dangerous weapon. Their legacy is a cautionary tale and a source of reflection. The Crusades were not a simple battle of good versus evil, but a multifaceted saga of humanity, striving and often failing to reconcile its highest aspirations with its basest impulses. Through their triumphs and tragedies, they reveal the enduring complexity of human history and the intricate interplay of faith, power, and ambition. The Mongol Empire and Genghis Khan. The story of the Mongol Empire, one of the largest and most transformative empires in history, begins on the vast windswept steppes of Mongolia. It is a tale of resilience, ambition, and vision, centered on a man who rose from humble beginnings to reshape the world. Born as Temujin in 1162, this boy from a harsh and unforgiving land would grow into Genghis Khan, the universal ruler, forging an empire that spanned continents and redefined the flow of history. Temujin's early life was marked by relentless adversity. His father, a tribal chieftain, was poisoned by rivals when Temujin was just a child, leaving his family abandoned and vulnerable. Stripped of their status, Temujin, his siblings, and his mother, Hoelun, struggled to survive on the barren steppes, often battling starvation and the constant threat of enemy tribes. These formative years forged in him an unbreakable will and an acute understanding of loyalty and leadership. From these harsh beginnings, Temujin learned to think beyond the narrow confines of tribal alliances. Unlike many leaders of his time who relied solely on family ties or bloodlines, Temujin valued merit, loyalty, and ability. He began to attract a small but fiercely devoted group of followers, united not by kinship but by a shared belief in his vision. Slowly, he started to unify the fractious Mongol tribes, overcoming centuries-old rivalries and ingrained distrust. This unification was not merely a consolidation of power. It was a revolution in the way the Mongols saw themselves, not as divided clans, but as one people with a shared destiny. By 1206, after years of warfare, diplomacy, and alliances, Temujin achieved what had once seemed impossible: the unification of the Mongol tribes. He was declared Genghis Khan, the universal ruler, marking the birth of the Mongol Empire. This moment was not just a turning point for the Mongols, but for the entire world. Genghis Khan transformed his people from scattered nomadic tribes into a disciplined and cohesive military machine. He abolished tribal feuds, implemented laws to ensure order, and prioritized loyalty and merit over birthright, a radical shift that set his empire apart. The Mongol army under Genghis Khan's leadership was unlike anything the world had seen. It was fast, adaptable, and devastatingly effective. Mongol warriors, mounted on swift horses, could travel vast distances with incredible speed, often surprising their enemies. Their expertise in horseback archery made them deadly and precise, while their innovative use of intelligence networks allowed them to outmaneuver and outthink opponents. Genghis Khan also employed psychological warfare, spreading fear through tales of Mongol brutality to encourage surrender without a fight. Yet Genghis Khan was more than a conqueror. He was a pragmatic and astute ruler. While his military campaigns were often marked by brutal efficiency, his approach to governance was surprisingly progressive for its time. He embraced diversity, allowing conquered peoples to practice their religions freely, and often incorporating local customs and expertise into his administration. For example, after conquering the Khwarezmian Empire in Persia, he adopted aspects of its bureaucratic systems, enhancing the efficiency of Mongol rule. By the time of his death in 1227, Genghis Khan's empire stretched from the Pacific Ocean to the Caspian Sea, encompassing much of Central Asia and parts of China. But the Mongol conquests did not end with him. His successors expanded the empire even further, pushing into Eastern Europe, the Middle East, and beyond. Under their rule, the Mongol Empire facilitated an unprecedented era of cultural, technological, and economic exchange across continents. This period, often referred to as the Pax Mongolica, or Mongol Peace, brought stability to vast regions of Asia and Europe. The Mongols safeguarded trade routes, particularly the Silk Road, creating an interconnected world where goods, ideas, and technologies flowed freely. Silk, spices, and precious metals moved westward, while innovations such as papermaking, printing, and gunpowder traveled eastward. Even diseases, including the Black Death, spread along these routes, illustrating the profound and far-reaching effects of the Mongol network. The Mongol Empire's influence extended beyond trade. In China, the Mongols established the Yuan dynasty, blending Mongol and Chinese traditions. In Persia, they revitalized cities and fostered the flourishing of Islamic art and science. In Russia, their governance left a lasting imprint on political structures. Their acceptance of diverse religions was equally impactful, fostering a level of religious tolerance that was rare for the time and allowing communities of Buddhists, Muslims, Christians, and others to coexist under Mongol rule. Despite their achievements, the Mongols' legacy is deeply complex. Genghis Khan and his armies are remembered for their ruthless conquests, which often involved widespread destruction and loss of life. Entire cities were razed and populations were displaced, leaving scars that endured for generations. Yet the same empire that instilled fear also connected disparate worlds, fostering exchanges that enriched civilizations and propelled humanity forward. The Mongol Empire eventually fragmented, weakened by internal divisions and the challenges of governing such a vast and diverse territory. By the late 14th century, its influence had waned, but its impact remained indelible. Genghis Khan's vision of unity and expansion reshaped the political, cultural, and economic landscapes of Asia, Europe, and beyond. Genghis Khan remains one of history's most polarizing figures. For some, he is a symbol of unbridled conquest and destruction. For others, he is a visionary leader who forged connections between distant worlds and championed principles of merit and tolerance that were ahead of his time. The empire he built was not merely a collection of conquered lands, but a dynamic force that bridged civilizations, reshaping the course of history. The story of Genghis Khan and the Mongol Empire is a testament to the transformative power of vision and resilience. From a boy surviving on the harsh steppes to a ruler who commanded the largest contiguous empire in history, Genghis Khan's journey illustrates the extraordinary heights humanity can achieve when driven by determination and ambition. His legacy, both inspiring and cautionary, serves as a reminder of how the past continues to echo in the present, shaping the world we know today. The Renaissance in Europe. The Renaissance, meaning rebirth, was a dazzling period in European history, spanning roughly from the 14th to the 17th century. It marked a profound cultural and intellectual awakening, a time when Europe emerged from the so-called darkness of the Middle Ages into an era of unparalleled creativity, scientific discovery, and philosophical exploration. This transformative age redefined art, science, politics, and human thought, laying the foundations for the modern world and placing humanity itself at the center of inquiry and innovation. The Renaissance was born in the vibrant city-states of northern Italy, with Florence serving as its beating heart. In the 14th century, Florence was not just a hub of commerce and trade, but also a crucible of ideas and ambition. Its wealthy merchant families, most famously the Medici, wielded their immense fortunes to patronize artists, architects, and scholars. They saw art and knowledge not merely as pursuits of beauty or utility, but as a way to immortalize their legacy and elevate their society. This patronage created fertile ground for a cultural explosion that would ripple across Europe. What ignited this rebirth was a rediscovery of the classical wisdom of ancient Greece and Rome. During the Middle Ages, much of this knowledge had faded from European memory, preserved instead in Islamic libraries and Byzantine archives. As these texts re-emerged, brought back through trade, conquest, and scholarly exchange, they rekindled a fascination with the human experience. Philosophers like Plato and Aristotle, poets like Virgil, and orators like Cicero became guides for a new generation of thinkers eager to explore human potential and the natural world. This revival of classical ideas gave rise to humanism, a movement that celebrated human achievement, dignity, and reason. Art became the most visible manifestation of the Renaissance spirit, breaking away from the rigid, symbolic styles of the Middle Ages to embrace realism, perspective, and emotion. Artists like Leonardo da Vinci, Michelangelo, and Raphael revolutionized their craft, producing works that captured the complexities of the human form and spirit. Michelangelo's David, carved from a single block of marble, became an emblem of human strength and beauty, while his Sistine Chapel ceiling brought biblical stories to life with unparalleled grandeur. Leonardo da Vinci epitomized the Renaissance ideal of the uomo universale, or universal man. He was not only a painter, but also an inventor, scientist, and anatomist. In his sketches, you see the boundless curiosity of a mind seeking to understand both the mechanics of flight and the secrets of the human body. His Vitruvian Man, a study of ideal proportions, symbolized the Renaissance belief in the harmony between art, science, and nature. Leonardo's notebooks, filled with designs for machines centuries ahead of their time, stand as a testament to the visionary scope of Renaissance thought. The Renaissance was not confined to art. It was an age of scientific daring when long-held beliefs were questioned and the universe was reimagined. Nicholas Copernicus shattered the geocentric model of the cosmos, proposing instead that the Earth orbited the Sun, a radical idea that upended centuries of religious and scientific doctrine. Galileo Galilei, armed with his telescope, confirmed Copernicus's theory and expanded humanity's understanding of the stars, despite fierce opposition from the Church. These breakthroughs symbolized a seismic shift, the pursuit of truth through observation and reason rather than tradition and dogma. One invention more than any other propelled Renaissance ideas far and wide: the printing press. Johannes Gutenberg's revolutionary device, introduced around 1440, democratized knowledge by making books affordable and accessible. Before its invention, manuscripts were painstakingly copied by hand, making them rare and expensive treasures. With the printing press, texts on philosophy, science, and art could reach audiences across Europe, fueling literacy, debate, and innovation. It also amplified the voices of dissenters like Martin Luther, whose 95 Theses ignited the Protestant Reformation, challenging the authority of the Catholic Church and reshaping Europe's religious landscape. At the core of the Renaissance was a shift in worldview. While the Middle Ages had been deeply centered on divine authority and the afterlife, the Renaissance celebrated life on Earth. Humanism championed the study of history, literature, and ethics, arguing that understanding the human condition was as noble a pursuit as understanding the divine. Figures like Petrarch, often called the father of humanism, encouraged individuals to seek wisdom and virtue through personal reflection and classical learning. This philosophical shift was mirrored in art, which began to depict humanity in all its complexity, from the serene divinity of Raphael's Madonnas to the raw emotion in Michelangelo's Pietà. The Renaissance's impact was not limited to Italy. From Florence, its ideas spread across Europe, influencing artists like Albrecht Dürer in Germany, writers like William Shakespeare in England, and architects like Christopher Wren. Each region interpreted the Renaissance through its own cultural lens, creating a mosaic of innovation that spanned continents. In Northern Europe, Renaissance art often combined meticulous realism with moral and religious themes, while writers like Shakespeare explored the depths of human nature with unparalleled eloquence. The Renaissance did not end abruptly but evolved, laying the groundwork for the Enlightenment and the scientific revolution. Its emphasis on reason, inquiry, and the value of the individual would shape modern democracy, science, and education. It shifted the center of knowledge from religious institutions to human observation and creativity, fostering the secular and individualistic values that define much of Western culture today. The Renaissance is more than a historical period. It is a reminder of humanity's boundless capacity for reinvention. It teaches us that even in times of upheaval, creativity and curiosity can spark profound change. From its origins in the bustling city-states of Italy to its spread across Europe, the Renaissance remains a beacon of human potential, celebrating the power of art, science, and ideas to transform the world. Its legacy is etched not only in marble and canvas, but in the very fabric of modern thought, a testament to the enduring brilliance of a time when humanity dared to rediscover itself. The Age of Exploration. The Age of Exploration, spanning from the 15th to the 17th centuries, was a transformative chapter in human history, a time when the boundaries of the known world expanded dramatically, fueled by ambition, curiosity, and the pursuit of power. It was an era of daring voyages across uncharted oceans that reshaped civilizations, economies, and cultures, leaving behind a legacy as complex as it was profound. The driving force behind this era was Europe's hunger for new trade routes. For centuries, the Silk Road had connected Europe to the wealth of Asia, bringing spices, silk, and other exotic goods. But by the 15th century, the rise of the Ottoman Empire had blocked many of these overland routes, forcing European nations to seek alternatives. The dream of reaching the fabled riches of India and China spurred a maritime revolution that would change the course of history. Portugal, a small but ambitious maritime nation, led the charge. Under the guidance of Prince Henry the Navigator, a patron of exploration, Portuguese sailors charted new paths down the western coast of Africa, dreaming of reaching the Indian Ocean. In 1488, Bartolomeu Dias achieved a historic breakthrough by rounding the Cape of Good Hope at Africa's southern tip. A decade later, Vasco da Gama completed the journey to India, establishing Portugal as a dominant force in the lucrative spice trade. Meanwhile, Spain pursued a different vision. Christopher Columbus, an Italian explorer, believed he could reach Asia by sailing west across the Atlantic. Backed by Queen Isabella and King Ferdinand of Spain, Columbus set sail in 1492 and landed in the Bahamas, unaware that he had stumbled upon a new continent. His voyage marked the beginning of a profound transformation as Europe and the Americas collided, reshaping the fate of both worlds. The consequences of Columbus's journey were far-reaching and often devastating. The Spanish conquistadors who followed in his wake, like Hernán Cortés and Francisco Pizarro, toppled powerful indigenous empires such as the Aztecs and Incas. These conquests brought vast wealth to Spain, but also unleashed catastrophic consequences for the native populations, who suffered from warfare, enslavement, and diseases like smallpox, which decimated entire communities. This era of exploration was made possible by groundbreaking advancements in technology. The invention of the caravel, a nimble and maneuverable ship, allowed explorers to sail further and more effectively than ever before. Navigational tools like the astrolabe and the magnetic compass enabled sailors to determine their position and direction, reducing the risks of long ocean voyages. These innovations transformed the oceans from barriers into highways, connecting continents and cultures in ways previously unimaginable. Among the most significant outcomes of the Age of Exploration was the Columbian Exchange, a vast and complex transfer of plants, animals, people, and ideas between the Old and New Worlds. Crops like potatoes, maize, and tomatoes, native to the Americas, became staples in Europe, Asia, and Africa, revolutionizing diets and agriculture. In return, Old World crops such as wheat, sugarcane, and coffee were introduced to the Americas, along with livestock like horses and cattle, which transformed indigenous ways of life. Yet the Columbian Exchange also carried a darker side. Diseases like smallpox, influenza, and measles, brought unwittingly by European explorers, ravaged indigenous populations in the Americas, causing one of the most devastating demographic collapses in history. Entire societies were irreversibly altered, their cultures disrupted, and their lands colonized. The race for exploration and colonization intensified as other European powers, including England, France, and the Netherlands, entered the fray. Spain and Portugal, early leaders in exploration, had divided the world between them in 1494 through the Treaty of Tordesillas, mediated by the Pope. But this division could not contain the ambitions of rival nations. By the 17th century, European powers were competing fiercely for control of trade routes, colonies, and resources, fueling conflicts and shaping the geopolitical map of the modern world. The Age of Exploration also sparked intellectual revolutions. As explorers charted unknown lands and encountered diverse cultures, they expanded the collective understanding of geography, biology, and anthropology. European maps grew more accurate, and curiosity about the natural world deepened, laying the groundwork for the scientific revolution. However, the era's darker legacies cannot be overlooked. The exploitation of indigenous peoples, the destruction of their civilizations, and the transatlantic slave trade are stark reminders of the human cost of exploration. The labor demands of European colonies gave rise to a brutal system of slavery, forcibly transporting millions of Africans across the Atlantic, a legacy of suffering that continues to reverberate through history. The Age of Exploration was not just a time of discovery, it was a time of transformation. It brought about a more interconnected world, establishing global trade networks and cultural exchanges that would shape the modern era. The era's explorers expanded the limits of human knowledge and ambition, proving that the world was far larger and far more interconnected than anyone had imagined. But this interconnectedness came at a price. It was an age of wonder and conquest, innovation and exploitation, curiosity and cruelty. The Age of Exploration reminds us of the dual nature of human progress, the incredible heights of achievement we can reach, and the devastating consequences of our ambitions when they go unchecked. It is a story of humanity's unquenchable thirst to know and to conquer, a testament to both our brilliance and our flaws, echoing through the centuries as a cautionary tale and a source of inspiration. The Protestant Reformation. The Protestant Reformation was a seismic shift in European history, a movement that redefined religion, politics, and culture during the 16th century. What began as a theological debate quickly escalated into a revolution, challenging the immense power of the Catholic Church and reshaping the fabric of Western civilization. At its core was a radical call for reform, but its ripple effects extended far beyond religion, touching every aspect of society and setting the stage for modernity. For centuries, the Catholic Church stood as the spiritual and political cornerstone of Europe, wielding authority over kings and commoners alike. But by the early 1500s, cracks were beginning to show in its edifice. Many Europeans were deeply troubled by the perceived corruption within the Church. Clergy were criticized for their wealth and opulence, and practices like the sale of indulgences, essentially payments for the forgiveness of sins, sparked outrage. For the faithful, it felt as though salvation itself had been commodified, and doubts began to grow about whether the church could truly guide them towards spiritual redemption. It was in this climate of discontent that Martin Luther, a German monk and theology professor, emerged. Luther was a deeply introspective man, often tormented by questions of sin and salvation. As he delved into the Bible, he came to a revolutionary conclusion. Salvation was not something to be earned through good works or purchased through indulgences. Instead, it was a gift of grace, attainable through faith alone. This idea, solidified or faith alone, would become the cornerstone of his challenge to the church. On October 31st, 1517, Luther took a bold step that would ignite a movement. He nailed his 95 Theses to the door of the Wittenberg church, a public declaration of his grievances against the church's practices. These theses questioned the authority of the Pope, condemned the sale of indulgences, and called for a return to Scripture as the ultimate source of truth. Thanks to the recent invention of the printing press, Luther's ideas spread rapidly, sparking debates and gaining followers across Germany and beyond. At the heart of Luther's message was the concept of sola scriptura, Scripture alone. He argued that the Bible, not the Pope or church tradition, was the ultimate authority in matters of faith. This was a radical notion, as it suggested that every individual had the right to read and interpret Scripture for themselves. By empowering believers to seek their own relationship with God, Luther dismantled the hierarchical structure that had long defined the Catholic Church. Luther's ideas resonated deeply with many, but they also posed an existential threat to the Church. His teachings undermined the Church's monopoly on spiritual authority, and his growing influence prompted swift backlash. In 1521, he was summoned to the Diet of Worms, a council convened by Holy Roman Emperor Charles V, and ordered to recant his views. Luther refused, famously declaring, "Here I stand, I can do no other." Branded a heretic, he was excommunicated, but by then his movement had gained too much momentum to be silenced. What began as a religious dispute quickly evolved into a broader social and political revolution. Across Europe, secular leaders saw Luther's ideas as an opportunity to assert their independence from the Catholic Church. In Germany, many princes embraced Protestantism, not just for its theological appeal, but as a means to seize church lands and consolidate power. This alignment between Protestant reformers and secular rulers ensured the movement's survival and expansion. But the Reformation also unleashed chaos and conflict. The religious divide sparked violent clashes between Catholics and Protestants, culminating in wars that devastated entire regions. The Peasants' War in Germany, inspired in part by Reformation ideals, saw thousands of peasants rise up against oppressive feudal lords, demanding greater social and economic equality. Luther, though initially sympathetic to their grievances, ultimately condemned the uprising, leading to its brutal suppression. As Protestantism spread, the Catholic Church launched its own reform efforts, known as the Counter-Reformation. The Council of Trent, 1545-1563, sought to address corruption, reaffirm Catholic doctrine, and counter the spread of Protestantism. New religious orders, such as the Jesuits, emerged as dynamic forces for Catholic renewal, focusing on education, missionary work, and the defense of Catholic orthodoxy. The Reformation's impact extended far beyond the religious sphere. It shattered the religious unity of Europe, giving rise to a patchwork of Protestant and Catholic states. It also fueled a surge in literacy and education, as the emphasis on reading the Bible encouraged the establishment of schools and the spread of printed materials. The power of the printing press became undeniable, demonstrating how technology could amplify ideas and challenge established authority. Culturally, the Reformation encouraged individualism and personal responsibility, values that would later influence the Enlightenment and the rise of democratic thought. The movement's emphasis on questioning authority and seeking truth resonated far beyond the confines of theology, shaping modern concepts of freedom and human rights. The Protestant Reformation remains one of history's most transformative events. It was a moment of profound spiritual and social upheaval, marked by both incredible achievements and devastating conflicts. It challenged long-held assumptions, redefined the relationship between the individual and authority, and laid the groundwork for a more pluralistic and diverse Europe. In hindsight, the Reformation serves as a testament to the power of ideas and the resilience of the human spirit in the face of institutional dominance. Martin Luther's defiance in Wittenberg was not just a stand against indulgences. It was a call for a more personal and authentic faith, a challenge to the status quo, and a catalyst for change that continues to shape the world today. The Scientific Revolution. The Scientific Revolution was one of the most profound transformations in human history, spanning the 16th to 18th centuries. It marked a seismic shift in the way people understood the universe and their place within it. This era shattered the old reliance on dogma and tradition, replacing it with a new approach driven by observation, experimentation, and the relentless pursuit of truth. The revolution redefined humanity's relationship with knowledge, ushering in a world governed by reason and evidence, and laying the foundation for modern science. Before this intellectual awakening, much of Europe's understanding of the natural world was rooted in ancient Greek philosophy and religious teachings. Aristotle's view of an earth-centered universe where celestial bodies moved in perfect divine circles had been embraced for centuries. This geocentric model, endorsed by the Catholic Church, placed humanity at the literal and figurative center of creation. It was a comforting worldview, but one that left little room for questioning or exploration. Truth was seen as fixed, eternal, and best understood through the interpretations of established authorities. But the seeds of change were already being planted. The Renaissance had revived an interest in classical learning, encouraging people to look beyond inherited wisdom. The rediscovery of ancient texts, coupled with the advances made during the Islamic Golden Age, began to stir curiosity about the natural world. Slowly, a shift began, a move away from accepting what was told, toward asking what could be proven. In 1543, Nicholas Copernicus, a Polish mathematician and astronomer, published De Revolutionibus Orbium Coelestium on the revolutions of the heavenly spheres. In it, he proposed a revolutionary idea. What if the Earth was not at the center of the universe? Instead, he suggested a heliocentric model, where the Sun was at the center, with the Earth and other planets orbiting around it. This concept was a radical departure from centuries of belief, challenging both scientific and theological orthodoxy. While his theory lacked the observational evidence to convince many at the time, it set the stage for others to explore and expand upon his ideas. The next giant leap came from Galileo Galilei, an Italian polymath who transformed the way people observe the heavens. In 1609, Galileo built a telescope that allowed him to peer into the cosmos with unprecedented clarity. What he saw was astonishing. Moons orbiting Jupiter, proving that not all celestial objects revolved around the Earth. The phases of Venus, which confirmed the heliocentric model. And the moon's surface, revealed to be rough and cratered, rather than the perfect sphere imagined by earlier thinkers. Galileo's meticulous observations, published in Sidereus Nuncius, Starry Messenger, struck a blow to the geocentric model and demonstrated the power of evidence-based inquiry. But Galileo's discoveries came at a cost. His findings contradicted the teachings of the Catholic Church, which clung to the earth-centered universe as a cornerstone of its doctrine. In 1633, he was tried by the Inquisition and forced to recant his views, spending the rest of his life under house arrest. Yet his work inspired a generation of scientists to question authority and trust their observations. Johannes Kepler, a German mathematician and astronomer, pushed the revolution further by uncovering the laws of planetary motion. Using data collected by his mentor, Tycho Brahe, Kepler demonstrated that planets moved in elliptical orbits rather than perfect circles. This was more than a mathematical breakthrough. It shattered the notion of a universe governed by divine perfection. Kepler's work introduced the idea that the cosmos operated according to precise, measurable laws, setting the stage for a deeper understanding of motion and gravity. The culmination of these efforts came with Isaac Newton, whose contributions synthesized the discoveries of the scientific revolution into a coherent framework. In 1687, Newton published Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, a monumental work that outlined his laws of motion and universal gravitation. Newton's insights revealed that the same force pulling an apple to the ground governed the orbits of planets around the sun. For the first time, humanity understood that the heavens and the earth were part of the same physical system, governed by universal principles that could be expressed through mathematics. The impact of Newton's work was staggering. It united centuries of fragmented observations and theories into a single vision of the universe as an ordered, predictable system. Newton's laws became the foundation for modern physics and exemplified the power of the scientific method, a disciplined approach that relied on observation, experimentation, and reasoning to uncover truth. The scientific revolution didn't just transform our understanding of the cosmos. It redefined the way humanity approached knowledge itself. The idea that truth could be discovered, tested, and refined through evidence marked a dramatic departure from the reliance on authority and tradition that had dominated for centuries. This shift empowered individuals to question, to experiment, and to explore, fostering a spirit of inquiry that would fuel innovations in medicine, engineering, chemistry, and countless other fields. It also democratized knowledge. The invention of the printing press played a critical role, making books and scientific ideas accessible to a broader audience. Scientists began publishing their findings, creating networks of correspondence that transcended borders and languages. Knowledge was no longer the exclusive domain of the elite. It became something that anyone with curiosity and discipline could pursue. The legacy of the scientific revolution is profound. It ignited the Enlightenment, inspired the Industrial Revolution, and continues to shape the modern world. It revealed a universe governed not by mystical forces, but by laws that could be understood and harnessed. It taught humanity to embrace skepticism, to value evidence over assumption, and to see knowledge not as a fixed truth, but as a journey of endless discovery. In many ways, the scientific revolution was humanity's first step into the modern era. It redefined what it meant to seek truth and revealed a cosmos far grander, more intricate, and more fascinating than anyone had imagined. Its story reminds us of the power of curiosity and the extraordinary progress that can arise when we dare to question the unknown. The Enlightenment Era. The Enlightenment Era, often called the Age of Enlightenment, was a transformative period that reshaped the way humanity viewed the world, spanning from the late 17th to the late 18th century. It was a time when the power of reason illuminated the darkness of ignorance and tradition, challenging entrenched dogmas and sparking revolutions in thought, governance, and society. This intellectual awakening not only questioned long-standing authorities, but also laid the foundation for modern democracy, human rights, and scientific progress, marking a profound shift in the trajectory of Western civilization. The roots of the Enlightenment can be traced to the fertile intellectual soil of the scientific revolution. Thinkers like Isaac Newton and Galileo Galilei had demonstrated that the universe operated according to discoverable laws, sparking a newfound confidence in reason and observation. Inspired by these scientific breakthroughs, philosophers and intellectuals of the Enlightenment sought to apply the same principles of inquiry and logic to human society, governance, and morality. They believed that through reason and evidence, humanity could improve itself and its institutions, breaking free from the chains of superstition and authoritarianism. Central to the Enlightenment was the idea that human reason was the primary source of knowledge and progress. This marked a radical departure from the past, where divine authority and rigid tradition often dictated truth. Enlightenment thinkers, known as philosophes, argued that individuals could and should seek truth through critical thinking and empirical evidence. This conviction was both liberating and provocative, as it directly challenged the dominance of monarchies and the Church, which had long served as the arbiters of knowledge and power. René Descartes, often regarded as the father of modern philosophy, embodied this spirit of intellectual independence. His famous declaration, cogito, ergo sum, I think therefore I am, placed human thought at the center of existence. By questioning established truths and emphasizing doubt as a tool for discovery, Descartes laid the philosophical foundation for the Enlightenment's focus on individual inquiry and skepticism. Equally influential was John Locke, whose ideas about government and human rights would ripple through history. In his two treatises of government, Locke proposed that all individuals are born with inherent rights to life, liberty, and property. He argued that governments derive their legitimacy from the consent of the governed and exist solely to protect these rights. These revolutionary ideas challenged the divine right of kings and inspired movements for democracy and self-governance, particularly in the American and French revolutions. Voltaire, the brilliant and sharp-tongued satirist, emerged as one of the Enlightenment's most prominent voices. A relentless critic of institutionalized religion and political tyranny, Voltaire championed freedom of speech, religious tolerance, and civil liberties. His wit and piercing critiques exposed the hypocrisies of the powerful, making him a symbol of the Enlightenment's commitment to truth and justice. His famous quip, "I disapprove of what you say, but I will defend to the death your right to say it," encapsulates the era's belief in the sanctity of free expression. Another towering figure, Montesquieu, advanced the concept of the separation of powers in government. In his seminal work, The Spirit of the Laws, he argued that dividing authority among legislative, executive, and judicial branches would prevent tyranny and safeguard individual freedoms. Montesquieu's ideas profoundly influenced the structure of modern democracies, including the United States Constitution. The Enlightenment wasn't confined to philosophy. It also ignited revolutions in education and knowledge dissemination. Denis Diderot's ambitious project, Encyclopédie, sought to compile and share the breadth of human knowledge, making it accessible to a wider audience. This monumental work reflected the Enlightenment's belief that education was the key to progress and that knowledge should not be hoarded by elites, but shared with all. While the Enlightenment celebrated reason and progress, it was not without contradictions. Many Enlightenment thinkers failed to extend their ideals of liberty and equality to women, enslaved people, and indigenous populations. For instance, while Rousseau championed individual freedom and direct democracy, his views on women were often regressive, relegating them to domestic roles. However, figures like Mary Wollstonecraft emerged during this time to challenge these limitations. In her groundbreaking work, A Vindication of the Rights of Woman, Wollstonecraft argued for gender equality and the importance of education for women, planting the seeds of modern feminist thought. The Enlightenment also grappled with the tension between reason and emotion. While it celebrated rationality as the pathway to truth, it sometimes undervalued the role of human emotion, imagination, and spirituality. This tension would later give rise to Romanticism, a movement that sought to balance the Enlightenment's focus on reason with an appreciation for the emotional and the sublime. The political impact of the Enlightenment was immense. In America, the ideas of Locke, Montesquieu, and others inspired the Declaration of Independence and the Constitution, creating a new nation built on principles of liberty and democracy. Across the Atlantic, the French Revolution erupted, fueled by the works of Rousseau, Voltaire, and Diderot. These revolutions were not merely political events. They were the realization of Enlightenment ideals, demanding that power be held accountable and that the rights of individuals be respected. The Enlightenment's legacy is profound and enduring. It laid the intellectual groundwork for the modern world, influencing everything from the development of human rights to the spread of secularism and the rise of scientific inquiry. Its emphasis on reason, skepticism, and the pursuit of knowledge continues to shape how societies approach challenges and opportunities. Yet the Enlightenment also serves as a reminder of the complexities of progress. While it broke down many barriers and inspired profound advancements, it also revealed the limits of its own ideals. The era's challenges and contradictions highlight the ongoing struggle to balance reason with emotion, freedom with responsibility, and progress with equity. In its essence, the Enlightenment was a daring act of intellectual courage, a call to question, to explore, and to imagine a better world. Its legacy endures in the democratic principles, scientific advancements, and human rights movements that define our age, reminding us of the power of ideas to illuminate the path forward. The Enlightenment continues to inspire humanity's pursuit of knowledge, freedom, and justice, proving that the light of reason, once ignited, can never truly be extinguished. The Industrial Revolution. The Industrial Revolution was a seismic transformation, reshaping human society in ways that were unimaginable just a few decades earlier. Spanning the late 18th to mid-19th centuries, it marked a shift from agrarian economies to industrialized powerhouses, forever altering how people worked, lived, and connected with one another. This era can be visualized as a tidal wave of innovation sweeping across Europe and beyond, leaving behind a world that was profoundly changed. Before this revolution, life was deeply rooted in rural traditions. Most people lived in small villages, farming the land or crafting goods by hand. The rhythms of life followed the seasons, and technological change was gradual, almost imperceptible. But as the 18th century progressed, subtle yet powerful forces began to stir. Advances in agriculture, including crop rotation and selective breeding, dramatically increased food production, freeing many from the toil of farming. This surplus of labor converged with growing urban centers, creating a fertile ground for industrialization. The revolution's beating heart was the factory, a new, almost mythical entity that symbolized both opportunity and upheaval. Factories became the engines of production, fueled by groundbreaking inventions like James Hargreaves' spinning jenny, which allowed one worker to spin multiple spools of thread simultaneously, and Richard Arkwright's water frame, which harnessed water power to drive machines. These innovations revolutionized the textile industry, transforming it from a cottage-based craft into a mass-production juggernaut. Imagine stepping into one of these factories in the early 1800s. The air hums with the rhythmic pounding of machines, the clatter of gears, and the voices of workers shouting over the noise. Men, women, and even children toil side by side, performing repetitive tasks for hours on end. While these factories were marvels of efficiency, they also brought profound social changes. The artisanal craftsman was replaced by the factory worker, marking the rise of a new working class, one bound not to the land, but to the clock. Urbanization was one of the most visible consequences of industrialization. Cities like Manchester and Birmingham swelled with waves of migrants seeking work in the burgeoning factories. These rapidly expanding urban centers became bustling hubs of activity, but they also faced immense challenges. Overcrowding, unsanitary living conditions, and pollution were common. The skies darkened with soot from coal-fired factories, and rivers became choked with industrial waste. For many, the promise of a better life in the city was tempered by harsh realities. Yet alongside these challenges came extraordinary technological breakthroughs that redefined the limits of human capability. The steam engine, perfected by James Watt, was a crowning achievement of the era. It powered trains, ships, and machinery, revolutionizing transportation and manufacturing. Steam locomotives connected cities like never before, transforming commerce and communication. Imagine a world where a journey that once took weeks by horse-drawn carriage could now be completed in days by train. The world became smaller, more interconnected, and more dynamic. Culturally, the Industrial Revolution sparked a rich dialogue about humanity's place in this rapidly changing world. The Romantic movement, led by figures like William Wordsworth and Mary Shelley, arose as a counterpoint to industrialization, emphasizing the beauty of nature and the emotional depth of the human spirit. At the same time, Enlightenment ideals of liberty and equality began to take root in this context. Workers, galvanized by the inequalities they faced, organized to demand better wages, shorter hours, and safer conditions. Their struggles planted the seeds for labor rights movements that would define the 19th and 20th centuries. The Industrial Revolution also reverberated far beyond Europe and North America. It was a global phenomenon, albeit one marked by both progress and exploitation. Industrialized nations sought resources and markets, intensifying colonialism and reshaping economies in Asia, Africa, and Latin America. The interconnectedness of trade and industry laid the foundation for the global economy, with enduring implications that we still grapple with today. In its wake, the Industrial Revolution left a world transformed. It brought unimaginable advancements in technology, medicine, and transportation, paving the way for modern civilization. Yet it also highlighted the cost of progress, environmental degradation, social inequalities, and the alienation of labor. This era stands as a powerful reminder of the dual-edged nature of human ingenuity, where every step forward carries both promise and peril. Ultimately, the Industrial Revolution was more than just a period of change. It was a reimagining of what was possible. It taught humanity to think beyond the constraints of the past, to innovate, adapt, and forge new paths. As we reflect on this transformative chapter in history, we are reminded that progress is not without its challenges, but it is through understanding and navigating these complexities that we continue to shape our shared future. The French Revolution. The French Revolution, a tumultuous and transformative era spanning from 1789 to 1799, stands as one of the most pivotal events in human history. It shattered the ancient structures of monarchy and feudalism, replacing them with ideals of liberty, equality, and fraternity that would inspire revolutions and political thought for centuries. This revolution wasn't merely a French affair. It ignited a global wave of change, challenging traditional authority and reimagining the relationship between people and power. To understand the roots of the French Revolution, imagine a nation on the brink of collapse, its social fabric fraying under the weight of inequality and economic despair. France in the late 18th century was a society divided into three estates: the clergy, the nobility, and the common people, or third estate. At the top, the clergy and nobility enjoyed vast privileges, wealth, and exemptions from taxes. Below them, the third estate, comprising peasants, urban workers, and the burgeoning middle class, bore the burden of heavy taxation, subsisting on meager incomes, while the ruling classes lived in luxury. This stark divide, akin to a chasm separating two worlds, created deep resentment. The financial strain of supporting costly wars, including France's intervention in the American Revolution, coupled with poor harvests that drove up bread prices, pushed the country toward economic ruin. The common people, already hungry for bread, now hungered for justice and representation. The Enlightenment, a philosophical movement championing reason, individual rights, and equality, provided the intellectual fuel for their growing dissatisfaction. Thinkers like Rousseau, Voltaire, and Montesquieu challenged the divine right of kings and argued for the rights of ordinary people, sparking a new vision of governance. By 1789, the pressure had reached a breaking point. King Louis XVI, facing financial chaos, convened the Estates General, a national assembly meant to address the crisis. However, the Third Estate, tired of being marginalized, broke away and declared itself the National Assembly, vowing to draft a constitution. This act of defiance marked the beginning of the Revolution. The storming of the Bastille on July 14, 1789, became the Revolution's defining symbol. Imagine a sea of desperate Parisians converging on the fortress prison, not only to seize its weapons, but to dismantle a centuries-old symbol of tyranny. Their victory was a cry of liberation, reverberating throughout France and galvanizing the masses. Soon, peasants in the countryside rose up in what became known as the Great Fear, burning manor houses and destroying feudal records as they sought to erase their oppression. The National Assembly moved swiftly to enact sweeping reforms. In August 1789, it issued the Declaration of the Rights of Man and of the Citizen, a groundbreaking document that proclaimed equality, freedom, and the inalienable rights of all citizens. Men are born and remain free and equal in rights, it declared, a radical statement that resonated far beyond French borders. For the first time, the idea of government accountable to the people began to take shape, a stark contrast to the centuries of monarchical rule. However, revolutions are rarely linear, and the French Revolution soon veered into darker waters. As power shifted, divisions emerged among revolutionaries over the future direction of France. External pressures from neighboring monarchies, alarmed by the upheaval, combined with internal conflicts, fueled paranoia and radicalism. The Jacobins, a revolutionary faction led by Maximilien Robespierre, seized control and ushered in the Reign of Terror from 1793 to 1794. This period was one of intense fear and violence. Picture a society turned on itself where accusations of counter-revolutionary behavior could lead to the guillotine. The very ideals of liberty and equality were overshadowed by a relentless pursuit of ideological purity. Thousands, including King Louis XVI and Queen Marie Antoinette, were executed. Yet amidst the chaos, the revolution achieved lasting reforms, such as the abolition of feudal privileges and the establishment of secular governance. The Reign of Terror ended with Robespierre's execution, and the revolution entered a more moderate phase. The Thermidorian reaction sought to stabilize the nation, but France remained a turbulent and divided society. Amid this uncertainty, a charismatic and ambitious military leader, Napoleon Bonaparte, rose to prominence. In 1799, Napoleon staged a coup d'état, effectively ending the revolution and establishing the consulate, with himself as first consul. Though he later declared himself emperor, Napoleon preserved many revolutionary reforms, such as the Napoleonic Code, which institutionalized equality before the law and secular governance. His reign, however, marked the revolution's conclusion, transitioning France from a republic to an empire. The impact of the French Revolution extended far beyond France's borders. It inspired revolutionary movements across the globe, from Haiti, where enslaved people fought for and won their freedom, to Latin America, where colonial subjects rose against European powers. The revolution also influenced political thought, embedding ideas of human rights, citizenship, and democracy into the fabric of modern governance. Yet the revolution's legacy is as complex as the event itself. While it championed liberty, it also unleashed violence and upheaval. It dismantled ancient hierarchies, but its promises of equality were often unrealized, particularly for women and marginalized groups. Nonetheless, the French Revolution remains a testament to humanity's capacity to challenge oppression and strive for a more just society. The French Revolution was not merely a historical event, but a profound turning point, a storm that swept away the old world and planted the seeds of modern democracy. Its ideals continue to resonate, reminding us of the power of collective action and the enduring struggle for liberty and justice. Through its triumphs and tragedies, the revolution remains a powerful symbol of humanity's quest for a better future. The rise of colonial empires. The rise of colonial empires between the 15th and 20th centuries marked a transformative chapter in human history, an era defined by exploration, conquest, and the reshaping of societies on a global scale. Picture the world as a vast map of uncharted oceans and mysterious lands, with European powers driven by ambition, greed, and an insatiable thirst for knowledge, casting their nets across the seas. What followed was a whirlwind of discovery and domination, a phenomenon that ignited competition, fostered cultural exchanges, and left profound and often painful legacies that echo to this day. Colonialism's roots took hold during the Age of Exploration, which began in the late 15th century as European nations sought new trade routes to the east. The fall of Constantinople in 1453 severed vital overland trade connections to Asia, spurring a desperate quest to find alternative paths to the riches of the Orient. It was during this time that figures like Christopher Columbus, Vasco da Gama, and Ferdinand Magellan embarked on voyages that would redefine the boundaries of the known world. Imagine Columbus, his 3 small ships, fragile yet daring, sailing into the Atlantic, their decks filled with the hopes of reaching Asia. Instead, he landed in the Caribbean, unknowingly unveiling a new world. This discovery was exhilarating, but it also unleashed waves of ambition and competition among European powers eager to claim territories and resources. Spain and Portugal quickly emerged as dominant players, carving out vast empires in the Americas, Africa, and Asia. The discovery of gold and silver in the New World flooded European markets, transforming economies and fueling further exploration. Visualize the bustling docks of Seville, where Spanish galleons returned laden with gold, silver, and other riches from the Americas. This wealth transformed Spain into a global powerhouse, but it came at a steep cost. Indigenous populations in the Americas faced enslavement, displacement, and the devastating effects of European diseases. Entire cultures were upended in the name of empire, with ancient civilizations like the Aztecs and Incas falling to the swords and guns of conquistadors such as Hernán Cortés and Francisco Pizarro. By the 17th century, the colonial race had expanded, with England, France, and the Netherlands entering the fray. Unlike Spain and Portugal, these powers focused on trade and the establishment of colonies in North America, the Caribbean, and parts of Asia. The rise of joint stock companies such as the British East India Company and the Dutch East India Company revolutionized colonialism by merging private enterprise with imperial ambitions. These companies wielded immense power, governing territories, waging wars, and reaping enormous profits from trade in spices, textiles, and enslaved peoples. Picture the harbors of Amsterdam or London, teeming with ships brimming with sugar, tobacco, and spices. These goods, extracted from distant colonies, fueled economic growth and transformed European societies. Yet this prosperity was built on the backs of enslaved laborers and the exploitation of colonized peoples. The transatlantic slave trade, driven by the demand for plantation labor in the Americas, stands as one of colonialism's darkest legacies. Millions of Africans were forcibly taken from their homelands, enduring unimaginable suffering and reshaping the demographics of the Atlantic world. Colonialism was not merely a story of economic exploitation. It also facilitated profound cultural exchanges. European missionaries sought to spread Christianity, often at the expense of indigenous belief systems. Imagine a remote village where missionaries introduced foreign religious practices, displacing local traditions and altering the cultural fabric. While some indigenous communities adopted aspects of European culture, others resisted fiercely, leading to uprisings and prolonged conflicts. The Enlightenment of the 18th century brought new ideas that challenged the moral and ethical foundations of colonialism. Philosophers like John Locke and Jean-Jacques Rousseau began to emphasize individual rights and the value of consent in governance, sowing seeds of doubt about the legitimacy of imperial rule. At the same time, these ideas inspired resistance movements within the colonies. The American Revolution and the Haitian Revolution demonstrated that colonized peoples could challenge and overthrow imperial powers, setting a precedent for future struggles for independence. The 19th century saw the Industrial Revolution reshape the dynamics of colonialism. Steamships, railroads, and telegraphs allowed for faster exploitation of resources and tighter control over colonies. European powers expanded their empires into Africa and Asia, often justified under the guise of bringing civilization to the uncivilized. This era, sometimes called the New Imperialism, saw a race to claim territories, exemplified by the Berlin Conference of 1884-85, where European nations divided Africa among themselves without regard for existing cultures or societies. Yet the very tools of empire, education, communication, and transportation began to fuel resistance movements. Nationalist leaders like Mahatma Gandhi in India and Kwame Nkrumah in Ghana emerged, drawing on Enlightenment ideals and the growing discontent of colonized peoples to demand independence. By the mid-20th century, the horrors of two world wars further eroded the legitimacy of colonial rule, ushering in a wave of decolonization that reshaped the global order. The rise of colonial empires was a paradox of human history, a tale of ambition and innovation intertwined with exploitation and suffering. It connected the world in unprecedented ways, fostering global trade and cultural exchanges, yet it also perpetuated inequality and injustice on a massive scale. Today, the legacies of colonialism continue to influence global politics, economics, and cultural identities, reminding us of the complexities of empire. As we reflect on this era, we are left with a profound lesson that the pursuit of power and wealth, when unchecked, often comes at an immeasurable human cost. The story of colonialism is a testament to humanity's capacity for both creation and destruction, a reminder of the delicate balance between ambition and responsibility in shaping our shared world. The American Revolution. The American Revolution, often celebrated as a cornerstone of modern democracy, was far more than a clash between Britain and its American colonies. It was a sweeping ideological upheaval, a struggle for liberty, self-governance, and the redefinition of individual rights. Picture 13 distinct colonies, each with its own identity, bound together by growing discontent against a distant monarchy that imposed its will without representation. This discontent would ignite a revolution that reverberated across the globe, altering the course of history. Long before muskets fired in Lexington and Concord, the seeds of revolution had been quietly planted. The British Empire, facing immense debts from the French and Indian War, turned to its American colonies as a source of revenue. Taxes like the Stamp Act of 1765 and the Townshend Acts of 1767 were levied, but they sparked outrage among colonists who lacked representation in Parliament. No taxation without representation became a rallying cry, a powerful declaration of the colonists' demand for autonomy and fairness. Imagine a crowded Boston tavern filled with animated conversations where merchants, artisans, and farmers voiced their frustrations over pints of ale. Their grievances soon turned to action with events like the Boston Tea Party in 1773, a dramatic protest where colonists disguised as Mohawk Indians dumped British tea into the harbor to defy oppressive taxation. The waters of Boston Harbor swirled with tea and rebellion, signaling the rising tide of resistance. Tensions boiled over into armed conflict on April 19, 1775, when British troops and colonial militias clashed at Lexington and Concord. The morning air was filled with the crack of musket fire, marking the shot heard round the world. These skirmishes were not merely a local disturbance, but the beginning of a larger struggle that would challenge the very foundations of monarchy and imperial power. As the conflict escalated, the Continental Congress emerged to unify the colonies. By June 1776, the bold idea of independence was gaining traction. In Philadelphia, a group of delegates drafted the Declaration of Independence, with Thomas Jefferson crafting its powerful words. The Declaration proclaimed that all men are created equal and endowed with unalienable rights, a statement of ideals that transcended its time and place. Imagine the tension and excitement in Independence Hall as delegates debated and ultimately signed this audacious document, setting the colonies on a path towards self-rule. But achieving independence would not come easily. The American forces, a patchwork of militias and volunteers, faced the formidable British Army, one of the most powerful military forces in the world. Under the leadership of General George Washington, the Continental Army endured staggering hardships. Picture the bitter winter at Valley Forge in 1777, where soldiers wrapped in tattered uniforms braved freezing temperatures, their spirits buoyed by an unshakable commitment to the cause of freedom. Key victories like the Battle of Saratoga in 1777 bolstered morale and convinced France to join the war as an ally, providing crucial military and financial support. The Revolution, once a colonial struggle, had now become a global conflict. French ships and troops bolstered the American effort, culminating in the decisive siege of Yorktown in 1781. Imagine the jubilation as British General Cornwallis surrendered, the combined American and French forces celebrating a victory that would echo through history. The Treaty of Paris in 1783 formally ended the war, granting the colonies independence and establishing the United States of America. However, the conclusion of the Revolutionary War marked only the beginning of a new challenge: building a nation. The fledgling republic grappled with questions of governance, unity, and rights. The Articles of Confederation, the first attempt at national government, proved inadequate, prompting the Constitutional Convention of 1787. The resulting U.S. Constitution established a framework for a government that derived its power from the consent of the governed, while the Bill of Rights enshrined individual freedoms. Yet, the lofty ideals of the Revolution were not fully realized for all. While the Declaration of Independence proclaimed equality, the new nation continued to grapple with the realities of slavery, women's rights, and the treatment of indigenous peoples. These unresolved issues would shape the American narrative for centuries to come. The impact of the American Revolution extended far beyond the newly formed United States. Its ideals inspired movements for self-determination and democracy around the globe, from the French Revolution to independence movements in Latin America. The Revolution proved that ordinary people could rise against tyranny and forge a government rooted in liberty and justice. In reflecting on the American Revolution, it becomes clear that it was not merely a war for independence, but a profound transformation of political thought and human aspiration. It demonstrated the power of collective action, the resilience of people striving for freedom, and the enduring influence of ideas grounded in equality and self-governance. Through the sacrifices and vision of its revolutionaries, the American colonies carved out a new nation, leaving an indelible mark on the world. The story of the American Revolution is a testament to the strength of ideals, the courage to challenge oppression, and the belief that a better future is always worth fighting for. The Napoleonic Wars. The Napoleonic Wars, spanning from 1803 to 1815, stand as a defining chapter in European history, a period of sweeping political change, relentless military campaigns, and the towering ambition of one man, Napoleon Bonaparte. Imagine a continent engulfed in turmoil, where revolutionary ideals clashed with imperial dominance, and the old monarchies grappled with the seismic forces of change. This was an era where empires rose and fell, borders shifted like sand, and the very fabric of European society was transformed. The roots of the Napoleonic Wars lay in the French Revolution, which erupted in 1789, toppling centuries of monarchic rule and igniting cries for liberty, equality, and fraternity. Amid the ensuing chaos, a young Corsican-born general, Napoleon Bonaparte, emerged as a beacon of stability and genius. Known for his extraordinary tactical mind and charisma, Napoleon rapidly ascended through the ranks, capturing both the imagination and loyalty of the French people. By 1799, he orchestrated a coup d'etat, seizing power and establishing himself as first consul. In 1804, in a moment of audacious self-assertion, Napoleon crowned himself Emperor of France at Notre Dame Cathedral, a dramatic act that declared his independence from any authority, even the Pope. As Napoleon consolidated power, his ambitions alarmed the monarchies of Europe, who saw him as both a product and a propagator of revolutionary chaos. These nations, Britain, Austria, Russia, and Prussia, formed coalitions to counter the growing French threat. The stage was set for a series of wars that would engulf Europe in fire and steel, with Napoleon at the center of the storm. Napoleon's military campaigns became the stuff of legend. The Grande Armée, his meticulously organized and highly disciplined force, operated like a well-oiled machine, capable of rapid movements and devastating precision. In 1805, at the Battle of Austerlitz, often called the Battle of the Three Emperors, Napoleon faced the combined forces of Russia and Austria. Using masterful feints and strategic positioning, he orchestrated a crushing victory, cementing his reputation as one of history's greatest military minds. Picture the battlefield shrouded in morning mist, with Napoleon's troops executing maneuvers so flawlessly that even his enemies marveled at their brilliance. At the height of his power, Napoleon reshaped the map of Europe. He dismantled the centuries-old Holy Roman Empire, replacing it with the Confederation of the Rhine, a collection of French-aligned states. His legal reforms, encapsulated in the Napoleonic Code, brought modern principles of equality and secular governance to much of the continent, leaving an enduring legacy. Yet Napoleon's vision of a unified Europe under French dominance also sowed the seeds of resistance. Nationalist movements began to stir in Spain, Germany, and elsewhere, fueled by a desire for self-determination and a rejection of foreign rule. Nowhere was this resistance more vividly displayed than in the Peninsular War. Initially welcomed as liberators, French forces soon faced fierce guerrilla warfare from Spanish partisans, supported by British troops under the Duke of Wellington. Picture the rugged Spanish countryside, where villagers transformed into fighters, ambushing French convoys and melting back into the hills. The Peninsular War drained French resources and morale, becoming a slow but relentless bleed on Napoleon's empire. The turning point came with Napoleon's ill-fated invasion of Russia in 1812. Determined to enforce his continental system, a blockade designed to cripple Britain's economy, Napoleon marched over 600,000 soldiers into the vast expanse of Russia. The campaign began with confident advances, but quickly turned into a nightmare. The Russians employed a scorched earth strategy, destroying supplies and luring the French deeper into their territory. When Napoleon reached Moscow, he found the city abandoned and ablaze, offering no shelter or victory. As winter closed in, the Grande Armée faced starvation, disease, and the unforgiving cold. Imagine a once mighty army reduced to a desperate, ragged procession, trudging through snow under the relentless bite of frost and enemy raids. Of the original force, fewer than 50,000 returned. The disastrous Russian campaign shattered the aura of Napoleon's invincibility. Coalition forces, sensing their moment, pressed their advantage, and by 1814 they marched into Paris. Napoleon abdicated and was exiled to the island of Elba, but his story was far from over. In 1815 he made a dramatic return during the 100 Days, rallying support and reclaiming the throne. Yet his resurgence was short-lived. At the Battle of Waterloo, Napoleon faced the combined forces of Britain and Prussia under the Duke of Wellington and General Blucher. The battle was a brutal and chaotic clash, with cannon fire and bayonet charges tearing through the ranks. Despite initial successes, Napoleon's forces were ultimately overwhelmed. The defeat at Waterloo sealed his fate, and he was exiled to the remote island of St. Helena, where he would spend the rest of his days. The Napoleonic Wars reshaped Europe and the world in profound ways. They redefined the nature of warfare, introduced modern tactics, and inspired nationalist movements that would later drive revolutions and unifications. The Congress of Vienna, held in the aftermath of Napoleon's defeat, sought to restore balance and stability to Europe, redrawing borders and establishing a framework for diplomacy that would last for decades. Yet the ideals of liberty and equality that Napoleon had both championed and subverted continued to resonate, influencing political thought and social movements well into the future. The story of the Napoleonic Wars is one of ambition and innovation, resistance and resilience. It is a tale of how one man's extraordinary vision and determination reshaped the destiny of a continent, leaving a legacy that continues to fascinate and inspire. As we reflect on this era, we are reminded of the complex interplay between power, ideology, and human will, a dynamic that continues to shape history to this day. The World Wars. The World Wars of the 20th century, World War I and World War II, stand as monumental events that reshaped the globe. These conflicts were not mere clashes of armies. They were titanic struggles that redefined borders, altered societies, and left deep psychological scars on nations and individuals alike. To understand their profound impact, we must journey through the causes, events, and aftermaths of these wars, illustrating how they shaped the modern world. The stage for World War I was set in the early 20th century amid a backdrop of nationalism, militarism, and complex alliances. Imagine a tightly wound spring under pressure, ready to snap at the slightest provocation. Tensions were high in Europe, with countries like Germany, Austria-Hungary, and France vying for dominance. The assassination of Archduke Franz Ferdinand of Austria in June 1914 acted as the spark that ignited this volatile landscape. The aftermath of the assassination was a cascade of events leading to war. Austria-Hungary declared war on Serbia, invoking a web of alliances that quickly dragged the major powers into the fray. The Central Powers, Germany, Austria-Hungary, and later the Ottoman Empire, faced off against the Allies, which included France, Russia, and Great Britain. By August 1914, Europe was engulfed in a conflict that would last for 4 long years. The nature of warfare had drastically changed. Gone were the days of traditional battles. The landscape was now dominated by trench warfare. Picture a grim, muddy battlefield where soldiers lived in cramped, unsanitary conditions, enduring the relentless sounds of artillery and the constant threat of death. The Western Front, stretching from the North Sea to Switzerland, became synonymous with stalemate, with both sides suffering horrendous casualties. Battles like the Somme and Verdun epitomized the brutal reality of this new form of warfare, with millions of lives lost for mere yards of territory. As the war dragged on, it profoundly affected the home fronts of the warring nations. Propaganda flooded newspapers, urging citizens to support the war effort. Rationing became common as resources were diverted to sustain the armies. In many countries, women stepped into roles traditionally held by men, working in factories and serving in various capacities, forever changing societal norms. The war's global impact was also significant. In the colonies, people fought for their imperial rulers, hoping that their sacrifices would be recognized and rewarded. This hope for greater autonomy would later fuel independence movements in Asia, Africa, and the Middle East. By 1918, the war was nearing its end. The Central Powers were weakening, facing internal dissent and economic collapse. In November 1918, an armistice was declared, bringing an end to hostilities. The Treaty of Versailles in 1919 would officially conclude the war, imposing harsh reparations on Germany and redrawing the map of Europe. However, the treaty sowed the seeds of future conflict, creating resentment and economic hardship in Germany. Fast forward to the 1930s, and the world was reeling from the aftermath of World War I. Economic depression and political instability fostered an environment ripe for totalitarian regimes to rise. In Germany, Adolf Hitler and the Nazi Party capitalized on public discontent, promoting a nationalistic and expansionist ideology. In Italy, Benito Mussolini's fascist regime mirrored these ambitions. Japan, seeking to expand its empire, began its militaristic pursuits in Asia. The invasion of Poland by Germany on September 1, 1939, marked the official beginning of World War II. The swift and brutal tactics employed by the Nazis, known as Blitzkrieg or Lightning War, caught the world by surprise. Picture a coordinated assault with tanks and aircraft overwhelming defenses in a matter of days, illustrating the new, terrifying face of modern warfare. The conflict quickly escalated, engulfing Europe and eventually drawing in nations from around the globe. The Allies, initially comprising Britain and France, soon expanded to include the Soviet Union and the United States after the attack on Pearl Harbor in December 1941. This global nature of the war set it apart from its predecessor, making it a truly worldwide conflict. One of the darkest chapters of World War II was the Holocaust, where 6 million Jews, along with millions of others, deemed undesirable by the Nazi regime, were systematically exterminated. This genocide serves as a stark reminder of the depths of human cruelty and the consequences of unchecked hatred and bigotry. The Holocaust's chilling narrative unfolded in concentration camps where people were stripped of their humanity and dignity, creating a haunting legacy that still resonates today. World War II saw the mobilization of entire nations in a total war effort. Civilians became active participants in the war, from working in factories, producing war materials, to serving in support roles in the military. Rationing, propaganda, and air raids became everyday realities. The Battle of Britain exemplified this, as the British populace endured relentless bombing while maintaining their resolve. As the war reached its climax, significant turning points such as the Battle of Stalingrad and the D-Day invasion at Normandy began to shift the balance in favor of the Allies. By 1945, Germany surrendered unconditionally, followed by Japan after the devastating atomic bombings of Hiroshima and Nagasaki. The war left an indelible mark on the world, with an estimated 70 to 85 million fatalities, making it the deadliest conflict in human history. The aftermath of the wars led to the establishment of the United Nations, aimed at fostering international cooperation and preventing future conflicts. The geopolitical landscape was forever altered, with the emergence of the United States and the Soviet Union as superpowers, setting the stage for the Cold War. The world wars serve as powerful reminders of the complexities of human nature, the dangers of totalitarianism, and the dire consequences of unresolved conflicts. They illustrate how quickly the world can be plunged into chaos and how ordinary people are affected by decisions made far above them. As we reflect on this tumultuous history, we are reminded of the need for dialogue, understanding, and cooperation to forge a more peaceful future. The legacy of the world wars continues to influence contemporary geopolitics, urging us to learn from the past to shape a better tomorrow. The Cold War. The Cold War, a term heavy with historical significance, defines an era of unparalleled geopolitical tension and ideological rivalry. Spanning nearly half a century, this struggle was not waged on battlefields, but in the realms of politics, technology, and influence. It was a chess match between the United States and the Soviet Union, where every move, every decision, carried the weight of a world balanced precariously between peace and annihilation. The roots of the Cold War were sown in the aftermath of World War II. As the Axis powers fell, the victorious Allies found themselves divided by their visions for the post-war world. On one side stood the United States, championing capitalism and democracy. On the other, the Soviet Union, advocating for communism and state-controlled economies. These ideologies were more than economic systems. They were worldviews, each claiming to offer the path to a better future. Imagine a vast chessboard stretching across continents, each piece representing a nation, as these superpowers sought to expand their influence. The first clash of this ideological divide became visible in the ruins of Europe. As nations rebuilt, the continent was split into Eastern and Western blocs. Winston Churchill's term, Iron Curtain, vividly captured the division, with the Soviet Union consolidating its hold on Eastern Europe, turning countries like Poland and East Germany into satellite states. Meanwhile, the United States and its allies moved to bolster democracy in the West, leading to the creation of NATO in 1949. This military alliance was a clear signal that the West would stand united against Soviet aggression. Berlin, a city divided both physically and ideologically, became the Cold War's most iconic symbol. In 1948, the Soviets attempted to force the Allies out of West Berlin by imposing a blockade, cutting off all road and rail access. The U.S. and its allies responded with the Berlin Airlift, flying in food, fuel, and supplies. For nearly a year, planes filled the skies, a testament to the West's resolve and an early victory in the Cold War chess game. The rivalry soon spilled beyond Europe. Proxy wars became a defining feature where the superpowers backed opposing sides in regional conflicts. The Korean War, 1950-1953, was among the first of these. North Korea, supported by the Soviets and China, invaded the South, prompting the U.S. and a coalition of United Nations forces to intervene. The war ended in a stalemate, leaving Korea divided along the 38th parallel, a division that persists to this day. The Cold War's battlegrounds were not limited to conflicts on the ground. The space above became a new frontier in the struggle for dominance. In 1957, the Soviet Union launched Sputnik, the world's first artificial satellite. This achievement shocked the United States, sparking the space race, a technological competition that embodied the Cold War's intensity. The U.S. responded with the Apollo program, culminating in the moon landing in 1969, a symbolic victory that asserted American technological superiority. Beneath these outward rivalries loomed an even darker shadow, the nuclear arms race. Both the United States and the Soviet Union amassed vast arsenals of nuclear weapons, creating a doctrine of mutually assured destruction, MAD. This precarious balance meant that any direct conflict between the superpowers could result in global annihilation. The Cuban Missile Crisis of 1962 brought this fear into stark reality. When the U.S. discovered Soviet missile installations in Cuba, the world teetered on the brink of nuclear war. For 13 tense days, the world watched as leaders negotiated a fragile resolution, pulling humanity back from the precipice. While the Cold War saw moments of near catastrophe, it also witnessed efforts at détente, a relaxation of tensions. Arms control agreements like the Strategic Arms Limitation Talks, SALT, in the 1970s, sought to curb the nuclear arms race. Yet these agreements were often undermined by renewed hostilities, such as the Soviet invasion of Afghanistan in 1979, which reignited tensions and drew the United States into another proxy conflict. By the 1980s, cracks began to appear in the Soviet Union's facade. Under the leadership of Mikhail Gorbachev, reforms aimed at reviving the struggling Soviet economy inadvertently accelerated its decline. Glasnost, openness, and perestroika, restructuring, unleashed forces of change that Gorbachev could not control. Eastern European nations, inspired by these reforms, began to assert their independence, culminating in the fall of the Berlin Wall in 1989. The image of East and West Berliners tearing down the wall with their bare hands became a powerful symbol of the Cold War's end. In 1991, the Soviet Union itself collapsed, dissolving into 15 independent republics. The Cold War, which had dominated global politics for decades, came to an abrupt end. The United States emerged as the world's sole superpower, while the former Soviet states faced the daunting task of rebuilding and redefining their futures. The Cold War's legacy is vast and multifaceted. It shaped international relations, fueled technological innovation, and left a profound cultural imprint. The ideological battles of the era influenced everything from literature and film to education and propaganda. Yet it also left scars, proxy wars, divided nations, and a pervasive sense of mistrust that lingers in some corners of the world. As we reflect on the Cold War, it serves as both a cautionary tale and a testament to human resilience. It reminds us of the dangers of division and the importance of diplomacy in navigating global challenges. The Cold War may have ended, but its lessons continue to resonate, urging us to seek cooperation over conflict and unity over division in our pursuit of a more peaceful world. The Space Race. The space race, a gripping chapter in human history, stands as a testament to ambition, competition, and boundless innovation. It was more than a contest between two superpowers, the United States and the Soviet Union. It was a reflection of humanity's determination to explore the cosmos and a pivotal battleground for ideological supremacy during the Cold War. To understand the space race is to witness a dramatic saga where the boundaries of possibility were redefined and the stars became the ultimate prize. In the aftermath of World War II, the world's geopolitical landscape was reshaped, with the United States and the Soviet Union emerging as rival superpowers. Each sought to demonstrate its technological and ideological dominance. The vast, uncharted frontier of space became the new arena for this rivalry, a place where dreams of exploration intertwined with strategic ambition. The race began in earnest in 1957 when the Soviet Union launched Sputnik 1, the first artificial satellite. Imagine a gleaming metal sphere orbiting Earth, emitting a steady beep that echoed around the world, a sound that both thrilled and terrified. Sputnik wasn't just a technological achievement. It was a clear signal that the Soviets had leapt ahead in the race for the cosmos. In the United States, this revelation ignited a wave of urgency and introspection. Suddenly, space was no longer an abstract frontier. It was a critical theater of the Cold War. In response, the United States ramped up its space efforts. Schools began emphasizing science and mathematics, and government funding for research surged. By 1958, NASA was established, signaling America's commitment to catching up and surpassing the Soviet Union. Yet the path forward was fraught with challenges. Early American attempts at space exploration faced public failures, with rockets that exploded on the launch pad and missions that fell short of their goals. These setbacks only heightened the stakes, turning the space race into a relentless struggle for both technological superiority and national pride. The stakes escalated further in 1961 when Yuri Gagarin became the first human to orbit Earth. His triumphant journey aboard the Soviet spacecraft Vostok 1 captured the world's imagination and underscored the Soviet Union's lead in the space race. For many in the West, Gagarin's feat was a stark reminder of the high stakes and the intense pressure to respond. The United States, galvanized by President John F. Kennedy's vision, set its sights on a bold and audacious goal: to land a man on the moon before the end of the decade. Kennedy's declaration, "We choose to go to the moon, not because it is easy, but because it is hard," electrified the nation. It was a call to action, embodying the spirit of innovation and resilience that defined the era. NASA's Apollo program became the centerpiece of this effort, a monumental undertaking that demanded cutting-edge technology, unparalleled coordination, and immense human courage. The journey to the moon was anything but smooth. The tragic loss of 3 astronauts during the Apollo 1 pre-launch test in 1967 served as a somber reminder of the risks involved. Yet these challenges only strengthened the resolve of those dedicated to the mission. Engineers, scientists, and astronauts worked tirelessly, refining every detail, driven by the belief that their efforts transcended national interests. They were advancing humanity's reach into the cosmos. On July 20th, 1969, the world watched in awe as Apollo 11 achieved the seemingly impossible. Neil Armstrong and Buzz Aldrin became the first humans to set foot on the moon, while Michael Collins orbited above in the command module. Armstrong's words, "That's one small step for man, one giant leap for mankind," resonated across the globe, capturing the profound significance of the moment. Imagine the silence that enveloped living rooms, classrooms, and public squares as people witnessed a human being walking on another celestial body for the first time. The moon landing was not just a technological triumph. It was a victory for human determination and ingenuity. It symbolized what could be achieved when nations dared to dream and work together, even amid intense rivalry. The space race continued in various forms, but the moon landing marked its zenith, a moment when humanity collectively reached beyond Earth's boundaries. While the space race was born out of competition, it also paved the way for collaboration. The 1975 Apollo-Soyuz test project, where American and Soviet spacecraft docked in orbit, demonstrated the potential for cooperation even in an era of rivalry. This spirit of partnership laid the foundation for future endeavors, such as the International Space Station, where nations work side by side to explore the final frontier. The legacy of the space race extends far beyond its immediate accomplishments. It spurred advancements in technology, from satellite communications to medical innovations. It inspired generations of scientists, engineers, and dreamers to reach for the stars. Perhaps most importantly, it reminded humanity of its shared destiny, our place as explorers in an infinite universe. In reflecting on the space race, we see a story not just of conflict, but of aspiration. It was a time when the impossible became possible, when nations dared to look up and imagine a future beyond Earth. Today, as we embark on new journeys to Mars, explore distant planets, and search for life beyond our solar system, we carry with us the legacy of those who first dared to leave our world behind. The space race remains a testament to what we can achieve when we challenge our limits and aim for the stars. The Digital Revolution. The digital revolution, a transformative era in human history, has profoundly reshaped our lives, connecting us in ways once unimaginable and redefining how we work, learn, and communicate. Picture waking up in a world where information flows like air, where connections span continents in an instant, and where knowledge is always within reach. Beginning in the mid-20th century, this technological upheaval continues to accelerate, influencing every facet of society, culture, and the global economy. The story of the digital revolution begins in the 1940s and 1950s, amidst the backdrop of World War II. Visionaries like Alan Turing and John von Neumann pioneered the development of early computers, massive machines powered by vacuum tubes and punch cards that filled entire rooms. These machines, while primitive by today's standards, were capable of calculations that would have taken humans months to complete. Imagine engineers surrounded by blinking lights and humming machinery, laying the groundwork for a technological renaissance. The breakthrough moment came in 1947 with the invention of the transistor. This tiny device replaced bulky vacuum tubes, paving the way for smaller, faster, and more efficient computers. By the 1970s, companies like Apple and IBM were introducing personal computers, bringing the power of computation into homes and offices. Picture the excitement of unboxing a computer, a portal to a new world of possibilities, right on your desk. Meanwhile, another revolutionary technology was quietly taking shape: the Internet. Initially developed in the 1960s as a military communication network, the Internet evolved into a decentralized system linking computers across the globe. Imagine creating an invisible web connecting distant lands, enabling the instantaneous sharing of ideas and information. By 1991, the introduction of the World Wide Web transformed this network into a user-friendly platform, allowing people to access vast reservoirs of knowledge with a simple click. The Internet democratized access to information, akin to walking into an infinite library where every book and idea is at your fingertips. This technological leap fundamentally changed how we interact with knowledge, making it possible to learn, communicate, and collaborate on an unprecedented scale. The digital revolution brought seismic shifts to daily life. Email and instant messaging revolutionized communication, shrinking the world and enabling people to connect across time zones and continents. Think of it as a global coffee shop where conversations happen in real time, no matter the distance. Social media platforms like Facebook, Twitter, and Instagram further transformed how we interact, building virtual communities that transcended geographic and cultural boundaries. Yet, this connectivity also brought challenges, including concerns over privacy, misinformation, and the mental health impacts of constant connectivity. Economically, the digital revolution redefined industries and created new ones. E-commerce giants like Amazon revolutionized shopping, offering consumers the ability to browse virtual storefronts and have goods delivered directly to their doorsteps. Imagine turning your smartphone into a mall where every item is just a click away. The gig economy emerged alongside, with platforms like Uber and Airbnb providing flexible work opportunities, challenging traditional employment models, and sparking debates about labor rights and job security. In education, digital technology broke down barriers, making learning accessible to anyone with an internet connection. Online courses, virtual classrooms, and educational apps have empowered individuals worldwide to acquire knowledge at their own pace. Picture a child in a remote village attending a lecture by a world-renowned scientist via livestream, illustrating the transformative potential of digital learning. The revolution also ushered in a data-driven era. Companies now leverage vast amounts of information to tailor products, predict trends, and optimize services. Data analytics have transformed industries from healthcare to finance, enabling precision and innovation previously unimagined. However, this reliance on data has raised critical ethical questions about privacy, surveillance, and control. Despite its many benefits, the digital revolution has also highlighted disparities. The digital divide remains a pressing issue, with many communities lacking access to reliable internet and technology. This inequity raises fundamental questions about inclusion and opportunity in the digital age, reminding us that technological advancement must be accompanied by efforts to ensure equitable access. As technology evolves at an unprecedented pace, the challenges grow more complex. Issues of cybersecurity, misinformation, and the ethical use of artificial intelligence loom large. We stand at a crossroads, navigating a delicate balance between innovation and responsibility, ensuring that digital tools serve humanity rather than undermine it. The digital revolution is far more than a technological phenomenon. It represents a cultural metamorphosis that continues to shape our world. With advancements like quantum computing, virtual reality, and artificial intelligence on the horizon, the possibilities seem boundless. Yet this era also calls for vigilance, critical thinking, and ethical stewardship to ensure that technology uplifts and empowers everyone. In the vast narrative of human progress, the digital revolution is a new dawn, illuminating the boundless potential of human creativity and connection. As we embrace the opportunities of this digital age, let us also commit to addressing its challenges, forging a future where technology enriches lives and unites us in our shared pursuit of knowledge, understanding, and progress. Globalization and modern history. Globalization and modern history are interwoven stories, chronicling humanity's journey toward ever deeper connections. Imagine a vast tapestry, each thread representing a unique culture, economy, or people, bound together by the forces of technology, trade, and communication. This intricate web has made the world smaller, yet it raises profound questions about identity, culture, and our shared future. Long before the internet allowed instant global connectivity, ancient trade routes like the Silk Road were lifelines of cultural and economic exchange. Picture merchants braving vast deserts and treacherous mountain passes, carrying silk, spices, and ideas that transcended borders. These routes not only transported goods, but also served as conduits for religions, philosophies, and technologies, sowing the seeds of globalization millennia ago. As empires like those of Alexander the Great expanded, they became melting pots of diverse traditions, languages, and innovations. His conquests introduced Greek culture across a vast expanse, blending with local customs to create the Hellenistic world, a vivid precursor to the cultural fusion that defines globalization today. The age of exploration in the 15th and 16th centuries marked a new era of global connectivity. Imagine Christopher Columbus and Vasco da Gama navigating uncharted oceans, driven by dreams of wealth and glory. Their voyages linked continents, sparking an unprecedented exchange of goods, ideas, and even diseases. The Columbian Exchange transformed diets worldwide. Potatoes and tomatoes revolutionized European cuisine, while horses and cattle reshaped the Americas. Yet this exchange came at a cost, as indigenous populations suffered devastating losses to disease and colonization. The Industrial Revolution of the 18th and 19th centuries accelerated globalization on an unprecedented scale. Envision the rise of factories, their chimneys billowing steam as workers toiled to produce goods at record speed. Railroads and steamships shrank distances, linking markets and enabling the flow of raw materials and manufactured products. Nations became interconnected as never before, but the exploitation of colonies for resources and labor highlighted the darker side of global integration. The 20th century brought both devastation and unity. World Wars I and II reshaped borders and societies, but they also fostered a desire for international cooperation. Imagine the founding of the United Nations in 1945, where representatives from diverse nations gathered to prevent future conflicts and promote human rights. This spirit of collaboration extended to the global economy, with institutions like the World Bank and the International Monetary Fund fostering trade and development. By the late 20th century, the digital revolution ushered in a new phase of globalization. Picture a world where a single email can cross continents in seconds and where vast databases of knowledge are accessible to anyone with an internet connection. The internet transformed communication, commerce, and culture, creating a global marketplace and fostering a sense of shared citizenship. Social media platforms connected billions, enabling individuals to share stories, build movements, and address global challenges together. Yet this era of hyperconnectivity also brought challenges. The digital divide left many communities without access to technology, while concerns about privacy, misinformation, and cyber threats underscored the complexities of our interconnected world. The very tools that unite us also expose vulnerabilities, requiring thoughtful navigation. Today, globalization is a double-edged sword. It fosters cultural exchange and economic growth, but it can also lead to cultural homogenization and widening inequalities. The delicate balance between embracing global connectivity and preserving local identities remains a central challenge. The latest pandemic revealed both the strengths and fragility of our global systems. Supply chains faltered, economies struggled, yet scientific collaboration across borders led to breakthroughs in record time. This crisis underscored our shared humanity and the necessity of collective action to address global challenges like climate change and public health. Globalization is not a monolithic force. It is a dynamic process shaped by human choices. As we navigate this interconnected world, we must ensure that its benefits reach everyone, not just a privileged few. Listening to marginalized voices, respecting cultural diversity, and fostering equity are essential for building a future that reflects our shared values. Imagine the tapestry of globalization as a work in progress, with each of us holding a thread. Together, we have the power to weave a world that celebrates diversity, fosters collaboration, and addresses the challenges of our time. As the story of globalization continues to unfold, let us strive to create a narrative of inclusion, understanding, and shared prosperity. The threads of our collective history remind us that, despite our differences, we are bound by a common humanity, capable of shaping a future worthy of our shared dreams.